Imagine ordering a new family home in Australia, then discovering that most of it is being manufactured inside a factory in China, packed for an ocean journey, and assembled on a suburban block in less than 3 weeks. That is no longer a futuristic concept. Australia's largest volume home builder has completed 2 3-bedroom houses in Melbourne's western suburbs, using prefabricated panels and modules made almost entirely overseas. From the moment the concrete slab was ready, the homes reportedly reached completion in only 20 business days. The main structure, including the walls and roof, became weatherproof in just 4 days. The project took place at Stockland's Mount Atkinson estate in Truganina, around 22 kilometers west of central Melbourne. Metricon partnered with a modern construction company called Synex to test whether an industrialized building system could work inside the processes of a major Australian home builder. About 90% of each house was completed off-site before the components reached the development. The foundation remained a conventional slab built in Australia, but much of everything above it arrived as a coordinated kit of wall panels, floor sections, windows, fittings, and a complete bathroom pod. This does not mean a finished house appeared from China and was simply dropped onto the land. The real process is more interesting. The panels take roughly 4 weeks to manufacture in a factory. Shipping them to Australia can require about another 4 weeks. Local workers then prepare the site, pour the slab, receive the components, lift them into position, connect the structure, complete services, and finish the home. The 20-day figure describes the construction period from the slab to completion, not the entire journey from factory order to handing over the keys. Even with that important distinction, the speed is remarkable. Metricon says the 20-day schedule was about 1/3 of its normal construction timeline. On the site, the most dramatic phase lasted only 4 days. Cranes positioned the large wall and floor sections, while workers connected each piece in sequence. The roof went on, the building reached lockup, and the bathroom was already functional because it arrived as one pre-built module. Carpets had been measured and cut before shipment. Wall panels arrived with windows installed and planned spaces for the kitchen. The finished houses do not look like shipping containers or temporary cabins. Both contain 3 bedrooms, 2 bathrooms, and open-plan living spaces. They were designed to achieve a 7-star energy rating and stand on familiar slab-on-ground foundations. Metricon says the homes are virtually indistinguishable from conventionally built houses. That matters because prefabrication has often struggled with an image problem. Many buyers still imagine a cheap portable building, but this pilot is trying to prove that factory construction can produce a normal suburban home with the appearance, comfort, and durability Australian families expect. Australia has a powerful reason to examine this approach. The country is trying to increase housing supply, while construction costs, labor availability, planning delays, and financing pressures make new homes difficult to deliver. The national target is 1.2 million new homes by the middle of 2029. Official projections released in 2026 suggested that delivery may fall well short of that goal and arrive more than a year late. At the same time, affordability has continued to deteriorate, with households spending more income on rent and requiring longer to save for a mortgage. That makes construction speed more than a technical curiosity. Every month saved on a building program can reduce financing exposure, weather delays, temporary accommodation costs, and uncertainty for developers and buyers. Traditional house building is highly dependent on work happening in the correct order. A crew may wait for another trade to finish. Rain can stop outdoor work. Materials can arrive late. A missing component can delay several later stages. Factory production changes the sequence because multiple parts of the home can be created simultaneously while the site and foundation are prepared separately. Inside a factory, workers do not need to rebuild the workplace around every house. Tools, materials, jigs, lifting equipment, and inspection stations remain in fixed positions. Components can move through repeatable stages, similar to a manufacturing line. Walls can be assembled horizontally at comfortable working heights rather than built piece by piece in changing weather. Measurements can be checked before shipment. Waste can be collected and reused more easily. Supervisors can inspect the same production process repeatedly instead of traveling between scattered suburban sites. The greatest advantage may be predictability. A conventional building schedule can look simple on paper, but become complicated when weather, subcontractors, deliveries, and site conditions collide. Prefabrication moves a large share of that work into a controlled environment. The builder knows when panels should leave each station, how many people are required, and which inspections must happen before packing. Standardization can expose problems earlier. If the same design is produced hundreds of times, each completed home provides information that can improve the next one. China is central to this story because it has spent decades developing enormous manufacturing ecosystems. The country already produces building materials, fixtures, appliances, electronics, vehicles, batteries, and industrial equipment for global customers. A prefabricated house combines many of those supply chains. Steel framing, panels, windows, plumbing modules, flooring, cabinetry, and packaged components can be coordinated near large factories and ports. The challenge is not merely making one wall cheaply. It is manufacturing thousands of different pieces so they arrive in the correct order and fit together on another continent. Sinex says it spent years waiting for Chinese manufacturing to reach the standard required for Australian homes. The company describes its system as a hybrid approach rather than a fully volumetric house. Most of the building uses panels, while the bathroom arrives as a three-dimensional module. This balance can make shipping more efficient because flat sections occupy less space than transporting entire rooms filled mostly with air. The bathroom remains modular because waterproofing, tiling, plumbing connections, and fixtures benefit from being completed and inspected in one controlled location. The system also keeps important work in Australia. Local crews still prepare the land, pour the foundation, operate cranes, assemble the structure, connect electricity and plumbing, install remaining finishes, inspect the building, and certify that it meets local requirements. Metrocon's chief executive has emphasized that the materials may be manufactured in China, but the houses are assembled in Melbourne under Australian standards. The company presents the method as an additional pathway, not a plan to eliminate traditional construction or replace the entire local workforce. That distinction is important. Housing shortages cannot be solved by one technology alone. Land must be available. Roads, schools, water, electricity, transport, and drainage must support new communities. Planning approvals must arrive. Buyers still need financing. Builders must manage warranties and long-term maintenance. A faster house does not automatically create a finished neighborhood. Modular construction addresses one part of the system, how the physical building is manufactured and assembled after a project is approved and the site is ready. Cost is another unresolved question. Faster does not always mean cheaper. Factory production can reduce labor hours, waste, delays, and rework, but overseas manufacturing introduces shipping, insurance, port handling, storage, customs, cranes, specialized design, and coordination expenses. A damaged panel could be difficult to replace quickly. Exchange rates can change. A project that works for hundreds of identical houses may not work for a buyer demanding a completely unique design. Metrocon has said the method still has some distance to travel before it becomes fully economically viable. Scale could change that calculation. Sinex says it has built only 8 residences using its system so far, but it has another 200 on order and is discussing a further 300 with builders and developers. Producing a handful of houses requires design work, testing, approvals, logistics planning, and training that must be spread across very few units. When hundreds use the same system, those costs can be distributed more widely. Factories can order materials in larger quantities, containers can be packed more efficiently, and site crews can repeat the assembly process until it becomes routine. This is why regional areas may be especially attractive. Large cities have more builders and trades, although they also have intense demand. Smaller communities and growth corridors can struggle to find enough skilled workers for major housing programs. A factory-made system allows much of the labor to happen somewhere else, then concentrates local activity into a shorter installation period. The same trained assembly team could potentially move from one development to another, completing homes quickly without requiring every regional town to support a full network of specialized trades. Weather is another major factor. Australia can experience heat, heavy rain, storms, and regional conditions that interrupt outdoor construction. Building walls and modules under a roof protects materials and workers. It also allows production to continue while a distant site is wet or being prepared. When the components arrive, the objective is to close the structure rapidly so the interior is protected. The Truganina pilot reaching a weatherproof stage in 4 days demonstrates why that sequence can reduce one of the biggest uncertainties in residential construction. Quality control may ultimately determine whether buyers trust the system. Speed creates attention, but a house is expected to last for decades. Connections between panels must remain strong. Waterproofing must survive. Windows must seal correctly. Plumbing and electrical systems must be accessible for repair. Materials must handle Australian temperatures, moisture, pests, wind, and fire requirements. The pilot homes reportedly met Australian standards and achieved a strong energy rating, but larger adoption will require consistent results across hundreds or thousands of properties. not only two carefully monitored demonstrations. There is also a question of design flexibility. Industrial production works best when products share common dimensions and components. Buyers, councils, and developers often want different facades, floor plans, roof shapes, materials, and neighborhood character. A successful platform must create variety without losing the efficiency of repetition. The answer may be a hidden standardized structure combined with customizable finishes. Cars use shared platforms beneath many different models. Housing manufacturers could use common wall sizes, bathroom pods, service connections, and structural systems while changing the external appearance. Financing and insurance must adapt as well. Traditional lenders release construction payments at familiar milestones on a building site. Factory-made homes shift value off-site before the structure appears on the land. Banks need confidence that components being manufactured overseas are protected, insured, and legally connected to the project. Builders need clear responsibility if something fails after installation. Buyers need warranties that remain meaningful even when materials, designers, factories, shipping companies, and local contractors all participate in the same home. The environmental impact is not automatically simple. Factory production can reduce waste, improve material efficiency, and make energy performance more consistent. Fewer months of activity on a residential site can reduce neighborhood disruption. But transporting large components across the ocean consumes energy, and materials may travel long distances before assembly. A complete assessment would compare manufacturing efficiency, shipping emissions, construction waste, building performance, and lifespan. The fastest method is not necessarily the most sustainable, but neither should overseas production be dismissed without measuring the entire system. The Australian government and several states are already looking more seriously at modern construction methods. New South Wales has announced plans to partner with industry on a modular housing facility, while federal funding has supported trials of prefabricated approaches. These programs show that the Metricon experiment is not happening in isolation. Governments, banks, builders, developers, and manufacturers are all asking whether housing can move from a mostly handcrafted process toward a more industrial model without sacrificing safety, quality, or local employment. The comparison with automobiles is useful. A century ago, cars were expensive products assembled slowly by skilled workers. Standardized parts, production lines, supplier networks, and quality systems made reliable vehicles available at enormous scale. Houses are different because every site has unique ground, planning, utility, and climate conditions. They cannot simply roll off one factory line and drive away. Yet much of a home is repetitive. Bathrooms, walls, windows, floors, wiring routes, and structural connections may benefit from the same manufacturing discipline that transformed other industries. If the system succeeds, the most important change may not be that Australia imports houses forever. Overseas production could prove the model, create demand, and teach builders which parts deliver the greatest savings. Some factories could eventually be established closer to Australian growth areas or ports, especially when transport distances and order volumes justify local investment. China's role might then evolve from direct manufacturer to equipment supplier, technology partner, or example of how building systems can scale. What happens next will matter more than the pilot itself. If the 200 confirmed orders move through production smoothly, builders will gain real data on defects, shipping times, labor requirements, customer satisfaction, and final cost. The additional 300 homes under discussion could then test whether the system works across different developers, councils, climates, and site conditions. That is the point where prefabrication stops being a demonstration and starts becoming an industry. Success would not require every Australian house to come from China. It would require enough projects to prove that standardized manufacturing can shorten schedules, protect quality, and give buyers another dependable option when traditional capacity is stretched across the country. For now, the Truganina houses are evidence of possibility, not proof of a national solution. 2 completed homes cannot erase a shortage measured in hundreds of thousands. They do show that a major builder can integrate Chinese factory production with Australian design, compliance, foundations, labor, and customer expectations. They also challenge the assumption that every suburban house must spend months being constructed almost entirely outdoors, one trade at a time. In my opinion, the most exciting part of this project is not the headline that China is shipping homes to Australia. It is the idea that house building can become more predictable. Australia needs traditional builders, local trades, planning reform, infrastructure, and more land supply, but it also needs methods that produce more with the workforce already available. Prefabrication should not replace the industry. It should become another tool, especially for regional housing, large developments, social housing, and projects where time matters. The real test will be whether these homes remain affordable, durable, easy to repair, and desirable after the excitement fades. If costs fall at scale and quality remains consistent, a 20-day build could move from an unusual pilot to a normal option. If shipping, customization, financing, or defects erase the advantages, the idea may remain limited to specialized projects. So what do you think? Would you live in a home largely manufactured in China and assembled in Australia if it met local standards, looked completely normal, and could be finished in 20 days? Or would you still prefer a house built through traditional methods? Share your opinion in the comments. And for more stories about China's factories, engineering, materials, construction technology, and the systems changing how the world builds, subscribe to the Eastern Engine channel. Turn off a computer, and something strange happens. The files on the SSD remain exactly where they were, but everything held inside RAM disappears. Open documents, active calculations, temporary AI data, the precise state of every running program, all of it vanishes the moment electrical power is removed. That is the basic compromise inside nearly every modern computer. Fast memory forgets. Memory that remembers is slower. But researchers at Fudan University in Shanghai have built a device that appears to challenge that division. Their experimental flash memory stored information without continuous power, survived more than 5.5 million write cycles, and completed a programming operation in just 400 picoseconds. A picosecond is 1/trillionth of a second. At that speed, the device can theoretically complete 2.5 billion programming events in 1 second. Compared with conventional flash memory, whose programming time is often measured in tens of microseconds, the difference can approach 100,000 times. And the researchers say their device can program faster than SRAM built with the same channel length. That sounds like the beginning of universal memory. One technology combining the speed of working memory with the persistence of storage. But this is not yet a commercial RAM replacement. It is not a terabyte SSD. And the 400 picosecond result came from a tiny experimental device under carefully controlled conditions. The real breakthrough is more fundamental. For decades, engineers assumed that flash memory could not cross the 1 nanosecond barrier because its method of storing charge was simply too slow. Fudan's team crossed it. Then, months later, the same researchers integrated their two-dimensional memory technology with conventional silicon electronics and created a functional flash chip. The first experiment proved the physics. The second showed a possible path toward actual hardware. Together, they raise a much larger question. What happens if computers no longer have to choose between speed and memory that survives when the power goes out? The chalkboard and the stone tablet. A computer's memory system is not one single pool. It is a hierarchy. At the top are tiny registers inside the processor. They are extraordinarily fast, but there are very few of them. Below that is cache, followed by system RAM. These layers hold data close to the processor so calculations can happen quickly. Farther away sits persistent storage, SSDs and hard drives. Storage provides far more capacity, but the processor must wait longer to reach it. The arrangement exists because no single memory technology delivers every desirable property at once. SRAM is extremely fast, but it takes a large amount of silicon area and loses information without power. DRAM is denser and cheaper, but it must constantly refresh its electrical charge and also forgets when powered down. NAND flash stores enormous quantities of data and remembers without electricity, but writing to it is dramatically slower. Think of RAM as a chalkboard. Writing is immediate, erasing is easy, but when the lights go out and the room is cleaned, the information disappears. Flash memory is closer to carving a message into a stone tablet. The inscription remains. The problem is that carving takes time. Fudan's POX device is an attempt to write on the stone tablet at chalkboard speed. Why normal flash is slow. Flash memory stores information by trapping electrical charge inside an insulated layer. The presence or absence of that charge changes how the memory cell behaves electrically, allowing the device to represent zeros and ones. The charge must cross an energy barrier to enter the storage region. In conventional flash, this commonly happens through tunneling or hot carrier injection. Both methods work. Neither is naturally instantaneous. In Fowler-Nordheim tunneling, a strong electric field encourages electrons to pass through an insulating barrier that they would not normally cross. The effect is reliable, but moving enough charge takes time and often requires relatively high voltage. Hot carrier injection takes another route. Electrons accelerate along the memory channel, Some gain enough energy to jump into the storage layer. The faster and more efficiently those carriers are accelerated, the faster the memory can be programmed. Silicon places practical limits on that acceleration. The electric field is not distributed perfectly, and only a small percentage of carriers become energetic enough to cross the barrier. Engineers have improved flash memory for decades through better materials, thinner structures, and more sophisticated control. But the underlying mechanism remains slow compared with volatile memory. The accepted assumption was simple. Flash could become denser, it could become cheaper, it could consume less standby power. But sub-nanosecond programming was beyond its natural limit. The Fudan researchers attacked that limit by changing the channel material itself. The graphene channel. The experimental memory uses graphene as its channel. Graphene is a sheet of carbon only one atom thick. Its electrons behave differently from those moving through ordinary silicon. Under the right conditions, they can travel with very high mobility and experience unusual energy relationships associated with what physicists call a Dirac material. The important feature here is not simply that graphene is thin, it is how that thinness changes the electric field inside the device. In a conventional silicon channel, the horizontal electric field used to accelerate carriers is distributed across a thicker body. In the two-dimensional channel, the field becomes more concentrated. The carriers accelerate more effectively. More of them reach the high-energy state needed to enter the storage layer. The researchers call this two-dimensional enhanced hot carrier injection. Imagine two ramps reaching the same wall. The first ramp is long and shallow. A rolling ball gains speed gradually, but friction removes much of the energy before it reaches the top. The second ramp is shorter and steeper. The ball accelerates more aggressively and reaches the barrier with far greater energy. The graphene channel creates something closer to the second ramp. The result was a much larger injection current than the researchers observed in a comparable silicon system. More charge entered the storage region in less time. That is what enabled the 400 picosecond programming pulse. What 400 picoseconds means? 400 picoseconds equals 0.4 nanoseconds. Light travels only about 12 centimeters in that amount of time. A modern processor running at 5 GHz completes one clock cycle every 200 picoseconds. So the POX programming operation occurred within roughly 2 processor clock cycles at that frequency. That is an astonishing figure for non-volatile flash memory. Conventional silicon flash can require 10 to 100 microseconds to program a cell. 10 microseconds divided by 400 picoseconds is 25,000. 100 microseconds divided by 400 picoseconds is 250,000. That is why describing the breakthrough as approximately 100,000 times faster is reasonable. But it is not one fixed multiplier for every existing flash technology. The comparison depends on the specific device, operating conditions, and definition of programming time. The researchers tested a graphene device with a channel length of 0.2 micrometers and a programming voltage of around 5 volts. They repeated the short pulse measurement and observed a stable memory response. They also demonstrated a related device using tungsten diselenide, another two-dimensional material, which achieved 1 nanosecond programming through hot hole injection. This suggests the mechanism is not limited to one isolated graphene sample. Different two-dimensional materials may support different versions of the same general approach. Never forgets needs context. The device does not literally remember forever. No physical storage medium does. Never forgets means the information remains when electrical power is removed. That makes it non-volatile. SRAM and DRAM require continuous power to preserve their states. Remove the voltage and the stored information disappears almost immediately. Flash traps charge inside an insulated region, allowing the state to survive. The Fudan device maintained a measurable non-volatile memory window, after programming and demonstrated endurance beyond 5.5 million cycles. That is important because speed alone would not make a useful memory. A device that writes in 400 picoseconds but fails after a few operations is a laboratory curiosity. A device that performs millions of cycles begins to look more credible. However, endurance testing on a small research device is not the same as proving reliability across billions of cells operating for years inside consumer hardware. Commercial memory must survive temperature changes, manufacturing variations, electrical noise, and repeated operation across a complete chip. The prototype established that the mechanism can be fast and repeatable. It did not complete the industrial journey. Why AI cares about this? Modern processors are becoming faster than the systems feeding them. This is known as the memory wall. An AI accelerator may contain thousands of arithmetic units capable of performing enormous numbers of calculations. But those units need model weights, activations, and intermediate results. If data arrives too slowly, the accelerator waits. The chip may be powerful enough to perform the operation. The memory system prevents it from starting. Moving data also consumes energy. In many AI workloads, transporting values between storage, DRAM, and the processor can use more energy than the calculation itself. That is why high-bandwidth memory has become so valuable. It places large amounts of fast memory extremely close to AI processors. But HBM is expensive, complicated to package, and still volatile. Every time a system starts, model data must be loaded from persistent storage into fast memory. Imagine a library that burns every book each night and reconstructs the collection every morning from a warehouse. The readers eventually receive the information. The rebuilding process wastes time and energy. A fast, non-volatile memory could preserve important data close to the processor even after shutdown. AI models might start more quickly. Edge devices could retain local model states without constantly refreshing memory. Computers could reduce the amount of data copied repeatedly between storage and working memory. This is the larger promise behind ultra-fast persistent memory. Could it replace RAM? Not today. The prototype demonstrated exceptional programming speed in an individual memory structure. A complete RAM system requires much more. Billions of cells must be arranged into dense arrays. Every cell must be selected without accidentally disturbing its neighbors. Read and write circuits must operate quickly. Manufacturing yield must be high. The chip must fit existing processor and memory interfaces. Cost per bit must compete with technologies produced in enormous factories. Latency also includes more than the programming pulse. A real computer must send an address, select the correct cell, move signals through wires, sense the stored state, correct errors, and transfer the result to the processor. A 400 picosecond device operation does not mean a future memory module will automatically deliver 400 picosecond system latency. The difference resembles a car engine capable of reaching a certain rotational speed. That number matters. But the speed of the complete vehicle also depends on the transmission, tires, aerodynamics, and road. The experimental device proved the engine. The researchers still needed to build more of the car, and that is exactly what they attempted next. The second breakthrough. Later in 2025, the Fudan team reported a full-featured two-dimensional NOR flash memory chip integrated with conventional silicon CMOS electronics. This was a major step beyond the original device demonstration. The new chip used the two-dimensional material as the memory core while mature silicon circuitry handled instruction control and system operation. The researchers called the integration method ATOM2CHIP. The chip supported random access, 8-bit instruction operations, and 32-bit parallel operation. Full chip testing produced a reported memory cell yield of 94.34%. Its integrated memory cells operated in 20 nanoseconds and consumed as little as 0.644 picojoules per bit. 20 nanoseconds is far slower than the original 400 picosecond pulse. That does not mean the later chip failed. It means integration introduces real-world overhead. The signal must pass through control circuits. Cells must be addressed. Operations must occur across an array rather than one optimized test device. The integrated chips sacrificed record-setting speed in exchange for functionality. That is often how new technology develops. The first prototype demonstrates an extreme physical result. The first system trades some of that result for reliability, control, and manufacturability. 20 nanoseconds is still fast for non-volatile flash memory. More importantly, the researchers showed that the two-dimensional memory could communicate with a conventional CMOS platform. Why integration is so difficult? Two-dimensional materials can be only one or a few atoms thick. That creates remarkable electrical properties. It also makes manufacturing difficult. A conventional silicon chip surface may look perfectly smooth to the human eye. At atomic scale, it resembles rough terrain. Different structures rise from the surface. Metal lines, insulating regions, and contacts create tiny height variations. Placing an atomically thin layer directly across that surface is like stretching plastic film over an entire city. From an airplane, the land looks flat. At street level, buildings, bridges, and towers make a smooth covering impossible. The film can wrinkle, tear, lose electrical performance, or fail to contact the correct region. The Fudan team's solution was modular. They manufactured the two-dimensional memory section and conventional CMOS control circuitry separately, then connected them through dense vertical interconnects. This allowed the new material to preserve its performance without requiring the entire silicon surface to become atomically flat. The approach also avoids rebuilding every part of the computer from experimental materials. Conventional CMOS remains excellent at logic. The two-dimensional layer performs the memory function, where its unusual physics provides the greatest advantage. This hybrid strategy may be more realistic than attempting to replace silicon completely. NOR flash versus the SSD in your computer. The integrated chip was a form of NOR flash. That distinction matters. Most large SSDs use NAND flash. NAND is optimized for extremely high density and low cost per bit. It arranges cells in long strings and reads or writes data in larger blocks. NOR flash offers direct random access and is commonly used for firmware and code storage, where rapid, precise access matters more than maximum capacity. The Fudan device therefore should not be imagined as an immediate replacement for a multi-terabyte NAND SSD. Its potential may first appear in applications requiring fast persistent access, processor boot code, AI accelerator configuration, embedded systems, automotive electronics, edge computing devices, persistent cache, memory placed close to specialized processors. These markets may tolerate higher cost per bit if the technology reduces startup time and energy consumption. Only after manufacturing improves could the concept challenge larger portions of the memory hierarchy. The dream of universal memory. Engineers have pursued universal memory for decades. The ideal technology would combine 5 properties: SRAM-like speed, DRAM-like density, flash-like persistence, low energy consumption, and nearly unlimited endurance. No existing memory provides all 5. Phase change memory retains data and can be fast, but heat and material changes create challenges. Magnetic memory offers strong endurance, but scaling and density remain difficult. Resistive memory can switch quickly, yet device-to-device variation complicates large arrays. Ferroelectric memory is promising, but integration and long-term reliability remain active engineering problems. POX adds another candidate. Its unusual advantage is that it remains a charge storage device related to flash, but changes the injection mechanism using two-dimensional materials. That connection to familiar flash principles could help engineers understand and adapt the technology. Still, universal is an extremely demanding word. A memory can be fast but too expensive, persistent but insufficiently dense, efficient but difficult to manufacture. The winner will not be determined by one record. It will be determined by which technology can survive a factory. What still has to happen? The first challenge is scale. The research team must move from small arrays to millions and eventually billions of memory cells. Yield becomes harder as the array grows. A 94% yield sounds strong for an early research chip. For mass production, even a small defective percentage can become unacceptable when billions of cells are involved. The second challenge is uniformity. Atomically thin materials must behave consistently across large wafers. A small difference in thickness, contamination, or contact resistance can change device performance. The third challenge is density. The memory must store enough bits per unit area to justify its cost. The fourth challenge is voltage. The prototype used programming voltages around 5 volts. Future systems may need lower operating voltage to reduce power and simplify integration. The fifth challenge is economics. Graphene and other two-dimensional materials must be deposited, patterned, and connected using processes compatible with high-volume semiconductor manufacturing. A technology can outperform existing memory and still lose if each chip costs 10 times more. The final challenge is time. The researchers have discussed expanding toward much larger integration within several years. That is ambitious. Even successful semiconductor technologies can require a decade or more to move from laboratory demonstration to widespread commercial use. My take. My view is that the most important result is not the 100,000 times headline. The speed is spectacular. But research laboratories produce spectacular isolated numbers regularly. What makes this story different is the sequence. First, the team demonstrated a 400 picosecond non-volatile flash device. Then it built a functional hybrid chip around the same broader two-dimensional memory concept. The system was slower than the record prototype, but it could execute instructions, perform parallel operations, and access memory randomly. That is progress in the correct direction. The first result said, the physical speed limit can be broken. The second said, the device can begin participating in a real circuit. China has not eliminated RAM. It has not produced a commercial universal memory chip. And no laptop shipping today contains POX memory. But the traditional boundary between fast volatile memory and slow persistent storage looks less permanent than it did before. For most of computing history, the rule was simple. Anything fast enough to serve the processor forgot when power disappeared. Anything that remembered was forced into a slower tier. The Fudan experiments show that this rule is not fundamental. It is a consequence of the materials and device structures we currently use. Change the material, reshape the electric field, accelerate the carriers differently, and flash memory can enter a speed range that once appeared impossible. The hardest work begins now: scaling, manufacturing, reducing voltage, improving yield, and proving that the technology can remain reliable outside a research laboratory. But every commercial memory technology began with a device that looked too small, too unusual, or too expensive to matter. The question is whether POX follows the same path or remains a brilliant record in a scientific paper. So what do you think? Could ultra-fast non-volatile memory eventually replace both RAM and flash with one universal technology? Or will manufacturing cost and scaling challenges keep the computer's memory hierarchy intact? Let me know your view in the comments. And if you want more grounded stories about the chips, materials, and hidden engineering breakthroughs reshaping computing, subscribe to Eastern Engine, because the next revolution in memory may not be a drive with more capacity, it may be a chip that refuses to forget. For years, the entire world agreed on one thing. If you want to build the most advanced computer chips on Earth, the tiny, mind-bendingly complex processors that power your phone, your laptop, the AI everyone's talking about, you need one specific machine, a single machine built by a single company in a single country. Without it, the experts said, you simply cannot cross a certain line. You'd be stuck, permanently. That machine was deliberately kept out of China's hands. The logic was airtight. No machine, no advanced chips, no way forward. China would hit a wall at a certain level of technology and stop there, frozen, while everyone else raced ahead. Except China just walked straight through that wall. A Chinese company called SMIC has now started mass-producing a 5-nanometer class chip, a genuinely advanced processor, a full generation ahead of what most analysts swore was China's ceiling. And it did it without the machine it was banned from buying. The chip is real. It's already inside a phone you can hold in your hand, and its existence is quietly rewriting one of the core assumptions of the entire global technology war. Now, like every story on this channel, there's important fine print, and I'm going to give you all of it, honestly, because the truth here is more interesting than the hype on either side. By the end of this video, you'll understand exactly what SMIC built, why everyone said it was impossible, the brutal trick they used to pull it off, what it cost them, and why this single chip has people in boardrooms around the world genuinely rattled. Let's get into it. To understand why this is such a big deal, you need to understand the machine. Because this isn't just a machine. It might be the single most complex object humanity has ever manufactured. It's called an EUV lithography system, extreme ultraviolet. And making chips is, at its heart, a printing process. You're printing unimaginably tiny patterns onto a wafer of silicon, patterns so small they're measured in nanometers, billionths of a meter. The smaller and finer you can print those patterns, the more transistors you cram onto a chip, and the more powerful it becomes. That's been the engine of all computing progress for decades. To print the very finest patterns, the cutting edge, 5 nanometers and below, you need light with an extremely short wavelength. And generating that specific kind of extreme ultraviolet light is so monstrously difficult that only one company on the entire planet can build a machine to do it, a Dutch firm called ASML. Just one, nowhere else. How hard is it? Each EUV machine costs around $200 million. It weighs as much as 2 loaded buses. To create the light, the machine fires a high-powered laser at microscopic droplets of molten tin 50,000 times per second. It contains the flattest mirrors ever manufactured by human beings. It is a genuine marvel, and there is exactly one source for it on Earth. So here's what happened. The United States, wanting to slow China's technological rise, pressured the Netherlands to block the sale of these EUV machines to China. The reasoning was simple and on paper, devastating. EUV is the only known way to make chips at 5 nanometers and below. China can't buy EUV. Therefore, China is locked out of advanced chips, stuck at an older level called 7 nanometers, unable to go further. That was the plan. The entire strategy rested on one belief, that EUV was absolutely, non-negotiably required to break past 7 nanometers. China just proved that belief wrong. The company at the center of this is SMIC, Semiconductor Manufacturing International Corporation, China's largest chipmaker. And in late 2025, something showed up that analysts immediately pounced on. Huawei released a new phone with a processor inside it called the Kirin 9030. And when the respected analysis firm Tech Insights physically tore that chip apart to examine it, which is exactly what these firms do, They literally dissect chips under powerful microscopes. They confirmed something remarkable. The Kirin 9030 was built on a brand new SMIC process called N+3, a 5-nanometer class node, China's most advanced chip ever made in volume production, sitting inside a consumer phone. And critically, made without a single EUV machine. Let that land for a second. This is a full generation jump. SMIC's previous best was a 7-nanometer class process called N+2. That's what powered Huawei's earlier AI chips. Jumping from 7-nanometer to 5-nanometer class is not a small step. It's the kind of leap the entire industry insisted was impossible without EUV. SMIC didn't just inch forward, it leapfrogged an entire generation, using only the older machines it's actually allowed to have. So the obvious question is, how? If EUV is the only way to print patterns that fine, and China doesn't have EUV, how is there a 5-nanometer chip sitting inside a phone right now? The answer is one of the most impressive, and most punishing, feats of engineering in the modern chip industry. And once you understand it, you'll understand both why it's brilliant and why it comes at a brutal price. Here's the workaround, and I'm going to make it simple. The machine China is allowed to have is the previous generation tool, called DUV, Deep Ultraviolet. It uses light with a longer wavelength than EUV. Think of it this way. EUV is like a fine-tipped pen that can draw an incredibly thin, crisp line in a single stroke. DUV is like a fat marker. With one stroke of a fat marker, you simply cannot draw a line as thin as the fine pen can. So how do you draw an ultra-thin line with a fat marker? You cheat. You don't draw the line directly, you draw around it. You make multiple careful passes, each one laying down part of the pattern, building up the final ultra-fine result through a sequence of steps that no single pass could achieve. In the industry, this is called multi-patterning, and SMIC used an especially aggressive form of it known as self-aligned quadruple patterning. Quadruple, as in 4 times. Picture trying to paint an incredibly intricate, razor-sharp design on a wall. The fine-tipped airbrush, EUV, does it in one clean pass. You don't have the airbrush. So instead, you paint the wall, then mask part of it, and paint again, then mask and paint again, and again, 4 separate, perfectly aligned passes, slowly sculpting a level of detail the fat brush could never achieve in one go. Done perfectly, the final result rivals what the airbrush would have produced. That is, essentially, what SMIC did. They used brute force, engineering brilliance and sheer stubbornness to squeeze a 5-nanometer class result out of machines that were never designed to reach it. Where EUV does the job in one elegant exposure, SMIC stacks pass after pass after pass, each one demanding flawless precision, to mimic what the forbidden machine does naturally. It's a genuinely stunning achievement. It proves that the wall everyone thought was solid had a way around it after all. But, and this is the part the hype videos skip, painting the same wall 4 times instead of once is not free. It costs you, badly. And that cost is the whole reason this story has a second, more sober half. Here's where I have to be completely straight with you, because this is exactly the kind of story that gets twisted in both directions online. Every single one of those extra patterning passes is another chance for something to go wrong. Each pass has to line up with the previous one with almost supernatural precision. If the alignment drifts even slightly across 4 stacked passes, the tiny features blur, defects creep in, and the chip fails. So the more passes you add, the more chips come out broken. This is the central problem, and the industry has a word for it: yield. Yield is the percentage of chips on a wafer that actually come out working. With EUV's clean single pass, yields are high. With SMIC's 4-pass brute force method, yields are reportedly much lower, meaning a larger share of every batch is wasted. Analysts at Tech Insights specifically flagged yield as the key challenge. More broken chips per batch means each working chip is dramatically more expensive to produce. There are 2 more honest caveats you deserve to hear. First, even though SMIC reached a 5-nanometer class node, experts note its actual transistor density still falls short of the true 5-nanometer chips that companies like TSMC and Samsung made years ago. It's 5-nanometer class, a major achievement, but not a perfect match for the global leaders. Some analysts argue it sits closer to a souped-up 6-nanometer in real-world terms. And second, the most important nuance of all, while SMIC did this without EUV, it most likely still used advanced DUV machines that were originally imported from ASML before the tightest restrictions hit. So this isn't yet a 100% homegrown miracle. The achievement is doing it without EUV, not yet doing it without any foreign tools at all. That fully independent version is what China is racing toward next, and there are already reports of domestic Chinese DUV scanners and even an EUV prototype in testing. But we're not there yet, and I won't pretend we are. So here's the fair summary. SMIC has not matched TSMC, and it's not doing this cheaply or with perfect independence. What SMIC has done is shatter the belief that 5nm class chips were flat out impossible without EUV. The "it can't be done" wall is gone. What remains is an "it's expensive and hard" wall, and that is a completely different and far more survivable kind of problem. So, if it's expensive, lower yield, and not quite TSMC level, why are people genuinely rattled by this? Why does a single phone chip matter so much? Because of what it proves about the direction of the entire strategy. The export controls were built on a specific bet that cutting off EUV would stop China cold at 7nm. Not slow it, stop it. The whole point was a hard ceiling. SMIC just demonstrated that the ceiling isn't a ceiling at all. It's a speed bump, a painful, expensive, yield-crushing speed bump, but China drove right over it anyway. The wall meant to halt China's progress turned out to be something China could climb, slowly and at great cost, but climb nonetheless. And here's the deeper pattern, the one we keep seeing on this channel across story after story. Cut off from EUV, China didn't give up. It poured everything into mastering DUV multi-patterning to a degree nobody thought commercially viable. The restriction didn't kill the ambition. It redirected it, and forced a kind of engineering creativity that might never have happened otherwise. The same shape as the light chips, the GPU-free supercomputer, the new approach to Moore's law. A wall goes up, the water finds another way around it. There's also a brutal economic irony buried in here. Those same restrictions that blocked NVIDIA's top chips from China handed Huawei an enormous captive domestic market with no foreign competition, which gave Huawei and SMIC both the motivation and the guaranteed customers to justify pushing through these insanely difficult, expensive processes. In trying to choke the supply, the restrictions may have supercharged the demand for a homegrown alternative. The pressure designed to weaken the domestic industry instead gave it a reason to grow up fast. None of this means China has won the chip war. It hasn't. TSMC is still ahead. The cost and yield problems are real and serious. But the core assumption that a single banned machine could permanently cap China's progress, that assumption is now visibly, demonstrably cracked. And rewriting a foundational assumption like that is exactly the kind of thing that keeps strategists up at night. Let me zoom out because the trajectory matters more than this one chip. Right now, SMIC's path forward splits into two races. The first is improving yield, taking this expensive, difficult 4-pass process and grinding it down, batch after batch, into something cheaper and more reliable. That's the unglamorous, year-after-year factory work that turns a breakthrough into a business. History shows that yields, once a process exists at all, tend to climb steadily as engineers learn the quirks of their own line. Painful today doesn't mean painful forever. The second race is independence, replacing those imported DUV machines with fully domestic Chinese ones, so the entire process, top to bottom, can be done with no foreign parts at all. That's the holy grail Beijing is openly chasing, and there are already early reports of domestic immersion DUV scanners in testing, and even a homegrown EUV prototype reportedly undergoing trials. If, and it's still an if, China eventually cracks its own EUV machine, the entire export control strategy could lose much of its remaining grip. The honest near-term reality is that China is still a step behind the absolute frontier, and it's paying more to be there. But the gap between permanently locked out and a step behind and catching up is the difference between two completely different futures. SMIC just moved China from the first category into the second, and in a race like this, the direction you're moving matters far more than exactly where you stand today. Here's my honest opinion. I think the two loudest reactions to this are both wrong, and the truth sits in the uncomfortable middle. The people shouting China has caught up and beaten the sanctions are way ahead of the facts. The yields are poor, the costs are high. It's not true TSMC grade 5nm, and it probably still leans on imported tools. Anyone selling you China 1 is selling a fantasy. But the people insisting, this is nothing, it's expensive and low yield, ignore it, are making the bigger and more common mistake. Because they're focused on the cost and missing the proof. The entire export control strategy was built on the word impossible. EUV is required, full stop, no workaround. SMIC just turned impossible into expensive, and in engineering, those are not remotely the same thing. Impossible is a wall, expensive is a to-do list. You can grind down expensive over time. You cannot grind down impossible. What strikes me most, yet again, is the pattern. Every time a barrier goes up to contain China's technology, the response isn't surrender. It's a workaround that nobody thought was viable, forced into existence by the pressure itself. Light instead of electrons, CPUs instead of GPUs, and now 4-pass DUV instead of the one machine they were denied. I genuinely don't think that's coincidence anymore. Necessity isn't just the mother of invention here, it's becoming the entire engine of an industry. So here's my question for you, and I want your honest answer, because this is the real debate. Did the export controls fail by proving they can be engineered around, or did they actually succeed by forcing China to spend enormous money and effort on a slower, more expensive path it otherwise wouldn't have needed? In other words, is making your rival's progress expensive a win, even if you couldn't make it impossible? Drop your real take in the comments. I read every single one, and this one genuinely splits smart people down the middle. If you want to keep following this, the workarounds, the breakthroughs, the moves the rest of the world keeps underestimating until they can't, subscribe to Eastern Engine and hit the notification bell. Chips, light, energy, the whole foundation of modern technology is being rewritten right now, and we break it all down before the mainstream catches on. Thanks for watching. I'll see you in the next one. For nearly 50 years, there was a number that every fusion scientist on Earth treated as a law of nature. It wasn't written into the universe like gravity or the speed of light. It was a wall discovered by experiment, a hard ceiling that showed up again and again, in reactor after reactor, country after country. Push your fusion fuel past this particular density, and the whole thing falls apart. The superheated plasma, the star stuff you're trying to control, destabilizes, tears itself apart, and the reaction collapses. Every time. Scientists gave it a name, the Greenwald limit, and it was one of the great frustrating barriers standing between humanity and the dream of limitless clean energy. Because to make fusion actually produce more power than it consumes, you need that fuel, dense and hot and stable all at once, and the Greenwald limit said you couldn't have all three. Then, on the first day of 2026, a team of Chinese scientists running a reactor they nicknamed the Artificial Sun did something the textbooks said shouldn't be possible. They blew straight past that limit, not by a little, but by as much as 65%. And the plasma didn't collapse. It stayed stable. It held. A wall that stood for nearly half a century just developed a door. Now, and you know this is coming if you watch this channel, there is crucial context here, and I'm going to give you all of it, honestly, including why this is not the free energy by next year miracle some headlines are selling. But the real story, the true one, is arguably more important than the hype. By the end of this video, you'll understand what fusion actually is, why this specific limit terrified scientists for 50 years, exactly how China broke it, and what it really means for the future of energy on this planet. Let's get into it. Let's start with the basics, because the nickname is doing a lot of work, and it's worth understanding why it's earned. Look up at the sun. Every bit of warmth and light pouring off it comes from one process: fusion. Deep in the sun's core, under crushing pressure and unimaginable heat, hydrogen atoms are smashed together so hard that they merge, they fuse into helium. And every time they do, a tiny bit of mass gets converted into an enormous burst of energy. That's it. That's what powers every star in the sky. It is, quite literally, the engine of the universe. Now imagine bottling that. Imagine building a machine on Earth that recreates the heart of a star, that fuses atoms the same way the sun does, and harnesses the energy that pours out. That's the dream of fusion power, and the prize is almost too good to believe. The fuel is essentially a form of hydrogen you can pull from seawater. It produces no carbon emissions. It can't melt down like a conventional nuclear plant. It generates only tiny amounts of short-lived waste compared to the fission reactors we use today. A single glass of fusion fuel could, in theory, hold the energy of barrels and barrels of oil. Clean, safe, and very nearly limitless. That's why nations have poured tens of billions of dollars into chasing it for over half a century. It's arguably the most valuable engineering goal in human history. The machine China uses to chase it is called EAST, the Experimental Advanced Superconducting Tokamak, located in Hefei. A tokamak is a specific design, a giant donut-shaped chamber wrapped in incredibly powerful magnets. Here's the central problem it solves. To make atoms fuse on Earth, you have to heat your hydrogen fuel to insane temperatures. EAST runs its plasma well beyond 100 million degrees Celsius, which is several times hotter than the core of the actual sun. And here's the obvious question. What do you build a container out of that can hold something hotter than the center of a star? The answer is nothing. No material on Earth can touch it. So the tokamak doesn't use a physical container for the hot part. It uses a cage made of pure magnetic force, suspending that star-hot plasma in midair so it never touches the walls. That is the artificial sun, a man-made knot of magnetic fields holding a sliver of star glowing at 100 million degrees in the middle of a steel donut in eastern China. And the limit they just broke is all about how much fuel you're allowed to pack into that magnetic cage. Here's where we get to the heart of it, the Greenwald limit, and why it haunted fusion for so long. To get useful power out of fusion, 3 things have to be true at once. Your fuel has to be hot enough, it has to be held together long enough, and it has to be dense enough, meaning you've packed enough fuel particles into the space for them to actually collide and fuse in large numbers. Temperature, time, and density. Crank up all 3 together, and you approach the Holy Grail. Ignition, the point where the reaction produces more energy than you put in and becomes self-sustaining, like a fire that keeps itself burning. The problem was density. Back in the 1980s, a physicist named Martin Greenwald noticed a stubborn pattern across fusion experiments. Every tokamak seemed to hit a density ceiling, try to pack in more fuel beyond a certain point, and the plasma would suddenly become violently unstable. It would develop disruptions, lose its confinement, and the reaction would crash. It happened so consistently that it became an empirical law of the field. The Greenwald limit, a line you simply did not cross, and it was a genuine roadblock to the entire dream. Because if you can't increase density past this line, you're capped on how much fusion power a reactor of a given size can produce. It forced designs to be bigger, more expensive, more conservative. For decades, fusion scientists essentially had to build around this wall, accepting it as a fixed fact of nature. Here's the part that makes the new result so striking. For nearly 50 years, most people assumed the Greenwald limit was something close to fundamental, a hard rule baked into how plasmas behave. But a newer theory suggested something more hopeful. That the limit wasn't a law of physics at all. It was a consequence, a side effect of how the plasma interacts with the walls of the reactor as it forms. And if that was true, then in principle, with exactly the right conditions, you might be able to sidestep it entirely. That theory had a name: plasma wall self-organization. It was elegant, it was promising, and for years, nobody had ever proven it actually worked in a real reactor. It was a beautiful idea waiting for evidence. China's artificial sun just provided that evidence. So how do you walk through a wall that stopped everyone for 50 years? The answer is surprisingly subtle and genuinely clever. The Chinese team, led by Professor Ping Zhu and Associate Professor Ning Yan, didn't break the limit with brute force, not by simply building bigger magnets or cranking up the power. They broke it by carefully choreographing the very beginning of the reaction, the startup phase, the first moments when the plasma is being born. Here's the core idea, simplified. Normally, as you cram more fuel into the plasma, the edge of that plasma, where it meets the reactor, gets cold and dirty. Impurities build up, energy leaks away, and that cascade is what triggers the instability that crashes the whole thing at the Greenwald limit. The wall and the plasma get into a destructive relationship. The Chinese team's insight was to manage that relationship from the very first instant. They precisely controlled 2 things: the amount of fuel gas they started with, and a special type of heating called electron-cyclotron resonance heating, essentially using carefully tuned microwaves to energize the electrons in the plasma at exactly the right moment. By dialing in those startup conditions just so, they got the plasma and the reactor walls to settle into a balanced, self-regulating relationship, the self-organization the theory predicted. In that balanced state, something remarkable happens. The plasma stops fighting to high density. Instead of becoming unstable as you pack more fuel in, it stays calm and confined. The team sustained stable plasma at densities between 1.3 and 1.65 times the Greenwald limit. That's 30 to 65% past the line that crashed reactors for half a century, with no disruptions. And critically, this was the first time anyone had ever experimentally confirmed that the self-organization theory actually works in a real tokamak. They didn't just break a record, they proved a theory that could reshape how every future reactor is designed. It's the difference between forcing a locked door and discovering it was never truly locked. You just had to turn the handle the right way. That's what makes this more than a number. It's a new understanding of how the rules actually work. Now here's where I have to be completely straight with you, because this is exactly the kind of story that gets wildly overhyped, and I'd rather you trust this channel than mislead you. This breakthrough does not mean fusion power is arriving next year, or even this decade. It does not mean your electricity bill is about to vanish, and here are the honest reasons why. First, and most important, no fusion reactor on Earth, including East, currently produces net positive energy when you account for the entire system. Right now, these machines still consume more energy to run than they generate. Breaking the density limit is a crucial ingredient toward changing that, but it is not the same as achieving it. East is an experiment, not a power plant. it will never put a single watt into anyone's home. Second, fusion still faces brutal engineering challenges that have nothing to do with this particular limit. Building materials that can survive years of relentless neutron bombardment and star-level heat. Sustaining the reaction not for seconds or minutes, but indefinitely. Turning the heat into electricity efficiently and affordably. These are enormous, unsolved problems, and progress on the materials side has actually been slower than progress on the plasma physics side. And third, even the scientists involved are careful here. As one expert put it, this breakthrough improves confidence in future reactor designs rather than accelerating timelines. It doesn't suddenly make commercial fusion arrive sooner. It makes the eventual reactors potentially smaller, cheaper, and easier to design, because they may not need to be as enormous or as conservative about density as everyone assumed. So the honest framing is this: China did not just solve fusion. What China did is remove one of the longest-standing roadblocks on the path, and prove that a barrier everyone treated as nearly fundamental was actually beatable. That's not the finish line, but it's a genuine, verified, peer-reviewed step toward it, published in the journal Science Advances, and it matters for every fusion project on Earth, not just China's. Here's the part that makes this bigger than a single experiment in Hefei. This discovery doesn't just help China. Because it's a fundamental insight into how plasma behaves, it potentially helps everyone chasing fusion. The world's largest fusion project, ITER, a massive international collaboration in France involving dozens of countries, could potentially use this density-free regime to reach its own goals more easily. The same is true for the wave of private fusion startups that have collectively attracted billions of dollars in investment. A barrier that constrained all of their designs may have just been loosened for all of them at once. There's even a fascinating bonus buried in the data. For years, there's been a rivalry between two reactor shapes, the donut-shaped tokamaks and a twisted design called a stellarator. Each had different strengths around density. The EAST results suggest tokamaks can now operate in a high-density regime that was previously thought to be a stellarator's advantage, effectively giving the most common reactor design a new superpower it wasn't supposed to have. And then there's the strategic picture, which is impossible to ignore. China has now formally written controllable nuclear fusion into its national 5-year plan as a major strategic priority, with a roadmap targeting a pilot reactor around 2035 and a demonstration reactor by roughly 2045. While much of the world has treated fusion as a someday maybe science project, China is treating it as a national industrial goal with a timeline and serious funding behind it. EAST breaking the Greenwald limit isn't an isolated lab result. It's one milestone in a deliberate, long-term national march toward being the country that figures out how to put a star in a bottle first. And whoever does that first, whoever cracks practical, commercial fusion, doesn't just win a scientific prize. They potentially gain control over the cheapest, cleanest, most abundant energy source in human history. The country that masters fusion could reshape the entire global balance of power, because energy underlies everything, every factory, every data center, every economy. This isn't only about science, it's about who powers the next century. Here's my honest opinion. I think the right way to hold this is to resist both of the easy reactions. The breathless headlines screaming "China just solved fusion, unlimited energy is here," are flatly wrong. We're still decades from a commercial reactor, no machine yet produces net energy, and the hardest engineering problems remain unsolved. Anyone promising you a fusion-powered home by 2030 is selling fantasy. But the cynics who shrug and say fusion is always 30 years away, ignore it, are making a subtler mistake. Because the nature of the progress is changing. For 50 years, the Greenwald limit was treated as a near-permanent wall. China just demonstrated, with peer-reviewed evidence, that it was never a wall at all, just a problem waiting for the right understanding. That's not 30 years away, that's a barrier falling in real time. When the supposedly impossible limits start breaking one by one, the old joke about fusion being perpetually distant stops being quite so funny. What strikes me most is the shift in posture. Fusion used to be a graveyard of broken promises that no one wanted to bet on. Now, there's billions in private money flowing in, nations writing it into industrial plans, and reactors breaking limits that stood since the 1980s. The momentum is real, even if the finish line is still far off. And the fact that one of the biggest recent breakthroughs came out of an artificial sun in eastern China tells you something about who's taking this prize most seriously right now. So here's my question for you, and I genuinely want your honest answer. Do you think we'll see practical, commercial fusion power in our lifetimes? Or is it still the technology that's always 30 years away, no matter how many limits get broken? Are you a fusion optimist or a fusion skeptic? Drop your real take in the comments. I read everyone, and I have a feeling this splits people right down the middle. If you want to keep following this, the breakthroughs, the broken limits, the race to power the future before the rest of the world catches on, subscribe to Eastern Engine and hit the notification bell. Energy, chips, the foundations of the modern world are being rewritten right now, and we break it all down clearly and honestly. Thanks for watching. I'll see you in the next one. On May 25, 2025, something quietly historic happened that most of the global media barely covered. A freight train pulled out of a station in western China, carrying 32 containers of cargo. 15 days later, that same train arrived in Iran, more than 10,000 kilometers away, having crossed 4 separate countries, 2 major mountain ranges, and some of the harshest desert terrain on the planet, without ever touching an ocean. The journey that train completed in 15 days would have taken between 30 and 40 days by sea. But the duration is not really the story. The story is the route itself. For decades, moving large volumes of goods between Asia and the Middle East has meant one thing: ships, oceans, and a small handful of narrow waterways that determine which cargo arrives where. That arrangement has shaped global trade, global politics, and the balance of economic power for generations. This railway represents something different. It is the first serious attempt in modern history to build a major commercial corridor between 2 continents that bypasses maritime trade routes entirely. And the implications of that, once you sit with them, are genuinely significant. In this video, we are going to walk through how this railway was built, what it means for the countries connected by it, the broader expansion plan that involves 5 additional nations, and the parallel Arctic shipping route that is developing alongside it. The full picture is more strategic and more carefully designed than any single train run can communicate on its own. To understand why this railway exists, you first have to understand a single narrow stretch of water that almost no one outside the shipping industry talks about. It is called the Strait of Malacca, and it sits between Malaysia and Indonesia. Roughly 94,000 ships pass through it every year: oil tankers, container vessels, bulk carriers, and everything in between. It is one of the most heavily trafficked maritime corridors on the planet, and it functions as the primary gateway between the Indian Ocean and the Pacific. For China, this passage is not just useful, it is structural. Approximately 80% of China's oil imports flow through this single waterway. The energy that powers Chinese factories, vehicles, power grids, and consumer products travels through one narrow corridor on its way to refineries and storage facilities across the country. Now consider what that means in practical terms. If the Strait of Malacca were to close for even a short period, the economic effects would compound rapidly. Estimates put the daily cost of a closure in the tens of millions of dollars, and a sustained disruption would begin shutting down industrial activity within weeks. The world's second largest economy depends on a single maritime passage staying open and accessible. This is where geopolitical context enters the picture. Since 2019, the United States has maintained the ability to dock its naval vessels at deepwater facilities in Singapore, which sits at the southern entrance to the Strait of Malacca. In a major conflict scenario, the U.S. Navy has the capability to severely restrict maritime traffic through this corridor on a short timeline. That is not a theoretical concern in Beijing. It is a planning assumption. There are alternative maritime routes that could in theory be used. The Lombok Strait and the Sunda Strait both connect the same broader regions, but neither has the port infrastructure, the depth profile, or the logistical capacity to absorb meaningful volume on short notice. Switching even a portion of China's energy imports to these backup routes would require years of port expansion and supply chain restructuring. The conclusion that Chinese strategic planners reached was straightforward. The vulnerability of relying on a single maritime choke point was unacceptable in the long term, and the solution was to build a way to move energy and goods that did not depend on the ocean at all. The country whose geography made that solution possible was Iran. The route itself is an engineering challenge of a kind that very few projects in modern history have attempted at this scale. Starting in western China, the corridor heads west through Kazakhstan, then south through Uzbekistan and Turkmenistan, and finally crosses into Iran, where it terminates at the apron dry port near Tehran. 10,400 kilometers of connected railway track, spanning 4 sovereign nations, traversing some of the most punishing terrain on Earth. The terrain alone tells you something about the ambition behind this project. Vast stretches of open desert where shifting sand can bury rail infrastructure between maintenance cycles. Mountain ranges located in seismically active zones where the ground beneath the track is itself unstable. Summer temperatures that warp metal and crack concrete. Winter conditions cold enough to disrupt fuel and lubrication systems. The total cost of the project exceeded $2 billion, financed through a combination of Chinese policy banks, the Asian Infrastructure Investment Bank, and bilateral loan agreements between the participating governments. One of the most technically demanding aspects of the project was solving the rail gauge problem. China and most of Central Asia use different track widths, a legacy of historical infrastructure decisions made over a century ago. Russia and the former Soviet states use a broader gauge than the Chinese network, which historically meant cargo had to be transferred manually between different carriages at each border. That added hours to every shipment and made the route impractical for time-sensitive freight. The engineering response was the construction of automated bogie exchange facilities at the key border crossings. These systems allow the same container, on the same shipping platform, to be transferred between rail systems of different gauges in under 30 minutes. The technology is not new, but its deployment at this scale and across this many borders is unprecedented. There is also a structural detail that speaks to how seriously both sides took this project's strategic importance. Sections of the Iranian portion of the railway were built underground rather than at surface level. Officially, this protects the line from extreme weather. Realistically, it also protects the infrastructure from potential aerial threats. That is not the kind of design decision you make for a routine commercial freight corridor. When the first train completed the full route in May 2025, Chinese state media described the corridor as an energy lifeline between the two countries. That framing was not exaggeration. It was a clear statement of intent. The context for understanding why this railway matters so much to Iran requires looking at the broader economic situation the country has been operating under for years. International sanctions have constrained Iranian access to global financial systems for over a decade. Major banks have been disconnected from international transaction networks. Foreign companies that pursue significant business relationships with Tehran have faced regulatory consequences in Western jurisdictions. Oil buyers have been pressured through secondary sanctions to avoid Iranian crude. The cumulative effect of these measures has been to push Iran toward economic partnerships that operate outside the dollar-denominated global trade system. China made the strategic decision to be that partner. In 2021, the two countries signed a 25-year comprehensive cooperation agreement valued at approximately $400 billion. This was not a routine trade agreement. It was a generational commitment covering energy, infrastructure development, manufacturing partnerships, and technology cooperation. The follow-through has been substantial. In 2024, China purchased the overwhelming majority of Iran's crude oil exports, representing roughly $29 billion in trade. Iran's total oil revenue for the year reached approximately $67 billion, the highest figure the country had recorded in over a decade. The official sanctions remained in place. Their practical impact on Iranian oil exports had diminished significantly. With the railway now operational, those trade flows can move along a corridor that is structurally insulated from external interference. Iranian oil can move onto trains, travel across Central Asian territory, and arrive in China without involving any Western financial institution, insurance provider, or shipping line at any point in the chain. There is also a currency dimension to this arrangement that deserves attention. Since 2012, China has been settling its Iranian oil purchases in yuan rather than US dollars. This sounds like a technical detail. It is actually one of the most quietly consequential elements of the entire relationship. The dollar's role as the default global currency for energy trading is one of the foundations of contemporary American economic influence. Every major oil transaction conducted in an alternative currency reduces that role incrementally. Russia has pursued a parallel strategy with its own energy exports since 2022. The combined volume of energy trade settling outside dollar systems has grown notably over recent years, and this railway adds further infrastructure to that broader shift. Iran's geography also gives it strategic value that extends well beyond its own borders. The country sits directly along the Strait of Hormuz, through which approximately 20% of global oil shipments pass. It also has direct land borders with several Central Asian nations that have historically struggled with limited access to ocean trade routes. For landlocked countries like Tajikistan, Kyrgyzstan, and Afghanistan, a railway network connecting through Iran to Persian Gulf ports represents a fundamental change in their economic options. China gains influence across a region that has traditionally operated within other spheres of geopolitical power. It is a development that benefits multiple parties, which is exactly the kind of arrangement that tends to grow rather than fragment. The China to Iran corridor is the foundation of a larger network that has been under development in parallel. The Five Nations Railway Corridor project connects China, Kyrgyzstan, Tajikistan, Afghanistan, and Iran in a single integrated rail network. The new track required for the project totals around 1,300 kilometers, with the largest single section running through northern Afghanistan. The initial framework agreement was signed in late 2014, and the project has continued advancing through various phases since then. A significant milestone occurred in May 2023, when the first cargo run traveled from Iran into Afghanistan, along the Kaf-Herat segment of the network. That shipment carried 655 tons of railway construction equipment, meaning the network was, in a literal sense, transporting the materials needed for its own expansion. In May 2025, senior officials from Iran, China, Kazakhstan, Uzbekistan, Turkmenistan, and Turkey met in Tehran specifically to discuss the next phase of the transcontinental rail expansion. The momentum behind the project has accelerated rather than slowed. For the landlocked nations involved, the implications are significant. These countries have operated with severe disadvantages in global trade since their independence. Moving goods to or from their territories has always required navigating multiple borders and ultimately depending on ports they did not control. A rail network connecting them to Persian Gulf shipping points changes that situation in fundamental ways. The financing structure supporting all of this is also worth understanding. China's Belt and Road Initiative has committed well over $1 trillion to infrastructure projects globally since its launch in 2013. Central Asia represents one of its most strategically concentrated investment zones. The loan structures attached to these railway projects typically feature extended repayment timelines and resource-backed arrangements, which create durable economic relationships between China and partner countries. While the overland railway is moving freight east-west, China is simultaneously developing a maritime corridor in the opposite direction, one that runs through the Arctic. The Northern Sea Route follows the northern coast of Russia through Arctic waters and represents the most direct shipping path between Asia and Europe. A journey that takes around 45 days via the Suez Canal can be completed in roughly 30 days via the Northern Sea Route. Until recently, the obstacle was simple. Most of the route was locked under ice for most of the year, leaving only a brief 88-day operational window annually. That window is expanding. Climate change has steadily increased the period during which Arctic shipping is viable, and the operational window now extends to around 90 to 100 days per year. In June 2024, Russia and China formally agreed to develop year-round container shipping along this corridor. Russia has been investing in the icebreaker fleet required to make this practical. The latest generation of Russian nuclear-powered icebreakers, including the Arktika and the Sibir, can operate continuously through ice up to several meters thick. The Arktika weighs 33,000 tons, is powered by 2 nuclear reactors, and can operate for 7 years between refueling cycles. The strategic significance of the Arctic route lies in what it bypasses. The Suez Canal, despite being administered by Egypt, operates within a broader Western economic ecosystem. Insurance, financing, and logistics for vessels using it overwhelmingly involve European and American institutions. A functioning Arctic corridor allows trade to flow without any of those touch points. What is taking shape is a pattern. One corridor cutting across Central Asia by land, another opening up through the Arctic by sea, both moving in directions that reduce dependency on the maritime routes and financial infrastructure that have defined global trade for generations. It is worth being honest about the limitations of what this railway can accomplish in the short term. A single oil supertanker carries roughly 2 million barrels of crude oil, the equivalent of hundreds of freight train shipments. Scaling rail transport to fully replace maritime shipping is simply not realistic in any near-term timeframe. The corridor also faces real operational challenges. Multiple border crossings mean coordination overhead. Desert conditions stress rail infrastructure heavily. Fixed rail lines have inherent vulnerabilities that ocean-going vessels do not share. The early operational record reflects some of these realities. Within weeks of the inaugural freight run in May 2025, regional security developments interrupted further commercial services along sections of the corridor. The launch did not progress smoothly into routine operations, but focusing only on the operational hiccups misses what this railway actually represents. It does not need to replace maritime shipping to matter. It needs to exist as a working option that gives all parties involved choices they did not previously have. When China has a functioning land route for at least a portion of its energy imports, the strategic leverage associated with maritime choke points diminishes. When Iran has a major trading partner operating through infrastructure that exists outside the reach of Western financial systems, the practical impact of sanctions weakens. When Central Asian nations have rail access to global markets, they gain leverage in choosing their economic partners. There is also a broader signaling element to consider. Every kilometer of new track in this region sends a quiet message to other countries watching from the sidelines. There are alternatives to the existing global trade and financial architecture, and the alternatives are being built in real time. What I find most interesting about this story is not really the train itself. It is what the project tells us about how infrastructure is being used as long-term strategy rather than short-term capacity. The countries building this railway are not trying to win a single contest with the West. They are constructing an alternative architecture for trade, finance, and energy that can operate in parallel to the existing system. It does not need to replace anything to be effective. It just needs to exist, function reliably, and demonstrate that other options are viable. That is a much harder thing to respond to than a single competitive challenge, because it is not really a confrontation. It is the steady, patient construction of a different way of doing things, one project at a time, across a region that has historically been at the margins of global trade. Whether this approach succeeds at the scale its architects intend will depend on factors that take decades to play out: regional stability, sustained investment, technological developments, and broader geopolitical shifts. But the work being done right now is laying foundations that will shape that future regardless of how individual events unfold. My question for you is this: do you think infrastructure projects like this railway will end up shifting the balance of global trade meaningfully over the next 20 years? Or will the existing maritime system remain dominant despite these alternatives? Drop your honest answer in the comments. I am genuinely curious which way most people are leaning on this one. If this kind of deep dive analysis on global infrastructure and engineering strategy is what you come here for, please subscribe to Eastern Engine and hit the notification bell. We cover the major projects reshaping the global economic landscape with the depth they actually deserve. There is a lot more coming on this topic. And you do not want to fall behind. China may have just moved one of the most important parts of artificial intelligence hardware away from organic circuit boards and toward glass. BOE, the Chinese company best known for display panels, says it has completed a large, high-layer count glass core substrate sample for advanced chip packaging. The structure uses a 929 build with 20 total layers. More importantly, BOE says the sample passed demanding reliability tests, including 1,000 thermal compression bonding cycles, moisture tests, high-temperature storage, low-temperature storage, and preconditioning. That does not mean China has mass-produced a finished glass AI processor. It does not mean silicon has disappeared. And it does not mean every copper connection inside a computer is about to vanish. But it does mean glass packaging is moving from concept demonstrations toward hardware that can survive the stresses expected in manufacturing and operation. BOE is also forming a dedicated team to develop micro-LED optical interconnects and glass substrate co-packaged optics. The future bottleneck inside AI systems may not be computing power. It may be the copper wiring carrying data between processors, memory, and network devices. If glass substrates can support larger packages, finer wiring, better dimensional stability, and optical links placed closer to chips, they could change how future AI computers are assembled. So has China built a 20-layer glass AI chip that could end copper? But it may have passed one of the tests required to make that possibility serious. What BOE actually built? A modern AI accelerator is not simply one small silicon rectangle. The finished product can include multiple computing dies, high-bandwidth memory stacks, power delivery components, controllers, and communication links. These parts must be positioned, powered, cooled, and connected with extraordinary precision. The structure supporting them is called a package substrate. It sits between the silicon devices and the larger system board, carrying power and signals across thousands of tiny electrical connections. Most advanced substrates today use organic materials. But as packages grow larger and wiring becomes denser, organic substrates face physical limitations. They can expand, shrink, bend, or warp during heating and cooling. Even tiny dimensional changes matter when engineers align extremely fine connections across a package containing many chiplets. Glass offers a different foundation. It can remain flatter across large areas, provide strong dimensional stability, support very fine features, and offer useful electrical properties for high-speed signals. BOE says its 20-layer sample uses a 929 configuration. In simple terms, that means 9 buildup layers on one side, a central 2-layer glass core section, and another 9 buildup layers on the opposite side. The design matters because advanced packages need many routing layers to distribute power and connect processors, memory, and external interfaces. Building a large 20-layer substrate that remains aligned and reliable is much harder. Why the reliability test matters. Computing hardware repeatedly heats during operation and cools when workloads stop. Different materials expand at different rates. That creates stress around copper vias, solder joints, wiring layers, and interfaces. High temperatures can weaken materials, while low temperatures can create contraction and cracking. Manufacturing steps such as bonding add pressure and heat before the package reaches a customer. BOE says its samples passed several industry reliability tests. One was thermal compression bonding cycling, reported at 1,000 cycles. Thermal compression bonding uses controlled heat and pressure to create fine electrical connections. Repeated cycling helps reveal whether interfaces separate, crack, or lose electrical performance under stress. The sample also reportedly passed accelerated temperature and humidity testing, biased humidity testing, high-temperature storage, low-temperature storage, and preconditioning. These tests do not prove the substrate will survive every product, factory process, or operating environment. The company is testing whether a complex multi-layer structure can remain functional after repeated environmental and manufacturing stress. That is essential before chip companies will trust a new substrate beneath expensive processors and memory. Why AI packages keep getting bigger. One package may contain several compute dies and multiple stacks of high-bandwidth memory. A single piece of silicon cannot grow forever. Manufacturing defects become more expensive as die size increases, while practical size is limited by lithography equipment. Chip makers therefore divide large designs into smaller chiplets and connect them inside one package. But it moves a major engineering challenge from the silicon die into the package. The substrate must connect many devices with enough bandwidth that they behave like one system. It must remain flat enough for thousands of fine connections to align correctly. And it must support larger physical dimensions without warping. Glass is attractive because it can potentially support larger package formats than organic materials while maintaining tighter dimensional control. That does not make glass automatically cheaper or easier. Drilling and filling extremely small vertical holes is difficult. Cutting large glass panels without damaging stress is also challenging. BOE says it developed capabilities including high aspect ratio through glass via formation, deep hole copper filling, low stress metallization, multi-layer lamination, high density routing, and low stress cutting. Those processes turn plain glass into a usable electronic platform. The copper bottleneck. The title says copper may be finished. Copper is not disappearing from electronics. Even BOE's glass substrate relies on copper-filled vias and metal wiring. Power delivery will still require conductive paths, and short electrical connections will remain essential. The real problem is distance and bandwidth. As data rates increase, copper links consume more energy and become harder to operate reliably across longer paths. Electrical signals lose strength, generate heat, interfere with nearby channels, and require increasingly complex equalization. Inside a large AI system, processors and memory must move enormous quantities of data every second. Engineers can improve copper, but the energy cost per transmitted bit is becoming a concern. Optical communication sends information using light. Light can move large amounts of data with lower loss across distance and reduced electromagnetic interference. The industry already uses optical transceivers for many network links. The next step is bringing optical components much closer to the processor. That idea is called co-packaged optics. Instead of sending high-speed electrical signals from a chip across a long board to a separate optical module, optical engines are placed near or inside the main package. The electrical path becomes shorter. This can reduce power consumption and support higher bandwidth. Why glass and optics fit together? Glass is interesting for optical integration. It is dimensionally stable, can support precise structures, and can provide a platform for electrical routing and optical components. BOE says it formed a project team focused on micro-LED optical interconnect systems and glass substrate co-packaged optics. Micro-LEDs are extremely small light-emitting devices. They are best known as display technology, but their size and fast response make them candidates for short-distance optical communication. A micro-LED array could potentially transmit many optical channels in parallel across short distances. That could help AI servers move enormous bandwidth between nearby devices while minimizing power. BOE has decades of experience processing large glass panels and developing display technologies, including micro-LED manufacturing. The company is trying to reuse those capabilities in semiconductor packaging and optical interconnects. Display manufacturing and advanced chip packaging have different tolerances, materials, customers, and reliability demands. But BOE already understands large area glass processing, precision patterning, multi-layer structures, and mass production automation. From display factory to chip packaging, BOE's move is part of a larger shift. Display manufacturers built factories capable of processing large glass panels with fine patterns, thin films, and precise alignment. Advanced semiconductor packaging is one of those markets. BOE brought a glass core substrate pilot line online with a design capacity of roughly 1,000 substrates per month. The company says it delivered samples to domestic customers. Some customers reportedly completed concept verification and entered technical testing. However, BOE also says the business has not reached mass production and has not generated mass production revenue. That distinction matters. A pilot line proves samples can be produced repeatedly. It does not prove competitive yield, cost, throughput, or customer adoption. For a commercial AI package, every substrate must meet strict specifications. A small defect can ruin a product containing extremely expensive processors and memory. The challenge is not producing one successful piece. It is producing thousands with consistent quality at a price customers will accept. The global glass race. China is not alone in pursuing glass substrates. Intel has spent years researching glass core packaging. Other substrate makers, equipment companies, foundries, and display manufacturers are also developing glass processes. The attraction is global because every major AI chip company wants more memory bandwidth, more chiplets, larger packages, lower power, and faster interconnects. Glass is one possible solution, not the only one. Organic substrates continue improving. Silicon interposers remain important for extremely dense connections. Fan-out packaging, advanced bridges, and new redistribution technologies are also evolving. The winning architecture may combine several materials rather than replacing everything with glass. China's significance comes from manufacturing scale. If BOE adapts large panel glass processing to semiconductor requirements, it could build substrates using panel-level methods rather than treating every package like a small wafer. Panel processing may increase the number of large substrates produced per cycle, but larger panels also create more opportunities for defects, alignment errors, stress, and breakage. The economic advantage exists only if yields become high enough. What the 20-layer result does not prove, the reliability milestone is important, but several things remain unproven. BOE has not announced a commercial AI accelerator shipping on this substrate. It has not disclosed the customer, final package design, production yield, selling price, or long-term field reliability. The company has not shown that its glass substrate is superior to every competing organic, silicon, or glass solution. Its optical interconnect project is still under development. A dedicated team is not the same as a finished co-packaged optics product. The phrase "copper may be finished" should be understood as a direction, not a completed transition. Copper links are reaching limits in the highest bandwidth parts of AI systems. Optics may gradually replace longer, faster electrical connections. But copper will remain inside packages, boards, power systems, and many short-reach links. The likely future is hybrid. Electricity will deliver power. Copper will handle many local connections. Optical links will move increasing amounts of data where electrical transmission becomes inefficient. Glass could become the platform allowing those technologies to coexist inside one large package. Why this matters for China? Advanced packaging is strategically important because computing performance no longer depends only on manufacturing the smallest transistor. A company can combine chips, memory stacks, and optical links to create a powerful system even when individual dies use different process nodes. Packaging does not erase the value of leading-edge fabrication. It gives engineers another path to improve performance. China faces restrictions on advanced semiconductor equipment and high-end AI hardware. That creates pressure to improve every part of the domestic computing stack. Glass substrates, panel-level packaging, optical interconnects, domestic memory, and chiplet integration can help China extract more performance from available chips. BOE represents a different type of semiconductor competitor. It is entering through glass, displays, micro-LEDs, and large-scale panel manufacturing rather than a traditional foundry. That cross-industry approach could create new options if conventional substrate suppliers cannot scale quickly enough for AI demand. My take is that BOE's 20-layer reliability result is meaningful, but the headline should not be mistaken for a finished revolution. China has not replaced silicon with glass. BOE has not eliminated copper, and a pilot line producing customer samples is not a mature commercial supply chain. What BOE has done is more specific. It built a large, complex glass core substrate, developed processes to route signals and power through it, and pushed the sample through serious reliability testing. At the same time, it is connecting that glass strategy to micro-LED optical interconnects and co-packaged optics. That combination matters, because future AI systems need larger packages and faster, more efficient communication. Glass may help solve the mechanical problem. Optics may help solve the bandwidth problem. If BOE combines them economically, China could become an important supplier of the platform beneath future AI chips, even without manufacturing the processors themselves. The next test is not another laboratory record. It is customer qualification, production yield, cost, and deployment inside a real computing product. So what do you think? Will glass substrates and optical links become the foundation of future AI hardware? Or will manufacturing complexity keep organic packages and copper connections dominant? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the race for AI leadership is no longer happening only inside the transistor. It is also happening beneath the chip, between the memory, and across every connection carrying the data. There is a country that most of the world rarely thinks about when the conversation turns to ambitious engineering. And yet, over the past few decades, this country has quietly been building some of the most surprising infrastructure projects on the planet. Projects that, in many cases, barely register in international headlines. We are talking about the largest shopping complex on Earth, a railway network spanning 15,000 kilometers, an underground metro system so visually striking that travelers stop walking just to look at the ceilings, a car manufacturing industry that ranks among the 15 largest in the world, and perhaps the most audacious project of all, an effort to take seawater from the ocean and move it hundreds of kilometers inland to transform desert into livable land. That country is Iran, and whatever your views on its politics, the scale of what its engineers have built is genuinely worth understanding. This video is going to walk through these projects one by one, and some of them get more remarkable the deeper we go. Let's start with the one that sounds most unbelievable. When people think of the world's biggest malls, they usually picture Dubai or the United States. The actual record holder sits next to Chitgar Lake in northwest Tehran. Iran Mall covers nearly 2 million square meters across 7 enormous floors, making it the largest shopping complex in the world by total area, larger even than the famous Dubai Mall. The construction effort required more than 25,000 workers and over 1,000 contractors. At one point during the build, crews poured concrete continuously for 6 straight days, setting a Guinness World Record for the largest continuous concrete pour. But the scale is not really the interesting part. The interesting part is what is inside. The complex houses 12 cinemas, including IMAX screens, a full Olympic-sized ice rink, a 2,000-seat theater, a luxury hotel, a convention center, and rooftop sports courts. It also contains a library holding over 45,000 books and manuscripts, a mirror hall constructed from an estimated 38 million individually crafted mirror pieces, and a traditional bazaar designed to echo the historic markets of Isfahan, Shiraz, and Tabriz. The intention was never to build a simple shopping destination. It was designed to function as a self-contained world, a place where the architecture itself is the attraction. The shopping mall was a concept popularized in America. Iran took that concept and scaled it to a size few people thought was practical. Iran does not only build at scale. Some of its most celebrated work is about beauty and design, and one project in particular became a global architectural sensation, designed by an architect who was only in her 20s when she conceived it. Layla Aragian was a young Iranian architect when she looked at a busy highway cutting between 2 parks in Tehran and asked a deceptively simple question. What if a bridge could become part of the natural landscape rather than just passing over it? The result was the Tabiat Bridge. Tabiat means nature in Persian, and the structure lives up to the name. It stretches 270 meters in length and rises 40 meters above the highway below, with 3 full levels containing walking paths, cafes, seating areas, and open viewing platforms offering panoramic views of Tehran and the snow-capped Alborz Mountains. 3 large supporting columns hold the structure up, deliberately shaped to resemble trees with branches spreading outward to echo the surrounding parks. The engineering is serious. Roughly 2,000 tons of steel and 14,000 individually cut components, designed to withstand earthquakes above magnitude 7 and built to last a century. The bridge has won several of the most prestigious architecture awards in the world, including the Aga Khan Award for Architecture. In its first year alone, around 4 million people visited, and most of them did not come to cross from one park to the other. They came simply to experience the structure itself. Iran's railway story stretches back nearly a century and connects to one of the most impressive engineering legacies in the region. The country operates a railway network spanning roughly 15,000 kilometers, one of the largest in the Middle East. That network moves tens of millions of tons of freight and tens of millions of passengers every year. And its foundations are remarkably old. The original Trans-Iranian Railway was constructed between 1927 and 1938. It crossed 2 mountain ranges and 4 distinct climate zones, requiring 174 major bridges and 224 tunnels to complete. It is now recognized as a UNESCO World Heritage Site, a testament to engineering ambition that predates most modern construction technology. What is striking about Iran's infrastructure culture is the speed of repair when something goes wrong. There are documented cases of major railway bridges being restored to operational status within a matter of days, rather than the months such work typically takes elsewhere. A civilization with thousands of years of building history tends to approach repair and reconstruction with a particular kind of practiced efficiency. Beneath the streets of Tehran sits a transportation system that very few people outside Iran are aware of, and it ranks as the largest metro network in the Middle East. More than 3 million passengers ride the Tehran metro every single day. The system includes over 310 kilometers of track and more than 160 stations, with trains arriving every 3 minutes during peak hours. The expansion plans are ambitious. By 2040, the network is projected to reach 500 kilometers of track and 330 stations across 11 lines. But what makes the system genuinely remarkable is the design of the stations themselves. Many of them feel less like subway platforms and more like underground galleries, featuring Persian mosaics, intricate geometric ceilings, detailed artwork, and grand halls that prompt passengers to pause and look around. The system is also impressively modern in its features: fully accessible stations, smart card and QR code ticketing, dedicated carriages, and comprehensive security infrastructure. In 2022, Iran unveiled its first fully domestically manufactured metro train set, certified to meet European safety standards, with passenger service beginning in 2024. And the fare for a ride of any distance remains remarkably low by international standards. One station in particular drew worldwide attention when it opened in October 2025. The Maryam-e-Moghada station, named in honor of the Virgin Mary, the mother of Jesus in Christian tradition, was built with an architectural style that blends Persian geometric design with church-inspired elements. The station features vaulted arches, a large decorated dome, religious frescoes, and sculptures referencing Christian iconography. It took roughly a decade to complete, and when photographs of the station spread online, they captured global interest precisely because of the cultural blend it represented. A thoughtful piece of architecture, honoring a figure revered across multiple faith traditions. Iran's rail offering extends well beyond commuter transport. One of its premium long-distance services has earned a reputation that rivals luxury hotels. The Fadak Express is often described by Iranians not as a train but as a moving 5-star hotel. It runs at speeds up to 200 kilometers per hour, connecting Tehran with Mashhad, Shiraz, and Qom. Its coaches were comprehensively redesigned under the supervision of a Swiss engineering firm, with upgraded air conditioning, electrical systems, and interiors built around a combination of Iranian aesthetics and high-end comfort. Each private compartment accommodates only 4 passengers and comes fully equipped with an entertainment system, charging outlets, and sound insulation effective enough that the movement of the train is barely audible. Meals are included in the ticket price, with catering quality compared to some of Iran's finest restaurants. The service offers 5 travel classes, ranging from economy to a premium tier that includes dinner and a hotel stay. The result has been a notable shift in traveler behavior. People who previously flew between Iranian cities began choosing the Fadak instead, not because it was cheaper, but because the overall experience was simply more pleasant. While Iran is rarely associated with car manufacturing in global conversation, the country has quietly developed an automotive sector that ranks among the largest in the world. Iran Khodro, commonly known as IKSO, was founded in 1962. Today, Iran ranks as roughly the 13th largest automobile producer globally, manufacturing more than 1.3 million vehicles annually. IKSO sits at the center of that production, and its vehicles are notable for being designed specifically for Iranian conditions rather than simply assembled from foreign designs. The Samand became Iran's national vehicle and was exported to countries including Venezuela, Belarus, and Azerbaijan. The Dena, named after a peak in the Zagros Mountains, featured a turbocharged engine producing around 150 horsepower. The Runa was developed as domestic intellectual property and proved successful enough to be adopted as a national vehicle in Tunisia. And in 2024, Ikeso unveiled the Rira, including a fully electric variant. That last detail is worth pausing on, because Iran was experimenting with electric vehicle development as far back as 2010, well before electric cars became a mainstream topic across much of the region. Beyond passenger vehicles, the Baumann Group, founded in 1952, has built an export business in trucks and vans serving markets across multiple continents. One of Iran's most significant energy infrastructure projects involves a pipeline designed to connect it with neighboring Pakistan. The Iran-Pakistan gas pipeline, sometimes called the Peace Pipeline, was designed to carry natural gas from Iran's South Pars field, one of the largest natural gas fields on Earth, across roughly 2,700 kilometers to Pakistan. Iran completed its 1,100-kilometer section by 2012, on schedule using domestic engineers and technology. Pakistan's portion of the project, however, has faced extended delays for a range of complex political and economic reasons. The Iranian section sits ready, the gas is available, and the two neighboring countries have a clear complementary need, one with abundant gas supply, the other with significant energy demand. Many regional energy analysts have noted that if the obstacles to completion were resolved, the project could become one of the more impactful energy initiatives in the region, potentially supplying gas to millions of homes and supporting industrial activity. For now, the infrastructure on the Iranian side waits, a completed piece of engineering held back primarily by factors outside the realm of construction. Here is where Iran's ambition becomes genuinely remarkable, because the country faces a fundamental geographic challenge. A large majority of its territory is arid desert, and much of its rainfall occurs along coastal regions far from where tens of millions of people actually live. Iran's response has been to engineer its own water security on a massive scale. The country has constructed more than 600 dams, which at one point ranked it among the top 3 dam-building nations in the world. Collectively, these dams store an enormous volume of water, making Iran one of the largest water storage nations in its region. The flagship of this effort is the Karkhe Dam, the largest dam in Iran and one of the largest in the Middle East. It generates electricity, irrigates agricultural land, and manages billions of cubic meters of water, built largely through domestic engineering expertise. But storing water solved only part of the problem. The water existed. It was simply in the wrong place geographically. So Iran undertook one of its most ambitious projects yet, moving water from the sea to the dry interior. At the center of this effort is an interbasin water transfer system anchored by a large desalination network near Bandar Abbas. Built by Iranian engineers using domestic technology, the system draws water from the Persian Gulf and the Sea of Oman, and pumps it through roughly 3,700 kilometers of pipelines to reach drought-affected provinces in the interior. To put that distance in perspective, it is longer than the distance from London to Cairo. The main desalination hub alone can produce around 1.5 million cubic meters of fresh water per day, with longer-term plans to serve tens of millions of people across dozens of facilities. A significant portion of the supporting infrastructure, including a major plant on Chesham Island, was constructed using domestically produced components, in part because importing certain parts was not an option, so Iranian engineers manufactured them locally. This is the project that gives the video its title. The idea of taking ocean water and forcing it hundreds of kilometers inland to make the desert livable sounds almost impossible. Iran is doing it. Moving and processing that much water requires enormous amounts of energy, and Iran's answer included nuclear power. The Bushehr nuclear power plant holds the distinction of being the first civilian nuclear facility in the Middle East. Its history is unusually long and complicated. Construction was initially started by a German firm in 1975, then abandoned after the political changes of 1979, and the site sat incomplete for decades. The plant was eventually completed with Russian assistance and connected to Iran's power grid in 2011, more than 3 decades after work first began. Since then, it has produced tens of billions of kilowatt-hours of electricity. 2 additional units are currently under construction, and Iran has set a long-term goal of significantly expanding its nuclear generation capacity over the coming decades. The story of Bushehr is, in many ways, a microcosm of Iran's broader infrastructure approach. Projects that take a very long time, face repeated setbacks, and get completed anyway. What strikes me most about all of these projects, when you lay them out together, is the underlying pattern. Iran's engineering culture seems to operate on a principle of self-sufficiency that has produced genuinely impressive results, regardless of external constraints. When parts could not be imported, engineers manufactured them domestically. When a needed technology was not available, the country developed its own version. The Tabiat Bridge, the desalination pipelines, the domestically built metro trains, the car industry. Across all of these, there is a consistent theme of building capability internally rather than waiting for external solutions. I find that fascinating from a pure engineering standpoint, because necessity-driven innovation often produces solutions that are more creative and more durable than projects developed under comfortable conditions. Iran has thousands of years of building history behind it, and that long-term perspective shows up in how the country approaches construction, patiently, ambitiously, and with an apparent willingness to attempt things others consider impractical. Whether these projects reach their full potential will depend on many factors that extend well beyond engineering. But the work itself, viewed purely as feats of construction and design, deserves far more recognition than it typically receives. My question for you is this: which of these projects surprised you the most? The world's largest shopping complex, the museum-like metro stations, or the effort to pipe ocean water across the desert? Let me know in the comments, because I genuinely did not expect some of these to exist before researching this, and I am curious whether you felt the same. If you enjoy deep dives into the engineering and infrastructure stories that most media overlooks, please subscribe to Eastern Engine and turn on notifications. We cover the projects reshaping the world with the depth and curiosity they deserve. There is a lot more coming, and you do not want to miss it. On March 27, 1989, a room full of Soviet engineers on the Crimean Peninsula sat waiting for a signal that was already overdue. 400 million kilometers away, in orbit around Mars, their spacecraft had just performed what should have been a routine maneuver. It rotated to photograph one of Mars's two small moons. To aim its cameras, it had to swing its main antenna away from Earth and fall silent for a few minutes. The engineers expected that. They knew almost to the minute when the signal should return. The minute came. The signal did not. About 4 hours later, something finally arrived. But it was wrong. It was the garbled, broken kind of pulse a spacecraft sends when it is no longer pointed at anything at all, when it is tumbling helplessly through space. That faint, distorted transmission was the last thing anyone on Earth ever received from the probe. It had crossed the entire solar system to reach Mars, and to slip closer to one of its moons than any machine before it. And in its final minutes, circling the red planet, it captured a photograph. What that photograph showed, and what made the spacecraft fall silent at the exact moment it turned to look, became one of the strangest and most disputed episodes in the history of spaceflight. Let's find out what was actually out there. The spacecraft was called Phobos 2, and it carries a distinction most people don't know about. It was the final interplanetary probe the Soviet Union ever designed. To understand why that matters, you have to understand how long the Soviets had been away from Mars. After a string of disappointing Mars probes in the early 1970s, the political leadership had largely lost patience with the red planet. The results weren't impressive enough to justify the enormous cost, and the funding dried up. But the scientists never stopped thinking about it. At the Space Research Institute in Moscow, known by its Russian initials IKI, a group of researchers kept turning the problem over. They knew that to return to Mars, they needed an idea compelling enough to change the leadership's mind. By the end of the 1970s, they had one. The idea was this: don't go to Mars itself, go to its moons. Mars has two, and they are tiny. The larger is called Phobos, the smaller Deimos. What made Phobos so attractive wasn't only the science, it was the orbit. Phobos circles Mars on a path a chemically powered spacecraft could actually reach without too much difficulty. It was, in a sense, the easy door into the Martian system. And targeting a moon instead of the planet carried one more advantage that mattered enormously in 1980s geopolitics. It let the Soviets do something the Americans hadn't done, rather than repeating something they already had. In early 1985, the government approved the mission, with public announcements following that March. Here is where the human story begins, and it explains everything that follows. The man running the Space Research Institute at the time was a physicist named Roald Sagdiv. His institute had just pulled off the Vega missions, an international effort that had sent Soviet probes past Venus and on toward Halley's Comet in 1986. It was a triumph, and it had placed Sagdiv and his scientists firmly in the spotlight. According to Sagdiv himself, that spotlight created a problem. The leadership of the Soviet rocket industry resented the attention the scientists were receiving. So when the Phobos project was organized, overall control was handed not to the scientists who had conceived it, but to the ministry responsible for building the rockets. In practice, the manufacturer got to dictate terms to the customer. The people who would fly the mission no longer fully controlled how it was built, and there was one more pressure, the one that would haunt the entire story. By the Institute's own estimate, a project this complex needed 6 or 7 years to do properly. They were given 3.5. Remember that number, because it comes back. Yet, for all the rush and rivalry, this was also a hopeful project. It arrived precisely as the Soviet Union was beginning to open to the world, and it became one of the largest international science efforts the Soviets had ever attempted. Scientists from 14 countries contributed, from both sides of the Iron Curtain: Austria, Bulgaria, Hungary, Finland, France, Sweden, the United States, both German states, and institutions of the European Space Agency among them. That openness went remarkably far. In 1987, before either probe had launched, the Soviets displayed full-scale models of the Phobos spacecraft at an air and space show in France. In the final days before launch, Western visitors were invited to tour the Baikonur Cosmodrome itself, including an Apollo astronaut and a delegation from the US Air Force. The old reflexes hadn't entirely vanished. Rank-and-file soldiers were still ordered to swap their uniforms for civilian clothes when foreigners visited, to disguise the military nature of the site. But the direction was unmistakable. This was the Soviet space program trying to step into the light, which is part of what makes everything that came next so painful. Phobos 2 did not fly alone. It had a twin. The plan called for 2 identical probes, Phobos 1 and Phobos 2, launched a few days apart in July 1988, both bound for Mars. The logic was redundancy. If one failed, the other would carry the mission. 2 spacecraft, 2 chances. Phobos 1 lifted off first, on July 7th. For the first weeks, it behaved beautifully. It made its course correction, switched on an X-ray telescope, and photographed the sun, capturing well over 100 images of the solar corona and even catching a solar flare in the act. Then, on September 2nd, during a routine communication session, Phobos 1 simply didn't answer. Here's what happened, and it is one of the most quietly devastating facts in the history of spaceflight. A controller on the ground had sent the spacecraft a long string of commands, a routine package meant to keep the probe stable during an upcoming gap in communications. Somewhere in that string of code, a single character was wrong. One missing digit. Let that sit for a second. Not a hardware fault, not a collision, not a cosmic ray frying a circuit, a typo. That missing digit changed the meaning of the command. Instead of doing what it was supposed to, the code reached into the spacecraft's memory and triggered an old test program. A routine written to check the attitude control system on the ground, which, because there hadn't been enough time before launch, had never been erased from the spacecraft's memory. The test program ran, and the very last thing it did by design was switch off the attitude control system. So that is exactly what Phobos 1 did. 11 million kilometers from home, it shut off the system that kept it oriented. With nothing holding it steady, the spacecraft drifted, slowly nudged off axis by the faint constant pressure of the solar wind. Its solar panels turned away from the sun. The power faded, the batteries emptied. After weeks of trying to revive it, the Soviets declared Phobos 1 lost in early November. The mission had lost half its fleet before reaching Mars. Everything now rested on the second probe. Phobos 2 was built on a brand new platform, a full generation's leap beyond the old Venus probes. At its heart sat a ring-shaped instrument compartment atop a powerful propulsion unit fed by 8 fuel tanks. That propulsion design was so good, it would later live on as a rocket stage called Fregat, which still flies today. But the most important part of Phobos 2 for our story isn't the engine, it's the brain. The spacecraft was controlled by 3 identical onboard computers, working on a principle that sounds almost democratic. For any decision, the 3 computers would effectively vote, and the spacecraft would do whatever at least 2 of the 3 agreed on. The logic was sound. If a stray cosmic ray flipped a bit and made one computer briefly malfunction, the other 2 would outvote it. 3 brains, majority rules, no single point of failure. Hold on to that idea. The mission plan was extraordinary. Phobos 2 would enter a wide orbit around Mars, then gradually tighten it until it circled in step with the moon Phobos itself, eventually flying in formation just 35 kilometers above the surface. Then came the part that made this mission unlike anything before it. Once it had mapped the moon, Phobos 2 was supposed to descend until it hovered just 50 meters above the surface. Not landing, hovering. Landing on Phobos is nearly impossible because the moon's gravity is so feeble that a hard touchdown would simply send a craft bouncing back into space. While hovering, it would fire a laser at the surface, vaporizing a tiny puff of soil into a glowing cloud, then read the light from that cloud to determine exactly what the moon was made of, a way to taste a world without ever touching it. Finally, it would release landers. One designed to hop across the surface on spring-loaded legs, another built to fire a small harpoon into the ground to anchor itself to a moon that barely wanted to hold anything at all. To point its cameras at Phobos, the spacecraft had to turn its body, and turning its body meant swinging its main antenna away from Earth. Every close look at the moon required the probe to stop looking at home. It had done this before, more than once, without trouble. Just file that away. Phobos 2 launched on July 12, 1988. 5 days behind its doomed twin. Almost immediately, it began to show the strain of the rush it had been built in. Remember the 3.5 years versus the 6 or 7 the scientists said they needed. This is where that shortfall started to bite. During the long cruise to Mars, things began to fail. By the time Phobos 2 reached Martian orbit, its 3-computer brain had quietly become a crisis. One of the 3 computers was completely dead. A second was beginning to fail. Now go back to the voting rule. The spacecraft does whatever 2 of 3 computers agree on, with 1 healthy computer and 2 failing ones. The single working computer was outnumbered. It could be entirely correct, and it wouldn't matter, because the system was built to trust the majority, and the majority was now the failures. A safeguard designed to protect against a single failure had, through sheer attrition, turned into a trap. And it wasn't only the computers. The high-speed transmitter meant to pour data back to Earth had developed its own problems, forcing the probe to trickle its findings home at a fraction of the intended rate. The spacecraft had crossed the entire inner solar system and arrived at Mars already wounded, already dying by degrees. And yet, remarkably, it kept working. It entered orbit around Mars on January 29, 1989. It built a thermal map of the surface, photographed the planet in visible and infrared light, and studied the atmosphere. Its science kept flowing slowly through a half-broken transmitter controlled by a brain one bad day away from being unable to vote itself out of disaster. By early 1989, a crippled spacecraft, the last hope of an entire program, was circling Mars and slowly closing in on a tiny moon. Its handlers knew it was failing. They knew the clock was against them. They decided to push forward anyway, because the alternative was to have come all that way for nothing. The final close approach was scheduled for April 7th. The probe just had to survive a few more weeks. So it began photographing the moon in stages, like a camera slowly pulling focus. On February 21st, it imaged Phobos from roughly 1,000 kilometers away. A week later, from 300 to 400 kilometers. On March 25th, from less than 300. Each pass closer, each image sharper, a potato-shaped little world resolving out of the dark, scarred with craters and strange parallel grooves, swelling larger in the frame. In total, across its short life at Mars, the probe sent home fewer than 40 images of Phobos, some resolving features just tens of meters across. For a dying spacecraft trickling data through a damaged transmitter, that was a genuine scientific haul. Then came March 27th. Phobos 2 was scheduled to make another imaging run, to turn and face the moon for a fresh series of pictures. To do that, exactly as before, it had to point its body at Phobos, swinging its antenna away from Earth. You already know what happened. The spacecraft went quiet for the imaging session as planned. The session ended, and the probe never cleanly returned. 4 hours later came that faint, garbled, indecipherable signal, the signature of a spacecraft tumbling out of control, unable to hold itself steady or aim its antenna home. A tumbling spacecraft can't keep its solar panels in sunlight. By early April, the temperature inside would fall to freezing. By mid-month, it would be too cold for anything to function. On April 14, 1989, with the probe surely frozen in orbit around Mars, the Soviets declared the mission over. Here is the strange part, the part that turned an engineering tragedy into a legend that refuses to die. When investigators later tried to explain the loss, they could agree on what the spacecraft did. It tumbled, lost power, and froze. What they could not fully explain was why it started tumbling in the first place. That initial push, during the few minutes the probe had turned away from Earth, remained. In the words of one detailed account, a mystery. Officially, blame settled on human error somewhere on the ground, as it had with Phobos 1. Other explanations circulated. A failure of the attitude control system, a loss of the transmitter, or a final breakdown of that ailing flight computer, which had been showing signs of trouble for months. That last explanation is generally considered most likely. But notice the word likely. There has never been a single definitive public failure report that closes the case. Into that open question, the stories came rushing in, and here we have to be careful and honest about what is fact and what is not. The most famous claim came from a remarkable woman named Marina Popovich. She was a Soviet test pilot, one of the best the country ever produced. They called her Madame MiG. In 1964, she became the first Soviet woman to break the sound barrier, and over her career, she set more than 100 aviation world records. After the Soviet Union collapsed, she became one of the most prominent voices in the Russian UFO movement. At her public appearances, she would display a photograph she said was the last image taken by Phobos 2, claiming it showed an unexplained, elongated cylindrical shape near the spacecraft just before the transmission stopped. So what do we actually have? We have a heroic but controversial figure, presenting an image and a story. We have a spacecraft that really did die suddenly, never fully explained, while turning to photograph a moon. And we have a public hungry to connect those two facts. Let's separate the threads. The spacecraft really did photograph something. It photographed Phobos, a real, moving, dark little world crossing in front of Mars. The probe's final frame really was an image of Phobos taken from less than 200 kilometers away. That part is completely true. The claim that the image showed an artificial object, however, is attached to one person with no confirmation behind it. And the claim that Moscow deliberately cut the transmission to hide a discovery runs straight into the most boring and most likely explanation of all: a spacecraft built in half the time it needed, flying on a brain that could no longer outvote its own failures, finally losing its grip during a routine turn. But there is a grain of truth buried in the conspiracy. Moscow did not cut the transmission. The spacecraft died on its own. What Moscow did was something quieter and, in its way, more revealing. When the failures were discussed in May 1989, the head of the team that built the spacecraft tried to blame the loss on outside forces, the kind of bad luck no engineer could be held responsible for. According to those present, his arguments were met with open ridicule by the Institute's own scientists, while the foreign partners watched the Soviets argue among themselves. The old guard wanted to keep systemic problems in-house and pin any failure on meteoroids or radiation. The scientists who had flown the mission wanted an honest public investigation because they believed the real problems had to be admitted before they could ever be fixed. So when people say Moscow covered something up, they are half right and half wrong. There was no hidden photograph of anything unexplained, but there was a deep instinct in the system to reach for an external villain rather than confront a failure of its own making. The thing being concealed wasn't a secret in the sky, it was a flaw on the ground. There is, however, one genuinely strange detail in this story, and it has nothing to do with the supernatural. It's about the moon itself. Phobos is barely like a moon at all. It's small, only about 22 kilometers across on average, and lumpy, irregular, shaped like a potato. Its gravity is so weak, less than 1,000th of Earth's, that it never pulled itself into a sphere. It races around Mars in roughly 7 hours, so fast that from the Martian surface it crosses the sky in the wrong direction. Its dominant feature is a vast crater called Stickney, about 9 kilometers wide, taking up nearly half of one face. Whatever carved out Stickney very nearly shattered the moon. Back in the 1960s, a brilliant Soviet astrophysicist named Iosif Shklovsky looked at Phobos and noticed something that bothered him. For its size, the moon seemed too light. Its density seemed too low. Shklovsky floated a startling thought in the popular press. What if Phobos was so light because it was partly hollow? And if hollow, perhaps even artificial? It was a wild idea, but it came from a serious scientist, and it stuck. For decades, the notion drifted through the culture. So by the time Phobos 2 fell silent while staring at the moon, the cultural ground was already prepared for a mysterious interpretation. There's even a real object on Phobos that keeps the story alive: the Phobos monolith. A single large boulder roughly 85 meters across near the edge of Stickney crater, casting a long, sharp shadow. In low-resolution images, it looks oddly upright and out of place. But science has a calm answer. When something smashed into Phobos hard enough to blast out Stickney, it would have flung enormous boulders across the surface. The monolith is almost certainly one of them, a chunk of debris frozen in place on a low-gravity world. It looks strange mostly because our cameras can't quite resolve it, and a blurry rock often reads to the human eye as something too regular to be natural. But here is the honest twist that survives all the debunking. Shklovsky was wrong about why Phobos is light, but he wasn't wrong that it is light. Modern measurements confirm Phobos really is less dense than solid rock should be, most likely because it isn't fully solid at all, but a loose, porous pile of rubble full of empty space. and we still cannot say for certain where it came from. Some scientists think Phobos and Deimos are captured asteroids. Others think they formed from debris blasted off Mars in a colossal ancient impact. After all these years, we still don't know what the moons of Mars actually are. As a final footnote, the instruments on Phobos 2 searched the moon for any sign of water before the end. They found none. Phobos 2 was the last interplanetary probe the Soviet Union ever designed, and the system that built it didn't outlast it by much. Within 2 years, the Soviet Union collapsed, and planetary exploration funding collapsed with it. A later attempt to fly a similar design, Mars 96, failed when its rocket fell back to Earth. Russia tried once more, decades later, with a probe called Phobos Grunt, aimed at the very same moon. And it failed too, stranded in Earth orbit in 2011. Add it all up, and you reach a sentence that sounds almost impossible. To this day, there has never been a fully successful mission to Phobos. We have flown past it, photographed it, mapped its craters, even filmed it from the Martian surface drifting across the sun. But we have never landed on it. We have never held a piece of it. The story, though, isn't quite finished. Right now, a spacecraft is being readied by Japan with help from agencies in the United States, France, Germany, and Europe. Its mission is the one the Soviets dreamed of and never completed: to fly to Phobos, land on it, scrape up a few grams of that ancient surface, and carry them home. If everything holds, sometime in the next several years, a small capsule will fall through Earth's atmosphere, carrying the first piece of Phobos human hands have ever touched. Then perhaps, we'll finally learn whether it's a captured asteroid, the shattered child of Mars, or something we haven't imagined yet. Until then, the moon keeps its secret. It keeps racing around Mars every 7 hours, casting its long shadow, falling imperceptibly toward the planet that will one day end it. And somewhere up there, frozen and silent for over 3 decades, is a small Soviet machine that crossed an entire solar system to look at it, and got close enough, in the very last moment, to see the grooves on its surface before it turned away from us for good. We built the probe. We aimed it across 400 million kilometers of empty space. We watched it reach the one small strange world it was sent to find. And then, at the exact instant it turned to look, we lost it. And the dark closed back over the moon, leaving us exactly where we have always been. Standing on one planet, staring at another, holding a blurry photograph, and realizing how little we truly know about the small worlds right next door. Deep beneath Jiaozhou Bay, engineers in eastern China have completed one of the most important stages of a tunnel project that sounds almost impossible. A giant boring machine has broken through after carving a highway passage below the seabed, at a depth reaching 115 meters beneath sea level. When the entire project is finished, the second Jiaozhou Bay undersea tunnel will stretch 17.48 kilometers, including 9.95 kilometers beneath the bay. Chinese project sources describe it as the world's longest undersea highway tunnel, and the latest breakthrough brings that record-setting connection much closer to reality. But there is an important distinction. The tunnel is not open, and the whole project is not finished. What crews completed in July 2026 was the main shield tunneling stage. The machine has finished excavating its planned section, but workers still need to complete internal structures, roads, electrical systems, lighting, ventilation, drainage, communications, safety equipment, testing, and many other tasks before normal traffic can enter. Current reporting says the broader project is expected to be completed in 2028, so this is a major engineering breakthrough, not an opening ceremony. The scale alone is difficult to picture. A total project length of 17.48 kilometers is longer than many entire urban road corridors. Almost 10 kilometers will pass directly beneath Jiaozhou Bay, separating the tunnel from ordinary mountain tunnels that remain surrounded by dry rock. Here, workers are excavating under seawater, where pressure, fractured geology, unpredictable water pathways, and limited access can turn a small problem into a serious emergency. At the deepest point, the route reaches 115 meters below sea level, placing cars far beneath the surface of the bay once the road eventually opens. The project is being built in Qingdao, a major port and industrial city in Shandong province. Jiaozhou Bay divides important urban and industrial areas, including Qingdao's main urban districts on one side and Huangdao on the other. The city already has an older undersea road tunnel and a major bridge across the bay. Yet continued growth has created demand for another high-capacity connection. The second tunnel is intended to strengthen travel between the eastern and western sides, support regional integration, and provide another route for residents, businesses, freight movements, and emergency planning. Unlike a small single-bore passage, This project is designed as a twin-tube highway connection, with 3 lanes in each direction. Vehicles are expected to travel at speeds of up to 80 kilometers per hour. That design requires far more than simply creating an empty hole. Each tube must provide enough space for traffic lanes, structural linings, drainage, ventilation equipment, lighting, monitoring systems, fire protection, communications, maintenance access, and emergency procedures. Everything has to operate reliably in an enclosed environment almost 10 kilometers beneath seawater. The most dramatic tool used on the project was an enormous shield machine developed for the conditions beneath the bay. China Communications Construction Company reported that the machine measured about 165 meters long, weighed roughly 5,300 tons, and used a cutter head 15.63 meters in diameter. That cutting diameter is wider than many buildings and large enough to create a road tunnel with room for multiple lanes and technical systems. The machine began its main tunneling work in January 2024 before completing the shield excavation milestone in July 2026. A shield machine does much more than drill forward. At the front, a rotating cutter head breaks rock and soil. Behind it, the machine controls pressure at the excavation face, so seawater and loose material do not rush into the tunnel. Excavated material must be collected and transported backward while the machine continues moving. At the same time, workers and automated equipment install reinforced concrete segments to create the tunnel's permanent circular lining. Those segments must fit precisely, resist external pressure, and seal against water for decades. This process becomes especially difficult when the geology changes. Under Jiaozhou Bay, crews faced hard rock, fractured zones, high water pressure, and fault structures. A boring machine that performs well in stable ground can behave very differently when it reaches broken rock filled with water pathways. Engineers must continuously study pressure, vibration, cutter wear, ground movement, water conditions, and the machine's position. Advancing too aggressively can damage equipment or disturb the surrounding ground. Advancing too cautiously can delay the project and increase costs. One of the most serious challenges was the F-13 undersea fault fracture zone. China Railway Engineering Corporation reported that one project section had to cross a fractured zone extending about 560 meters. Fault zones can contain crushed and weakened rock rather than one solid mass. They may allow water to move through cracks and can react unpredictably when excavation removes supporting material. Crews used carefully controlled methods to penetrate this section, and a separate drill and blast portion broke through the fault zone in 2025 after the final meters of rock were precisely removed. That detail reveals something important. The tunnel was not constructed with one method from end to end. The project combines shield tunneling with drill and blast excavation. Shield machines are powerful when conditions, alignment, and tunnel shape suit mechanized excavation. Drill and blast methods can offer flexibility in hard rock and complex sections, but they require controlled drilling, explosives, rock support, ventilation, debris removal, and careful monitoring. Combining methods allows engineers to match construction techniques to different geological and logistical conditions along the route. The shield section itself demanded a continuous underground supply chain. Cutting tools wear down and may require inspection or replacement. Concrete lining segments must arrive in the correct order. Slurry, water, power, ventilation, communications, personnel, spare parts, and excavated material all move through a narrow tunnel behind the machine. A delay far behind the cutter head can stop progress at the front. This means the achievement depends not only on the machine's power, but on scheduling, maintenance, transport, quality control, and thousands of coordinated decisions. Water pressure is the invisible force behind almost every design choice. At great depth, seawater pushes against the tunnel from every direction. The lining must resist that pressure while joints remain sealed. Drainage systems must manage any controlled water entry, and monitoring equipment must detect changes before they become dangerous. During excavation, face pressure must be balanced carefully. If pressure is too low, water or ground could enter. If it is too high, surrounding material could be displaced. Maintaining stability is a constant engineering calculation. The machine's huge diameter also increases complexity. A larger cutter head encounters more rock at once, creates more excavated material, and experiences greater forces. Its components must handle enormous torque while remaining accurately aligned. Even a small deviation can become significant over several kilometers. Sensors and navigation systems guide the machine along a three-dimensional path, while operators make adjustments to keep the tunnel within tight tolerances. When two independently excavated sections meet, the breakthrough must occur close enough for the final connection to be structurally sound and smoothly aligned. Project managers also use digital tools to supervise construction. China Communications Construction Company described a digital twin and a building information modeling platform that connected design and construction data. A digital twin is a computer-based representation of the physical project that can help teams visualize progress, compare actual conditions with plans, and coordinate decisions. This does not remove the need for experienced engineers underground. Instead, it gives them another way to understand a project too large and complex to manage through isolated drawings and reports alone. The project has also introduced systems intended to reduce resource use. Official company information says reclaimed water was used for shield machine operations, with potential savings of around 1 million cubic meters of fresh water. Wastewater could be treated and reused for dust control or irrigation. Excavated soil and rock were processed for uses including roadbed work, backfilling, and concrete aggregate. These measures do not eliminate the environmental impact of a massive tunnel, but they show how waste streams from construction can become useful materials rather than simply being transported away. Completing excavation does not end the difficult work. Long road tunnels require highly reliable ventilation because vehicle emissions, heat, smoke, and air movement behave differently underground. Operators need monitoring systems that can detect stopped vehicles, collisions, fires, unusual temperatures, and poor air quality. Lighting must guide drivers through a long enclosed route without creating dangerous changes in visibility. Communications must continue working during emergencies. Pumps, power supplies, and backup systems must remain available even when parts of the network fail. Fire safety is especially important. In an open road, smoke can disperse into the atmosphere. Inside a tunnel, smoke may travel along the roadway and reduce visibility quickly. Designers must plan detection, ventilation control, emergency access, evacuation routes, communications, and coordination with rescue teams. The exact final operating systems have not all been publicly detailed, but the length and depth of this crossing means safety testing will be one of the most important stages before opening. A record is meaningless if ordinary drivers cannot use it safely. Construction teams must also complete paving, lane markings, barriers, equipment rooms, drainage channels, electrical installation, and the connection between tunnel portals and the surrounding road network. These tasks may look less dramatic than a giant cutter head breaking through rock, but they determine how the tunnel performs every day. A modern highway tunnel is effectively an underground transportation system, power network, communications network, ventilation facility, and emergency environment combined inside one concrete structure. Why build another tunnel when Qingdao already has a bridge and an older undersea crossing? Different routes serve different parts of a growing metropolitan area, and additional capacity can reduce dependence on a limited number of links. Bridges can be affected by wind, weather, navigation requirements, and the locations of approach roads. Tunnels preserve the surface of the bay and do not create obstacles for ships above them, although they introduce different construction and maintenance challenges. A network containing multiple crossing types can provide greater flexibility. The second tunnel could also influence how development spreads around the bay. Faster and more predictable movement between urban districts can affect where companies build facilities, where people choose to live, and how industrial areas connect with services. Qingdao is not building an isolated engineering monument. The tunnel is part of a broader transportation system serving a major coastal economy. Its value will depend on how well it connects with existing roads, how traffic is managed, and whether the new capacity improves real journeys rather than simply moving congestion elsewhere. There is still reason for caution when describing any unfinished megaproject. Final schedules can change, costs can rise, equipment may perform well during construction but require expensive maintenance later. Traffic forecasts may not match reality. Water control, corrosion, ventilation, emergency response, and structural monitoring will remain long-term responsibilities after opening. The world's longest label attracts attention, but length alone does not guarantee economic value. The true test will come after years of operation, maintenance, and daily use. Still, the completed shield tunneling stage is genuinely significant. Moving a machine more than 15 meters wide beneath a bay, controlling water pressure, installing a permanent lining, crossing complex geology, and reaching the planned breakthrough requires an enormous combination of mechanical engineering, geotechnical knowledge, surveying, logistics, software, construction management, and human judgment. It is easy to focus on the dramatic moment when the cutter head reaches daylight. The deeper achievement is that thousands of systems work together long enough to make that moment possible. The project also demonstrates how China is applying industrial scale to underground transportation. Large shield machines, segment factories, digital monitoring, specialized contractors, and experienced crews can be reused and improved across many projects. Every tunnel creates lessons about geology, waterproofing, equipment reliability, emergency design, and construction logistics. That accumulated experience can reduce uncertainty on future crossings, although every site remains different. A machine built for one bay cannot simply be placed anywhere without redesigning the entire engineering plan around local conditions. Another reason this project attracts global attention is the contrast between what drivers will eventually see and what construction demanded. A driver may enter a clean portal, follow ordinary lane markings, and emerge on the opposite side without seeing the sea above. Behind that simple experience lies years of geological surveys, test drilling, machine design, segment production, underwater monitoring, and emergency planning. Successful infrastructure often hides its complexity. The smoother and more ordinary the journey feels, the more completely thousands of engineering problems have been solved before the first public vehicle arrives. The breakthrough also marks a transfer of risk from excavation to installation and operation. During tunneling, the dominant concerns include ground stability, cutter performance, water pressure, and accurate alignment. After excavation, attention shifts toward fitting permanent systems into a confined space and proving that they work together. Ventilation affects smoke control. Power affects lighting, pumps, communications, and monitoring. Drainage affects structural durability. Software connects sensors with control rooms. A failure in one system can influence several others, which is why integrated testing matters as much as individual equipment quality. Projects of this size also require discipline above ground. Concrete segments must be manufactured with consistent dimensions, transported without damage, and stored in the sequence needed underground. Excavated material must leave the site without overwhelming nearby roads. Workers enter and exit through controlled access points, while supplies travel through the same limited corridor. Surface teams, machine operators, surveyors, geologists, electricians, mechanics, and safety personnel must share accurate information. The tunnel advances underground, but its progress depends on an industrial network spread across factories, yards, offices, roads, and treatment facilities. For other coastal cities, Jiaozhou Bay will become a closely watched case study. Many growing regions face a similar question. How can two sides of a harbor or bay be connected without consuming valuable surface land or blocking navigation? Bridges are often cheaper and easier to inspect, while tunnels can remain protected from severe surface weather and preserve shipping routes. There is no universal answer. Geography, geology, traffic, environmental limits, maintenance capacity, and financing determine which solution makes sense. Qingdao's project will provide useful evidence, but its record-setting dimensions should not be copied where a smaller, simpler crossing would work better for local communities and budgets. In my opinion, the most impressive part is not the record length. It is the decision to combine multiple construction methods and manage extreme conditions beneath an active coastal city. The tunnel is still unfinished, so it would be premature to call the project a complete success. But finishing the main shield excavation proves that the central engineering concept works. The next challenge is turning an excavated structure into a safe, reliable road that people can trust every day. So what do you think? Are undersea highway tunnels worth their enormous cost and complexity when cities already have bridges and surface roads? Would you feel comfortable driving almost 10 kilometers beneath a bay, reaching 115 meters below sea level? Share your opinion in the comments. And for more stories about China's mega projects, factories, construction technology, energy systems, and engineering breakthroughs changing the physical world, subscribe to the Eastern Engine channel. For decades, analog computing carried a reputation for being fast but unreliable. Digital computers won because they could repeat the same calculation with predictable precision. Every value became a sequence of zeros and ones. Analog machines worked differently. They represented numbers with continuously changing physical quantities such as voltage, current, pressure, or resistance. That allowed them to solve some equations almost instantly, but tiny errors accumulated. Components drifted. Precision collapsed as problems became larger. Researchers at Peking University now say they have solved much of that problem. Their team built a foundry-made analog matrix solver using resistive random access memory, or RRAM. The system experimentally solved 16 by 16 real-valued matrix inversion problems at 24-bit fixed-point precision, which the researchers describe as comparable to FP32 digital computing. In massive MIMO signal detection, it reached digital-level accuracy after only 3 refinement cycles. and their benchmarking suggests that, with further circuit improvements, this architecture could deliver up to 1,000 times higher throughput and nearly 100 times better energy efficiency than leading digital processors at the same precision. That does not mean this prototype can run every AI model 1,000 times faster than an NVIDIA H100. It cannot replace a general-purpose GPU. The result applies to specialized matrix equation workloads, and the largest advantage is partly projected rather than fully measured in production hardware. Analog computing has always promised extraordinary speed. The missing piece was precision. Why digital computers dominated. A digital computer treats information as discrete values. At the lowest level, a transistor is interpreted as on or off. Software then performs arithmetic through carefully sequenced logic operations. Small electrical fluctuations usually do not change a 0 into a 1. Digital systems can use error correction, repeat operations, and store exact copies of data. Analog systems trade some of that certainty for direct physical computation. Imagine solving a mathematical equation by building an electrical circuit whose voltages naturally settle into the answer. The circuit does not need to execute millions of separate instructions. The physics performs the calculation as the signals move through the hardware. But real components are imperfect. Resistance changes with temperature. Amplifiers introduce noise. Manufacturing creates small differences from one device to another. The answer may be close, but not exact enough for scientific computing, communications, or modern AI. The Peking University team attacked the problem by separating speed from accuracy. One analog circuit produces a fast, approximate answer. A second analog operation measures the remaining error and corrects it. The system repeats this process until the solution reaches the required precision. What RAM actually does. The heart of the design is resistive random access memory. An RRAM cell stores information by changing the electrical resistance of a material between two electrodes. A low resistance state may represent one value. A higher resistance state may represent another. In this experiment, each cell supported 8 stable conductance levels, equivalent to 3 bits of information. The researchers used a 1 megabit RRAM chip for high-precision matrix vector multiplication and a smaller 8x8 RRAM array for low-precision matrix inversion. Both were fabricated using a commercial 40-nanometer CMOS platform. This was not a hand-built device assembled from exotic laboratory materials. The chips were produced through a foundry-compatible process, using 1 transistor, 1 resistor memory cells. An RRAM array can behave like a physical matrix. Each cell's conductance represents one matrix element. Input voltages represent a vector. When those voltages pass through the array, the resulting currents naturally combine according to Ohm's law and Kirchhoff's current law. The array performs matrix vector multiplication through its physical behavior. A digital processor would normally load data from memory, execute many multiplication and addition instructions, then write the result back. The RRAM array stores the values and performs the calculation in the same location. That reduces data movement and avoids much of the conventional von Neumann bottleneck. The matrix problem. Matrix equations appear almost everywhere in advanced computing. Wireless base stations solve them to separate overlapping signals from many antennas. Some neural network training methods also depend on matrix inversion or related linear system solving. A common form is A times X equals B. The matrix A and vector B are known. Digital methods solve this accurately, but the cost grows quickly as the matrix becomes larger. An analog circuit can produce a solution directly by placing the resistive array inside a closed feedback loop with operational amplifiers. However, the first answer is only approximate. The challenge is improving that result without handing the important calculation back to a digital processor. Earlier hybrid systems often used analog hardware for a rough estimate and digital floating point hardware for the precise correction. The Chinese team kept both major operations in the analog domain. How the two-stage solver works. The first stage performs low-precision analog inversion. Because the RRAM devices and supporting circuits are not perfectly accurate, the result contains an error. The second stage performs high-precision analog matrix vector multiplication. It calculates how far the approximate answer is from satisfying the original equation. That difference is called the residual. The solver then feeds the residual back into the low-precision inversion circuit to produce a correction. Each cycle moves the solution closer to the target. The researchers reported that precision improved by roughly 3 bits during each cycle, reflecting the 3-bit conductance levels in the RRAM cells. A 24-bit 4x4 real-valued matrix reached the maximum target precision after 9 cycles, Larger complex valued problems generally reach the same precision within about 10 cycles. This is the central idea. The fast analog inversion does not need to be perfect. It only needs to be good enough that repeated analog correction converges toward a precise answer. The design accepts analog error, measures it, and then removes it. That is very different from pretending the hardware is naturally exact. How bit slicing builds precision. One RRAM cell stores only 3 bits, but the complete system reaches 24-bit precision. It does this through bit slicing. A high-precision matrix value is divided into several lower-precision pieces. Each piece represents a different group of bits and is mapped into a separate RRAM array. The arrays perform low-precision calculations in parallel or sequence. Their partial outputs are then shifted according to their significance and added together. It is similar to separating a large decimal number into thousands, hundreds, tens, and units. Each part is easier to represent. Combining the weighted parts reconstructs the original value. Bit slicing was already useful for analog matrix vector multiplication. The harder problem was applying high precision to matrix inversion, where the same simple distributive rules do not transfer cleanly. The researchers solved this by keeping inversion low precision, while using bit-sliced matrix vector multiplication to calculate the correction accurately. Block AMC makes the design scalable. A physical RRAM array cannot grow without limit. Large arrays suffer from wire resistance, routing complexity, stronger currents, parasitic effects, and amplified noise. The team therefore used a block-based algorithm called Block AMC. A larger matrix is divided into smaller submatrices. Different RRAM arrays store different blocks. The system performs a sequence of inversion and multiplication operations on those blocks, then combines the intermediate results. Using this approach, the researchers experimentally solved a 16 by 16 real-valued matrix inversion problem with 24-bit fixed-point precision. The relative error reached roughly 1 part in 10 million after 10 cycles. 16 by 16 may sound small compared with giant AI models, but matrix inversion is more difficult to map into analog hardware than ordinary multiplication. The point was to prove that a precise analog solver could scale beyond one tiny hardwired circuit. The block method also allows future systems to use multiple moderate-sized arrays instead of depending on one enormous analog network. The massive MIMO test. The researchers demonstrated the solver on wireless signal detection. Massive MIMO uses many antennas at a base station to communicate with several devices at once. The received signals overlap. The base station must solve matrix equations to separate the different users and recover the transmitted information. The experiment modeled systems using higher-order 256 QAM modulation, which packs 8 bits into each transmitted symbol. That demands far more precision than earlier analog demonstrations limited to simpler modulation. The researchers transmitted a binarized image of the Peking University emblem through the modeled wireless channel. Their analog solver recovered the signal with bit error performance comparable to FP32 digital processing. For a 128 by 8 system, the detector reached comparable accuracy after only 3 iterative cycles. This matters because it connects the architecture to a real workload rather than only random laboratory matrices. Wireless communication, especially future 5G advanced and 6G systems, may require repeated matrix solving with strict limits on latency and energy. Where the 1000x claim comes from. The 1000 times figure needs careful explanation. The prototype did not directly defeat an NVIDIA H100 by 1000 times in a complete application. The researchers benchmarked their analog architecture against state-of-the-art digital processors at comparable precision. Their model considered matrix size, array dimensions, converter overhead, amplifier speed, and block processing requirements. At moderate array sizes, the analog design already showed advantages for specific matrix solving tasks. For larger optimized arrays and faster operational amplifiers, the projected throughput advantage could approach 3 orders of magnitude. Energy efficiency could improve by nearly 2 orders of magnitude. The paper also notes that block AMC reduces the advantage as matrices become larger because more stages and intermediate operations are required. Even then, the architecture remained ahead in the researchers' comparisons. The maximum result depends on better supporting circuits and dedicated integration. So the honest statement is that the demonstrated architecture could reach 1000 times higher throughput for precise matrix equation solving. It is not evidence that an analog chip will make every CUDA workload 1000 times faster. Why this could matter for AI? Modern AI depends heavily on matrix operations, but not every matrix operation is the same. Neural network inference is dominated by matrix multiplication. This chip focuses on matrix inversion and solving linear systems. Those operations appear in optimization, scientific machine learning, signal processing, and some second-order training methods. An analog solver could become a specialist accelerator. A conventional CPU or GPU would manage the overall program. When the workload reaches a suitable matrix equation, the system could send that task to the RRAM solver. The analog hardware would produce the answer quickly and efficiently, then return it to the digital processor. This is more realistic than expecting analog computing to replace digital machines completely. Digital hardware remains better for control flow, memory management, software compatibility, and exact general-purpose operations. Analog hardware may win by handling the narrow calculations where physics offers a shortcut. The honest catch: several engineering challenges remain. The low-precision inversion circuit still uses external components, including operational amplifiers, data converters, switches, and a microcontroller. The larger, high-precision RRAM array was integrated, but the complete solver was not one compact commercial chip. Scaling the inversion array beyond the demonstrated size requires dedicated design and fabrication. Larger arrays produce stronger currents and more complicated routing. Noise, wire resistance, device defects, and temperature variation must remain controlled. The system also needs programming and verification procedures to place every RRAM cell into the correct conductance state. Converters and amplifiers consume area and energy, and commercial software would need tools that identify suitable equations and map them efficiently onto the hardware. It does not prove that mass production will be easy. My take is that the breakthrough is not simply bringing analog computing back. It is making analog error part of the algorithm. The first circuit is allowed to be imperfect. The second measures that imperfection. Repeated correction turns a rough physical answer into one approaching digital precision. That is a powerful design philosophy. Future computers may not choose between analog and digital. They may combine both. Digital processors will coordinate the system and preserve programmability. Analog accelerators will solve selected equations using currents, resistance, and feedback, instead of long sequences of instructions. The 1,000 times estimate may shrink once complete commercial overhead is included, or better integration may allow the architecture to approach its projected advantage. Either way, this work moves analog matrix solving from a low-precision curiosity toward a credible specialist technology. So what do you think? Will analog accelerators become essential for AI, science, and 6G? Or will manufacturing variation and software complexity keep GPUs in control? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and engineering breakthroughs reshaping computing. Because China has not built a universal NVIDIA replacement, but it may have solved the precision problem that kept analog computing out of the modern chip era. There's a material so pure that, until a few days ago, only a tiny handful of places on the planet could make it. Not a handful of countries, a handful of facilities. It was one of those quiet, invisible bottlenecks that the rest of the world barely thinks about, yet it sits underneath one of the most important technologies of the next century. China just started mass producing it. The material is called silicon-28, and calling it pure doesn't quite capture it. It's purified to better than 99.99%, which earns it a nickname scientists actually use, the purest silicon on Earth. On June 15, 2026, China's National Nuclear Corporation announced it had achieved independent, large-scale production of this material for the first time. No headlines about a flashy new gadget, no glowing phone chip to hold up on a stage, just a slab of the quietest, cleanest silicon humanity knows how to make. And here's why that matters more than almost any product launch. This specific material is the foundation that one of the most promising paths to a working quantum computer is built on. Without it, an entire approach to quantum computing essentially can't scale. With a domestic, mass-produced supply of it, a door that was previously held shut by a few foreign suppliers just swung open for China. Now, like every story on this channel, there's important nuance here, and I'll give you all of it honestly, including why this is a foundation stone and not a finished building. But by the end of this video, you'll understand what makes this silicon so special, why noise is the great enemy of quantum computing, why only a few places on Earth could make this stuff, and why a quiet materials announcement might matter more than the loudest chip launch of the year. Let's get into it. Start with the basics, because silicon is one of those words everyone half knows. Silicon is the bedrock of the modern world. It's the second most abundant element in the Earth's crust. It's literally in sand. Purify it, Slice it into wafers, etch tiny circuits onto it, and you get the chips that run your phone, your laptop, every device you own. The entire digital age is built on refined sand. We've been making ordinary electronics-grade silicon at massive scale for over half a century. That part is not new and not hard for anyone anymore. But here's the thing most people never learn. Not all silicon atoms are identical. Silicon comes in slightly different versions of itself, called isotopes, atoms with the same chemical identity, but slightly different weights. Natural silicon is a blend of three: silicon-28, which makes up about 92%, silicon-29 at roughly 5%, and silicon-30 making up the rest. For normal electronics, this blend is completely fine. Your phone's processor does not care which silicon isotopes it's made of. For 70 years, nobody needed to separate them. The mixture worked perfectly. But quantum computing is not normal electronics. And in the quantum world, that small, harmless-seeming 5% of silicon-29 turns out to be a saboteur. It's the difference between silicon that's good enough to run a supercomputer and silicon that's good enough to run a quantum computer, and those are two completely different bars. To understand why that tiny fraction matters so enormously, you have to understand the single greatest enemy of quantum computing. And that enemy has a name: noise. Here's the heart of it, and I'll keep it concrete. A regular computer thinks in bits, switches that are either on or off, 1 or 0, rock solid, dependable, binary. A quantum computer uses something far stranger and far more powerful: the qubit. A qubit can exist in a delicate blend of both states at once, and it's this fragile in-between condition that gives quantum computers their almost magical potential to solve problems that would take a normal supercomputer billions of years. But that power comes with a curse. Qubits are unbelievably fragile. They hold their delicate quantum state for only a fleeting moment before the outside world disturbs them, and the information collapses into useless randomness. Scientists call this collapse decoherence, and it is the central villain of the entire field. The whole game of building a quantum computer is, in large part, a desperate fight to keep qubits in their delicate state for as long as possible. Every extra fraction of a second of stability is hard-won. So what disturbs them? Noise. Not sound, environmental interference, heat, stray electromagnetic fields, vibration, and, crucially, magnetic disturbance from the very material the qubit is sitting inside. This is where that 5% of silicon-29 becomes a wrecking ball. Here's the key piece of physics. Silicon-28 has a property called zero nuclear spin. In plain terms, its atomic nucleus is magnetically silent. It sits there perfectly still and quiet, generating no magnetic disturbance whatsoever. But silicon-29 is different. Its nucleus does have a spin. It acts like a tiny restless magnet, constantly flickering and wobbling. Scientists have a wonderfully descriptive name for the havoc this causes. They call it nuclear flip-flopping. Imagine you're trying to keep a single feather perfectly still and balanced on your fingertip. That's the qubit. Now imagine the room is full of tiny invisible fans randomly puffing air at it from every direction. Those puffs are the silicon-29 atoms magnetically jostling your qubit, knocking it off balance, destroying the delicate state you fought so hard to create. The more silicon-29 around your qubit, the more puffs of disturbance, and the faster your quantum information falls apart. Now the solution becomes obvious. If silicon-29 is the source of the noise, get rid of it. Strip it out. Engineer silicon that is almost pure silicon-28, magnetically silent, a calm and quiet home where a qubit can hold its delicate state in peace. Do that, and you've built what researchers describe as a solid-state vacuum, an environment so quiet the qubit can survive dramatically longer. That is exactly what the purest silicon on Earth is. And it changes everything about how stable a silicon qubit can be. So if everyone knows silicon-28 is the answer, why isn't every quantum lab swimming in it? Why was this announcement a genuine breakthrough rather than a routine purchase order? Because separating isotopes is one of the hardest things in all of industrial science. Remember, silicon-28, silicon-29, and silicon-30 are chemically identical. They behave the same in every chemical reaction. You cannot separate them with chemistry. There's no reaction that grabs one and leaves the others. The only thing that distinguishes them is a minuscule difference in weight, because each has a slightly different number of neutrons. So to purify silicon-28, you have to sort atoms by weight, one tiny mass difference at a time, until you've stripped out almost every last silicon-29 and silicon-30 atom from the mix. This is brutally difficult. It typically involves converting the silicon into a gas, then spinning that gas in sophisticated centrifuges, or using other exotic enrichment techniques to gradually concentrate the lighter silicon-28, repeating the process over and over to inch the purity higher and higher. Pushing past 99.99% purity at any meaningful quantity demands enormous technical mastery and expensive specialized infrastructure. It's closer to the world of nuclear-grade isotope enrichment than to ordinary chip making, which is precisely why China's nuclear corporation, not a traditional chip maker, is the one that cracked it. And here's the part that gives this story its strategic weight. Until now, the ability to produce ultra-pure silicon-28 at scale was concentrated in a very small group of overseas players, facilities tied to Russia, to Europe, and to US-linked supply chains. If you were a Chinese quantum lab and you needed this material, you were dependent on importing it from a handful of foreign sources. That's a choke point, a quiet, invisible one, not a banned machine or a blocked chip, but a raw material that a few outside suppliers controlled. This is the pattern that should feel familiar by now if you watch this channel. The most powerful restrictions aren't always the loud, obvious ones. Sometimes the real leverage is buried in an unglamorous material that nobody outside the field even knows exists. And China just removed that particular piece of leverage from the board by moving silicon-28 from imported from a few foreign suppliers to mass-produced at home. The achievement isn't a finished quantum computer. It's something quieter and, in the long run, possibly more important: supply chain independence in a material the future may be built on. Now, you might be wondering, there are several different ways people are trying to build quantum computers. Why does this particular path, the silicon one, matter so much that purifying its core material is a national-level achievement? Because silicon has one colossal advantage no other approach can match. The entire planet already knows how to manufacture it. Think about it. For decades, the world has poured trillions of dollars and unfathomable engineering effort into building silicon chips with billions of features etched at near-atomic precision. There are vast factories, refined techniques, and deep institutional knowledge dedicated to manipulating silicon better than any other material in human history. If you can build a quantum computer out of silicon, you can potentially tap into all of that existing manufacturing muscle to scale it up, instead of inventing an entirely new industry from scratch. That's the dream of silicon quantum computing. Other leading approaches, like the superconducting chips and trapped ion machines you may have heard of, are powerful, but require building exotic infrastructure largely from the ground up. Silicon qubits promise something seductive: the quantum future, manufactured on a foundation the world has already spent 70 years mastering. And critically, because silicon qubits can be incredibly small, this approach holds the promise of one day fitting thousands of qubits on a single chip, and potentially millions on one device, exactly the kind of scaling you'd need for a quantum computer that can actually change the world. But, and this is the catch, that entire vision rests on having silicon quiet enough to keep the qubits stable. The dream is only as good as the purity of the material underneath it, which is exactly why mass-producing the purest silicon on Earth isn't a footnote. It's the literal foundation the whole silicon quantum dream stands on. Remove the supply problem for that material, and you've cleared one of the biggest roadblocks standing between China and a scalable quantum computer. Now let me be completely straight with you, because I'd rather you trust this channel than oversell you a story. Mass-producing silicon-28 does not mean China has built a working quantum computer. It does not mean the quantum era arrived last week. What it means is that China has secured a critical ingredient, and ingredients, however essential, are not finished meals. There are real, hard problems still standing between this material and a useful quantum machine. Silicon qubits, across the whole field worldwide, are still at an early stage. Researchers have coherently controlled only a handful at a time, somewhere in the range of a few to a dozen qubits, with recent demonstrations reaching around 11. That's a long, long way from the thousands or millions you'd need for a quantum computer that can crack hard real-world problems. Getting from a dozen qubits to a million is a staggering engineering climb, and pure silicon alone does not get you there. You still need precise qubit control, error correction, packaging, wiring, and a dozen other unsolved challenges. So the honest framing is this: China has not won quantum computing. No one has. What China has done is eliminate a specific supply chain vulnerability and secure domestic control over a foundational material that its silicon quantum ambitions absolutely depend on. It's a step that's necessary but not sufficient, a cleared roadblock, not a crossed finish line. The headlines calling this the breakthrough that gives China quantum supremacy are getting ahead of reality, but the cynics waving it away as just some pure silicon, who cares, are missing the strategic point entirely. In a field where the whole game is fighting noise, controlling the quietest material on Earth is exactly the kind of unglamorous advantage that compounds over years. And there's a strategic dimension that makes this bigger than quantum computing alone. The same institute announced it has now mastered the production of 26 stable isotopes across 12 elements, materials with uses stretching into nuclear medicine, aerospace, particle physics, and deep space exploration. Silicon 28 is the headline, but the real story may be that China has built an entire domestic isotope enrichment industry, turning a whole category of materials it once imported into things it now makes itself. Step back, and you'll notice this is the same shape as story after story we've covered. It's almost never the loud, obvious component that becomes the decisive battleground. It's the quiet foundational layer underneath, the substrate beneath the chip, the memory beside the processor, the cooling material that keeps it from melting, and now the ultra-pure raw silicon beneath the qubit. Over and over, the real leverage in a technology race lives in the parts most people never see, and the country that secures those invisible foundations quietly buys itself a future the headlines won't notice until much later. And the response to restriction keeps rhyming too. Faced with dependence on a handful of foreign suppliers for a critical material, China didn't shrug. It built its own production from scratch, using expertise borrowed from its nuclear industry, and removed the dependency entirely. Whether it's lithography, memory, or now isotope enrichment, the pattern holds. A choke point identified becomes a choke point engineered around. I genuinely don't think it's a coincidence anymore. It's a deliberate, systematic march to control every foundational layer of the technologies that will define the rest of this century. This particular announcement won't trend the way a flashy gadget does. There's no screen to admire, no benchmark to gawk at. But years from now, when silicon quantum computers are real and scaling, the quiet ability to manufacture the purest silicon on Earth may turn out to have been one of the foundation stones the whole thing was built on. Here's my honest opinion. I find these boring material stories more revealing than the splashy ones, precisely because almost nobody pays attention to them. It's easy to get excited about a chip you can hold up on a stage. It's much harder to get excited about a slab of ultra-pure silicon, and that's exactly why this kind of move is so telling. The companies and countries that win technology races are usually the ones quietly locking down the unglamorous foundations, while everyone else is dazzled by the product launches. Silicon 28 is the definition of an unglamorous foundation, and China just made sure it owns its supply of it. Do I think this means China is about to leap ahead in quantum computing? No, the field is too young, the qubit count's too small, the road too long for any single material to decide it. But do I think it's a meaningful, deliberate piece of a much larger strategy that's easy to underestimate? Absolutely. The whole point of this kind of move is that it doesn't look like much until, one day, it suddenly looks like everything. The quietest silicon on Earth, made to silence the noise that kills qubits, secured at home instead of bought abroad. It's a small story that's secretly a big one. And those, in my experience, are usually the ones worth paying attention to. So here's my question for you, and I genuinely want your honest take. Do you think quantum computing is going to arrive sooner than we expect and quietly transform everything? Or is it overhyped, perpetually almost here, and decades further away than the headlines suggest? Are you a quantum optimist or a quantum skeptic? Drop your real opinion in the comments. I read every single one. If you want to keep following this, the breakthroughs, the invisible foundations, the quiet moves that matter long before the world notices, subscribe to Eastern Engine and hit the notification bell. Chips, materials, quantum, the entire foundation of modern technology is being rebuilt right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. China has demonstrated a new way to turn seawater into drinking water using sunlight instead of electricity from the grid. Researchers built an outdoor system covering less than 1 square meter. Under natural sunlight, the prototype reportedly produced just over 20 liters of fresh water per day. That is enough to cover the basic daily drinking water needs of roughly 10 people. The collected water met international drinking water standards, and the researchers even used it to irrigate a small test field through complete crop growing cycles. But the most important part is not simply that sunlight can evaporate seawater. Humans have known that for thousands of years. The breakthrough is the material inside the device. Chinese researchers created a three-dimensional photothermal structure designed to absorb sunlight, concentrate heat at the water's surface, accelerate evaporation, and operate without being connected to the electrical grid. In laboratory testing, the material reached an evaporation rate of 38.14 kilograms of water per square meter every hour. That was more than 8 times the performance of the researchers' earlier flat design. The system also absorbed more than 90% of incoming sunlight and reportedly reduced the energy needed for evaporation by nearly 46%. If the technology can be scaled reliably, it could provide drinking water to islands, coastal villages, farms, and disaster zones where large desalination plants are too expensive or where electricity is unreliable. But can a small solar prototype really compete with industrial desalination? Or is this another impressive laboratory result that becomes far more difficult once engineers try to build it at useful scale? To answer that, we need to understand why turning seawater into drinking water remains so expensive. Why desalination needs so much energy. The ocean contains an almost unlimited supply of water. But seawater also contains salt, minerals, microorganisms, and other contaminants that humans cannot safely drink in large quantities. Removing those substances takes energy. The most common modern method is reverse osmosis. A desalination plant uses powerful pumps to force seawater through membranes containing extremely small pores. Water molecules pass through, while most dissolved salts are blocked. The process works well and is used in large facilities around the world, but it requires high pressure. Creating that pressure consumes electricity, and the plant also needs pre-treatment equipment, filters, pumps, membranes, monitoring systems, and maintenance. Another approach uses heat. Seawater is evaporated, leaving salt behind, and the water vapor is then condensed into clean liquid. This resembles the natural water cycle. The sun evaporates ocean water, clouds form, and fresh water returns as rain. Industrial thermal desalination can produce large amounts of water, but heating that much seawater consumes enormous quantities of energy. That is why researchers are interested in solar evaporation. Instead of heating an entire tank of water, a photothermal material absorbs sunlight and concentrates the heat only where evaporation happens. The goal is to generate water vapor while wasting as little energy as possible. How the Chinese material works. The new system uses a three-dimensional photothermal structure. Photothermal simply means that the material converts light into heat. A flat, dark surface can already do this. Leave a black object in direct sunlight and it becomes hot because it absorbs more light than a reflective surface. But a high-performance solar evaporator needs to do much more. It must absorb a wide range of sunlight. It must transfer heat into a thin layer of water instead of heating the entire reservoir. It must continuously pull fresh seawater toward the evaporation surface. It must allow water vapor to escape. And it must prevent salt from blocking the structure. The Chinese team developed a three-dimensional design with a much larger active surface than a conventional flat absorber. That extra surface area allows more water to interact with the heated material at the same time. The structure also helps confine heat near the evaporation zone. Instead of allowing thermal energy to spread into the bulk seawater, more of the captured sunlight is used directly to change liquid water into vapor. The researchers reported solar absorption of up to 90.2%. They also said the design reduced the effective energy required for evaporation by 45.7%. That does not violate physics or create energy from nothing. Water molecules still need energy to escape the liquid. The material changes how efficiently heat is delivered and may also alter the local interaction between water and the internal surfaces. The result is faster evaporation from the same amount of sunlight. The 38.14 kilogram result. The headline laboratory number was 38.14 kilograms per square meter per hour. Because 1 kilogram of water is approximately 1 liter, that sounds like the device could produce more than 38 liters of drinking water every hour from 1 square meter. But that interpretation would be misleading. The figure describes the measured evaporation rate under controlled test conditions. Evaporated water is not automatically collected drinking water. A complete system must capture the vapor, move it toward a cooler surface, condense it into liquid, and store it without contamination. Every step introduces losses. Laboratory illumination may also differ from changing outdoor sunlight. Clouds, wind, temperature, humidity, and the angle of the sun all affect real-world output. That is why the outdoor prototype is more important than the laboratory record. The real outdoor prototype. The researchers constructed a system with an active area of approximately 0.75 square meters. It was tested outside using natural sunlight rather than a controlled indoor lamp. The complete device produced 20.16 liters of fresh water in one day. That is far lower than multiplying the peak laboratory evaporation rate across 24 hours. But it is a much more meaningful figure because it represents water actually collected by a working outdoor system. 20 liters is not enough for the complete daily water use of 10 people. Cooking, washing, sanitation, and agriculture require far more, but it may cover basic drinking needs. That could matter in remote places where fresh water must currently be transported by truck or boat. A small village could use several modules. A disaster relief team could deploy portable systems where the power grid has failed. Coastal farms might use larger arrays to supplement irrigation water. The system would still depend on weather and sunlight, but it could operate without the continuous electricity demand of a conventional reverse osmosis plant. What no grid power really means. The device is sometimes described as electricity-free. That wording needs context. The system does not operate without energy. Its energy comes from sunlight. The photothermal material absorbs solar radiation and converts it into heat. The correct claim is that the prototype can produce water without being connected to an external electrical grid. That is an important difference. A reverse osmosis plant may require continuous electricity for pumps. A solar evaporator can operate passively during daylight. However, a larger commercial system might still use small pumps, sensors, fans, or automated controls. Electricity could also be useful for moving seawater, collecting water, cleaning equipment, or operating at night. The central advantage is not that electricity becomes forbidden. It is that the main energy-intensive step, evaporation, is driven directly by the sun. The salt problem. Salt is one of the biggest obstacles facing solar desalination. When water evaporates, dissolved salt remains behind. As evaporation continues, the water near the surface becomes increasingly concentrated. Eventually, salt crystals can form on the photothermal material. Those crystals block sunlight, restrict water movement, and damage performance. A laboratory device may work well for several hours and then become far less effective after days of salt accumulation. Any practical solar evaporator needs a way to manage concentrated brine. Some designs allow salt to diffuse back into the larger seawater reservoir. Others use channels that continuously circulate water through the structure. Some devices are periodically flushed, while others are designed so that salt crystallizes in a separate location where it can be removed. Long-term durability will be one of the most important tests for the Chinese system. The prototype must prove that it can operate through repeated wetting, drying, heating, and salt exposure without losing performance. Coastal seawater also contains biological material and minerals that may clog surfaces over time. Producing water for one successful demonstration is different from operating every day for several years. The farming test. The researchers did not stop after measuring the water in a container. They used the fresh water to irrigate a test field covering approximately 5 square meters. The system reportedly supported complete crop growing cycles. That experiment matters because agriculture is the world's largest user of fresh water. Many water-stressed regions are located near oceans, but seawater cannot be applied directly to most crops. Salt builds up in soil, damages roots, and eventually makes farmland unproductive. A modular solar desalination system could provide small quantities of fresh water for greenhouses, seedlings, or high-value crops. It would not immediately replace the enormous irrigation networks used for rice, wheat, or corn. Those systems move thousands or millions of liters. But it could be valuable for remote islands, desert communities, or small coastal farms where every liter of clean water is expensive. The cost claim. The researchers estimate that after roughly 2 years of operation, the cost of the produced water could fall below the price of commercial bottled water. That is a projection, not a confirmed market price. Bottled water is also an easier benchmark to beat than municipal tap water. Bottled water includes packaging, transport, storage, and retail profit. A large reverse osmosis plant may produce water at a much lower cost per liter than bottled water, especially when operated at enormous scale. The true economics will depend on the cost of the photothermal material, the condenser, supporting structure, maintenance, cleaning, lifetime, and installation. If the device needs frequent replacement, the water will be expensive. If it survives for years with little maintenance, the economics become much stronger. Local conditions will also matter. In a city with an established water network, the system may not compete with tap water. On an isolated island where bottled water arrives by boat, it could be far more attractive. Can it scale? Scaling is the central question. A 0.75 square meter prototype can be carefully assembled and monitored by researchers. A commercial system may need hundreds or thousands of square meters. Every module must distribute seawater evenly. Vapor must be collected efficiently. Condensation surfaces must remain cool enough to turn vapor back into liquid. Strong winds, storms, dust, salt spray, and biological growth must not destroy the equipment. The system must also dispose of concentrated brine responsibly. Large desalination plants return salty waste to the ocean, where it can damage local ecosystems if it is not properly diluted. A solar system produces less water per unit, but a large field of modules could still create a significant waste stream. Manufacturing is another challenge. The photothermal structure must be cheap enough to produce in large quantities. A material with excellent laboratory performance may rely on complicated fabrication steps that make commercial production too expensive. Engineers will need to simplify the design without losing the properties that created the high evaporation rate. Where it could be used first. The technology is most likely to succeed first in places where water is valuable and electricity is limited. Small islands are one obvious market. Many islands have abundant sunlight and seawater, but depend on imported fuel or bottled water. Remote coastal villages could use modular units for drinking and cooking. Disaster zones are another possibility. Earthquakes, floods, and storms can damage power lines and contaminate freshwater supplies. Portable solar desalination equipment could begin producing water without waiting for the electrical grid to be restored. Military bases, research stations, ships, and offshore facilities may also value systems that reduce dependence on transported water. Agriculture could become another market if the device is combined with water storage and efficient drip irrigation. But the technology is unlikely to replace giant municipal desalination plants immediately. Cities need reliable water every hour of the day, regardless of weather. Large reverse osmosis facilities already produce hundreds of millions of liters daily. Solar evaporation will probably begin as a supplement rather than a complete replacement. My take is that this is a promising water technology, but the 20-liter outdoor result matters more than the spectacular laboratory number. The researchers have shown that the material can move beyond a small indoor sample and produce usable fresh water under natural sunlight. That is an important step. The system could be especially valuable where transporting water is expensive and grid electricity is unavailable. But it is not yet proof that China has solved global water scarcity. The prototype is small. Long-term salt resistance still needs to be demonstrated. The manufacturing cost must fall, and larger systems must show that they can collect and condense vapor efficiently in real weather. Still, the concept attacks one of desalination's biggest problems directly. Instead of spending large amounts of electricity pushing seawater through membranes or heating enormous tanks, the system uses a carefully designed material to place solar heat exactly where evaporation occurs. The ocean provides the water. The sun provides the energy. The material connects the two. If China can turn that laboratory efficiency into durable mass-produced equipment, the technology could give remote communities a new source of drinking water without waiting for a power plant or a massive pipeline. So what do you think? Could sunlight-powered desalination become a practical solution for water-stressed coastal regions? Or will scaling, salt, and maintenance keep it limited to small installations? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the technologies, factories, and engineering decisions reshaping the global economy. Because China has not eliminated the cost of desalination, but it may have found a way to replace part of that cost with sunlight. A laboratory in Oregon takes one of Huawei's newest smartphone processors and begins removing it layer by layer. The package comes apart. The memory is separated. The silicon is polished until structures invisible to the human eye become visible under powerful microscopes. And deep inside the chip, researchers find a number that appears to break the normal hierarchy of semiconductor manufacturing: 32.5 nanometers. That is the measured pitch of the lowest local metal layer inside Huawei's Kirin 9030 processor, manufactured by China's SEMIC using its N+3 process. Now compare that with Intel's newest commercial manufacturing technology. Inside Panther Lake processors built on Intel 18A, the equivalent layer is reportedly spaced at 36 nanometers. On that one measurement, China's 7-nanometer class process went smaller than the layer shipping inside Intel 18A. And it did so without EUV lithography. That sounds like SMIC somehow jumped beyond Intel. It did not. Intel's overall process remains denser, more efficient, and considerably more advanced. Intel 18A can also support a tighter metal pitch than the version used in Panther Lake. But the measurement is still remarkable because it reveals how aggressively SMIC has stretched older lithography equipment. The company did not overcome the problem with one secret machine. It attacked the chip from several directions at once. Quadruple patterning, narrower cells, fewer transistor fins, contacts placed in tighter positions, and a metal network compressed almost to the practical edge of DUV manufacturing. The result is not a clean victory, it is an engineering trade. SMIC gained density, but it paid for that density with additional masks, extra processing, tighter alignment tolerances, and greater manufacturing complexity. And that trade may tell us more about the future of Chinese chip making than a simple benchmark ever could. Modern semiconductor names are misleading. 7 nanometers, 5 nanometers, 3 nanometers, 18 angstroms. These labels sound like direct physical measurements, as though every important feature inside a 7 nanometer chip must be 7 nanometers wide. That has not been true for years. Process names have become generational labels. They describe a package of manufacturing improvements rather than one universal dimension. Intel 18A does not mean every structure measures 18 angstroms. SMIC N+3 does not mean every feature measures 7 nanometers. Two companies can use completely different names while producing structures that overlap in certain dimensions. That is why comparing 7 nanometer with 18A by name alone creates the wrong picture. A chip contains many different measurements. There is gate pitch, fin pitch, cell height, transistor density, metal pitch, SRAM density, and the spacing between contacts and wires. Each reveals one part of the process. The new teardown focused attention on M0, the first local metal layer sitting just above the transistor structures. Think of the transistors as tiny buildings. The metal layers are the roads connecting them. M0 handles extremely short local connections inside the smallest logic cells. Higher layers gradually become wider roads carrying signals across larger regions of the chip. A tighter M0 pitch allows more local wiring to fit into a smaller area. But one narrow street does not automatically mean the whole city is better. The city also needs highways, power delivery, intersections, and enough space for traffic to move. That is where the comparison becomes complicated. The chip examined was Huawei's Kirin 9030 Pro, part of the processor family used in the Mate 80 series. It is manufactured using SMIC's third-generation 7 nanometer class process, known as N+3. Researchers measured the M0 pitch at approximately 32.5 nanometers. That is around 10% tighter than the 36 nanometer M0 configuration found in Intel's Panther Lake processors. SMIC's M1 layer measured approximately 38 nanometers, while M2 measured around 40. These dimensions show that SMIC compressed the lowest wiring layers aggressively, but the larger picture is different. The teardown estimated SMIC N+3 at roughly 113 million transistors per square millimeter using a normalized logic density metric. That places it around the level of TSMC's older N6 process. Intel 18A's high-density library remains approximately 38% denser. So how can one local layer be tighter while the overall process remains far behind? Because density is not controlled by one dimension. SMIC squeezed M0 partly because it needed to. Intel could leave more space there because it had already removed one of the largest sources of congestion: power. Traditional chips deliver both data signals and electrical power through metal layers above the transistors. Imagine trying to build a city where delivery vans, commuter traffic, power cables, and water pipes all compete for the same narrow streets. The result is congestion. Intel's Power Via technology changes that arrangement. Instead of routing power through the front side metal stack, Intel brings power through the back of the silicon. Signals remain on one side. Power arrives from the other. This frees valuable routing space above the transistors and reduces resistance in the power network. With less front-side congestion, Intel does not always need to compress every local wire to the smallest possible pitch. Panther Lake uses a 36 nanometer M0 pitch, but Intel 18A reportedly supports a 32 nanometer option. Intel chose the looser configuration partly because Panther Lake relies heavily on higher performance cell libraries and because Power Via gives designers more routing freedom. That is why the headline needs the phrase "in one critical layer." SMIC produced a tighter M0 pitch in this shipping Huawei chip. But Intel's process is not limited to 36 nanometers, and a wider M0 layer does not automatically represent weaker technology. Sometimes additional space is not a failure to shrink. It is a choice enabled by a better architecture. The most impressive part of SMIC N+3 is not that the company found a magical replacement for EUV. It is that engineers extracted more resolution from DUV lithography through repetition. The key method is called self-aligned quadruple patterning, or SAQP. The concept sounds almost like a geometric trick. A DUV lithography system first prints a relatively wide guide pattern called a mandrel. A thin spacer material is deposited along the sides of that guide. The original guide is removed, leaving the spacers behind. Those spacers then become guides for another deposition and removal cycle. One original line effectively becomes 4 narrower lines. Imagine drawing one thick stripe on a road. You place barriers along both edges, then remove the original stripe. Next, place smaller barriers around the barriers that remain. After several carefully controlled steps, one broad pattern has been multiplied into several narrow, evenly spaced features. The lithography machine did not directly resolve every final line. The process created them through deposition and etching. That is how SMIC could form a roughly 32 nanometer grid using DUV equipment. But every added operation creates risk. The spacers must have nearly identical thickness. The etch must remove exactly the intended material. The new lines must remain aligned with contacts and structures created in other steps. If one stage shifts slightly, the error can propagate through the entire pattern. EUV can print finer features with fewer pattern-splitting steps. DUV can reach similar dimensions in selected layers, but the path is longer. SMIC replaced machine simplicity with process complexity. Quadruple patterning sounds clever because it is clever. It is also expensive. Each additional deposition, etch, cleaning, and inspection step consumes factory time. More steps require more equipment. More equipment means more maintenance. More masks increase cost before the first commercial wafer is even produced. Alignment becomes increasingly difficult because patterns created in separate operations must meet with extraordinary precision. A small overlay error can place one metal line too close to another, creating electrical leakage or a short circuit. Place it too far away, and the intended connection may fail. Then there is variation. If one spacer is slightly thicker than another, the final lines will not be identical. Resistance changes, timing changes. One region of the chip may behave differently from another. The teardown reportedly found that the tight M0 trenches had a more difficult profile than the looser metal layers above them. That does not mean the chip is defective. It means the manufacturing cost is visible in the structure. SMIC successfully created the feature, but the feature carries evidence of how hard it was to create. This is the central paradox of DUV scaling. The machine itself is older. The process surrounding it becomes more complicated. The metal layer was only part of the story. SMIC also used several design and manufacturing techniques to reduce the area of the basic logic cells. The first was fin depopulation. The Kirin 9030 uses FinFET transistors. In a FinFET, current flows through vertical silicon fins surrounded by the gate. More fins can provide stronger electrical drive, but more fins also consume space. SMIC N+3 uses 2 NMOS fins and 2 PMOS fins in its measured logic cells. Reducing the fin count allows cells to become narrower, but it can also limit drive strength. It is similar to replacing a wide multi-lane tunnel with a narrower one. The tunnel occupies less land. It may not move the same amount of traffic. The second technique is contact over active gate. Normally, the electrical contact connected to a gate may sit beside the active region, consuming additional space. Place that contact directly over the active gate, and the cell becomes shorter. Simple in a diagram. Difficult in production. The contact must land accurately without damaging or interfering with the transistor below it. The third technique is the single diffusion break. Logic cells need isolation between neighboring transistor regions. Older layouts often used a wider double break. A single diffusion break saves space, but it increases sensitivity to local manufacturing variations. Again, density improves. Margin becomes smaller. None of these ideas is unique to SMIC. Major foundries use similar density-enhancing techniques. What stands out is how aggressively SMIC combined them in one process generation. This is where the story moves beyond lithography. A foundry cannot simply shrink every shape and ask chip designers to continue as before. At these dimensions, the manufacturing process and the circuit layout must be developed together. This is called design technology co-optimization. The factory tells designers which shapes can be produced reliably. Designers reorganize logic cells around those restrictions. The factory then adjusts the process to support the new layouts. The result is a feedback loop. Suppose a transistor loses one fin to save area. The circuit may now switch more slowly. Designers compensate by changing the cell, adjusting the signal path, or using a stronger cell elsewhere. Suppose a metal layer becomes tighter but gains resistance. Engineers may shorten important routes or move selected connections to a higher layer. The process is no longer simply about drawing smaller transistors. It becomes a puzzle involving density, power, performance, heat, and manufacturability. SMIC N+3 appears to be a product of that puzzle. Its density did not come from one enormous leap in lithography. It came from dozens of smaller compromises that reinforce one another. Huawei used the denser N+3 process to fit more capability into a chip with a die area similar to its predecessor. The Kirin 9030 reportedly adds another middle CPU core, expands several caches, and increases GPU and neural processing resources. Individual CPU cores also became smaller. The prime core shrank despite receiving a larger private cache. The middle cores became significantly more compact. GPU compute units became smaller, allowing Huawei to increase the number of units while keeping the full graphics section within a manageable area. That is what process scaling is supposed to accomplish. The goal is not merely creating a beautiful cross-section under a microscope. The goal is using less area for existing functions, then spending the saved area on more capability. Huawei appears to have done that successfully, but performance reveals the limitation. The Kirin 9030 improved significantly over the previous generation, especially in graphics. It still trails current flagship processors from the leading mobile chip companies. Its CPU architecture and manufacturing efficiency remain behind the newest designs. The chip can contain more hardware than its predecessor. It cannot operate that hardware with the same power efficiency as a processor manufactured on a leading 3nm class process. Density matters. The voltage and frequency curve matters more. A smaller structure does not automatically switch faster. Narrower metal wires have greater electrical resistance. Smaller transistors can suffer from leakage and variability. More patterning can introduce dimensional differences across the wafer. A process must balance density with the ability to operate at useful voltage and frequency. This is where SMIC's disadvantage becomes clear. The Kirin 9030 is a credible modern smartphone processor, but it is not equal to the latest Apple, Qualcomm, or MediaTek flagship chips. Its strongest CPU core reportedly performs more like an older high-end design. Its GPU made a major generational jump, yet remains far behind current top-tier alternatives. Efficiency is the greater challenge. A processor can reach competitive performance by consuming more power, but a smartphone has strict thermal limits. The device cannot use a large cooling system. The battery must last. The surface cannot become uncomfortably hot. That means performance per watt determines how much of the chip's theoretical capability can be used continuously. SMIC compressed the layout. It has not yet matched the manufacturing characteristics of the most advanced nodes. In M0 pitch inside these two shipping products, yes, the Kirin 9030's measured 32.5 nanometer pitch is tighter than Panther Lake's 36 nanometer implementation. Across the entire manufacturing process, no. Intel 18 amps uses gate-all-around ribbon FET transistors, rather than conventional FinFETs. It includes backside power delivery. It offers substantially greater normalized logic density, and it provides a more advanced platform for performance and efficiency. Even the narrow M0 victory needs context because Intel 18A supports a tighter 32 nanometer version that was not used in Panther Lake. So the correct interpretation is not that SMIC's 7 nanometer process is better than Intel 18A. It is that process node names hide enormous complexity. A company working with older lithography can produce one dimension that looks more advanced than a dimension inside a newer process. But it may need more steps, more masks, and more compromise to get there. The number is real. The meaning is conditional. The significance lies in what SMIC proved can still be extracted from DUV. Many observers assumed that without EUV, advanced logic manufacturing would quickly reach a hard wall. The Kirin 9030 suggests the wall is not perfectly vertical. It is more like a steep mountain. Progress remains possible, but every meter becomes harder than the last. SMIC has tightened local metals, reduced cell dimensions, and incorporated multiple density boosters. It has reached roughly TSM6 class logic density, while using a more complicated manufacturing route. That is not parity with the leading edge. It is evidence of continued movement, and commercial shipment matters. This is not a research wafer designed only to demonstrate one small test structure. The process is manufacturing a complete smartphone system on chip containing CPU cores, graphics, AI processing, memory controllers, image processing, and communication hardware. Every one of those blocks must work together. A laboratory can optimize one line. A consumer processor must survive millions of interacting lines. That makes the result harder to dismiss. SMIC may still have additional scaling options. Cell height could be reduced again. Some local metal layers could be pushed into even more aggressive patterning. Gate pitch may shrink slightly. Future designs could use backside contacts or advanced three-dimensional stacking. But each option becomes more difficult. If another routing layer requires quadruple patterning, mask count rises again. If cells become shorter, designers lose wiring tracks. If contacts move to the backside, manufacturing requires wafer thinning, backside alignment, and new integration steps. None of these is impossible. Together, they become unforgiving. The danger is not that one individual step cannot work. The danger is that the combined process becomes too expensive, too slow, or too sensitive to variation. A foundry does not win by producing the world's most impressive cross-section. It wins by producing large numbers of functional chips at a competitive cost. That is why EUV remains so valuable. It does not perform magic. It reduces the number of tricks required. If shrinking the chip in 2 dimensions becomes increasingly expensive, the next option is to build upward. Huawei has discussed an approach called logic folding, which would divide parts of a logic block across multiple active silicon layers. Instead of placing every transistor beside the others on one flat surface, some functions could sit above or below their neighbors. Short vertical connections could replace longer horizontal wires. This could improve density per package area and reduce the time required for signals to travel across large blocks. The approach has its own difficulties. Stacked active logic creates heat. Bonding must be extremely precise. Testing becomes more complicated. The density comparison also changes because adding another layer increases transistors per package footprint without improving the transistor process itself. Still, the direction is logical. When the map cannot become much smaller, fold the map. SMIC N+3 may therefore represent both progress and a warning. It demonstrates how far planar DUV scaling can be pushed. It also demonstrates why the industry is looking beyond planar scaling. My view is that the 32.5 nanometer result is more interesting than the phrase "China beat Intel" suggests. A simple victory would almost be less revealing. SMIC did not create a universally superior process. It created an unusually aggressive one. The company used quadruple patterning, tighter local wiring, and several layout optimizations to achieve a dimension that looks extraordinary beside Intel's shipping configuration. But Intel's wider M0 layer exists partly because PowerVia removed power congestion from the front side. Intel could afford not to squeeze that layer as hard. One company compressed the road because space was scarce. The other redesigned the city so the road did not need to carry everything. Both are engineering achievements. The difference is cost and headroom. SMIC's approach demonstrates ingenuity, but each additional shrink will demand more complexity. Intel's architecture gives it more room for future optimization. So no, the Kirin 9030 does not prove that China has overtaken Intel. It proves something narrower, and still significant. A 7nm class chip, manufactured without EUV, can contain one local wiring layer tighter than the configuration used inside a commercial Intel 18A processor. That should not be exaggerated. It should not be ignored either, because technological progress does not always arrive as a clean leap from one machine generation to another. Sometimes it comes from taking an old tool, surrounding it with new processes, and forcing it to perform one more task that looked unreasonable. The final product may cost more. It may consume more power. It may remain behind the leader overall, but it works. And once something works in a commercial chip, the question changes. It is no longer, can this be done? It becomes, how far can they push it next? So what do you think? Is SMIC's 32.5 nanometer metal pitch evidence that DUV lithography still has meaningful life left? Or does the added cost and complexity prove that this approach is approaching its practical limit? Let me know your position in the comments. And if you want more grounded breakdowns of the machines, materials, and hidden engineering choices shaping the semiconductor industry, subscribe to Eastern Engine, because sometimes the most important part of a processor is not the feature advertised on the box. It is the wire buried at the very bottom of the chip. For more than a century, copper has quietly powered the modern world. Every major electrical grid, every data center, every factory, and nearly every computer has relied on copper to move electricity and information from one place to another. It became so essential that most people never stopped to question it. Copper was simply the material everything depended on. But today, something unexpected is happening. As artificial intelligence grows at an incredible pace, the technology that carried us into the digital age is beginning to show its limits. AI systems are becoming so powerful that moving data between thousands of processors has become almost as difficult as performing the calculations themselves. In many of the world's largest AI data centers, chips spend valuable time waiting for information instead of processing it. The processors are getting faster every year, but the connections between them are struggling to keep up. That has created one of the biggest engineering challenges of the AI era. Now, researchers and technology companies around the world are racing to solve it, and one country has been making an unusually large number of breakthroughs in exactly this area: China. Over the past few years, Chinese researchers have announced advances in optical networking, air-filled fiber, glass-based communication systems, photonic chips, and ultra-high-speed data transmission. While each announcement may seem unrelated on its own, together they point towards something much larger. Instead of asking how to make copper better, they're asking a completely different question. What if the future doesn't need copper at all? It sounds almost impossible. Copper has been one of civilization's most important industrial materials for generations. From power plants to smartphones, from electric vehicles to internet cables, it exists almost everywhere. Replacing it would require rethinking some of the most important technologies on Earth. Yet AI may be forcing exactly that transformation. The reason is surprisingly simple. Artificial intelligence doesn't just need faster processors. It needs those processors to communicate with each other almost instantly. Imagine trying to have a conversation with 10,000 people at the same time. Even if everyone could think incredibly fast, the discussion would still slow down if messages couldn't move quickly between them. The same thing happens inside AI supercomputers. Modern systems may contain thousands or even tens of thousands of advanced processors, working together as one enormous machine. Every second, those processors exchange enormous amounts of information. If the communication network can't keep up, the entire system becomes less efficient. For years, engineers have improved copper cables by making them faster, reducing electrical interference, and designing increasingly advanced connection technologies. But every improvement also introduces new challenges. Electrical signals generate heat. Higher speeds consume more power. Longer distances weaken the signal, requiring additional equipment to restore it before the information can continue traveling. As AI systems become larger, these problems grow exponentially. That's why many engineers now believe the next revolution won't come from faster processors alone. It will come from changing the way data moves. Instead of relying entirely on electricity flowing through copper, future systems may increasingly send information as pulses of light. Unlike electrical signals, light can travel enormous distances with extremely low loss. Optical communication also produces less heat and can carry significantly more information at the same time. For decades, fiber optic cables have already connected cities and continents using light instead of electricity. Now, researchers want to bring that same concept inside AI computers themselves. Rather than connecting processors with copper traces and electrical cables, future AI systems could increasingly use optical connections that move information using photons instead of electrons. That idea has become one of the hottest areas of research in modern computing. And this is where China's recent announcements begin to make more sense. Over the past several years, Chinese universities, telecommunications companies, and semiconductor researchers have repeatedly demonstrated new technologies involving optical communication. Some projects focused on photonic processors, others explored glass-based chips, some demonstrated record-breaking fiber transmission speeds, while others introduced entirely new networking techniques designed specifically for artificial intelligence workloads. Recently, Chinese researchers also reported transmitting data through air-filled optical fiber at extremely high speeds across long distances without traditional repeaters. While the technical details differ from project to project, the underlying direction remains remarkably consistent. Move more information, use less energy, reduce heat, eliminate bottlenecks. If these technologies continue improving, they could reshape far more than just data centers. Modern AI already influences healthcare, autonomous vehicles, robotics, scientific research, financial systems, manufacturing, logistics, and national infrastructure. Every improvement in computing efficiency has ripple effects throughout the global economy. That's why replacing even part of today's copper infrastructure would represent much more than an engineering milestone. It would represent a fundamental shift in how computers are built. Of course, this doesn't mean copper is about to disappear tomorrow. It remains one of the most reliable, affordable, and widely used industrial materials on Earth. Millions of miles of electrical wiring cannot simply be replaced overnight, But history shows that foundational technologies often remain dominant until a new generation quietly becomes good enough to solve problems the old one never could. Steam eventually gave way to electricity. Vacuum tubes gave way to transistors. Hard drives began sharing space with flash memory. And now, some engineers believe another transition may already be starting, not because copper suddenly became bad, but because artificial intelligence has created demands that copper was never originally designed to meet. If that's true, then what we're witnessing isn't simply another chip breakthrough. It may be the beginning of one of the biggest infrastructure changes the computing industry has seen in decades. And if China succeeds in leading that transition, the consequences could extend far beyond faster computers. To understand why so many researchers are looking beyond copper, it's important to understand just how dramatically artificial intelligence has changed the demands placed on modern computing. Only a few years ago, the world's largest data centers were designed primarily for cloud storage, video streaming, web applications, and online services. Those workloads certainly required fast hardware, but they were relatively predictable. Servers processed requests, sent responses, and repeated the cycle millions of times every day. Artificial intelligence changed the rules. Training a modern AI model requires thousands of processors working together as a single machine. Each processor constantly exchanges enormous amounts of information with every other processor in the system. Instead of sending occasional bursts of data, these networks operate almost continuously, moving information back and forth at incredible speeds. The challenge isn't performing the calculations anymore. The challenge is delivering the data fast enough. Imagine building the world's fastest sports car, but forcing it to drive through city traffic every day. No matter how powerful the engine becomes, the traffic limits its performance. That's essentially what's happening inside many AI clusters today. Modern processors can complete calculations at astonishing speeds, but if they have to wait for data to arrive, expensive computing power sits idle. Even a tiny delay becomes significant when multiplied across thousands of processors working simultaneously. Engineers often describe this as a communication bottleneck. It's one of the biggest reasons why building larger AI systems becomes increasingly expensive. Adding more processors doesn't automatically produce proportional performance gains. As systems grow, communication between processors becomes more complicated. More hardware means more cables. More cables mean more electrical interference. Higher data rates generate additional heat. More heat requires larger cooling systems, increasing electricity consumption and operating costs. Eventually, engineers reach a point where improving processors alone no longer delivers the expected performance. The network itself becomes the limiting factor. That's why some of the world's biggest technology companies are investing enormous resources into solving data movement instead of focusing exclusively on processing power. This is exactly where optical communication begins to stand out. Unlike traditional copper connections that transmit electrical signals, optical systems use pulses of light traveling through glass fibers or specialized photonic pathways. Light offers several important advantages. First, it can carry significantly larger amounts of information over long distances with minimal signal loss. Second, optical communication produces far less electrical interference than copper, making it easier to maintain signal quality as bandwidth increases. Third, because light doesn't generate electrical resistance in the same way as copper conductors, many optical systems can improve energy efficiency, especially when moving vast amounts of information between computing clusters. These advantages become increasingly valuable as AI infrastructure continues expanding. This helps explain why recent announcements from China have attracted so much attention. Rather than focusing only on designing faster processors, Chinese researchers have repeatedly introduced technologies aimed at improving the movement of information itself. Some projects explored advanced photonic chips capable of handling optical signals directly. Others focused on ultra-low-loss optical fibers capable of transmitting enormous amounts of information across impressive distances. Several research groups demonstrated new forms of integrated optical networking designed specifically for artificial intelligence workloads. Although these projects differ technically, they all pursue the same objective: remove communication bottlenecks before they become the biggest obstacle to AI progress. One particularly interesting direction involves bringing optical communication much closer to the processors themselves. Today, optical fibers already connect buildings, cities, and even continents. Inside computers, however, electrical copper traces still perform much of the communication between processors, memory, and networking hardware. Future systems may increasingly blur that distinction. Instead of converting information back and forth between electrical and optical signals multiple times, researchers hope to move light much deeper into computing systems. Some long-term visions even imagine optical communication operating directly between processors inside advanced AI servers. While that future remains under active development, progress is accelerating remarkably quickly. China has invested heavily in photonics research, semiconductor manufacturing, telecommunications infrastructure, and artificial intelligence over the past decade. These investments have created an ecosystem where universities, state laboratories, technology companies, and manufacturing firms often work on complementary parts of the same technological challenge. One team develops better optical materials, another improves photonic chips, another designs networking equipment, another optimizes AI software capable of taking advantage of faster communication. Together, these advances create momentum that individual breakthroughs alone cannot fully explain. This also helps explain why so many recent headlines appear connected. Glass AI chips, photonic processors, air-filled fiber, optical networking, high-speed AI interconnects. They aren't isolated inventions competing against one another. They're different pieces of a much larger puzzle. If enough of those pieces come together successfully, future AI systems could look fundamentally different from today's architectures. Instead of relying primarily on electrical pathways built around copper, much of the communication layer could gradually shift toward optical technologies. That doesn't necessarily eliminate copper completely. Power delivery will still require traditional electrical conductors. Many electronic components will continue depending on conventional circuit designs for years to come. But the role of copper in moving enormous quantities of digital information may begin changing. And that possibility has significant implications beyond engineering. Data centers consume enormous amounts of electricity. Artificial intelligence is increasing that demand every year. If faster optical communication allows AI systems to perform more work using less energy, the economic impact could be substantial. Lower operating costs, reduced cooling requirements, higher computing efficiency, better scalability. Those improvements matter not only for technology companies, but also for governments, research institutions, healthcare providers, manufacturers, financial firms, and virtually every industry beginning to adopt artificial intelligence. That's why replacing even part of today's copper infrastructure isn't simply about building faster computers. It's about enabling the next generation of AI itself. And if China's current pace of innovation continues, the country could play a major role in defining what that future looks like. The most interesting part of this story isn't that China is researching optical communication. It's that the entire technology industry is slowly reaching the same conclusion. For decades, progress in computing followed a familiar pattern. Engineers built faster processors, added more memory, improved manufacturing techniques, and shrank transistors. Each new generation delivered more performance without dramatically changing the overall architecture of computers. Artificial intelligence has disrupted that pattern. Today, simply building a faster processor is no longer enough. The real challenge is making thousands of processors behave like one giant computer. That sounds simple in theory, but it's incredibly difficult in practice. Imagine an orchestra with 10,000 musicians. Even if every musician is exceptionally talented, the performance falls apart if they can't hear the conductor or stay synchronized with one another. Timing becomes just as important as individual skill. Large AI clusters operate in much the same way. Every processor performs calculations independently, but they must constantly exchange information with the rest of the system. If synchronization slows down, overall performance drops dramatically. That's why engineers increasingly describe AI infrastructure as a communication problem rather than a computing problem. This shift is changing the priorities of the semiconductor industry. Instead of asking which company builds the fastest processor, engineers are asking a different question. Which company builds the fastest system? That's an important distinction. A complete AI system isn't just made of processors. It includes networking hardware, memory, storage, power delivery, cooling systems, advanced packaging, software, scheduling algorithms, optical communication, and increasingly, every one of those pieces must be optimized together. China appears to understand this very well. Rather than focusing exclusively on one breakthrough technology, Chinese companies and research institutions have spent years developing multiple pieces of the same ecosystem. We've already seen reports involving domestic AI accelerators designed to reduce dependence on imported hardware. We've covered memory manufacturers expanding production to challenge long-established industry leaders. There have been breakthroughs involving glass substrates capable of improving chip packaging. Chinese researchers demonstrated photonic processors that move information using light. There were advances in air-filled optical fiber capable of carrying astonishing amounts of data. And more recently, developments in AI networking technologies designed to reduce communication delays inside massive computing clusters. Individually, each story attracted attention. Together, they tell a much larger story. They're all solving different parts of the same challenge, building the infrastructure required for the next generation of artificial intelligence. That's also why many analysts believe the future AI race won't be won by whichever company builds the single fastest chip. Instead, it may be won by whoever integrates every component most efficiently. This is already becoming visible inside modern hyperscale data centers. Companies no longer purchase processors in isolation. They invest in complete platforms. Networking equipment must match processor performance. Memory bandwidth must keep pace with both. Storage systems must deliver information without delay. Power systems must support enormous energy demands. Cooling infrastructure must remove incredible amounts of heat. Software must coordinate every component with near-perfect efficiency. If even one layer falls behind, the entire system slows down. This systems-level thinking explains why optical communication has become so important. Replacing portions of copper infrastructure isn't only about transmitting data faster. It's about allowing every other component inside the AI ecosystem to perform closer to its full potential. Imagine spending hundreds of millions of dollars building one of the world's largest AI clusters, only to discover that processors spend a significant portion of their time waiting for information. That idle time represents lost performance, wasted electricity, and lower returns on enormous investments. Now imagine reducing those delays across tens of thousands of processors. Suddenly, the same hardware accomplishes more work. Training finishes sooner. Inference becomes more responsive. Operating costs decline. Energy efficiency improves. These benefits extend far beyond technology companies. Healthcare researchers could analyze larger medical datasets. Climate scientists could run more detailed simulations. Manufacturers could optimize production lines using increasingly sophisticated AI systems. Financial institutions could process larger volumes of information in real time. Autonomous vehicles could improve decision-making through more powerful training infrastructure. The ripple effects become enormous. This is one reason governments have begun treating artificial intelligence as strategic infrastructure rather than simply another software industry. Countries are investing not only in AI models, but also in the factories, supply chains, communication systems, and semiconductor technologies required to sustain long-term progress. China has been particularly active in this approach. Its investments span semiconductor manufacturing, optical communications, telecommunications equipment, artificial intelligence research, advanced materials, and industrial automation. Whether every individual project succeeds remains uncertain. Research always involves setbacks. Not every breakthrough reaches commercial production. Some technologies require years before becoming economically practical. Others may never leave the laboratory, but the overall direction is becoming increasingly clear. The industry is preparing for an era where moving information becomes just as important as processing it. And that's exactly where optical technologies could reshape the landscape. Instead of forcing electrical signals through increasingly complex copper pathways, future AI systems may rely more heavily on photons carrying enormous amounts of information with lower energy consumption and reduced heat generation. That transition won't happen overnight. Data centers represent trillions of dollars in existing infrastructure. Copper remains affordable, reliable, and deeply integrated into modern electronics. Replacing every cable, connector, and circuit would take many years. But technological transitions rarely happen all at once. They begin in specialized applications, where the advantages are greatest. Then costs fall, manufacturing improves, adoption spreads. We've seen this pattern before with solid-state storage, cloud computing, smartphones, and electric vehicles. Optical communication inside AI infrastructure may follow a remarkably similar path. If that happens, today's research announcements may eventually be remembered as the first signs of one of computing's biggest architectural changes since the arrival of the internet itself. So, does this really mean copper is finished? Not even close. Despite the excitement surrounding photonic communication and optical networking, copper remains one of the most important engineering materials ever discovered. It's inexpensive, durable, highly conductive, and supported by more than a century of manufacturing experience. Nearly every power grid, industrial machine, consumer electronic device, and data center still depends on it in some way. The future isn't likely to be a world without copper. It's far more likely to be a world where copper and optical technologies each handle the jobs they perform best. Electricity will continue flowing through copper, but information may increasingly travel through light. That distinction is becoming more important every year. Inside tomorrow's AI data centers, electrical power still needs to reach processors, memory modules, storage devices, cooling systems, and networking equipment. Copper remains exceptionally well suited for delivering power efficiently. The challenge isn't electricity. The challenge is information. Artificial intelligence has created computing systems that move unimaginable amounts of data every second. Every new generation of larger AI models increases that demand even further. Some experts already compare modern AI infrastructure to building highways. When traffic was relatively light, ordinary roads worked perfectly. As cities grew, those roads became congested. Eventually, engineers built multi-lane highways, bridges, tunnels, and entirely new transportation systems. Artificial intelligence is experiencing a remarkably similar transition. The processors themselves continue improving, but the highways carrying information between those processors must improve as well. That's why networking companies have become some of the most important players in the AI industry. It's also why semiconductor companies increasingly discuss entire computing platforms instead of individual chips. The future belongs to complete systems. Systems where processors, networking, memory, storage, cooling, software, and communication all work together with extraordinary efficiency. China appears determined to compete across every one of those layers. We've already seen domestic progress in memory manufacturing, advanced packaging, optical communication, AI accelerators, photonic research, glass-based technologies, ultra-fast networking. Each announcement may appear independent, but together they reveal a much broader strategy. Rather than relying on isolated breakthroughs, China is steadily building an entire ecosystem capable of supporting increasingly advanced artificial intelligence. Whether that ecosystem ultimately becomes the world's most powerful remains impossible to predict. Technology evolves rapidly. Companies in the United States, Europe, Japan, South Korea, and Taiwan continue making remarkable advances of their own. Competition remains intense, and many of today's experimental technologies still require years of engineering before reaching widespread commercial deployment. That's why it's important to separate exciting research from immediate reality. Not every laboratory breakthrough transforms the market overnight. Engineering challenges remain. Manufacturing must scale. Costs must fall. Software must adapt. Industry standards must evolve. Customers must be willing to invest. Those transitions take time. But history shows something equally important. Major technological revolutions often begin quietly. Few people recognize the importance of the first semiconductor. Very few imagined smartphones would replace cameras, music players, GPS devices, maps, calculators, and personal computers for billions of people. Cloud computing seemed unnecessary to many businesses before becoming essential. Artificial intelligence followed a similar path. For years, it remained largely inside research laboratories. Then, suddenly, it became part of everyday life. Optical communication inside AI infrastructure could follow that same pattern. At first, only the largest research centers and hyperscale cloud providers may deploy these technologies. Over time, manufacturing improves, costs decline, reliability increases. Eventually, techniques that once seemed futuristic become ordinary engineering. If that happens, future generations may look back at today's developments the same way we now look at the early internet. Not as isolated inventions, but as the beginning of an entirely new technological foundation. Perhaps that's the most fascinating part of this story. This isn't really about copper, it's about how artificial intelligence is forcing humanity to rethink decades of engineering assumptions. For over 100 years, moving electricity and moving information often relied on many of the same materials. AI is changing that. Instead of asking how to build slightly better cables, engineers are asking whether information should travel in an entirely different way. That's an enormous shift in thinking, and if countries like China continue advancing optical networking, photonic communication, and next-generation AI infrastructure, the competition may no longer revolve around building faster processors alone. It may revolve around building smarter systems that waste less energy, generate less heat, move more information, and allow artificial intelligence to scale far beyond today's limitations. Whether that future arrives in 5 years or 15, one thing already seems clear. The race is no longer only about chips, it's about everything connecting those chips together. Because in tomorrow's AI world, the fastest processor won't necessarily win. the processor that waits the least will, and if light eventually replaces copper for many of those critical connections, we may be witnessing one of the biggest infrastructure transitions in modern computing history. The age of artificial intelligence isn't simply creating faster computers, it's creating entirely new ways for computers to communicate, and that could change everything. If you enjoyed today's video, don't forget to like, subscribe, and turn on notifications. Every day we break down the biggest technology breakthroughs shaping China's future, from AI, semiconductors, photonics, robotics, energy, and advanced manufacturing to the innovations that could redefine industries around the world. Let us know in the comments, do you think optical communication will eventually replace copper inside AI systems, or will copper remain the backbone of computing for decades to come? Thanks for watching, and we'll see you in the next video. It is the largest power station ever built, a wall of concrete stretching more than 2 kilometers across the Yangtze River, holding back a reservoir that runs for hundreds of kilometers behind it. It can generate more electricity than any other single structure on Earth, and its construction required relocating well over 1 million people. The Three Gorges Dam is, by almost any measure, one of the most ambitious engineering projects in human history. But for years, it has also been the subject of persistent questions about the quality of its construction, about its effect on the region's environment, about sediment piling up behind it, and about whether the enormous benefits it provides come with risks that have never been fully accounted for. Critics have even given it a nickname that is stuck, a tofu dread project, a Chinese phrase used for construction work that looks solid on the surface but is allegedly poorly built underneath. So how much of this is genuine concern, and how much is exaggeration? Today we are going to walk through the real debate around the Three Gorges Dam, the documented concerns, the official responses, what has been verified, and what hasn't. Because the truth here is more complicated and more interesting than either side usually admits. Let's start with the scale of what we're actually talking about. The Three Gorges Dam sits on the Yangtze, China's longest river and one of the largest in the world. Construction officially began in 1994, and the project came online in stages over the following years, with full power generation reached around 2012. The total cost is generally estimated in the range of tens of billions of dollars, with figures around the 28 to 32 billion mark commonly cited. The dam was built with 3 primary goals. The first was flood control. The Yangtze has a long and devastating history of flooding, with major floods in the 20th century alone killing enormous numbers of people. The dam's reservoir was designed to absorb floodwaters and release them in a controlled way, protecting cities downstream. The second goal was power generation. The dam's turbines produce a massive amount of clean electricity, displacing what would otherwise be generated by burning coal. And the third was improved navigation, allowing larger ships to travel further up the river through a system of locks. On those headline goals, the dam has delivered real results. It generates an enormous quantity of carbon-free electricity every year, and it has been credited with moderating several flood events on the Yangtze. These are genuine achievements that any fair assessment has to acknowledge. But the scale that makes the dam impressive is also exactly what makes its critics nervous. When a structure is this large and holds back this much water, the consequences of anything going wrong are correspondingly enormous. And that is where the controversy begins. The most attention-grabbing criticism of the dam concerns the quality of its concrete. During construction, the project poured concrete at a record-setting pace. In one peak year around 2000, the volume of concrete placed was several times what the famous Hoover Dam required across its entire construction. Pouring concrete that fast creates a genuine engineering challenge, because as concrete cures it generates heat, and if that heat isn't managed carefully, the material can develop internal stresses, cracks, or voids as it expands and contracts. The Hoover Dam famously solved this problem by mixing its concrete with chilled water and running cooling pipes through the structure to control the temperature as it set. Critics of the Three Gorges project have alleged that, in the rush to set records and meet deadlines, similar temperature control measures were not applied as rigorously as they should have been, and that this led to cracking and voids in parts of the structure. These concerns are not purely the invention of outside critics. Some of the people involved in the project's own quality inspection process raised flags during construction. There are documented references to inspection teams finding surface defects, cracks, and seepage in certain areas, particularly around the ship lock system, where teams reportedly found voids in the concrete during the early 2000s. Internal correspondence from quality reviewers described the overall quality at the time using cautious, hedged language rather than glowing approval. Here's the crucial context that often gets left out, though. According to the same engineering records, those defects were identified and then remediated. Reports document that water-seeping cracks in the lock system, totaling thousands of meters in length across hundreds of instances based on mid-2000s surveys, were subsequently repaired to meet design requirements. In other words, the concerns were real, but they were also addressed through ongoing maintenance and repair, which is, to be fair, a normal part of operating any massive piece of infrastructure. So the honest picture is this. There were genuine quality concerns during construction, some raised by insiders, and there has been ongoing repair work since. Whether that represents a structure that is fundamentally sound but high maintenance, or one with deeper problems, is the heart of the dispute, and reasonable engineers have landed on different sides of it. In July 2019, a story exploded across the internet. Someone posted satellite images appearing to show the dam visibly warping and bending out of shape, sparking a wave of panic that the structure was deforming and at risk of failure. This is worth examining closely, because it became one of the most widely shared claims about the dam, and it turned out to be misleading. The apparent warping in those images was not real structural deformation. It was an artifact of how certain satellite mapping services process images, automatically stretching and distorting flat imagery to drape it over three-dimensional terrain models. When you look at a long, straight structure laid over uneven terrain in those systems, it can appear to curve even when it is perfectly straight in reality. Other satellite images of the same dam, processed differently, showed no such bending. Chinese authorities responded by stating the dam was operating normally and within its safety parameters, and independent observers who examined the imagery agreed that the viral deformation was an image processing illusion rather than evidence of a failing structure. This episode is important for two reasons. First, it shows how quickly alarming claims about the dam can spread regardless of whether they hold up. And second, it's a useful reminder to treat dramatic claims in either direction with some caution. The dam has genuine, documented issues worth discussing. The 2019 It's Bending panic was not one of them. Beyond the structure itself, some of the most substantial debate concerns the dam's effect on the surrounding environment. And here, the science is genuinely complex and still debated. One area of concern is local climate. After the reservoir filled, the surface area of standing water in the region expanded enormously, by some estimates more than doubling. Some researchers, including geologists who have studied the area, have argued that this large new body of water altered local weather patterns, contributing to increased evaporation, shifts in temperature, and changes in rainfall in parts of the surrounding region. They point to a series of extreme weather events in nearby provinces in the years after the reservoir filled, including severe flooding in areas that had historically been prone to drought. A NASA-affiliated study using satellite data did examine the reservoir's potential influence on regional precipitation and surface temperatures, and found measurable effects on rainfall in certain areas near the reservoir. However, it's important to be precise here. Attributing specific weather disasters to the dam is scientifically difficult. The same years saw broader climate variability across China and the wider world, and separating the dam's local influence from larger regional and global climate trends is genuinely hard. So while the idea that a reservoir of this size affects its immediate microclimate is plausible and supported by some research, sweeping claims that the dam caused every flood or heat wave in the broader region go well beyond what the evidence can support. Other documented environmental concerns are more clear-cut. Sediment management is a real and ongoing engineering challenge. The Yangtze carries a heavy load of silt, and dams interrupt that natural flow, causing sediment to build up in the reservoir over time. Water quality changes in slow-moving reservoir water are a recognized issue, and there are well-studied concerns about reservoir-induced geological activity, where the immense weight of stored water and fluctuating water levels can increase the frequency of small landslides and seismic events near large reservoirs. These are not unique to the Three Gorges Dam. They are known challenges for major dams worldwide, but the sheer scale here amplifies them. One of the more thought-provoking concerns raised by critics involves not the Three Gorges Dam alone, but the entire system of dams now operating on the Upper Yangtze and its tributaries. Over the years, China has built a series of additional large hydropower stations upstream on the Jinsha River, which feeds into the Yangtze. On one level, this makes engineering sense. Upstream dams can hold back floodwater and trap sediment before it reaches the Three Gorges Reservoir, easing pressure on the main dam. But critics point out a less comfortable implication. Stringing many massive dams along the same river system creates a chain. The concern is that if any single dam in that chain were to fail catastrophically, the sudden release of its stored water could threaten the dams downstream of it in a cascading sequence. It's a low probability but high consequence scenario, and it's the kind of systemic risk that's genuinely worth engineers thinking carefully about. not because failure is likely, but because the stakes are so high. It's worth stressing that this is a hypothetical risk, not a prediction. Modern dams are built with significant safety margins, and a cascading failure would require an extraordinary chain of events. But the more dams you build on one system, the more the individual structures become interdependent, and that interdependence is a legitimate subject for ongoing safety analysis. Part of what fuels skepticism about the dam is the series of expensive follow-on projects that have been built around it over the years. Projects that critics argue exist partly to manage problems the dam itself created. One example is the bypass system for shipping. Because traffic through the dam's locks can back up significantly, with ships sometimes waiting days to pass, authorities built an over-dam transport route. Goods are unloaded from ships on one side, trucked overland along a dedicated highway, and reloaded onto ships on the other side, bypassing the lock bottleneck. The highway portion alone reportedly cost hundreds of millions of dollars, and that's before adding the upstream and downstream port facilities. Another major project is a large water diversion tunnel, begun in 2022, designed to carry water from the Three Gorges Reservoir area through a nearly 200-kilometer tunnel to the Han River. Officially, this is framed as a follow-up to China's broader water diversion programs, aimed at maintaining water levels downstream. But analysts have noted it also serves another function, giving the dam an additional channel to discharge water during flood conditions, helping relieve the difficult balancing act the dam operators face. When a major flood hits, releasing too much water risks flooding cities downstream, while holding too much back risks flooding cities upstream. An extra outlet gives operators more flexibility in that trade-off. Supporters would frame all of this as sensible infrastructure that maximizes the value of a major asset. Critics frame it as evidence that the original project created cascading problems requiring ever more expensive fixes. Both interpretations describe the same facts, which is often how these debates work. Underlying all of these specific concerns is a deeper debate that goes back to before the dam was ever built. During the project's planning and evaluation in the late 20th century, it was not universally supported, even within China's own expert community. The environmental impact assessment process was genuinely contentious. Some experts argued that the ecological and environmental downsides of the project were serious enough to warrant reconsidering whether it should proceed at all. And there were disagreements about how the official conclusions were ultimately framed. This internal debate is part of the historical record, and it reflects something true about megaprojects everywhere. Enormous infrastructure decisions involve real trade-offs, and reasonable experts can disagree about whether the benefits justify the costs. That tension has never fully gone away. Supporters point to the clean electricity, the flood control, and the navigation improvements as transformative benefits for a country of over 1 billion people. Critics point to the displaced communities, the environmental disruption, the sediment and water quality challenges, and the ongoing maintenance burden, and argue the full costs were understated from the beginning. The most honest assessment is probably that both things are true at once. The Three Gorges Dam is a genuine engineering achievement that delivers real, measurable benefits. It is also a project with real, documented downsides and ongoing challenges that its operators have to manage continuously. Whether the balance comes out positive or negative depends heavily on which costs and benefits you weigh most heavily, and that's ultimately a question of values as much as engineering. Let's come back to the question in the title. Is the Three Gorges Dam facing a new crisis? The responsible answer is, not in the dramatic, imminent collapse sense that sometimes circulates online. The dam has now operated for roughly 2 decades. It has weathered major floods. The viral claims about it physically bending were debunked. There is no credible evidence that the structure is on the verge of failure. What the dam does face is a set of ongoing chronic challenges that don't make for dramatic headlines, but are genuinely significant. Sediment accumulation that worsens over time, environmental effects on the surrounding region, the maintenance burden of a structure built at record-breaking speed, and the systemic questions raised by an entire chain of dams on one river system. These are real engineering and environmental issues that will require attention for as long as the dam exists. So rather than a single sudden crisis, the more accurate picture is a massive piece of infrastructure that delivers enormous benefits while carrying a long tail of complicated, slow-moving problems. Exactly the kind of trade-off that comes with building at this scale. What do you think? Do the flood control and clean energy benefits justify the environmental and engineering trade-offs? Or do you think projects on this scale create more problems than they solve? Let me know your honest take in the comments. This is one of those topics where thoughtful people genuinely land on different sides. And if you found this balanced breakdown useful, consider subscribing so you don't miss the next deep dive into the engineering megaprojects shaping our world. Alibaba has spent years building one of the largest cloud businesses in China, but now it is making a much bigger move. The company has unveiled a new artificial intelligence chip called the Renewable M890, a new networking processor, a new software stack, and a rack-scale system that places 128 AI accelerators inside a single unit. Alibaba calls that system the Pangeo AL128. And the important part is not simply that China has produced another AI chip. The important part is that Alibaba is trying to build the entire computing platform around it. The chip, the interconnect, the software, the cloud service, and the AI models are all being developed inside the same corporate ecosystem. That is the strategy that made NVIDIA so difficult to challenge. And it is now the strategy Alibaba is attempting to reproduce inside China. So has China just created a serious new NVIDIA rival? Or is Alibaba still years away from matching the hardware, software, and manufacturing scale NVIDIA already controls? To answer that, we need to look beyond the headline and examine what Alibaba has actually built. The chip at the center. The Renewable M890 was developed by T-Head, Alibaba's semiconductor design subsidiary. Alibaba says the processor delivers 3 times the performance of its previous Renewable 810E. That comparison is important. Alibaba did not claim that the M890 is 3 times faster than an NVIDIA H100, H200, or Blackwell processor. The 3 times figure refers only to Alibaba's own previous generation chip. The company has not published enough independently verified benchmark data to prove that the M890 can beat NVIDIA's leading products. But the specifications reveal what Alibaba is trying to optimize. The M890 includes 144 gigabytes of memory and supports precision formats ranging from FP32 down to FP4. Higher precision formats are useful when accuracy matters, while lower precision formats can make AI inference faster and cheaper. The processor also includes 800 gigabytes per second of inter-chip bandwidth. Those features target AI agents, systems that do more than answer one question. An agent may search databases, call software tools, coordinate with other agents, remember long sequences, and complete tasks that continue for hours. That creates heavy demands on memory and communication. A processor may be powerful on paper, but if it cannot move data quickly enough between chips, much of that computing power remains underused. This is why Alibaba is presenting the M890 as the foundation of a larger machine. The 128 chip server. The Pangeo Ali128 integrates 128 AI accelerators into one rack-scale system. Alibaba says the server can deliver internal bandwidth at the petabyte per second scale. That does not mean one chip performs at that level. It means the rack is designed to move enormous amounts of data between accelerators. This system-level approach has become essential because modern AI models have grown too large for one processor. Training and inference now depend on hundreds or thousands of chips working together. If the connection between chips is slow, processors sit idle while waiting for data. If communication is fast and predictable, the cluster becomes more efficient. Alibaba has therefore created a dedicated networking chip called ICN Switch 1.0. The company says it provides up to 25.6 terabits per second of aggregate bandwidth and supports full bandwidth connections across 64 accelerators. Alibaba also introduced a proprietary software platform called T-Head Sail, designed to extract performance from the hardware. Together, the M890, the networking chip, Sail, and the Pangeo server form an attempt to control the complete AI computing stack. Why the full stack matters. NVIDIA's dominance was never built only on transistor counts. Its strongest advantage is CUDA, the software ecosystem developers use to program NVIDIA graphics processors. Over many years, CUDA accumulated libraries, tools, training materials, optimized code, and a massive developer community. A company purchasing NVIDIA hardware is not simply purchasing chips. It is purchasing access to an ecosystem that already supports thousands of workloads. That creates high switching costs. Even if another company produces a competitive accelerator, customers may hesitate because their engineers, models, and software pipelines were built around CUDA. Alibaba understands this problem. That is why it is connecting its hardware directly to Alibaba Cloud, its Balium model platform, and its Qwen family of AI models. The company can design chips around workloads running inside its own cloud and optimize the software and models together. The goal is not necessarily to produce one standalone processor that defeats NVIDIA in every benchmark. The goal is to reduce dependence on NVIDIA by building a tightly integrated alternative for Alibaba's own cloud ecosystem. Why Alibaba needs its own chips? Alibaba has historically been a major buyer of NVIDIA processors. Like other Chinese technology companies, it preferred NVIDIA because the hardware was powerful, the software mature, and developers already knew how to use it. But that dependence became a strategic weakness as the United States expanded export restrictions on advanced AI hardware. A chip permitted 1 year could require a license the next. Products designed specifically for China could later become restricted. For a cloud provider building data centers that must operate for years, uncertainty itself becomes a cost. Alibaba cannot base its entire AI strategy on the assumption that every future NVIDIA generation will remain available. Domestic chips provide another option. Even if they are less powerful or efficient, they can offer a supply chain that is more predictable inside China. This does not mean Alibaba no longer wants NVIDIA products. Chinese technology companies have continued showing interest in NVIDIA hardware whenever access becomes possible. But Alibaba now has a strong incentive to ensure NVIDIA is no longer its only path to advanced computing. From experiment to real deployment. One reason the M890 deserves attention is that T-Head is no longer a small laboratory project. Alibaba says more than 560,000 Zhenwu processors have been shipped across all generations. More than 400 external customers in 20 industries have deployed them, including companies in automotive and financial services. Those figures are cumulative and should not be confused with shipments of the new M890 alone. Alibaba has not disclosed how many M890 processors it can manufacture or how quickly it can produce them. Still, the installed base shows T-Head has moved beyond prototypes. IDC data, reported for 2025, estimated that T-Head shipped around 265,000 AI accelerators in China, placing it behind Huawei, but ahead of several other domestic suppliers. That does not make Alibaba a global NVIDIA competitor, but it does make it one of China's most important domestic AI chip suppliers, with a cloud platform capable of consuming its own hardware at enormous scale. The Huawei question. Alibaba's most immediate competitor may not be NVIDIA. It may be Huawei. Huawei has become the leading Chinese supplier of domestic AI accelerators and has built its own Ascend hardware, networking systems, software tools, and large-scale clusters. But Alibaba has reasons to avoid complete dependence on Huawei. The two companies compete in cloud services, enterprise software, AI, and consumer technology. Alibaba's own chips allow it to control cost, product schedules, software integration, and cloud capacity. This could produce a new structure inside China. Huawei may lead the broader domestic accelerator market. Alibaba may optimize T-Head chips for Alibaba Cloud and Qwen. Baidu may continue developing Kunlun Xin. Instead of one Chinese replacement for NVIDIA, China may develop several competing ecosystems. That fragmentation creates software problems, but it may also accelerate innovation. The manufacturing problem. Designing a chip is only one part of the challenge. Manufacturing it at high volume is much harder. Alibaba has not publicly disclosed all important details about the M890's fabrication process, production yield, advanced packaging, or memory supply. These omissions matter. NVIDIA benefits from access to TSMC's leading manufacturing technology, advanced packaging capacity, and a global supply chain for high-bandwidth memory. Chinese chip designers operate under restrictions that limit access to some of the world's most advanced semiconductor equipment and services. A design may look impressive, but customers need thousands of reliable processors delivered on schedule. If Alibaba cannot produce enough M890 chips, the Panju architecture will remain limited. Low yields or high power consumption could make deployment expensive. This is the largest unanswered question. Alibaba has revealed the architecture. It has not revealed whether it can manufacture the platform at the scale required to challenge NVIDIA or Huawei. Performance without independent benchmarks. Another uncertainty is real-world performance. The headline numbers come from Alibaba. There are not yet enough independent tests comparing the M890 with NVIDIA, Huawei, AMD, or other accelerators across the same models and power limits. AI chip comparisons are complicated. A system may be fast for Alibaba's Qwen models but less efficient for workloads designed around CUDA. This is why the M890 should not be described as an NVIDIA killer. There is no evidence it has defeated NVIDIA's latest products across the board. The more accurate conclusion is that Alibaba has built a credible domestic platform that may be good enough for a growing range of Chinese workloads. In a restricted market, good enough can be extremely valuable. An available chip with stable local support may be more useful than a faster foreign chip customers cannot reliably purchase. The roadmap signal. Alibaba has also outlined a multi-year plan. The company says the M890 will be followed by the V900 in the third quarter of 2027 and the J900 in the third quarter of 2028. Roadmaps are promises, not completed products. But publishing a roadmap tells customers that T-Head is not intended as a temporary response to export controls. Alibaba wants enterprises to commit software, engineers, and infrastructure to a platform that will continue improving. The company has also committed more than 380 billion yuan, approximately $53 billion, to cloud and AI infrastructure over 3 years. The investment covers far more than chip design, but domestic silicon is clearly becoming part of Alibaba's long-term cloud strategy. What this means for NVIDIA. NVIDIA is still far ahead globally. It leads in accelerator performance, software, developer adoption, networking, and complete data center systems. Alibaba has not shown it can replace NVIDIA for every frontier training workload. But NVIDIA does not need to lose globally for this development to matter. China is one of the world's largest technology markets. Every workload moved to T-Head hardware reduces the number of future Chinese systems built entirely around CUDA. Every engineer trained on SAIL becomes less dependent on NVIDIA. Every Quen model optimized for Alibaba hardware makes the domestic platform more useful. This creates a feedback loop. More chips produce more users generate more software attracts more customers. That is the mechanism that helped NVIDIA build its dominance. The difference is that Alibaba's ecosystem is being accelerated by export controls, domestic policy, and the company's enormous cloud customer base. My take is that the Zhenwu M890 is important, but not because it has already beaten NVIDIA. It is important because Alibaba has crossed the line from designing individual chips to constructing a complete AI infrastructure platform. The Panju AL128 combines 128 accelerators, dedicated networking, proprietary software, cloud access, and models developed inside one ecosystem. That vertical integration gives Alibaba a path to improve the whole system, even when it cannot match NVIDIA chip for chip. There are still serious unknowns. We do not know the true manufacturing scale of the M890. We do not have enough independent performance data. We do not know whether developers outside Alibaba's ecosystem will embrace SAIL. And we do not know whether the 2027 and 2028 roadmap will remain on schedule. But the direction is clear. China's AI hardware market is no longer waiting for one national champion to replace NVIDIA. Huawei is expanding. Alibaba is building its own stack. Baidu and other suppliers are developing alternatives. Chinese models are being optimized for domestic infrastructure. The result may not be one chip that defeats NVIDIA. It may be an entire market that gradually learns how to operate without NVIDIA. That is the real threat. NVIDIA cannot easily reverse the political and commercial incentives pushing Chinese companies towards self-reliance. Alibaba's 128-chip server is therefore more than a piece of hardware. It is a signal that China's largest cloud companies are preparing for a future in which access to American chips can never be guaranteed. So what do you think? Can Alibaba turn the Zhenwu M890 and Panju AL128 into a genuine alternative to NVIDIA? Or will manufacturing limits and software compatibility keep China's domestic accelerators behind? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because NVIDIA still leads the global AI industry, but Alibaba is building a system designed to make that lead less important inside China. Apple has spent decades building one of the most controlled supply chains in the technology industry. It designs its own processors. It negotiates enormous component contracts. It forces suppliers to meet strict standards on performance, reliability, efficiency, and cost. And because Apple sells hundreds of millions of devices, even the possibility that it could approve a new supplier can reshape an entire industry. That is why Washington is now paying extremely close attention to a Chinese memory technologies, better known as CXMT. According to recent reports, Apple has been testing CXMT's DRAM chips for potential use in devices sold inside China. Apple has also reportedly approached the United States government seeking clearance to purchase memory from the company as global chip prices rise. But before Apple could make a final decision, lawmakers in Washington delivered a warning. They urged the Commerce Department not to allow American companies to buy memory chips from CXMT and called for stronger restrictions that could place the Chinese company behind an even higher regulatory wall. So Apple now finds itself trapped between two completely different pressures. On one side, it needs more memory suppliers to control costs and protect its production system. On the other, the United States increasingly views Chinese semiconductors not as ordinary commercial products, but as a national security issue. And behind the political fight is a much larger development. China's domestic memory industry is no longer small enough to ignore. CXMT has grown into the world's fourth largest DRAM producer, and its expansion could eventually threaten the market controlled by Samsung, SK Hynix, and America's Micron. This is not just a disagreement over one Apple supplier. It is a battle over who will control one of the most essential components inside modern technology. Every smartphone, laptop, gaming computer, and data center server needs memory. The processor performs calculations, but DRAM holds the information the processor needs immediately. Without enough fast memory, even an advanced CPU or GPU becomes limited by how quickly data can be delivered. That importance has grown dramatically during the artificial intelligence boom. AI servers consume enormous amounts of memory. Chip companies are directing more production toward high-bandwidth memory for NVIDIA accelerators because those products can generate higher profits than ordinary consumer DRAM. That shift has consequences throughout the market. When manufacturers dedicate more capacity to expensive AI components, supplies for traditional smartphones, computers, and consumer electronics can tighten. Prices rise, contracts become more difficult to negotiate, and companies like Apple lose some of the leverage they normally use against suppliers. Apple has traditionally sourced much of its memory from major companies in South Korea, Japan, and the United States, but Apple rarely wants to depend too heavily on one supplier. Its entire procurement strategy is built around competition. When several companies can produce the same component, Apple can divide orders between them, negotiate lower prices, and protect itself if one supplier experiences a factory problem. A new qualified supplier gives Apple another option, and right now, CXMT wants to become that option. CXMT is China's leading producer of DRAM, the temporary working memory used inside electronics. The company is still behind Samsung, SK Hynix, and Micron in the most advanced forms of memory, especially high-bandwidth memory used beside NVIDIA's AI processors. But CXMT does not need to defeat those companies in every category to become strategically important. It only needs to manufacture enough competitive mainstream DRAM to win contracts in smartphones, laptops, and conventional servers. That is where Apple becomes extremely valuable. Supplying memory for even part of Apple's Chinese product line would give CXMT more than revenue. It would provide validation. Apple's qualification process is famously demanding. A component has to perform consistently across huge production volumes, maintain reliability over time, and integrate smoothly with the rest of the device. If CXMT memory passed those tests, other electronics manufacturers would pay attention. The message would be simple. China's leading DRAM company is no longer producing chips only for protected domestic customers. It may be capable of entering the supply chains of the world's most valuable consumer electronics company. That possibility explains why this story has caused such a strong reaction in Washington. Two members of the House Select Committee on China, Republican John Molinar and Democrat George Whitesides, recently urged Commerce Secretary Howard Lutnick to prevent American purchases of memory chips from Chinese companies. Their request specifically focused on CXMT and Yangtze Memory Technologies, or YMTC. CXMT produces DRAM, YMTC produces NAND flash, the longer-term storage used in smartphones, solid-state drives, and other electronics. Together, the two companies represent China's attempt to challenge foreign dominance across both major categories of memory. The lawmakers argued that allowing American companies to rely on those chips could create national security, economic, and supply chain risks. They also called for CXMT to be added to the Commerce Department's entity list, and for existing restrictions on YMTC to be strengthened. It is important to understand what that means. CXMT has been designated by the Pentagon as a Chinese military company, but that designation does not automatically create a complete ban on American companies purchasing every product CXMT manufactures. The Commerce Department's entity list is different. Companies placed on that list face strict limitations on receiving American goods, software, and technology without government licenses. Washington has already used export controls to restrict China's access to advanced semiconductor equipment, AI processors, and chip design technology. Adding CXMT to the entity list would make it harder for the company to access foreign tools and expertise needed to improve its production. But the lawmakers want Washington to go further than simply limiting what CXMT can buy. They are concerned about what American companies may be allowed to buy from CXMT. That turns Apple's reported testing into a much larger strategic question. Should an American company be allowed to purchase a component from a Chinese semiconductor producer that Washington considers a potential security concern? Apple may look at the issue from a supply chain perspective. If CXMT can meet technical requirements and offer lower prices, it becomes another commercial supplier. Washington looks at the same transaction differently. Every major Apple contract could generate revenue that helps CXMT expand capacity, improve technology, and compete more aggressively against Micron and allied memory producers. From that perspective, Apple would not simply be buying RAM. It could be helping create a new global competitor in a market the United States considers strategically important. This is where the commercial and political interests begin to collide. Apple wants reliable components at competitive prices. American policymakers want to prevent China from dominating another critical technology sector. And Micron wants to protect its position as the only major American DRAM manufacturer. For decades, the memory industry has been controlled by a small group of companies because producing DRAM at scale is extremely difficult. Memory chips may look like simple commodities, but manufacturing them requires enormous factories, advanced lithography, precise process control, and years of experience managing microscopic defects. A tiny problem on the production line can destroy yields and turn a profitable chip into a loss. That barrier removed many competitors from the market. Today, Samsung, SK hynix, and Micron dominate global DRAM production. CXMT is trying to break into that structure. According to company disclosures reported by Reuters, CXMT held roughly 7.7% of the global DRAM market in 2025, making it the fourth largest producer. That share is still far behind the leaders, but its direction matters more than its current position. CXMT's revenue reportedly increased rapidly during the latest memory upcycle, and the company is preparing to raise billions of dollars through a major public offering in Shanghai. That money is expected to support new production capacity, technology upgrades, and research. China has seen this pattern succeed before. The country entered industries such as solar panels, batteries, and electric vehicles from a weaker technological position. Domestic companies received investment, built supply chains, expanded factories, and competed aggressively on cost. At first, established foreign producers dismissed them. Then Chinese manufacturing reached scale. Prices fell, exports increased, and foreign governments began introducing tariffs and restrictions after Chinese companies had already become major competitors. American lawmakers fear memory chips could follow the same path. The concern is not necessarily that CXMT already makes the world's most advanced DRAM. It does not. The concern is that CXMT could use massive domestic demand, state-linked financing, and access to China's electronics industry to improve faster than expected. Even if CXMT begins by competing mainly in ordinary consumer memory, that could pressure Samsung, SK hynix, and Micron. Lower-cost Chinese DRAM could reduce prices in the mainstream market. That sounds positive for buyers. Cheaper memory could lower production costs for smartphones, computers, and servers. Consumers might benefit from more affordable electronics or more RAM inside devices at the same price. But memory manufacturing requires continuous investment. If prices fall too far, established producers earn less money to fund their next generation of factories. That is why the memory industry moves through brutal cycles. Companies expand production when prices are high. Supply eventually catches up. Prices collapse. Manufacturers cut investment. Then shortages return and prices rise again. A heavily backed new competitor could make that cycle even more difficult. Micron faces the greatest political exposure because it is the only large American company producing DRAM at global scale. If Apple began buying significant volumes from CXMT, even only for products sold inside China, it could reduce potential demand for established suppliers. It could also encourage other American companies to request similar permission. Dell, HP, and other hardware brands constantly search for ways to reduce component costs. Once one major American company qualifies Chinese memory, pressure increases on competitors to consider the same option. Washington understands that supply chains become difficult to reverse once companies build products around a supplier. A small trial can become a limited contract. A limited contract can become a multi-year purchasing agreement. And a domestic Chinese supplier can eventually become part of a global product line. But Apple also has serious reasons to explore the relationship. China remains one of Apple's most important manufacturing and consumer markets. The company faces intense competition there from Huawei, Xiaomi, Oppo, and Vivo. Chinese smartphone manufacturers increasingly use domestic components, and Beijing continues encouraging technological self-reliance. Using CXMT memory inside devices sold in China could potentially help Apple lower costs and present itself as more connected to the local supply chain. It could also give Apple protection against global memory shortages. The AI boom has transformed the economics of the memory industry. Samsung, SK Hynix, and Micron are investing heavily in high-bandwidth memory because NVIDIA, AMD, and other AI chip companies need enormous quantities of it. HBM stacks several layers of memory close to an AI processor, allowing data to move much faster than it can through conventional memory systems. The technology is complicated, expensive, and extremely profitable. As suppliers focus more attention on HBM, ordinary DRAM buyers face stronger competition for manufacturing capacity. Apple does not use HBM in the same way an NVIDIA data center accelerator does, but Apple still purchases huge volumes of conventional memory for iPhones, iPads, and Macs. When memory prices rise, even a small increase per device becomes enormous across Apple's total shipments. That helps explain why the company reportedly approached Washington. Apple is not necessarily choosing China because CXMT has the best memory technology in the world. It may be trying to create another source of supply before costs increase further. But the political environment surrounding Chinese chips has changed dramatically. A decade ago, sourcing a lower-cost component from China would primarily have been a commercial decision. Today, nearly every advanced semiconductor transaction is examined through national security. Washington has restricted NVIDIA from selling its most powerful AI chips to China. It has limited exports of advanced manufacturing tools. It has pressured the Netherlands and Japan to align controls on semiconductor equipment. It has investigated Chinese telecommunications hardware and supported domestic chip factories through large government incentives. Now, memory chips are moving closer to the center of that conflict. Unlike cutting-edge AI processors, DRAM is not always seen as glamorous. It does not generate the same headlines as NVIDIA's newest GPU or Apple's latest processor. But memory is foundational. An AI accelerator cannot function effectively without it. A smartphone cannot multitask without it. A data center cannot operate without enormous amounts of it. Control memory, and you control a critical layer of the computing supply chain. That is why China has invested so much into CXMT. And that is why Washington may be unwilling to let Apple help it scale. The irony is that American export controls may have accelerated China's determination to build domestic alternatives. When Chinese companies believed they could continue buying foreign chips indefinitely, developing a complete domestic supply chain was less urgent. Once Washington began restricting access, self-reliance became a national priority. Chinese smartphone and computer manufacturers increased their use of domestic semiconductors. Local governments invested in factories. State-linked funds backed chip companies. Engineers searched for ways to produce advanced components without the newest American-controlled equipment. CXMT is one result of that pressure. The company still faces significant challenges. It remains behind global leaders in advanced HBM. Restrictions limit access to some cutting-edge manufacturing tools. Its products must prove that they can deliver consistent quality across millions of chips. Recent independent testing has also suggested that some CXMT consumer DDR5 chips do not yet match the consistency and overclocking performance of leading SK Hynix products. But Apple does not need record-breaking overclocking memory. It needs components that satisfy its own specifications reliably, efficiently, and at scale. That is why the testing matters. Testing does not mean Apple has signed a contract. It does not mean CXMT memory will definitely appear in the next iPhone or MacBook. And it does not mean Washington has approved the purchase. The process remains uncertain. Apple, CXMT, and the White House have not publicly confirmed the full details reported by the Financial Times and Reuters. But the fact that the discussion has reached Washington shows how far China's memory industry has progressed. A few years ago, CXMT was mainly discussed as a domestic Chinese project trying to survive export controls. Now lawmakers are reacting to the possibility that Apple may use its chips. That is a major change. The final decision could establish a precedent for the entire American technology industry. If Washington approves Apple's request, other companies may argue that they should also be allowed to buy Chinese memory for products manufactured or sold in China. That could provide CXMT with valuable customers, revenue, and international credibility. If Washington blocks the request and tightens restrictions, Apple will remain more dependent on Samsung, SK Hynix, Micron, and other approved suppliers. That could protect allied memory manufacturers but leave American technology companies exposed to higher prices and a smaller supplier base. Either decision has consequences. Allow Chinese memory, and Washington risks strengthening a strategic competitor. Block it, and American companies may pay more while China continues developing its semiconductor industry through domestic customers. There is also a bigger question. How long can the global technology industry maintain two separate supply chains? One centered on the United States and its allies, another centered on China. Apple represents the difficulty of separating them. It is an American company. Its processors are designed in the United States. Many are manufactured by Taiwan's TSMC. Its memory may come from South Korea, the United States, or Japan. Much of its final assembly still takes place in China, even as production expands elsewhere. Its products are then sold around the world. Modern electronics were built through integration. The semiconductor conflict is pushing the same industry towards separation. CXMT sits directly in the middle of that transition. For China, the company represents independence from foreign memory suppliers. For Micron, it represents a heavily supported new competitor. For Apple, it represents another possible source of affordable RAM. For Washington, it represents a strategic industry that could become much harder to contain if American companies help it reach global scale. That is why this story is bigger than Apple testing one memory chip. It reveals the contradiction at the heart of the technology war. The United States wants American companies to remain globally competitive. But global competitiveness often depends on accessing the largest, cheapest, and most flexible supply chains. At the same time, Washington wants to prevent strategic Chinese companies from gaining money, technology, and credibility from American customers. Apple wants more options. Washington wants more control, and CXMT wants the contract that could prove China's RAM industry has finally arrived. The decision has not been made. Apple has not announced that CXMT will supply its products. Washington has not introduced a complete new purchasing ban covering every Chinese memory chip. But the battle lines are now clear. The next phase of the semiconductor war may not be fought over the world's most advanced processor. It may be fought over the memory sitting beside it. And somewhere inside Apple's testing laboratories, a small Chinese DRAM chip may be forcing the world's most valuable technology company to choose between the supply chain it wants and the government restrictions it cannot ignore. Because this is no longer only about where Apple buys its RAM. It is about whether China's next semiconductor giant will be allowed into the American technology ecosystem or blocked before it becomes too powerful to stop. Silicon has been the foundation of the modern world for more than half a century. Every smartphone, every gaming PC, every AI server, every data center, every satellite, every electric vehicle, and nearly every advanced electronic system relies on one material more than any other. Silicon quietly became the invisible backbone of civilization. It powered the internet, fueled the smartphone revolution, and now drives the AI race that has reshaped the global economy. For decades, the assumption seemed impossible to challenge. If you wanted faster chips, you improved silicon. If you wanted smarter AI, you built more silicon. If you wanted more computing power, you invested billions into making silicon smaller, faster, and more efficient. But what if the entire industry has been chasing the wrong answer? Because while much of the world continues investing hundreds of billions of dollars into squeezing another few percentage points out of silicon, researchers in China have been quietly pursuing something far more ambitious. Instead of asking how to improve silicon, they asked a completely different question: what comes after it? That question has suddenly become one of the biggest discussions inside the semiconductor industry. Not because silicon is disappearing tomorrow, but because the physical limits that engineers have warned about for years are becoming increasingly difficult to ignore. As transistors shrink toward atomic dimensions, every new manufacturing generation becomes exponentially more expensive, more complicated, and more difficult to produce. The roadmap that carried computing for decades is beginning to slow down. And whenever one era starts slowing, another usually begins. Across China, universities, research institutes, advanced laboratories, photonics companies, material scientists, and semiconductor manufacturers are all exploring technologies that could fundamentally change how information moves through computers. Some projects focus on light instead of electricity. Others replace traditional semiconductor materials with entirely different compounds. Some abandon conventional transistor designs altogether. Individually, many of these breakthroughs seem incremental. Together, they begin to paint a picture of where computing may be heading next. That possibility is making investors, governments, and technology companies pay very close attention. Because replacing silicon wouldn't simply create another faster processor. It could reshape AI infrastructure, data centers, telecommunications, cloud computing, autonomous vehicles, defense technologies, and countless industries built on digital hardware. And unlike previous generations of chip improvements, this transition may not simply be about making today's computers faster. It could redefine what computers actually are. The reason this matters now is because artificial intelligence has changed the rules. Modern AI models require staggering amounts of computational power. Companies are building data centers consuming gigawatts of electricity. GPU clusters now contain tens of thousands of processors, communicating simultaneously. Memory systems struggle to keep pace. Heat generation continues increasing. Power consumption rises year after year. Ironically, many of today's biggest AI limitations are no longer caused by software. They're caused by physics. Moving electrical signals through microscopic copper wiring generates resistance, heat, latency, and energy loss. Shrinking transistors further introduces quantum effects that engineers spent decades trying to avoid. Every new manufacturing node requires increasingly expensive lithography equipment and unprecedented engineering precision. Silicon hasn't stopped working. It's simply becoming much harder to improve. That reality has pushed scientists around the world to search for alternatives that were once considered experimental. Photonic computing, advanced glass materials, optical interconnects, wide bandgap semiconductors, two-dimensional materials, and entirely new computing architectures have all moved from academic research into serious engineering programs. China has invested heavily across nearly all of these fields. Some of those investments are beginning to produce results that have attracted attention well beyond China's borders. The conversation is no longer whether alternative technologies will exist. The real question has become which country commercializes them first, because history shows something remarkably consistent. The companies that dominate one generation of computing rarely dominate the next without adapting. Mainframes gave way to personal computers. Desktop computing gave way to smartphones. Traditional CPUs were joined by GPUs. AI accelerators emerged alongside them. Every technological transition created new leaders, while forcing established giants to reinvent themselves. The next transition may prove even larger. If silicon eventually stops being the default foundation for advanced computing, entire supply chains could shift. Manufacturing priorities would change. Equipment vendors would adapt. Software developers would optimize for different hardware. Data centers could be redesigned from the ground up. That doesn't mean silicon suddenly disappears. Far from it. Silicon will almost certainly remain essential for years, perhaps decades. But the industry's focus may gradually move toward hybrid systems where silicon works alongside entirely new technologies rather than carrying the entire workload alone. And that's where China's latest research becomes especially interesting. Because instead of trying to replace every silicon chip overnight, many of its projects focus on replacing only the components where silicon performs worst. Communication between chips, high-speed data transfer, AI memory bottlenecks, heat generation, optical computing, advanced materials, one breakthrough at a time. Individually, none of these developments may seem revolutionary. Combined, they could represent the early stages of something much bigger, a transition away from an era that has defined computing for more than 50 years. And if that transition accelerates faster than expected, the biggest question won't simply be whether silicon has reached its limits. It will be who built what comes next. To understand why researchers are searching beyond silicon, you first have to understand how extraordinary its success has been. Silicon didn't become the world's dominant semiconductor by accident. It offered an almost perfect combination of affordability, stability, electrical performance, and manufacturability. As fabrication techniques improved, engineers discovered they could place more transistors onto a single chip while reducing cost per calculation. That simple trend became the engine behind modern computing for decades. Every 2 or 3 years, processors became faster, smartphones became smarter, video games became more realistic, cloud computing became practical. Artificial intelligence evolved from science fiction into everyday reality. Silicon made all of it possible, but every technology eventually reaches a point where improvement becomes increasingly difficult. For silicon, that challenge arrives at the atomic scale. Modern transistors are now measured in just a few nanometers. At these dimensions, engineers aren't simply designing electronic circuits anymore. They're designing around the strange behavior of quantum mechanics. Electrons begin leaking through barriers they were never supposed to cross. Heat becomes increasingly difficult to remove. Manufacturing tolerances shrink to astonishing levels. A tiny defect invisible to the human eye can ruin an entire wafer worth millions of dollars. This is one reason semiconductor fabrication has become one of the most expensive industries on Earth. Building a leading-edge fabrication plant now costs tens of billions of dollars. Every new manufacturing generation requires increasingly sophisticated equipment. Extreme ultraviolet lithography, atomic layer deposition, advanced packaging, high-precision metrology. Each improvement demands more investment while delivering smaller performance gains. Engineers sometimes describe this as the easy progress coming to an end. For decades, shrinking transistors solved nearly every problem. Today, shrinking them further solves fewer problems while creating entirely new ones. Artificial intelligence has made those limitations impossible to ignore. Modern AI models no longer rely on a single processor performing calculations independently. Instead, thousands of processors work together simultaneously. Each processor constantly exchanges enormous amounts of information with every other processor. That communication consumes time, it consumes electricity, it generates heat, and increasingly, it limits overall system performance. Ironically, some of the world's most powerful AI processors now spend part of their time waiting. Not because they're too slow, because information can't reach them quickly enough. That's a remarkable reversal. For years, processors represented the bottleneck. Now the bottleneck often exists between the processors. Moving data has become almost as important as processing data. This shift explains why researchers are exploring technologies that don't simply improve silicon. They're trying to redesign the entire architecture surrounding it. China has become particularly active in this area. Over the past several years, we've seen Chinese researchers publish advances involving photonic chips capable of transmitting information using light rather than electrical signals. Glass-based packaging technologies designed to improve chip communication. Air-filled optical fibers capable of transmitting enormous amounts of data across impressive distances. Novel semiconductor materials intended to reduce energy loss. Optical interconnects designed specifically for AI infrastructure. Advanced chip packaging that shortens communication pathways. Viewed separately, each breakthrough appears highly specialized. Viewed together, they reveal a consistent strategy. Instead of asking how to build a slightly faster processor, researchers are asking how to eliminate the limitations surrounding today's processors altogether. That's an important difference. Imagine upgrading the engine inside a race car while leaving narrow tires, weak brakes, and poor suspension unchanged. The engine becomes more powerful. The car doesn't necessarily become much faster. Modern AI faces a similar challenge. Processors have advanced rapidly. Memory has improved. Storage has become dramatically faster. But communication between all those components hasn't improved at the same pace. That imbalance has created entirely new engineering priorities. This helps explain why many semiconductor conferences today focus as much on packaging, networking, photonics, and material science as they do on transistor density. The future isn't being defined by one component. It's being defined by how every component works together. China's semiconductor strategy appears increasingly aligned with that philosophy. Rather than concentrating every investment on traditional silicon scaling, the country has expanded research across multiple complementary fields. Advanced materials, optical communication, AI networking, memory technology, chip packaging, photonics, integrated manufacturing. Each area addresses a different weakness inside conventional computing. Individually, none replaces silicon. Collectively, they reduce dependence on silicon doing everything alone. That's why the title of this video isn't suggesting silicon suddenly disappears tomorrow. It suggests something arguably more significant. Silicon may no longer be the only foundation capable of supporting next-generation computing. Future AI systems may rely on entirely new combinations of technologies working alongside traditional semiconductor designs. Processors optimized for specific workloads, photonic communication replacing electrical signaling, advanced packaging reducing communication distances, novel materials handling specialized calculations, silicon remaining where it performs best. This hybrid approach could extend computing far beyond what conventional transistor scaling alone can achieve. Some researchers even argue that the future of computing won't belong to a single revolutionary material. Instead, it will belong to ecosystems capable of combining multiple technologies into one highly efficient platform. That possibility is attracting enormous investment worldwide, because whoever successfully builds that platform may define the next era of computing, not by making silicon slightly better, but by making the entire system fundamentally smarter. If silicon is approaching practical limits, the obvious question becomes surprisingly simple. What exactly replaces it? The answer is more complicated than many headlines suggest. There probably won't be a single material that suddenly takes over the semiconductor industry overnight. Instead, engineers increasingly believe the next generation of computing will emerge from several technologies working together, each solving a different problem that silicon struggles to handle. In many ways, the future of computing may look less like a replacement and more like an evolution. That's where China's recent research becomes particularly interesting. Rather than betting everything on one breakthrough, Chinese laboratories have been exploring multiple paths simultaneously. One of the most promising involves photonic computing. Traditional processors move information using electrons flowing through microscopic circuits. Photonic systems replace some of those electrical signals with light. At first glance, that may not sound revolutionary, but light behaves very differently from electricity. Photons travel at incredible speeds. They generate far less heat while transmitting information. They experience minimal electrical interference. And perhaps most importantly, they can carry enormous amounts of data simultaneously through optical pathways. These advantages become especially valuable inside artificial intelligence infrastructure. Modern AI isn't limited by mathematical calculations alone. It's limited by communication. Thousands of processors constantly exchange data. Memory modules feed enormous datasets into GPU clusters. Networking hardware moves information between racks. Storage systems continuously deliver new training data. Every delay reduces efficiency. If light can move that information faster than electricity, AI systems become more productive without necessarily building faster processors. That's one reason photonic technologies have become one of the semiconductor industry's hottest research areas. China isn't alone in pursuing this vision. Companies and research institutions across the United States, Europe, Japan, South Korea, and Taiwan are investing heavily in optical computing as well. But China's pace of announcements has accelerated noticeably over the past few years. We've covered breakthroughs involving photonic processors, glass-based chip packaging, air-filled fiber capable of record-breaking transmission speeds, optical interconnects, integrated AI networking. Each project addresses a different communication challenge. Together, they point toward a future where electrical signaling no longer carries every piece of information inside advanced computers. Another promising direction involves entirely new semiconductor materials. For decades, silicon dominated because it balanced cost, reliability, and manufacturing simplicity. But other materials possess electrical properties that outperform silicon in specific applications. Gallium nitride allows higher power efficiency. Silicon carbide excels in electric vehicles and industrial power electronics. Two-dimensional materials measured only atoms thick are being explored for future transistor designs. Researchers are investigating carbon-based structures with remarkable electrical behavior. None of these materials completely replaces silicon today. Instead, each one solves particular problems where silicon reaches its limits. That's an important distinction. The semiconductor industry rarely abandons successful technology immediately. It gradually introduces specialized alternatives where the benefits justify the cost. We've already seen this happen in memory. Traditional hard drives still exist. Solid-state storage expanded alongside them. Cloud storage joined both. Each technology found its own role. The same pattern may emerge with computing materials. Silicon remains excellent for general-purpose processing. Photonics may dominate communication. Wide bandgap materials may power electric infrastructure. Advanced packaging may reduce communication delays. Novel memory technologies may eliminate existing bottlenecks. Instead of replacing silicon entirely, future computers may simply rely on silicon much less than they do today. That shift could prove just as significant. China's strategy appears designed around exactly this kind of diversification. Rather than concentrating every research dollar on one revolutionary invention, investments span nearly every layer of modern computing. Semiconductor manufacturing, memory technology, advanced packaging, optical communication, artificial intelligence hardware, materials science, telecommunications, industrial automation. This creates something more valuable than isolated breakthroughs. It creates an ecosystem where improvements in one field immediately benefit another. Faster networking improves AI clusters. Better packaging enhances processor performance. Advanced materials reduce energy consumption. Optical communication eliminates bottlenecks. Each improvement strengthens the others. That's why many analysts increasingly evaluate semiconductor competition differently than they did 10 years ago. The question isn't simply who builds the fastest chip. It's who builds the strongest ecosystem around that chip. Because artificial intelligence has fundamentally changed what high-performance computing requires. Success no longer depends on processor speed alone. It depends on communication, power efficiency, heat management, memory bandwidth, packaging technology, networking architecture, manufacturing capability, software optimization, supply chains. The winners of tomorrow's computing industry will likely master all of them. That's why replacing silicon isn't really about one material defeating another. It's about building an entirely new generation of computing infrastructure. And if China's current strategy succeeds, the biggest breakthrough may not be a single revolutionary processor. It may be something much larger, a computing platform where silicon is no longer the star of the show. Instead, it becomes just one component inside a far more advanced technological ecosystem. Whether silicon is truly nearing the end of its dominance remains an open question. Predicting the future of technology has never been easy, especially in an industry that has repeatedly surprised even its own experts. Every few years, a breakthrough emerges that changes expectations, reshapes investment, and forces companies to rethink their long-term strategies. What's different today is the scale of that transformation. Artificial intelligence has accelerated demand for computing faster than almost anyone anticipated. Data centers continue growing larger. AI models require exponentially more processing power. Energy consumption keeps climbing. At the same time, the physical limits of traditional chip design are becoming increasingly difficult and expensive to overcome. That reality is pushing the entire industry to think differently. Instead of relying on one material to solve every problem, researchers are building systems where multiple technologies work together. Silicon may continue handling general-purpose computing, while photonics speeds up communication. Advanced materials improve efficiency, and new packaging techniques reduce delays between components. In many ways, the future may not belong to a single revolutionary invention. It may belong to whoever integrates these technologies into one seamless platform first. China appears determined to compete in exactly that race. Over the past several years, we've seen growing investment across semiconductor manufacturing, AI hardware, optical networking, advanced materials, memory technologies, and chip packaging. Each announcement on its own may seem incremental, but together they suggest a broader strategy, one focused on shaping the next era of computing rather than simply catching up to the last one. Of course, none of this means silicon suddenly becomes obsolete tomorrow. Billions of devices around the world will continue relying on silicon for many years to come. The semiconductor industry doesn't replace foundational technology overnight. It evolves step by step, generation by generation. But history shows that every technological era eventually reaches a turning point. Vacuum tubes gave way to transistors. Mainframes gave way to personal computers. CPUs were joined by GPUs. Now, the industry is searching for what comes after today's AI hardware. Whether the next breakthrough comes from photonics, new semiconductor materials, hybrid architectures, or an approach nobody has imagined yet, one thing is becoming increasingly clear. The future of computing will likely look very different from the systems we've relied on for the past 50 years. And if that future arrives sooner than expected, today's biggest advantage may not belong to the company with the fastest silicon chip. It may belong to the country that successfully builds what comes next. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications so you never miss our latest deep dives into AI, semiconductors, and the technologies shaping the future. Thanks for watching, and I'll see you in the next one. There is a building in the city of Wuhan, China, that has its own weather. Every single morning, an artificial sun rises inside it. It climbs across a simulated sky, shifting color as the hours pass, pale blue at dawn, warm amber by midday, deep orange and violet toward evening, and then it sets. The tens of thousands of people inside, shopping, skiing, riding roller coasters, watching their children splash along an indoor lakeside beach, can glance upward and watch the whole cycle unfold in real time. This is Dream Plaza, and it is one of the most ambitious buildings operating anywhere on the planet today. The numbers alone are staggering. The complex covers nearly 800,000 square meters of floor space. The retail center by itself spans 370,000 square meters across 9 floors above ground and 4 below. But those figures only describe the shell. They tell you nothing about what was put inside it, or why. And that is the far more interesting story. Because Dream Plaza is not just big, it represents a completely different theory of what a building in the center of a modern city is even supposed to be. To understand why it exists, you first have to understand what it was built to escape. Almost every country that built shopping malls in the second half of the 20th century eventually watched them decline. The formula was always identical: a large enclosed space, Anchor stores at either end, smaller shops filling the corridors between them, a food court somewhere in the middle, and a vast parking lot wrapped around the whole thing like a moat. For decades, this worked beautifully. People drove in, walked the corridors, and spent money. Then online shopping arrived, and the formula came apart. The question that broke the traditional mall was brutally simple. Why would anyone drive to a building, hunt for a parking space, walk to a store, and pay a marked-up price for something they could order from their couch and have delivered the next morning? Increasingly, the answer was that they wouldn't. Foot traffic dropped. Anchor tenants packed up and left. The corridors emptied out. Across much of the West, shopping centers became half-lit monuments to a retail model the world had quietly moved beyond. Chinese developers watched this happen, and rather than simply copying the format that was already dying, they studied the failure carefully. They traced it back to its root cause. The malls had stopped offering a reason to show up that couldn't be replicated by staying home. And from that, they drew a conclusion that seems obvious in hindsight, but that most Western developers were too invested in the old model to act on. People have never primarily left their homes in order to buy things. They leave to experience things, to be somewhere specific, to feel something, to do something that requires their body to physically be present in a place. You can buy almost anything online, but you cannot ski online. You cannot take your child on a roller coaster through a screen. You cannot feel the cold of manufactured snow on your face from your living room. That single insight became the foundation of everything Dream Plaza is. The decision was locked in at the very start of the design process, and it was irreversible. This would not be a place to buy things. It would be a place to be. The building itself would be the product. Start at the bottom. The indoor theme park occupying the lower floors is not a token entertainment corner. A few arcade machines and a carousel squeezed into leftover space near the escalators. It is a full-scale attraction featuring roller coasters, high-speed rides, and multi-sensory experiences designed for adults and children alike. It runs year-round, regardless of season, regardless of weather, regardless of whatever the city outside is doing. In Wuhan, that matters enormously. Summer temperatures there routinely climb past 35 degrees Celsius, and winters arrive with real force. A venue that depends on pleasant weather might work 3 months out of the year. A fully climate-controlled one earns repeat visitors every single weekend without exception. Move upward through the building, and the temperature starts to drop before you understand why. The snow park, among the first and largest indoor ski facilities in the region when it opened, keeps its floors below freezing around the clock. Families living in a city where natural snowfall is rare and unpredictable can ski, snowboard, or simply play in manufactured powder on any Tuesday in July. That jarring transition, going from a sweltering Wuhan summer to a genuine ski slope in the time it takes to ride a few escalators, is precisely the point. Dream Plaza is selling sensory experiences the city outside its walls simply cannot offer. You want winter? Winter is on the 4th floor. The dining and retail areas are arranged unlike a standard mall. Instead of corridors lined with shops on either side, optimized purely for storefront exposure, the spaces are organized as a series of distinct atmospheric environments, each one designed to feel genuinely different from the last. The design team built the concept around the idea of time travel and the 4 seasons. Moving through Dream Plaza is meant to feel like passing through different eras and different climates. Warm golden zones that evoke high summer, cool blue-toned spaces that recall deep winter, transitional passages that shift the light and mood and texture as you walk. The atmosphere isn't background decoration. It is the architecture. It is what people came for. Beyond the enclosed floors, the complex spills outward into curated open-air areas, a lifestyle and leisure zone designed for adults, and a children's lakeside precinct built around water, open-ended play equipment, and natural shapes. In a dense urban district where green space and real outdoor room for kids is scarce, this isn't a luxury add-on. For families living in surrounding high-rise apartments, it's what turns the building into part of their weekly routine rather than an occasional outing. Now, the sky. The centerpiece of Dream Plaza's central atrium is one of the boldest single design decisions in any commercial building currently operating on Earth. The building doesn't simply provide artificial lighting the way every other indoor space does, fixed overhead sources angled to flatter products and keep shoppers comfortable enough to linger. It provides an artificial sky. A dynamic overhead display system spans the full width of the atrium, simulating the complete arc of a day. It moves from pale early morning blue, through warm midday amber, into the deep orange and violet of late afternoon, and finally into a simulated night sky as the building's evening hours begin. The sun that crosses the interior isn't a spotlight. It is a calibrated system designed to reproduce the quality and character of natural daylight. the specific kind of light human biology uses to track time, regulate mood, and maintain the circadian rhythm that governs energy, sleep, and even appetite. This matters more than it first appears. Every large enclosed building, every shopping center, every airport, every windowless venue is quietly fighting the same biological reality. Human beings are profoundly sensitive to their light environment. When that environment stops signaling what time it is, people's relationship with the space starts to break down. They tire faster. They become subtly disoriented. They want to leave. The artificial sky is engineered to prevent exactly that. It gives the building a pulse, a rhythm, a sense of time genuinely passing, which makes spending hours inside feel less like confinement and more like inhabiting a real place. It's worth pausing on how counterintuitive this is. Casino designers famously stripped windows and clocks from gambling floors, deliberately severing guests from any sense of time to keep them inside longer. Dream Plaza did the precise opposite. It introduced a complete simulated day-night cycle into a building where every door opens onto another interior room. One approach traps you by making time vanish. The other holds you by making time feel real. Both work, but only one of them also earned an international award for Best Retail Interior Design. Wuhan deserves a closer look because it is far more significant a city than most people outside China realize. With a population of around 12 million, Wuhan is one of the largest urban centers in China's interior. It sits at the meeting point of the Han and Yangtze rivers, a geographic position that made it a critical trading hub for centuries and continues to make it one of China's most important logistics nodes today. Dozens of universities are based here. A major industrial and manufacturing base operates here. A fast-growing technology sector has taken root here. This is not a secondary city playing catch-up. It is a city that has spent decades building the infrastructure and institutional weight to compete at the very top of China's urban hierarchy. The Eastern District, where Dream Plaza was built, is the densest and most historically significant of Wuhan's three main urban cores. Dropping a building of this scale into that district was not the speculative gamble that defines so many Chinese megaprojects, where enormous structures rise on the urban fringe and then wait years for the surrounding population to catch up. Dream Plaza opened in an already dense, already commercially active neighborhood, surrounded by millions of existing residents with disposable income and a clear appetite for experiential spending. When it opened in November 2022, the response was immediate. Opening day crowds were enormous. The experiential attractions reported wait times stretching for weeks. The building gave a major city a genuine reason to celebrate something extraordinary, and people showed up in force to do exactly that. Dream Plaza earned its design award for a specific reason. It breaks with conventional mall logic, not just in what it contains, but in how it expects people to move through it. Standard commercial architecture is built on one overriding principle: maximize exposure. Every shopper who enters should pass as many storefronts as possible. Corridors are kept straight so sightlines stretch further. Escalators are positioned to pull foot traffic through peripheral zones. Floor plans are arranged so the route to the supermarket or cinema runs through 3 departments you never intended to visit. Every decision is optimized to ensure the path to wherever you're going routes you past as many things you weren't planning to buy as possible. This is effective retail science, and it has driven billions in unplanned purchases for 60 years. But it is also, increasingly, the wrong approach for a generation that grew up in information-saturated environments and has become highly skilled at recognizing and resisting the feeling of being managed. Dream Plaza's internal geometry is curved, branching, and deliberately non-linear. There are no long straight corridors. Routes turn unexpectedly into plazas, open into soaring double-height atriums, narrow into intimate passages, then expand again. Navigation isn't optimized for efficiency, it's optimized for surprise. The underlying assumption is no longer that you came to reach a specific destination. The assumption is that you came to see what happens next. The building rewards wandering. It withholds its best moments until you've earned them by moving through something else first. Here, the journey genuinely is the destination, in the most literal architectural sense. The four-season atmospheric concept pushes this even further. Stepping from a warm, gold-toned environment into a cool, wintry blue one acts as a sensory reset, a way of making an 800,000 square meter building feel like it holds multiple distinct worlds, rather than one endless commercial space. It's the difference between a building that is merely enormous and one that somehow feels larger than its own floor plan. Dream Plaza is extraordinary, but it is also, in ways its designers haven't fully resolved, a set of open questions wearing the clothing of a solution. And the same features that make it remarkable also make it, in certain respects, genuinely fragile. That fragility doesn't show up in the steel frame or the foundations, it shows up in the assumptions the entire project rests on. The first is environmental. Keeping a snow park below freezing in a city where summers exceed 35 degrees is an enormous continuous energy commitment. Running a dynamic artificial sky, a full-scale theme park, a cinema, climate-controlled retail across 13 floors, and an outdoor lakeside precinct, all at once represents an energy demand that would be striking even before you account for the tens of thousands of daily visitors, adding to the heating, cooling, and ventilation load on every system in the building. Detailed energy consumption figures haven't been published, so the true environmental math is genuinely unknown. It may turn out to be more efficient per visitor than a city full of smaller, scattered venues. It may not. For now, no one can say for certain. The second question is economic. The experiences that make Dream Plaza feel exceptional today were new in 2022. The ski slope was novel, the artificial sky was astonishing, the indoor roller coasters were reason enough to cross the city and spend a Saturday. But what are they in 2030? In 2035? The history of experiential venues is full of attractions that felt revolutionary at opening and felt tired within a decade. Keeping genuinely novel experiences alive isn't only a financial cost, it's a creative one. Dream Plaza will have to keep reinventing itself, keep adding fresh reasons to return, or risk the same slow attrition that killed the conventional mall it was designed to replace. The artificial sun will keep rising. The real question is whether people keep finding a reason to come watch it. The third question is the most thought-provoking, and it's one cities everywhere should probably be asking more openly. Dream Plaza is, among other things, a machine for not leaving. Everything a family might want for an entire day. Exercise, entertainment, food, play, shopping, spectacle, outdoor space sits inside a single set of walls. The incentive to engage with the rest of the city is reduced by exactly the degree to which Dream Plaza succeeds at replacing it. Cities aren't just collections of services and amenities. They're systems where people encounter one another in unplanned ways, where public space generates the kind of spontaneous social friction that builds community over time. A building that substitutes for the city, rather than serving it, raises a question urban planners haven't yet answered. What happens to the street when the building beside it becomes more appealing than the street itself? Here is the honest version of what Dream Plaza is. It is not a mall. It is not a theme park. It is not a hotel complex or a civic center or an entertainment district. It is the first generation of a new kind of building that doesn't yet have a widely agreed upon name, a type that will very likely define how the world's most ambitious cities approach their downtown cores for the next several decades. Every major city on Earth is wrestling with the same fundamental question. What do you build at the heart of a dense urban district when buying things online is easier than going to a store? When entertainment competes directly with the device in everyone's pocket? When the bar for what counts as a good enough reason to leave the house has risen to a level no urban planner 50 years ago would even recognize? The answer most Western cities have offered is to wait and see, to rezone incrementally and hope that coffee shops, farmers markets, and creative offices fill the void left by departing retailers. That answer largely isn't working. Dream Plaza's answer is the opposite. Build something a screen cannot replace. Build an environment so deliberately physical, so sensory, so committed to the idea that being somewhere specific genuinely matters, that simply being inside becomes its own justification. Give it a ski slope that defies the weather outside. Give it roller coasters that make adults feel like kids again. Give it a beach and an atrium so tall it needs its own sky. And then give that sky a sun that rises, moves, and sets on a schedule, reminding everyone inside that time is passing, that this moment will end, and that there's nowhere else they'd rather spend it. Whether that answer holds for a generation is something 12 million people in Wuhan will decide with their feet, weekend after weekend, for years to come. For now, the artificial sun inside Dream Plaza rises every morning. And for now, people keep coming to stand beneath it. A normal solid-state drive has one job: store data. It receives files from the computer, places them inside flash memory cells, and returns them when requested. The controller organizes the traffic, corrects errors, and tries to keep the drive alive as thousands of writes gradually wear down the NAND. But a Chinese memory company believes the SSD should do much more than move data from one place to another. Longsys has introduced a 5-nanometer chip called the WM8500. The company describes it as an SPU, a storage processing unit. And according to Longsys, this chip can compress data inside the drive in real time, without requiring the host processor to handle the work. Across text, source code, databases, and similar workloads, the company reports an average compression ratio of approximately 2:1. That creates an extraordinary possibility. A drive containing 128 terabytes of physical flash could provide as much as 256 terabytes of effective storage. No additional NAND package, no second SSD, no magical new memory cell. The same physical drive simply stores certain data more efficiently. But capacity doubling is only the beginning. Longsys says the SPU can also move selected AI data out of expensive DRAM and into high-speed storage, reducing memory requirements by nearly 40% in one tested scenario. The company has even demonstrated a system built around AMD's Ryzen AI Max Plus 395, running a 397 billion parameter model locally. That sounds almost impossible for a compact machine. Yet the idea behind it is surprisingly simple. Instead of treating storage as a passive warehouse, Longsys wants the SSD to become an active participant in computing. The drive does not merely hold the data, it compresses it, sorts it, predicts when it will be needed, and in some cases, acts as an extension of system memory. If the technology works as described, the future SSD may not be measured only by how many terabytes it contains. It may be measured by how intelligently it uses every byte. The storage problem. II created. For years, computer performance was discussed mainly in terms of processors. Faster CPU, faster GPU, more cores, higher clock speeds. But artificial intelligence has exposed a different bottleneck: memory. A large AI model may contain billions or hundreds of billions of parameters. Each parameter represents a numerical value learned during training. To run the model, those values must be stored somewhere and moved repeatedly into the processor. The calculations can be fast. Moving the data is often slower. Imagine owning a factory with thousands of extremely powerful machines. The machines can assemble products at incredible speed, but every component is stored in a warehouse several kilometers away. The machines spend less time working than waiting for deliveries. That is the AI memory problem. High-end data centers attack it with massive amounts of high-bandwidth memory, large pools of conventional DRAM, and extremely expensive storage systems. An ordinary PC cannot do that. Even a powerful workstation may have 64, 128, or 256 gigabytes of memory. A large model may require far more. So developers use a technique called offloading. Part of the model remains in fast DRAM. The rest is stored on an SSD and loaded only when needed. This makes larger models possible, but it introduces another problem. SSDs are much slower than DRAM. If the wrong data is requested at the wrong moment, the processor must wait. Longsys is trying to reduce that delay by making the drive itself more intelligent. From SSD controller to storage processor, every SSD already contains a controller. The controller translates commands from the computer, decides where data should be written, manages bad memory cells, and performs error correction. Without it, NAND flash would be difficult to use reliably. But the traditional controller is largely a traffic manager. It moves data. The WM8500 is designed to process data too. Longsys says the SPU combines a conventional storage control engine with an intelligent processing engine on the same chip. That distinction matters. A normal controller asks, where should this file be placed? The SPU can ask additional questions. Can this file be compressed? Is it used frequently? Should it remain close to the processor? Can part of it be moved into a cheaper region of the drive? Will the system need it again soon? The company calls the software layer controlling these decisions ISA, or Intelligence Storage Agent. The SPU is the muscle. The ISA is the planner. Together, they turn the drive from a passive destination into something closer to a data assistant. The idea resembles what happened to graphics cards. A GPU was once a specialized component responsible mainly for drawing images. Over time, it became a general computing engine used for science, simulation, and artificial intelligence. Longsys is suggesting that storage controllers may follow a similar path, not by replacing CPUs or GPUs, by performing the data management work those processors should not have to do. How 128 terabytes becomes 256 terabytes? The headline number comes from lossless compression. Lossless means the original data can be reconstructed perfectly. Nothing is thrown away, nothing is blurred, nothing is approximated. A photograph saved as a low-quality image may use lossy compression, where some visual information is permanently removed. That can reduce file size dramatically, but the original cannot be recovered exactly. Lossless compression works differently. It searches for repeated patterns and replaces them with shorter instructions. Suppose a document contains the word semiconductor 10,000 times. Instead of storing every letter 10,000 times, a compression system can store the word once and then record where it repeats. The file becomes smaller. When it is read, the system reconstructs the full version. Longsys says the WM8500 performs this process directly inside the storage device. The computer sends data to the SSD. The SPU analyzes it. Compressible data is reduced before being written to flash. When requested, the SPU decompresses it before returning it to the host. To the operating system, the process can appear transparent. The user does not need to place files inside an archive manually. The drive handles it automatically. With an average 2:1 ratio on suitable workloads, 1 physical terabyte can store approximately 2 terabytes of original information. That is how 128 terabytes can provide up to 256 terabytes of effective capacity. But the phrase suitable workloads is essential. Not all data compresses equally. The files that refuse to shrink. Text compresses extremely well because language contains repetition. Source code also contains repeated words, structures, commands, and symbols. Databases may contain recurring values, empty fields, and predictable patterns. These are the kinds of workloads Longsys highlights. Video is different. Modern video files are already heavily compressed. A movie encoded with an efficient codec has already had most of its obvious redundancy removed. Trying to compress it again may save almost nothing. The same applies to JPEG photographs, compressed archives, and many encrypted files. Encryption deliberately makes data appear random. Random-looking data contains fewer predictable patterns for a compression engine to exploit. So a 128 terabytes drive will not always behave like a 256 terabytes drive. One user may see close to the full 2:1 benefit. Another may see only a small improvement. A data center filled with text logs, program code, and database records could benefit greatly. A media archive filled with compressed movies may not. This is not a flaw unique to Longsys. It is a basic limit of compression. You cannot repeatedly squeeze information forever. Eventually, the obvious repetition disappears. That is why the most honest description is not, Longsys created a physical 256 terabytes SSD. It created a 128 terabyte storage platform that may hold as much as 256 terabytes of uncompressed source data under favorable conditions. Still impressive, just not magic. Why put compression inside the drive? Computers have compressed files for decades. Operating systems can compress folders. Databases use compression. Servers use software tools to reduce storage needs. So why build dedicated compression hardware inside an SSD controller? Because compression requires computation. If the CPU performs it, processor time is consumed. Data must move through system memory, power is used. Other programs may slow down. A dedicated engine can perform the same task more efficiently. Think of a restaurant kitchen. The head chef can wash every plate personally. But that is probably not the best use of the most valuable worker in the building. A dedicated dishwasher handles the repetitive task while the chef focuses on cooking. The SPU attempts to do the same for data. The CPU and GPU focus on applications and AI calculations. The storage processor handles compression, caching, and movement. Longsys claims the process introduces no meaningful performance penalty. But that is one of the areas where independent testing will be important. Compression always requires work. The real question is whether the 5-nanometer engine can perform that work fast enough that the user barely notices. If the drive can compress at full interface speed, the savings could be substantial. If compression slows sustained writes or increases latency, the value becomes more complicated. Capacity is not useful if access becomes painfully slow. The 5nm chip at the center, the WM8500, is manufactured using a 5-nanometer process. That does not automatically make it revolutionary. Process node names are not direct measurements, and a smaller node does not guarantee better architecture. But 5-nanometer manufacturing provides a practical advantage. More processing logic can fit inside a compact controller while keeping power consumption manageable. Traditional SSD controllers already perform difficult tasks. They manage multiple NAND channels, calculate error correction codes, track wear, translate logical addresses, maintain caches, encrypt data, support PCI Express communication. Now add hardware compression, workload classification, predictive prefetching, and AI data scheduling. That requires more transistors. more processing, more memory, and careful power control. A storage controller cannot behave like a desktop CPU, consuming 100 watts. It lives inside a drive where heat can reduce performance and shorten flash memory life. The 5nm process gives Longsys room to add intelligence without turning the SSD into a small oven. The WM8500 also supports PCI Express 5.0, allowing high-speed communication with the host system. That bandwidth matters because the entire concept depends on moving model data quickly enough to hide the difference between SSD and DRAM. The drive does not need to become as fast as DRAM. It needs to become fast and predictable, enough that software can plan around it. The second trick, using SSD as slower memory. Compression creates the headline. HLC may create the bigger long-term impact. Longsys calls it high-level cache. The idea is to use the SSD as an extension of DRAM. Computers already use virtual memory. When physical RAM becomes full, the operating system moves some data to storage. Historically, this was painful. Hard drives were so slow that a computer using large amounts of virtual memory could become nearly unusable. Modern SSDs are much faster. They are still far slower than DRAM, but the gap can be managed more intelligently. Not all data needs immediate access. Some information is hot. The processor uses it constantly. Some is warm. It may be needed soon. Some is cold. It exists in memory but is rarely touched. HLC attempts to identify those categories. Hot data remains in DRAM. Warm and cold data moves to the SSD. If the system predicts correctly, the processor sees little delay because required data is fetched before it is needed. This resembles organizing a workshop. The tools used every minute remain on the table. Tools needed occasionally sit in a nearby drawer. Tools rarely used go into storage. A badly organized workshop forces the worker to walk across the building constantly. A well-organized one keeps the right objects close at the right time. Longsys says HLC can reduce required DRAM capacity by nearly 40% in a tested 256,000 token scenario involving a 122 billion parameter workload. That does not mean every computer can remove 40% of its RAM. It means this particular architecture reportedly achieved that reduction under a specific AI workload. The 397 billion parameter demonstration. The most eye-catching demonstration involved AMD hardware. Longsys says it jointly optimized an intelligent agent system built around the Ryzen AI Max Plus 395 processor. That AMD chip is designed for powerful local AI systems, combining CPU cores, graphics resources, and a large unified memory architecture. Using the SPU and ISA system, Longsys reports that the machine successfully deployed a 397 billion parameter model locally. That figure requires context. Deployed does not necessarily mean the model ran at cloud data center speed. It does not tell us the exact precision used for the weights. It does not reveal the token generation rate. It does not tell us how much of the model remained in memory and how much was streamed from storage, but it demonstrates the direction. A model too large to fit entirely inside conventional system memory can still run if inactive sections remain on the SSD and are loaded intelligently. Many modern models use a mixture of experts architecture. An MOE model may contain hundreds of billions of total parameters, but only a fraction activates for each token. Imagine a company employing hundreds of specialists. One question requires a lawyer, another requires an engineer, a third requires an accountant. The company does not need every employee in the meeting room simultaneously. The ISA system attempts to keep currently active experts in fast memory while storing inactive experts on the SPU-equipped SSD. When the system predicts that a different expert will be needed, it begins loading that expert early. If the prediction is accurate, the data arrives before the model asks for it. The delay becomes less visible. That is intelligent prefetching. The KV cache problem. Large language models face another memory burden, called the KV cache. As a model processes a conversation, it stores information about previous tokens so it does not need to recalculate everything repeatedly. The longer the conversation, the larger the cache grows. A short prompt may be manageable. A document containing hundreds of thousands of tokens can consume enormous amounts of memory. Longsys says its system can move older or less active portions of the KV cache onto the SSD while keeping important sections in DRAM. Compression may reduce the space required further. Again, timing is everything. If the model suddenly needs an old section and the data has not been prefetched, inference can pause. The SSD becomes a bottleneck. If the scheduler correctly predicts future needs, the storage delay can overlap with computation. The model continues working while the next data block arrives. This is why the ISA software may matter as much as the WM8500 hardware. A fast drive with poor scheduling is still slow at the wrong moment. An intelligent scheduler can make slower storage feel faster by requesting data before the wait begins. Can this replace DRAM? No, at least not in performance-sensitive roles. DRAM operates with latency measured in tens of nanoseconds. NVMe SSD latency is usually measured in microseconds. A microsecond is 1,000 nanoseconds. That difference is enormous. Even a highly advanced SSD cannot become genuine system memory simply through clever software. It can, however, reduce the amount of expensive DRAM required. This distinction is important. The SPU does not replace the workbench. It makes the storage room more useful. The most frequently used tools remain on the workbench. The rest can move to an automated shelf that delivers them when requested. For AI systems, that can change economics. DRAM is expensive. High-capacity memory configurations increase device cost and power consumption. If a manufacturer can build a system with 96 gigabytes of DRAM that behaves like a larger memory machine under selected workloads, the savings could be meaningful. But the user experience depends on the workload. Interactive applications may be sensitive to small delays. Batch processing may tolerate them. Models with predictable expert activation may work well. Other architectures may not. One benchmark cannot answer every case. Could smart SSDs replace hard drives? Longsys also presents the SPU as a possible alternative to large-capacity hard drives. HDDs remain popular because they provide huge capacity at low cost. SSDs are faster, quieter, and more efficient, but large enterprise SSDs can be extremely expensive. Compression changes that calculation. If a 128 terabytes flash drive stores the same amount of suitable data as 256 terabytes of conventional capacity, its effective cost per stored terabyte falls. It may still cost more than hard drives, but total ownership includes more than purchase price. Hard drives use mechanical parts. They require more physical space. They consume energy. They produce vibration. They need cooling. They may fail differently. An SSD with intelligent compression could become attractive in environments where space, power, and access speed matter more than the lowest possible purchase price. However, flash endurance remains important. Compression may actually help by reducing the amount of data physically written to NAND. If 2 terabytes of original data compress to 1 terabyte, fewer flash cells need to be programmed. That could extend drive life. But only independent endurance testing can show how the complete system behaves under sustained heavy use. The SPU itself also creates new complexity. More intelligence means more firmware. More firmware means more opportunities for bugs. Storage errors are unforgiving. A graphics glitch is annoying. A corrupted database can be catastrophic. The questions Longsys still needs to answer. The company's claims are fascinating. They are not the same as a full independent review. We still need to know the sustained compression speed. Can the controller maintain performance when writing hundreds of gigabytes continuously? How does latency change when compression is active? What happens with data that compresses poorly? How much power does the SPU consume? How hot does the controller become? How consistent is the 2-to-1 ratio across real enterprise workloads? How does the system protect data if power fails during a compressed write? How many drives can operate together in a server? What is the cost compared with a conventional enterprise SSD? And perhaps most importantly, when can customers actually buy one at scale? A technology demonstration can show possibility. A commercial product must show reliability, support, firmware stability, and manufacturing volume. Storage buyers are conservative for a reason. They are trusting the drive with information that may be more valuable than the hardware itself. My take. My view is that the most important part of the WM8500 is not the headline capacity doubling. Compression is useful, but it depends heavily on the data. Some users may approach 2-to-1. Others may see far less. The deeper shift is architectural. Longsys is treating storage as a computing layer. For decades, the hierarchy was simple. The CPU computes. DRAM feeds the CPU. Storage waits. AI is breaking that arrangement because model sizes are growing faster than affordable memory capacity. The SPU offers another approach. Let the storage device perform part of the data work. Compress information before it consumes flash. Keep inactive model experts outside DRAM. Predict which data will be needed next. Move old KV cache entries into a lower-cost tier. None of those ideas individually eliminates the memory bottleneck. Together, they may make local AI systems far more capable. The risk is that intelligent storage becomes complicated storage. Prediction errors create delays, compression adds processing, firmware bugs create new failure modes, and company demonstrations may look better than mixed real-world workloads. Still, the direction makes sense. We are approaching a point where adding more raw storage and more raw DRAM cannot be the only solution. Efficiency must improve too. A 128 terabytes drive should not merely be a bigger bucket. It should understand how the bucket is being used. That is what the WM8500 is trying to become. Not just an SSD controller, a storage processor, a chip that turns capacity into something flexible, a chip that lets flash behave partly like memory, and under the right conditions, a chip that allows 128 physical terabytes to hold 256 terabytes of original data. The achievement is not that Longsys created storage from nothing. It is that the company may have found a better way to use what was already there. So what do you think? Would you trust a smart SSD that automatically compresses your files and manages part of your AI memory? Or would you prefer a simpler drive with predictable physical capacity and fewer layers of processing? Let me know your view in the comments. And if you want more grounded breakdowns of the chips, memory systems, and hidden hardware reshaping computing, subscribe to Eastern Engine, because the next storage revolution may not come from adding more flash. It may come from teaching the drive what to do with it. For the entire history of electrical power, almost every power plant on Earth has worked the same fundamental way. You take a heat source, burning coal, splitting atoms, concentrated sunlight, it doesn't matter which, and you use that heat to boil water. The water turns to steam. The steam, under enormous pressure, blasts through a turbine and spins it. The spinning turbine turns a generator, and the generator produces electricity. Then you cool the steam back into water and do the whole thing over again, millions of times. That cycle is so old, it predates the light bulb. The basic principle of using boiling water and steam to do mechanical work goes all the way back to the steam engines that powered the Industrial Revolution. For more than 2 centuries, through every advance in fuel and engineering and materials science, the working fluid at the heart of nearly every power plant stayed exactly the same. Water in, steam out. Spin the turbine. China just broke that 200-year tradition. In a steel plant tucked into the mountains of southwest China, engineers have switched on a power generator that doesn't use steam at all. Instead, it runs on the one substance the entire world spends enormous effort trying to get rid of. It runs on carbon dioxide, the gas we blame for climate change, the byproduct of every furnace and engine and power station, the thing scientists are racing to capture and bury underground. China has turned it into the beating heart of a power plant. And the headline number is staggering. This system is reportedly around 50% more efficient at squeezing electricity out of waste heat than the steam technology the world has relied on for generations. So how does a power plant run on a pollutant? Why did this take 200 years to figure out? And what does it actually mean for the future of energy? Let's break it all down. Before we go any further, I have to clear something up, because the way this story gets told online is genuinely misleading, and I'd rather give you the honest version. When people hear a power plant that runs on CO2, they immediately picture giant machines sucking carbon dioxide out of the sky, cleaning the atmosphere while generating electricity. A magic device that fixes climate change and powers your home at the same time. That is not what this is. I want to be completely straight with you about that. This technology does not pull CO2 out of the air. It does not reduce the amount of carbon dioxide in the atmosphere. And it does not burn CO2 as a fuel. You can't burn carbon dioxide. It's already been burned, which is what makes it CO2 in the first place. So what is actually happening here? The carbon dioxide isn't the fuel, it's the messenger. In every power plant, you need something to carry heat from your heat source to your turbine. For 200 years, that messenger has been water turned to steam. What China has done is replace the water with carbon dioxide, a fixed amount of it, sealed inside the system, used over and over in a closed loop. The CO2 never escapes. It never gets used up. It just shuttles heat back and forth, endlessly. Why does that matter? Because it turns out carbon dioxide, when you treat it the right way, is a dramatically better messenger than water ever was. And understanding why requires us to look at one of the stranger states that matter can exist in. You already know the 3 everyday states of matter: solid, liquid, gas, ice, water, steam. Carbon dioxide has the same 3 states. Frozen, it's the dry ice that fogs up a concert stage. As a gas, it's the invisible thing you exhale. But there's a 4th condition, and it's the key to this whole story. If you take carbon dioxide and crush it under enormous pressure while also heating it past a certain temperature, something bizarre happens. It stops being clearly a gas and stops being clearly a liquid. It enters a hybrid state that scientists call supercritical. In this state, the CO2 flows freely and fills its container like a gas would, but it's also dense and packed tight, carrying heat the way a liquid does. Think of it as getting the best of both worlds at once. A gas is easy to push around and compress, but it's terrible at holding heat. A liquid is fantastic at holding and moving heat, but it's heavy and hard to pump. Supercritical CO2 behaves like both simultaneously. It moves like a gas and carries heat like a liquid. That combination is exactly what you want in the messenger that carries energy through a power plant. And it gives supercritical CO2 a set of advantages over steam that are honestly difficult to overstate. First, it transfers heat far more efficiently than steam does, which means more of your precious heat energy actually ends up spinning the turbine instead of being lost along the way. Second, and this is the part engineers get genuinely excited about, supercritical CO2 is so dense and energetic that the turbine it spins can be a fraction of the size of a conventional steam turbine for the same power output. We're talking about a turbine you could potentially hold in your arms doing work that would normally require a machine the size of a bus. And third, there's a subtle but enormous efficiency win hiding in the physics. To make steam, you have to boil water, and boiling water requires a huge amount of energy just to force it through that phase change from liquid to vapor. It's a wasteful, energy-hungry step. Turning CO2 into its supercritical state takes far less energy than boiling water into steam. You skip a giant chunk of waste right at the start. Put all of that together and you get a power system that is smaller, more efficient, and able to wring electricity out of heat that older technology would have simply thrown away. Here's the obvious question. If supercritical CO2 is so much better than steam, why has the entire world been boiling water for 2 centuries instead? The answer is that this idea is not new at all. In fact, it's shockingly old. The concept of using a supercritical CO2 cycle to generate power was first seriously explored back in the 1960s. Engineers in Italy and the United States looked at the thermodynamics and realized this approach could, on paper, outperform conventional steam plants. The math worked. The theory was sound. The promise was clear. And then it sat on a shelf for 60 years. Because there was a problem, and it was a brutal one. To make this work, you have to hold carbon dioxide at extreme pressure and extreme temperature, continuously, for years on end, while it surges through your machinery. And the materials available in the 1960s, and for decades afterward, simply could not survive those conditions. The metals would corrode, the seals would fail, the turbine components would degrade under the relentless assault of hot, high-pressure CO2. The fluid that made the system so efficient was also aggressive enough to chew through the equipment meant to contain it. So the idea remained exactly that, an idea. A tantalizing concept that worked beautifully in theory and fell apart the moment you tried to build it and run it for real. For 60 years, supercritical CO2 power was the technology of the future, and it seemed like it always would be. Cracking it required advances in metallurgy, in high-pressure engineering, in turbine design, and in materials that could shrug off conditions that would destroy ordinary steel. It required someone willing to pour money and time into solving a problem the rest of the world had largely given up on. That part of the story should sound familiar if you follow Chinese engineering. It's a pattern we've seen again and again. The project is called Kaitan-1, sometimes referred to as Supercarbon No. 1, and it was developed by the Nuclear Power Institute of China, part of the China National Nuclear Corporation, working alongside industrial partners. It's located inside a working steel plant in Liupan Shui, a city in mountainous Guizhou province in southwest China. And the choice of location is not random. It's central to the whole point. Steelmaking generates staggering amounts of heat. Furnaces run at blistering temperatures, and a huge portion of that thermal energy normally just escapes into the atmosphere as waste. It does no work. It powers nothing. It simply radiates away, lost forever. Every steel plant on Earth is, in a sense, constantly throwing away energy. Kaitan-1 captures that waste heat, the heat that would otherwise have vanished, and feeds it into the supercritical CO2 system. The hot CO2 expands and drives the compact turbine. The turbine spins the generator. Electricity flows out to the grid, and the CO2 cycles back around to grab more heat and do it all again. Nothing is burned. No new emissions are created. The plant is generating genuinely useful electricity out of energy that was previously garbage. The system was built in 2 units, each producing 15 megawatts. The first unit connected to the grid on December 20, 2025, and ran stably for months. Then, on May 30, 2026, engineers brought the second unit online, bringing the total installed capacity to 30 megawatts. With both units running, China National Nuclear Corporation declared it the world's first full-scale commercial demonstration of supercritical CO2 waste heat power generation, and the largest and most advanced project of its kind anywhere on the planet. And here is where that efficiency figure comes back. According to the teams behind it, the system is roughly 50% more efficient at capturing and converting waste heat from steel production than the steam-based technology that would traditionally do this job. 50% more electricity from the same wasted heat with smaller equipment. Now you'll have noticed this was built by China's nuclear corporation at a steel plant, and you might be wondering where exactly the nuclear angle fits. This is where the story gets genuinely forward-looking. The waste heat steel plant is the proving ground. It's the place to demonstrate that supercritical CO2 power works reliably in the real world, in a commercial setting, day after day. But the steel plant isn't the ultimate target. The reason the Nuclear Power Institute developed this technology is that the same supercritical CO2 cycle could one day replace the steam systems inside nuclear reactors themselves. Think about what that would mean. Today's nuclear plants use their reactor heat to boil water and make steam, just like a coal plant does. They just generate the heat in a cleaner way. If you swapped that steam system for a supercritical CO2 system, a nuclear plant could become significantly more efficient and dramatically more compact. The enormous turbine halls that define conventional nuclear stations could shrink. The whole plant could get smaller, cheaper, and more powerful per square meter. And it doesn't stop at large reactors. The engineers behind this project have openly pointed toward a whole family of future uses where compact, efficient power generation matters enormously. Mobile nuclear power sources, reactors small enough to be transported and deployed where they're needed. Concentrated solar power plants, which generate heat from focused sunlight and currently rely on steam. And perhaps most strikingly, space-based power generation, where every kilogram and every cubic meter is precious, and a compact CO2 turbine could be worth its weight in gold. That's the real ambition here. The steel plant is step one. The destination is a fundamentally better way to turn heat into electricity across nuclear power, solar power, mobile generators, and even spacecraft. A 200-year-old bottleneck finally opened. Now, I don't want to oversell this, because part of why you're hopefully here is that I try to give you the real picture rather than pure hype. This is a genuine, significant achievement. The world's first commercial-scale operation of a technology that defeated 60 years of materials problems. That's real, and it deserves recognition. But it's also a demonstration project, and demonstration is not the same as proven at scale. 30 megawatts is meaningful, but it's small in the context of the global power grid. A single large conventional power plant produces dozens of times that. The big open questions now are about durability and cost. Can this equipment survive the relentless assault of high-pressure, high-temperature CO2, not just for months, but for the decades a power plant is expected to operate? Will the maintenance costs stay reasonable? Can it be scaled up and manufactured cheaply enough to compete with the steam technology it's meant to replace? Some energy analysts have raised exactly these concerns, and they're fair ones. A breakthrough that works for a few months in one steel plant still has to prove it can work everywhere, for years, at a price that makes sense. But here's the thing. Every transformative technology starts exactly like this. Small, demonstrated, surrounded by skeptics asking reasonable questions about whether it'll last. The steam turbine itself was once a fragile experiment. The question is never whether the first version is perfect. It's whether the underlying idea is sound, and whether someone is committed to refining it. On both counts, supercritical CO2 looks like the real deal. Step back for a second and consider what this actually represents. Roughly the entire planet's electricity, the power running through the device you're watching this on, is generated by spinning turbines, and the overwhelming majority of those turbines are spun by steam. We have built our entire civilization on top of a 200-year-old method of boiling water. Any improvement to that fundamental process, even a small one, ripples out across literally everything. A technology that's 50% more efficient at recovering waste heat is not a niche curiosity. The world's heavy industries, steel, cement, chemicals, glass, bleed enormous quantities of heat into the atmosphere every single day, heat that represents wasted energy and, indirectly, wasted fuel and extra emissions. If that heat can be efficiently recaptured and turned into electricity, you're getting more power out of the energy you've already spent, without burning anything extra. That's a genuine climate win, even though the system itself isn't pulling carbon from the sky. And if this technology eventually migrates into nuclear reactors, solar plants, and compact mobile power units, the efficiency gains compound across the entire energy landscape. Smaller, cheaper, more powerful generation, everywhere heat needs to become electricity. There's also a bigger pattern worth naming. This is, once again, a case of a technology invented in the West, abandoned as too difficult, and then revived and commercialized by Chinese engineers willing to grind through the hard materials problems that made everyone else give up. The supercritical CO2 cycle was dreamed up in Italian and American labs in the 1960s. The United States has continued researching it, and institutions like the Southwest Research Institute have built their own demonstrators. But it was China that put the first commercial version on the grid. That's becoming a recognizable story in energy and engineering, and it's one worth paying close attention to, regardless of how you feel about it. Here's my honest opinion, for what it's worth. What I find most compelling about this isn't the CO2 angle, even though that's what makes the headline pop. It's the willingness to attack a 200-year-old assumption that nearly everyone else treated as permanent. The entire power industry decided decades ago that steam was simply how you do this, and the supercritical CO2 idea was filed away as too hard. China didn't accept that. They spent more than a decade working the problem until the materials and engineering caught up with the theory. I think the steam plant era is genuinely going to start winding down over the next few decades, and supercritical CO2 is one of the technologies most likely to replace it. Not overnight. The durability and cost questions are real, and the first version will need years of refinement. But the physics is undeniable, and once a better method gets a commercial foothold, the rest of the industry tends to follow whether it wants to or not. The thing that makes me cautious is the same thing that makes every demonstration project uncertain. We won't truly know if this is a revolution or just an impressive experiment until it's run for 10 or 20 years at full scale. But the direction is unmistakable, and the bottleneck that stopped this for 60 years has finally been broken. So here's my question for you. Do you think supercritical CO2 will actually replace steam turbines across the world's power plants in your lifetime? Or do you think steam is too deeply entrenched to ever fully go away? Drop your honest answer in the comments. This is one of those topics where I genuinely want to know which way people are leaning. If you enjoy these deep dives into the engineering breakthroughs quietly reshaping the world, do me a favor and subscribe to Eastern Engine, and tap the notification bell so you don't miss what's next. We break down these stories clearly, without the hype, and there's a lot more coming. Thanks for watching. I'll see you in the next one. For the last 3 years, one company has held the entire world of artificial intelligence in the palm of its hand. Not Google, not OpenAI, not Microsoft. A chip company, NVIDIA. Because every major AI model you've ever heard of, every chatbot, every image generator, every breakthrough that made headlines, was trained and run on NVIDIA's chips. The company became so essential, so unavoidable, that it briefly became the most valuable company on planet Earth. If you wanted to build serious AI, you went through NVIDIA. There was no other door. And it wasn't just the chips. NVIDIA's real fortress was something most people have never heard of. A piece of software called CUDA, the invisible layer that every AI developer on Earth has been building on for over a decade. People in the industry have a name for this trap. They call it the CUDA moat. A castle wall so wide and so deep that even if a rival built a faster chip tomorrow, no one could use it, because the entire world's AI software was written for NVIDIA and NVIDIA alone. That was the situation. That was the lock on the door. And a few weeks ago, a Chinese AI company called DeepSeek did something that was supposed to be nearly impossible. It built a brand new frontier-class AI model that runs from top to bottom without a single piece of NVIDIA software anywhere in its stack. No CUDA. Running instead on chips made by Huawei, a company the United States sanctioned years ago specifically to keep it away from this exact moment. Now, and you know this is coming, there's crucial nuance here, and parts of this story cut against the hype in ways that are genuinely fascinating. I'm going to give you all of it, honestly. But by the end of this video, you'll understand what just happened, why NVIDIA's own CEO publicly admitted he's losing China, why the CUDA moat suddenly looks less like a wall and more like a dam with a crack in it, and why this might be remembered as one of the most important moments in the AI race. Let's get into it. To understand why this is such a big deal, you have to understand how complete NVIDIA's grip really was. And it came down to two things working together. The first is the chips themselves. Training a modern AI model requires a staggering amount of raw mathematical horsepower, and NVIDIA's chips, originally designed to render video game graphics, turned out to be almost perfectly suited to the kind of massively parallel math that AI demands. For years, they were simply the best on Earth at it, by a wide margin. If you wanted to train a serious model, you needed NVIDIA silicon. Full stop. But the chips were only half the fortress. The other half, the part that really locked everyone in, was the software. CUDA is NVIDIA's programming platform, the bridge that lets AI code actually talk to the chips. And here's the thing, the entire global AI community has been building on CUDA for more than a decade. Every framework, every tool, every tutorial, every trick built for CUDA. An entire generation of engineers grew up speaking it. That's the moat. Imagine a country where every road, every gas station, every mechanic, and every driving school was built for exactly one brand of car. Even if a competitor released a better vehicle, who would buy it? You couldn't fuel it, fix it, or find anyone trained to drive it. That's what NVIDIA built. Not just a better car, but the entire road system everyone else was forced to drive on. Switching away wasn't just hard. For most companies, it was unthinkable because it meant abandoning every tool and rebuilding from scratch. So when the United States wanted to slow China's AI progress, the strategy seemed obvious and airtight. Cut China off from NVIDIA's most powerful chips. No advanced NVIDIA silicon, no frontier AI. The leash was the chip, and the lock was the software. And for a while, that logic held, until a cornered company decided the only way out was to build its own road system from scratch. The company at the center of this is DeepSeek, a Chinese AI lab that already shocked the world once. Back in early 2025, when its earlier model launched, it was so unexpectedly capable and so cheap to run that it wiped out hundreds of billions of dollars from NVIDIA's market value in a single day. Investors suddenly panicking that maybe the future of AI wouldn't need quite so many expensive NVIDIA chips after all. Now DeepSeek is back with its new generation, V4, a genuinely frontier-class model, a colossal system with 1.6 trillion parameters, competitive on serious benchmarks with the best models from American labs. On certain coding and reasoning tests, it ranks at or near the very top, trading blows with the flagship models from the biggest names in Western AI. But the benchmarks aren't the real story. The real story is what's underneath. According to multiple reports, V4 is the first DeepSeek model with no NVIDIA CUDA dependency anywhere in its core stack. Instead, it was natively built to run on Huawei's Ascend chips, using Huawei's own software framework, called CNN, as the replacement for CUDA. Think of CNN as Huawei's homegrown version of that road system, its own bridge between AI code and its own chips. And the engineering effort this took is staggering, which is actually why V4 was so delayed. For months, the model kept slipping past its expected release dates, and there was a single reason. Migrating a system this enormous off of CUDA and onto Huawei's completely different software framework, essentially from scratch, is brutally hard. There's even a detail that perfectly captures the difficulty. The team developed its own specialized programming language, called Tilelang, so the model's core operations wouldn't be permanently chained to any one company's chips. Months of delay weren't a failure, they were the price of independence. Here's the detail that drives the point home like nothing else. DeepSeek reportedly gave Huawei weeks of exclusive early access to optimize the model for its chips, a courtesy it pointedly refused to give NVIDIA and AMD. The Chinese company put its own domestic chip maker first and made the American giants wait. A few years ago, that would have been unthinkable. If you want a single piece of evidence for how serious this is, you don't have to take China's word for it. You can take NVIDIA's. NVIDIA's CEO, Jensen Huang, one of the most powerful figures in all of technology, publicly admitted that his company has largely conceded China's advanced AI chip market to Huawei. Let that sink in. The head of the most dominant chip company on Earth, openly acknowledging that in the world's second largest economy, he's handing the field to his Chinese rival. CEOs do not say things like that lightly. That is not spin. That is a man reading the board and admitting he's losing a piece of it. And the market is moving on exactly that belief. Reports indicate that China's three internet giants, Alibaba, ByteDance, and Tencent, have collectively pre-ordered hundreds of thousands of Huawei's new AI chips, positioning themselves to run models like V4 at massive scale. Pre-orders on that scale don't happen on a hunch. They happen when the biggest players in a market have decided which way the wind is blowing. Huawei is now bracing for something like $12 billion in AI chip revenue, with reports that Chinese fabs can barely keep up with demand, while NVIDIA's share of that same market quietly craters. The picture is unmistakable. A model the world's developers actually want to use, running on Chinese chips, bought in enormous volume by China's biggest companies, with NVIDIA's own CEO conceding the territory. The lock on the door didn't just loosen. Someone built an entirely new door. But, and this is where I have to be honest with you, Because the truth here is more interesting than the clean headline. The door isn't quite as wide open as it first appears. Here's the nuance that separates this channel from the breathless headlines. Because there are 3 big caveats, and you deserve every one of them. First, and most important, V4 was still trained mostly on NVIDIA. Building an AI model has 2 phases: training, the immensely expensive process of creating the model's intelligence, and inference, the cheaper process of actually running it for users. The NVIDIA free achievement is strongest on the inference side. For the hardest part, frontier training, Chinese firms, including DeepSeek, have still largely leaned on NVIDIA hardware, because Huawei's chips and software aren't yet reliable enough for that brutal workload. In fact, DeepSeek reportedly couldn't complete a clean training run for an earlier model on Huawei chips even with Huawei's own engineers on site. So cut NVIDIA out completely is true for running the model, but the deepest, hardest layer of AI still has NVIDIA footprint. Second, DeepSeek deliberately kept V4 compatible with NVIDIA too. Buried in the technical details, V4 was validated on both Huawei and NVIDIA platforms. Why? Because if the model only ran on Huawei chips, the global community of developers, who overwhelmingly own NVIDIA hardware, couldn't use it. And an open-source model that nobody outside China can run is just a political statement, not a living technology. So DeepSeek is playing a clever double game. Prove independence is possible, while keeping global compatibility so the model stays relevant everywhere. That's not weakness, it's strategy. But it means the total break is more nuanced than it sounds. Third, Huawei's KNA software still trails NVIDIA's CUDA by a wide margin, by something like an order of magnitude in ecosystem maturity. A decade of global development doesn't get matched in a year. KN works because DeepSeek controls its own full stack and tuned everything by hand. For the average developer worldwide, CUDA is still the default and will be for a long time. So here's the fair summary, the one the hype skips. China has not matched NVIDIA. Huawei has not caught up. KN has not equaled CUDA. What actually happened is subtler and honestly more important than any of those simple claims. For the first time, a frontier-class AI model exists that was built from chip to model, with no American software at its core. Proving the thing everyone said was years away is possible right now. The wall isn't gone, but everyone just watched someone climb over it. So if China hasn't fully caught up, why is this such a big deal? Because of what it starts, not what it finishes. The real significance is something experts call a learning loop, and it's the thing NVIDIA should actually fear. Here's how it works. DeepSeek optimizes its model for Huawei's chips. Huawei gets a serious, real-world, world-class workload to learn from. Its canned software gets battle-tested and improves. Cloud providers gain experience running it. Other Chinese AI labs see it working and start building for Huawei too. And the next model becomes easier to run on Chinese chips than the last one. Round and round, each loop making the domestic alternative a little stronger. That's how an ecosystem is born. Not in one dramatic leap, but through exactly this kind of repeated, workload-driven improvement. NVIDIA's moat was never really just the chips. It was the ecosystem, the decade of everyone building on CUDA. And the only way to challenge an ecosystem is to start a rival one and let it compound. V4 is the starting gun for precisely that. It gives the Chinese stack its first true frontier-class workload to organize around. And the strategic ripple effects are already spreading. Because V4 is open source and dramatically cheaper to run than Western alternatives, reportedly by a huge margin, it becomes attractive far beyond China. Governments and institutions in countries that can't or won't rely on American cloud infrastructure can now run a top-tier AI model entirely on a non-American stack. That's a genuinely new option in the world, and it didn't exist a year ago. Step back and the pattern is the one we keep seeing on this channel. A restriction was designed to lock China out. Instead, it forced China to build the one thing the restriction was meant to prevent: a complete, independent, domestic alternative. The export controls didn't stop the parallel ecosystem. They may have been the very thing that created it. Cut off from the road system everyone else uses, China started paving its own. Here's my honest opinion. I think the two loudest reactions to this are both wrong, and the truth is more interesting than either. The people shouting China just destroyed NVIDIA and won the AI war are flatly ahead of the facts. Frontier training still leans on NVIDIA, KNA still trails CUDA badly, and DeepSeek itself kept NVIDIA compatibility on purpose. Anyone selling you NVIDIA is finished is selling a fantasy. But the people waving this away, it's nothing, they still need NVIDIA, ignore it, are making the bigger mistake, the same one that's been made at every stage of this story. Because they're fixated on the fact that the wall still stands, and missing that someone just proved it can be climbed. The single most important word in this entire story is not chip or model, it's possible. For 3 years, the iron assumption was that you simply could not build frontier AI without the American stack. That assumption is now dead. Not weakened, dead. And once something is proven possible, it almost always gets better, cheaper, and more common from there. What strikes me most is that NVIDIA's own CEO seems to understand this better than the cheerleaders on either side. He didn't dismiss it, he conceded ground. That tells you the person with the most to lose and the best view of the board is taking it seriously. Maybe the rest of us should too. The CUDA moat was the widest, deepest competitive wall in modern technology. It still stands, but for the first time, there's a crack in the dam, and water has a way of finding every crack and slowly, relentlessly making it bigger. So here's my question for you, and I genuinely want your honest answer. Did the chip restrictions backfire? By forcing China to build a complete, independent AI ecosystem it might never have bothered to build otherwise, or were they still worth it, because they've kept China a step behind and burning enormous resources to catch up? Did cutting the cord set China free, or just slow it down? Drop your real take in the comments. I read every single one, and this is exactly the debate I love seeing down there. If you want to keep following this, the breakthroughs, the workarounds, the shifts the rest of the world keeps underestimating until they can't, subscribe to Eastern Engine and hit the notification bell. Chips, AI, computing, the entire foundation of the modern world is being rewritten right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one.
So Apple looking for relief from the chip crunch behind this week's Mac and iPad price hikes. And I'm told by a person briefed on the discussions, that includes asking the administration for more flexibility to work with Chinese memory suppliers. And of course follows CEO Tim Cook telling the Journal just last week that all vendor options are back on the table. Now, the two key names in question are YMTC and CXMT, China's heavily state-backed domestic memory players. YMTC makes NAND flash storage, CXMT makes DRAM, the working memory.
China's largest memory chip maker has reportedly secured a deal worth nearly $3 billion from Tencent, one of the biggest technology companies in the country. Just days after reports said Apple was asking Washington for political clearance to buy memory from the same Chinese supplier, Changshin Memory Technologies, better known as CXMT, has landed what may be the strongest commercial endorsement in its history. The reported agreement covers more than 20 billion yuan, or roughly $2.94 billion, in DRAM chips for Tencent servers over several years. That memory will support cloud computing, databases, and artificial intelligence workloads. CXMT is no longer being treated only as a protected domestic challenger. It is becoming a supplier that major Chinese technology companies may be willing to depend on at enormous scale. If Tencent is prepared to commit billions of dollars to CXMT, could Apple be next? It is a story about how the global memory shortage, the AI infrastructure boom, and political pressure are rewriting the semiconductor supply chain. For decades, the DRAM market has been dominated by three companies. Samsung Electronics, SK Hynix, and Micron control most global production. That concentration gave them enormous influence over pricing, technology, and supply. When demand rises faster than new factories can respond, there are very few alternative suppliers capable of filling the gap. AI data centers are consuming huge amounts of advanced memory. Large models need memory close to processors so data can move quickly enough to keep expensive computing systems busy. Cloud companies also require conventional server DRAM for databases, virtualization, storage systems, and general computing. High bandwidth memory receives most of the attention because it sits beside advanced AI accelerators. And when the biggest technology companies build infrastructure at the same time, demand spreads across the entire market. According to the latest reporting, DRAM contract prices rose roughly 95% quarter over quarter during the first quarter of 2026.
Used in iPhones, PCs, and servers. Both are young companies compared with Samsung, SK Hynix, and Micron, which built their businesses decades ago. But they are gaining share quickly. Counterpoint says YMTC now has 13% of the global NAND market, while CXMT has 8% of DRAM. CXMT also gaining ground fast, preparing for what could be mainland China's largest IPO in years. And Counterpoint is hearing from stakeholders in the supply chain that these Chinese memory names can
Large cloud companies do not want to enter every quarter uncertain about price, availability, or delivery. And in some cases, they are willing to provide prepayments or commit years in advance to secure supply. The reported CXMT agreement may run for 3 years, while another source suggested it could extend as long as 5. That means Tencent is not simply making a spot purchase to cover a temporary shortage. DRAM is one of the most difficult semiconductor businesses to enter. The product may look simple compared with a central processor or graphics chip, but manufacturing it profitably requires extraordinary precision. A memory producer must create billions of microscopic cells that store data reliably. Those cells must work at high speed, consume little power, survive repeated use, and maintain consistency across huge production volumes. That increases cost and makes it difficult to compete with established companies that have spent decades refining their processes. Its early products were aimed mainly at China's domestic market, and many international customers had little reason to take the company seriously. A company does not need to be the global technology leader to become strategically important. It only needs to offer acceptable products, meaningful capacity, and a willingness to sign contracts when other suppliers are constrained. The company reportedly held about 7.7% of the global DRAM market in 2025, making it the 4th largest producer. In a tight market, even a single-digit share can influence prices and customer negotiations. It currently operates major 12-inch DRAM fabrication plants in Hefei and Beijing, with combined output estimated at around 300,000 wafers per month. New facilities and additional expansion could eventually double that figure to approximately 600,000 wafers per month. The company is also developing operations in Shanghai, including DRAM production and high-bandwidth memory packaging. But Tencent's reported commitment gives CXMT something extremely valuable: demand visibility. It can help a manufacturer plan equipment purchases, staffing, material supply, and future process development. CXMT received approval in May for an initial public offering on Shanghai's Star Market. The company reportedly aims to raise 29.5 billion yuan. Investors want proof that growth is not based only on policy support or optimistic forecasts, and they want evidence that the company's products are important enough for large buyers to sign long-term commitments. Major Chinese technology companies are trying to reduce their exposure to foreign supply restrictions. Tencent, Alibaba, ByteDance, Lenovo, Xiaomi, and other firms all depend on semiconductors produced or controlled by companies outside mainland China. Export controls have already restricted China's access to advanced AI accelerators and semiconductor manufacturing equipment.
Undercut incumbent suppliers by up to 30% depending on the contract. Now, Apple, it's been here before. 4 years ago, the company explored using YMTC chips in China-sold iPhones, then retreated under pressure from Washington. But the shortage is more severe now, and Apple has a lot less leverage with its traditional suppliers. That's why more tech companies are looking for alternatives. HP and Lenovo are both reportedly pursuing Chinese memory as a way to diversify supply. But this is not a quick swap.
A cloud company cannot expand infrastructure if it cannot secure enough components. So Chinese technology firms have strong reasons to support a domestic supplier, even if that supplier remains behind the global leaders. This does not mean they will accept any product at any price. Large data center operators care about performance, failure rates, power consumption, compatibility, and total operating cost. Server memory must run continuously under heavy workloads. A defective module can create outages, corrupted data, or expensive maintenance. Tencent therefore has to believe that CXMT can meet a meaningful standard. That is why the reported agreement is more important than a symbolic government order. Tencent is not buying memory for a demonstration project. It needs chips for real servers supporting real customers. The contract could therefore become one of the strongest tests of CXMT's manufacturing discipline. Success would generate more than revenue. It would create operational data. Every shipment provides information about defect rates, system compatibility, thermal behavior, and long-term reliability. That feedback can help CXMT improve future products. Higher production volumes also allow engineers to identify recurring process problems and improve yield. Semiconductor manufacturing becomes more competitive through repetition. The more wafers a company processes, the more opportunities it has to learn. This is one reason large customers can accelerate a supplier's development. Tencent may be buying memory because it needs supply today, but the partnership could help create a stronger competitor tomorrow. That is where Samsung, SK Hynix, and Micron should pay attention. CXMT is not about to replace them. The established leaders remain ahead in manufacturing technology, scale, customer trust, and advanced products. They also dominate high-bandwidth memory, which currently delivers some of the strongest margins in the industry. CXMT still faces serious challenges. One reported problem is low yield on next-generation DDR5 products. That matters because DDR5 is increasingly important for modern servers and personal computers. A company can announce impressive specifications, but customers ultimately care about how many reliable chips can be produced at acceptable cost. If yield remains weak, expansion alone will not solve the problem. More factory capacity can simply produce more expensive defective wafers. CXMT must therefore improve technology while expanding volume. That is difficult, but the Tencent deal provides time and money. And if CXMT can use this period of high prices to improve yield, the competitive landscape could change. The memory industry is cyclical. Shortages produce high prices and heavy investment. High prices encourage companies to build more capacity. Eventually, supply catches up. Prices fall. Weak producers then struggle because memory becomes a commodity again. CXMT's challenge is to use the current upcycle to become efficient before the market turns. The company's recent financial performance shows how powerful the upcycle has been. Its first quarter revenue reportedly reached 50.8 billion yuan, an increase of about 700% from a year earlier. It also recorded a net profit of 25 billion yuan after reporting a loss in the previous year. Those numbers are extraordinary, but they should be interpreted carefully. A booming memory market can make almost every producer look stronger. The real test comes when prices normalize. Can CXMT still compete when buyers have more options? Can it maintain margins? Can it continue investing? And can it keep customers when Samsung, SK hynix, and Micron have available capacity again? Tencent's long-term agreement may protect CXMT from some of that uncertainty. Now we come to Apple. Reports say Apple has been lobbying the United States government for clearance to purchase memory chips from CXMT. The request does not mean a contract has been signed. It does not mean CXMT memory is already inside MacBooks or iPads. And it does not mean Apple plans to abandon its current suppliers. Apple still depends on Samsung, SK hynix, and Micron. But the company recently raised prices on several Mac and iPad models after memory and storage costs rose sharply.
Qualifying a new supplier can take months to as long as 2 years with device testing, reliability checks, factory audits, and technical sharing. And it's especially complicated with YMTC. It's been on the Commerce Entity List since 2022, meaning that U.S. companies need approval to share their blueprints and other proprietary details with them.
That makes another supplier extremely attractive. Apple does not need CXMT to replace the market leaders. It only needs CXMT to provide qualified products at meaningful volume. Even a limited supply agreement could strengthen Apple's negotiating position. It could reduce dependence on 3 dominant producers. And it could help Apple avoid even larger price increases if the shortage continues. The Tencent agreement may make CXMT easier for Apple to evaluate. A multi-billion-dollar server contract gives the company commercial credibility. It shows that another major technology buyer is willing to make a long-term commitment. But Apple's standards are different. For laptops and tablets, power consumption is critical. Memory affects battery life, heat, system stability, and product reliability. Apple also demands consistency across millions of devices. A supplier must deliver the same quality from one production batch to the next. It must support product launches, regional demand changes, and strict delivery schedules. So Tencent's approval would not automatically lead to Apple qualification. Server DRAM and low-power mobile memory serve different needs. Apple would still need extensive testing, audits, traceability, and supply guarantees. The political barrier may be even harder. CXMT is included on a Pentagon list of companies alleged to have links to China's military. That listing does not create a simple universal ban on every commercial transaction, but it creates serious political and reputational risk. American lawmakers may argue that allowing Apple to purchase from CXMT would strengthen a strategic Chinese semiconductor producer. They may also warn that Apple could become dependent on a supplier that Washington later restricts. Apple wants confidence before spending months qualifying products and redesigning logistics. A deal that is legal today could become impossible tomorrow. That uncertainty explains why Apple reportedly approached the government before moving forward. The White House has not publicly approved the request. Apple has not announced a supply agreement. And CXMT has not confirmed that it will supply Apple. So the title, Apple may be next, must remain a possibility, not a conclusion. Still, the Tencent deal changes the context. Before this agreement, CXMT could be described as a rising Chinese memory producer, seeking credibility. After a $3 billion commitment, it begins to look like a strategic supplier with major customers, rapid growth, expanding capacity, and access to capital. That does not guarantee Apple will follow, but it makes the possibility more believable. My take is that the most important part of this story is not the dollar amount. It is the speed at which CXMT's position is changing. A global shortage has turned capacity into leverage. AI demand has pushed memory from a commodity component into a strategic resource. Chinese technology companies are locking in domestic supply, and Apple is reportedly considering a supplier that would have seemed politically unrealistic only a short time ago. The old memory market was built around three dominant companies and predictable customer relationships. The new market is becoming more fragmented, more political, and more expensive. Tencent wants supply security. CXMT wants scale and validation. China wants semiconductor independence. Apple wants lower costs and another negotiating option. Washington wants to limit the growth of strategic Chinese technology. Those goals are now colliding inside one of the most basic components in modern computing. A small memory chip has become part of a much larger contest over AI, industrial power, and national security. The Tencent contract may prove that CXMT can serve China's largest technology companies. The Apple decision could determine whether it can cross into the supply chain of one of America's most influential corporations. So what do you think? Should Apple be allowed to buy memory from CXMT if the chips meet its technical standards? Or would that strengthen a Chinese semiconductor company at the expense of long-term American supply chain security? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because CXMT did not just win a $3 billion order. It may have won the credibility needed to compete for something even bigger. For years, the world's fastest supercomputers have followed one dominant formula. Start with powerful central processors. Add enormous numbers of specialized GPU accelerators. Connect everything with an ultra-fast network. Then, use those GPUs to perform the mathematical work that would overwhelm ordinary CPUs. America's El Capitan follows that model. It combines AMD server processors with AMD Instinct MI300A accelerators and delivers more than 1 quintillion calculations every second. It held the official title of the world's fastest publicly ranked supercomputer. Until now, a previously unlisted Chinese machine called Lineshine has entered the official TOP 500 ranking at number 1. Its verified performance is 2.198 exaflops. America's El Capitan recorded 1.809 exaflops. That places the Chinese system approximately 21.5% ahead on the benchmark used to determine the global ranking. But the most surprising part is not simply that China moved into first place. It is how Lineshine got there. The machine reached more than 2 exaflops of sustained double-precision computing without dedicated GPU accelerators. No NVIDIA GPUs. No AMD Instinct accelerators. No Intel data center GPUs. Instead, Lineshine uses millions of custom Chinese CPU cores, a proprietary interconnection network, and a domestic software stack. It is the first publicly ranked supercomputer to sustain more than 2 exaflops using CPUs alone. That does not automatically make it the best AI computer in the world. It does not mean GPUs are suddenly obsolete, and one benchmark can never describe every workload a machine may encounter. But this result is official. China has taken the number 1 position on the TOP 500 for the first time since 2017, and it did so by rejecting the architecture used by almost every other leading exascale machine. What officially number 1 actually means. The top 500 list has ranked the world's most powerful publicly disclosed supercomputers since 1993. It is updated twice each year. To determine the ranking, systems run a benchmark known as High Performance LinPack, or HPL. HPL asks the computer to solve an enormous system of dense linear equations using high-precision, 64-bit floating-point mathematics. This kind of calculation appears in scientific simulation, engineering, and numerical analysis. The benchmark measures how many floating-point operations the machine can sustain each second while solving the problem. A petaflop is 1 quadrillion operations per second. An exaflop is 1 quintillion. Lineshine sustained 2.198 exaflops. Written out, that is roughly 2.198 quintillion floating-point operations every second during the benchmark. The number is not a theoretical marketing figure. Lineshine's theoretical peak is higher, at approximately 2.736 exaflops. But theoretical peak assumes every component operates perfectly. Every cycle is fully utilized and no time is lost to communication, memory access, or software overhead. Real machines never maintain theoretical peak continuously. Lineshine converted slightly more than 80% of its theoretical capability into measured HPL performance. That is one of the most important details in this story. Building millions of processor cores is difficult. Keeping them busy at the same time is much harder. A supercomputer does not become fast merely because it contains many processors. The processors must communicate, share data, synchronize, and divide a single enormous problem without spending most of their time waiting. Lineshine's 80% result suggests that its architecture is not simply large, it is highly coordinated, inside the CPU-only machine. Lineshine is installed at the National Supercomputing Center in Shenzhen. The machine was built by the Shenzhen Cloud Computing Center and is based on a custom platform called Lingkun. At its core is a Chinese processor known as the LX2. Each LX2 contains 304 CPU cores running at 1.55 GHz. The complete system contains 13,789,440 cores. Divide that total by 304, and the architecture appears to use roughly 45,360 of these processors. That is not 45,000 individual desktop computers. These processors are installed in densely packed computing nodes, surrounded by memory, cooling equipment, power distribution systems, and the network required to connect the entire machine. A modern GPU may contain thousands of smaller parallel computing units. Lineshine instead spreads its work across a vast population of general-purpose CPU cores. The individual clock frequency of 1.55 GHz may sound modest compared with a consumer desktop processor that can exceed 5 GHz. But supercomputers are not built to make one core run as fast as possible. They are designed to make millions of cores work together. A higher clock frequency increases power consumption and heat. At this scale, efficiency, parallelism, and communication matter more than winning a single core benchmark. Imagine trying to move a mountain. One extremely strong worker cannot do it. 45,000 organized teams might, but only if every team knows exactly which section to move, where to place it, and when to act. Without coordination, adding more workers can make the project slower. That is why the processor count is only half the story. The hidden weapon is the network. Every processor inside a supercomputer needs data. A calculation performed on one node may depend on a result produced somewhere else. If those results move slowly, the processors sit idle. At exascale, even tiny communication delays become enormous when repeated trillions of times. Lineshine connects its processors using a proprietary Chinese interconnect called Lingqi. The public technical information remains limited, but the benchmark results reveal that this network is doing serious work. HPL involves regular, predictable mathematics, making it easier to divide efficiently than many real scientific applications. However, Lineshine also ranked first on a second benchmark called HPCG. HPCG stands for High Performance Conjugate Gradients. Unlike HPL, it places greater pressure on memory access, communication, and irregular data movement. These are the parts of supercomputing that often prevent theoretical performance from becoming useful performance. Lineshine achieved approximately 22 petaflops on HPCG. El Capitan achieved around 17.4 petaflops. That places Lineshine roughly 26% ahead on this second measurement. This result is important because it weakens the simplest criticism. The machine did not merely win one highly optimized matrix calculation while collapsing on a more communication-intensive workload. It also led the benchmark intended to represent patterns found in real scientific applications more closely. HPCG is still only a benchmark. No single test can reproduce climate modeling, fluid dynamics, molecular simulation, seismic analysis, and every other scientific workload. But finishing first on both HPL and HPCG suggests that Lineshine's interconnect and memory system are not afterthoughts. The architecture appears balanced enough to keep millions of CPU cores supplied with data. Why build a supercomputer without GPUs? The obvious question is why anyone would avoid accelerators. GPUs became dominant in supercomputing for a reason. A CPU is designed to handle a broad range of instructions. It is flexible. It can manage operating systems, complicated decision-making, serial code, and workloads with unpredictable branches. A GPU is narrower but massively parallel. It excels when the same mathematical operation must be applied across enormous arrays of data. Scientific simulations and neural networks are filled with those operations. That is why America's leading machines use accelerators. El Capitan combines AMD EPYC processors with MI300A accelerated processing units. Frontier uses AMD MI250X accelerators. Aurora uses Intel GPU Max accelerators. Europe's Jupiter booster uses NVIDIA Grace Hopper superchips. Against that field, line shine looks almost deliberately unconventional. One possible advantage is programming simplicity. Accelerated systems divide applications between CPUs and GPUs. Developers must decide which code runs where, move data between different memory spaces, and optimize software for specialized hardware. A CPU-heavy machine can provide a more uniform programming environment. The same processor type handles more of the workload. That does not make programming easy, especially across nearly 14 million cores, but it can reduce the architectural divide between a host processor and an accelerator. CPU-based systems may also perform well on workloads that contain complex control logic, irregular memory access, or sections that do not map cleanly onto GPUs. The disadvantage is efficiency. GPUs can perform far more parallel arithmetic per watt on suitable workloads. To compete without them, Lineshine must deploy an enormous number of CPU cores and keep those cores highly utilized. The machine is not proving that accelerators were a mistake. It is proving that accelerator-free exascale computing remains possible when processors, memory, software, and networking are designed as one system. An entirely custom computing stack. Lineshine is not only unusual because it avoids GPUs, its major layers are Chinese developed. The processors are custom LX2 chips. The computing platform is called Ling Kun. The interconnect is Ling Qi. The operating system is Qilin. The benchmark submission also lists a customized compiler and locally adapted mathematical software. This matters because supercomputer performance depends on more than silicon. A powerful processor running poorly optimized code can waste most of its theoretical capability. The compiler must translate software into instructions that exploit the processor's architecture. The mathematical libraries must perform common operations efficiently. The operating system must coordinate resources across thousands of nodes. The communication software must move messages across the network without creating unnecessary delays. When a system achieves 80% of its theoretical peak on HPL, that usually means multiple layers have been optimized together. The hardware team cannot work in isolation. Neither can the software team. The machine behaves less like a collection of separate products and more like one enormous engineered instrument. This full-stack approach may be the real achievement. China did not simply build a processor and insert it into an existing American or European supercomputer design. It submitted a complete domestic platform capable of taking first place on two major rankings. The power bill behind the performance. There is a cost. Lineshine draws approximately 42.2 megawatts while delivering its submitted performance. That is industrial-scale power consumption. At that rate, operating continuously for 24 hours would require more than 1,000 megawatt-hours of electricity. Cooling the hardware adds another major engineering challenge. Every watt entering a processor eventually becomes heat. Thousands of high-density computing nodes must be cooled continuously, because overheating can reduce performance or damage components. Lineshine achieves an energy efficiency of approximately 52.07 gigaflops per watt. El Capitan records around 60.94 gigaflops per watt. That makes the American system roughly 17% more efficient on the reported metric. This is where the accelerator advantage becomes visible. Lineshine wins the raw HPL ranking. El Capitan produces more computation from each watt. Neither result cancels the other. The Chinese system was designed to maximize sustained high-precision CPU performance. The American system combines CPUs and specialized accelerators to improve performance across traditional simulation and mixed precision workloads. Two different architectural philosophies produce different strengths. In an era when electricity and cooling are becoming limits on both supercomputers and AI data centers, energy efficiency cannot be ignored. Winning the performance crown is impressive. Operating the machine economically for years is a separate challenge. The AI benchmark changes the story. This is the most important caveat. Lineshine is officially number 1 on HPL. It is also number 1 on HPCG. But when the benchmark shifts toward lower precision mathematics used heavily in artificial intelligence, the ranking changes. The HPL MXP benchmark measures mixed precision performance. Traditional scientific calculations often use 64-bit precision because tiny errors can accumulate and affect the final result. Many AI workloads can use 32-bit, 16-bit, 8-bit, or even lower precision numbers. Specialized accelerators are extremely fast at these operations. On HPL MXP, Lineshine achieved approximately 7.92 exaflops and ranked 4th. El Capitan achieved 16.7 exaflops and remained number 1. That means El Capitan delivered more than twice Lineshine's mixed precision result. This is why the phrase "world's fastest supercomputer" needs context. Lineshine is the fastest system on the official benchmark used to rank the top 500. That benchmark measures sustained double-precision performance. It does not prove that Lineshine will train the largest AI model faster than El Capitan. It does not prove that it will outperform GPU systems on every application. For AI-style low-precision mathematics, El Capitan's accelerators provide a major advantage. The two machines are like different vehicles. Lineshine is an enormous high-precision freight engine capable of moving a massive scientific workload. El Capitan is a hybrid machine with specialized engines for different terrain. On the official straight-line test, Lineshine wins. On the mixed precision AI test, El Capitan pulls far ahead. Does no GPU mean the return of the CPU? Not exactly. GPUs are not disappearing from supercomputing. In fact, accelerator adoption continues to grow across the TOP 500. AI demand is making specialized low-precision computing more important, not less. Lineshine demonstrates a different point. There is no single correct architecture for every supercomputer. The best design depends on the workload. If a research center prioritizes high-precision scientific simulation, CPU flexibility, and a uniform programming environment, a massive CPU-based design may remain competitive. If the goal is training neural networks or running mixed precision mathematics, specialized accelerators are difficult to beat. Future systems may become even more heterogeneous. They may combine CPUs, GPUs, AI accelerators, photonic processors, and custom chips, assigning each task to the hardware that performs it most efficiently. Lineshine stands out because it moves in the opposite direction. Instead of adding more types of processors, it scales one processor architecture to an extraordinary level. That simplicity at the component level creates extreme complexity at the system level. Nearly 14 million cores must operate as one computer. The fact that they do so efficiently enough to reach 2.198 exaflops is the central engineering story. What will China use it for? The public top 500 entry identifies Lineshine as a research system at the National Supercomputing Center in Shenzhen. Supercomputers at this level can support many categories of scientific work. Possible workloads include weather forecasting, materials discovery, fluid dynamics, engineering simulation, molecular modeling, and large-scale numerical research. However, the precise workload mix and access policies for Lineshine have not been fully disclosed publicly. That lack of detail matters. Benchmark numbers tell us what the machine achieved during controlled tests. They do not tell us how much useful scientific work it completes each week, how easy it is to program, or how reliably it operates under sustained demand. A supercomputer becomes valuable when researchers can use it efficiently. Applications must be rewritten or optimized for the architecture. Scientific teams need access. Storage systems must feed enormous data sets into the machine. The system must remain stable, while millions of components operate simultaneously. China has demonstrated the hardware platform. The next evidence will come from published scientific results produced using it. Why this changes the global supercomputing picture. Before Lineshine entered the ranking, the top positions were dominated by American accelerated systems. El Capitan was first, Frontier was second, Aurora was third. The United States had established a clear lead in publicly ranked exascale computing. Lineshine did not slowly climb from 10th place to 5th and eventually first. It appeared directly at the top. That creates two important changes. First, the official performance lead has moved back to China for the first time since 2017. Second, the machine expands the definition of what an exascale system can look like. The industry had been moving toward the belief that accelerators were practically mandatory at this scale. Lineshine proves that a CPU-only approach can still win the traditional performance crown. Whether that approach becomes widely copied is another question. The power demand is substantial. Its AI performance is weaker than El Capitan's, and the public technical details are not yet deep enough for outside experts to evaluate every design decision. But the result cannot simply be dismissed. Top 500 accepted the submission. The measured numbers place Lineshine first, and its HPCG result strengthens the claim that this is more than a narrowly optimized demonstration. The honest catch. There are four major caveats. First, Lineshine is number one on specific benchmarks, not automatically on every real application. Second, its lack of dedicated, low-precision accelerators limits its advantage in modern AI computing. Third, it consumes more power per unit of reported performance than El Capitan. Fourth, Many architectural details remain proprietary or publicly unexplained. We know the processor core count, clock frequency, system platform, interconnect, operating system, and benchmark results. We know much less about the internal design of the LX2 core, its memory hierarchy, vector capabilities, manufacturing process, packaging, and the exact topology of the Lingqi network. Those details would help explain how China reached this level without GPUs. Until more information or scientific performance results appear, some questions must remain open. But uncertainty around the details does not erase the verified result. Lineshine sustained more than 2 exaflops of high-precision performance and displaced El Capitan from the top of the official list. My take is that the #1 ranking is important, but the architectural divergence is even more important. China did not win by building a slightly larger copy of El Capitan. It chose a different route. America concentrated enormous parallel performance inside advanced accelerators. China distributed the work across nearly 14 million custom CPU cores and built a network powerful enough to keep them synchronized. The American design is more efficient and much stronger on mixed precision AI mathematics. The Chinese design is now faster on the traditional HPL benchmark and also leads HPCG. This is not a simple story of one country possessing better technology in every category. It is a story of 2 systems optimized around different strengths. Lineshine shows what can happen when processor design, networking, software, and system architecture are developed together around one objective. It also shows that mature technologies can still produce surprising results. The CPU was supposed to become a supporting actor in the exascale era. Lineshine put millions of CPUs at the center of the machine and reached #1. The question now is whether this is a one-time engineering achievement or the beginning of a broader CPU-first supercomputing strategy. Will China continue scaling the Lincoln platform? Will future LX processors improve energy efficiency and mixed precision performance? Will Lineshine produce scientific results that justify its enormous size and power demand? And will American laboratories respond with even larger accelerated systems? The supercomputer race has not ended. It has become more interesting because the leading machines are no longer following the same blueprint. So what matters more to you? Should Lineshine be considered the world's most powerful supercomputer because it officially ranks first on HPL and HPCG? Or does El Capitan's stronger efficiency and AI-oriented performance make it the more capable overall machine? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and computing systems changing the global technology industry. Because China did not take the supercomputer crown by copying the dominant design. It took the crown by proving there was another road to exascale. For years, the world's biggest technology race has been about artificial intelligence. Every week, headlines focused on faster chips, more powerful AI models, and trillion-dollar companies competing for dominance. But something much bigger is quietly happening behind the scenes. Artificial intelligence is no longer staying inside computers. It's getting a body, and nowhere is that happening faster than China. While much of the world is still debating whether humanoid robots are decades away, Chinese factories are already preparing to deploy them at an unprecedented scale. Hundreds of robotics companies have emerged almost overnight. Entire industrial zones are being redesigned around automation. Robot manufacturers are slashing prices, improving performance, and producing machines at a speed that has surprised even industry experts. This isn't just another technology trend. It could become one of the biggest industrial shifts since the invention of the assembly line. What's making headlines isn't just the number of robots China is building, it's how quickly the economics are changing. Only a few years ago, humanoid robots cost hundreds of thousands of dollars and were mostly research projects or expensive demonstrations. Today, several Chinese companies are racing to bring prices down to levels that many manufacturers can actually afford, opening the door for much wider adoption over the coming years. And that changes everything. Because once a humanoid robot becomes cheaper than employing a human worker for several years, the conversation stops being about science fiction and starts becoming a business decision. Factories don't ask whether a robot is impressive, they ask whether it saves money. For decades, China built its economy on one simple advantage: an enormous workforce capable of manufacturing almost anything at scale. From smartphones and laptops to household appliances and electric vehicles, millions of workers powered the country's rise into the world's manufacturing giant. But China is facing a challenge that many people outside the country rarely discuss. Its population is aging. Birth rates have fallen dramatically over the past decade, while younger generations are becoming less interested in repetitive factory jobs. At the same time, wages have steadily increased as China's economy developed. Companies now face growing labor costs while also competing against manufacturers in other countries. For Beijing, automation isn't simply about showing off advanced technology. It's becoming an economic necessity. If factories cannot easily hire enough workers in the future, machines will have to fill the gap. That's one reason the Chinese government has identified robotics as a strategic industry. Local governments, research institutes, universities, and private companies have all invested heavily in developing the technologies needed to make humanoid robots commercially viable. The results are beginning to show. Chinese companies now account for a significant share of the global humanoid robotics supply chain. Many key components, including electric actuators, motors, sensors, cameras, batteries, and precision manufacturing systems, are already produced domestically. That gives Chinese manufacturers an advantage similar to what happened in electric vehicles. Once the supply chain becomes local and highly competitive, costs begin falling much faster than many analysts expect. Another reason this industry is accelerating is artificial intelligence itself. Building a robot capable of walking has never been the hardest problem. Teaching that robot to understand its surroundings, recognize objects, follow instructions, and adapt to unexpected situations has always been far more difficult. Modern AI changes that equation. Large language models and vision systems now allow robots to interpret spoken commands, identify tools, navigate unfamiliar environments, and improve through continuous training. Instead of programming every movement individually, developers can increasingly teach robots through demonstrations and massive amounts of data. That dramatically speeds up development. Several Chinese robotics companies are now combining advanced AI models with rapidly improving hardware, creating humanoid robots that can perform increasingly complex tasks inside real factories, not just carefully controlled laboratories. And that's why investors, manufacturers, and governments around the world are paying close attention. Because this race is no longer about building the smartest chatbot. It's about building millions of physical workers that never get tired, don't require breaks, and can potentially operate around the clock. If that vision becomes reality, the impact won't be limited to China. It could reshape global manufacturing, supply chains, labor markets, and the competitive balance between the world's largest economies. And the companies leading this transformation may not be the names most people expect. To understand why China has become the center of the humanoid robot revolution, you have to look beyond the robots themselves. The real story begins with manufacturing. For more than 20 years, China has built the world's largest industrial ecosystem. Nearly every major product, from smartphones and batteries to electric vehicles and consumer electronics, depends on factories that either operate inside China or rely heavily on Chinese suppliers. Over time, that manufacturing base created something incredibly valuable: an unmatched supply chain. A humanoid robot may look futuristic, but underneath the sleek exterior, it's built from components that China already manufactures in enormous quantities: electric motors, gearboxes, lithium batteries, high-resolution cameras, LiDAR sensors, AI processors, precision machined metal parts, advanced wiring. Every year, Chinese factories produce millions of these components for other industries. That means robotics companies don't have to build an entirely new supply chain from scratch. They can source many parts locally, reducing costs and speeding up production. This is exactly what happened in China's electric vehicle industry. At first, many Western analysts believed Chinese EV companies would remain years behind established automakers. Instead, fierce domestic competition created a massive manufacturing ecosystem where hundreds of suppliers competed to improve quality while driving prices lower. The result was simple: better products, lower costs, faster innovation. Now, many experts believe humanoid robotics is entering a similar phase. Instead of a handful of companies dominating the industry, dozens of Chinese startups are competing aggressively to build better robots faster than their rivals. Every improvement forces competitors to respond, creating a cycle of rapid innovation. One company attracting enormous attention is Unitree Robotics. Originally known for its agile four-legged robot dogs, Unitree has expanded aggressively into humanoid robotics. Videos of its robots walking, running, balancing, dancing, and performing complex movements have spread across social media, giving millions of people their first glimpse of just how quickly the technology is improving. But impressive demonstrations are only part of the story. The real goal isn't making robots dance, it's making robots work. Factories are interested in repetitive tasks that humans often find exhausting, dangerous, or difficult to staff. Moving heavy boxes, transporting materials, sorting components. loading machines, performing inspections, operating around the clock. Unlike industrial robotic arms, which are fixed in one location, humanoid robots can move through environments originally designed for humans. That matters because replacing an entire factory with custom automation is incredibly expensive. Replacing a worker with a robot that can simply walk to the same workstation is often much cheaper. Another rapidly growing player is Agibot, which is focused heavily on combining artificial intelligence with physical robotics. The company's vision extends beyond hardware. It aims to create robots capable of learning new tasks through AI, rather than requiring extensive reprogramming every time the environment changes. This flexibility could become one of the biggest breakthroughs in modern manufacturing. Imagine buying one robot today. Next month, instead of purchasing another specialized machine, you simply download new software that teaches it a completely different job. That's a radically different business model. Software updates become productivity upgrades. The same machine becomes more valuable over time. Chinese companies are also benefiting from another advantage that often goes unnoticed: speed. In many Western countries, scaling advanced manufacturing can take years due to permitting, labor shortages, and fragmented supply chains. China operates differently. When a promising technology emerges, suppliers, manufacturers, universities, investors, and local governments often move simultaneously. New factories are built quickly. Component suppliers expand production. Engineering talent shifts toward growing industries. Entire industrial clusters emerge within a remarkably short period. That ability to scale rapidly has become one of China's biggest competitive strengths, and it's one reason many analysts believe the country could dominate the first generation of commercially successful humanoid robots. Of course, competition isn't standing still. Tesla continues developing Optimus, while companies across the United States, Europe, Japan, and South Korea are investing billions into robotics research. But China's advantage isn't necessarily having the single most advanced prototype. It's having the ability to manufacture thousands, and eventually hundreds of thousands, of robots at prices that competitors may struggle to match. History has shown that manufacturing scale often becomes just as important as technological breakthroughs. The smartphone industry proved it. The solar industry proved it. Electric vehicles proved it. Now many believe humanoid robots could be next. And if that happens, the biggest winners may not simply be the companies building robots. They could be the nations capable of producing them faster, cheaper, and at a scale the rest of the world cannot easily replicate. If all of this sounds familiar, that's because we've seen this pattern before. A new technology appears. Most people dismiss it as expensive, impractical, or years away from widespread adoption. Then costs collapse, production scales, and suddenly, an industry transforms almost overnight. That's exactly what happened with solar panels. It happened with lithium-ion batteries. It happened with electric vehicles. And many experts believe humanoid robots are approaching the same tipping point. The biggest reason is cost. Only a few years ago, a capable humanoid robot could easily cost hundreds of thousands of dollars. At that price, only research labs and large corporations could justify buying one. But today, Chinese robotics companies are racing to reduce costs through mass production, domestic supply chains, and standardized components. As more manufacturers enter the market, competition is accelerating price reductions while improving performance at the same time. For factory owners, that changes the entire equation. Imagine a manufacturing plant that employs hundreds of workers to perform repetitive tasks around the clock. Every employee requires wages, training, insurance, safety measures, vacations, shift scheduling, and replacement when someone leaves. A robot doesn't eliminate every one of those costs, but it changes the economics dramatically. It doesn't call in sick. It doesn't need overtime pay. It doesn't require years of experience before becoming productive. And unlike traditional industrial machinery, a humanoid robot can potentially perform multiple different jobs depending on how it's trained. That's a huge advantage. Instead of buying 5 specialized machines, a factory could eventually deploy one fleet of adaptable robots capable of handling different tasks throughout the day. The return on investment suddenly becomes much easier to justify. This is one reason manufacturers around the world are watching China's robotics industry so closely. Even companies that don't plan to buy Chinese robots immediately know that increased competition usually benefits everyone. Prices fall, capabilities improve, innovation speeds up. At the same time, artificial intelligence is making these machines far more useful than previous generations of industrial robots. Traditional factory automation works best in predictable environments. If every object arrives in exactly the same position every single time, robotic arms can perform incredibly precise tasks. But real factories are rarely perfect. Boxes move, parts shift, tools end up in unexpected places, workers change workflows. Unexpected problems happen every day. Humanoid robots powered by modern AI are being designed to handle those situations much better than earlier machines. Instead of stopping every time something changes, they can increasingly recognize objects, adjust their movements, understand spoken instructions, and adapt to new environments with far less human intervention. That flexibility could become one of the industry's biggest competitive advantages. And China isn't just building robots, it's generating enormous amounts of data to train them. Every successful movement, every failed attempt, every object picked up, every task completed, all of that information can be used to improve future software models. Just like chatbots became smarter by processing billions of words, humanoid robots become more capable by collecting billions of real-world interactions. The more robots operating in factories, the more data they generate. The more data they generate, the smarter future robots become. It's a feedback loop that's incredibly difficult for competitors to ignore. This is also where China's manufacturing scale becomes a strategic advantage. Deploying thousands of robots means collecting millions of hours of operational data far faster than companies with only small pilot programs. That data can improve navigation, dexterity, balance, object recognition, decision-making, and overall reliability. Over time, the gap between companies with massive real-world deployment and those relying mostly on laboratory testing could become increasingly significant. That's why many analysts believe the real competition isn't simply about who builds the best humanoid robot today. It's about who deploys the most robots first, because whoever collects the most operational data may improve the fastest. And if China succeeds in scaling humanoid robots the same way it scaled electric vehicles, batteries, and solar manufacturing, this industry could evolve much faster than many people currently expect. Which brings us to perhaps the biggest question of all. If millions of intelligent robots begin entering factories over the next decade, what happens to the people currently doing those jobs? The idea of humanoid robots replacing people makes for dramatic headlines, but reality will almost certainly be more complicated. History shows that automation rarely eliminates work altogether. Instead, it changes the kind of work people do. When tractors replaced horses, millions of farming jobs disappeared, but entirely new industries emerged. The same happened during the Industrial Revolution, with computers, and later with the internet. Every major technological leap disrupted existing jobs, while creating opportunities that didn't exist before. Humanoid robots are likely to follow a similar pattern. Some repetitive factory positions may gradually disappear, especially where labor shortages already exist. But demand for robot technicians, AI engineers, maintenance specialists, software developers, and manufacturing operators is expected to grow alongside the industry. The transition won't happen overnight. Factories don't replace thousands of workers in a single week. New technology has to prove itself. Companies test small deployments, measure productivity, calculate costs, and only then expand. Even if humanoid robots become significantly cheaper, adoption will take years as businesses evaluate where they actually deliver value. But one thing is becoming increasingly clear. This is no longer a question of if humanoid robots become part of manufacturing. It's a question of who leads the industry. And right now, China has built a formidable lead. The country combines massive manufacturing capacity, one of the world's deepest electronic supply chains, rapidly improving artificial intelligence, and strong investment into robotics. That combination allows companies to move from prototype to production faster than many competitors. At the same time, rivals aren't standing still. Tesla continues developing Optimus with the goal of creating a general-purpose humanoid robot. Companies in Japan and South Korea remain global leaders in industrial automation. European firms continue pushing advanced robotics for specialized applications. The United States is investing heavily in AI software that could eventually power the next generation of intelligent machines. In other words, this isn't a race that's already over. It's a race that's accelerating. And the next few years could determine who builds the operating system for the physical AI era. Because that's what humanoid robots really represent. For decades, AI mostly lived inside screens. Now it's stepping into warehouses, factories, construction sites, hospitals, retail stores, and eventually, perhaps even homes. That shift could become every bit as significant as the arrival of smartphones or the internet itself. The winners won't simply sell robots, they'll build ecosystems of hardware, software, AI models, cloud services, maintenance platforms, and manufacturing networks that reinforce each other over time. China understands that. That's why it's investing across the entire value chain, instead of focusing on a single company. Whether China ultimately dominates the humanoid robot market or faces stronger competition than many expect, one fact is difficult to ignore. The pace of progress has accelerated dramatically. Just a few years ago, humanoid robots were mostly technology demonstrations that struggled to walk across a room. Today, they're lifting boxes, moving materials, operating in factories, and becoming more capable with every new generation of AI. That transformation is happening faster than many analysts predicted, and if costs continue falling while performance continues improving, the conversation may soon shift from whether businesses should adopt humanoid robots to whether they can afford not to. The AI race is no longer confined to data centers and computer chips. It's moving into the physical world. And the country that masters both artificial intelligence and advanced manufacturing could shape the next era of the global economy. The question isn't whether robots are coming. They're already here. The real question is whether the rest of the world can keep up with the speed at which China is turning science fiction into industrial reality. If you enjoyed this deep dive, don't forget to like the video, subscribe to Eastern Engine, and let me know your thoughts in the comments. Are humanoid robots going to create more opportunities than they replace? Or are we witnessing the biggest transformation of the global workforce since the Industrial Revolution? Thanks for watching, and I'll see you in the next one. Artificial intelligence has spent years solving one problem by buying more hardware, more GPUs, more memory, more power, larger data centers, faster networking, and increasingly expensive cooling systems. But Chinese researchers at Peking University say they have demonstrated another path. Instead of making one processor dramatically more powerful, they connected several modest processors with light and redesigned the neural network so every chip could work at the same time. The result was extraordinary. Their hybrid optical system completed a distributed artificial intelligence inference task nearly 149 times faster than a commercial GPU. Even though the combined processors provided only about 1/9 of the GPU's theoretical computing capacity. The system processed 1,000 images in 105.16 microseconds. The GPU needed 15.643 milliseconds for the same workload. The Chinese system was not powered by a magical all-optical processor. It did not train a giant language model, and it did not replace NVIDIA's most advanced accelerator. The computing was still performed electronically on 5 programmable FPGA chips. What changed was the connection between them. Each processor was linked through custom silicon photonic transceivers capable of 400 gigabits per second and a 16 by 16 optical switch that routed information using light instead of conventional electronic switching. That allowed the 5 stages of a neural network to operate like an assembly line. While one chip processed the first layer of a new image, the next chip processed the second layer of an earlier image, and the remaining chips worked on later stages simultaneously. The processors stopped waiting for one another. They stopped repeatedly moving intermediate data into distant memory, and nearly all of their available computing capacity was finally used. The question is not whether China has built a chip that is simply 100 times more powerful than every NVIDIA GPU. It has not. The real question is more important. What happens if the biggest limitation in artificial intelligence is no longer calculation but the time and energy wasted moving data between calculations? Because if light can remove that bottleneck, the future of AI may depend less on purchasing more GPUs and more on connecting the chips we already have far more intelligently. The bottleneck nobody sees. A modern AI accelerator can perform trillions of mathematical operations every second, but raw arithmetic is only one part of the job. Before a processor can calculate, it needs data. It needs model weights, input information, intermediate feature maps, instructions, and results produced by earlier stages. All of that information must move between memory, processors, network devices, and sometimes separate servers. The physical movement of data creates delay. It also consumes energy. A processor may be capable of an enormous theoretical performance, yet achieve only a fraction of that performance if its computing units spend time waiting for information. This is often described as the memory wall or communication wall. The industry's normal response is to build faster memory and wider electrical connections. High bandwidth memory places stacked DRAM beside an accelerator. Advanced packaging shortens the distance between chiplets. NVLink, InfiniBand, Ethernet, and other systems connect processors inside and between servers. These technologies are powerful, but they cannot completely escape the physical limits of electrical signaling. As data rates increase, electrical links lose more energy, generate heat, become harder to route, and require additional circuitry to recover and correct signals. The problem becomes even more difficult when an AI workload is divided among several processors. One processor may finish its assigned calculation and then wait while data travels to the next processor. If every stage operates sequentially, adding more chips may increase theoretical capacity without producing an equivalent increase in real performance. The Peking University team attacked this problem from 3 directions at once. They changed the interconnect, they changed the processing architecture, and they changed how the neural network algorithm was divided across the hardware. That combination is why the result matters. What the researchers built. The experimental system contains 3 main pieces. The first pieces are 5 field programmable gate arrays, commonly called FPGAs. An FPGA is a chip whose internal logic can be reconfigured after manufacturing. Unlike a fixed processor designed for one permanent architecture, an FPGA allows engineers to create custom data paths, processing units, buffers, and interfaces for a specific task. FPGAs are widely used in telecommunications, industrial systems, autonomous vehicles, aerospace equipment, data centers, and hardware prototypes. They are not automatically faster than GPUs. Their advantage is flexibility. Engineers can organize the hardware around one workload instead of forcing that workload through a general architecture. In this experiment, each FPGA handled one layer of a 5-layer convolutional neural network. The second component is a custom silicon photonic transceiver attached to each processing chip. The FPGA produces electrical data. The transceiver converts that data into optical signals, sends it through the network, receives incoming light, and converts it back into electrical form for the next processor. Each transceiver provided a 400 gigabit per second optical input and output interface. The third component is a non-blocking 16 by 16 optical switch. A non-blocking switch can connect available inputs to outputs without forcing one route to interfere with another. The device was manufactured on a silicon planar lightwave circuit platform. It operated around a wavelength of 1,300 nanometers and produced total optical loss of no more than 5 decibels across a broad spectral range. The network transmitted data at 400 gigabits per second, without errors and without optical amplification during the test. Together, these parts formed a reconfigurable optical fabric, capable of connecting as many as 16 processing chips. The researchers used 5 processors for the demonstrated AI workload, but the central switch provides room for a larger system. In theory, 16 400 gigabit links would provide up to 6.4 terabits per second of aggregate switching bandwidth, although the actual system remains limited by the input and output capabilities of the attached processors. How the optical pipeline works. The most important innovation is not simply replacing a copper cable with fiber. The researchers created what they call optical pipeline parallelism. Imagine a factory assembling a product in 5 stages. If one worker completes every stage alone, the next product cannot begin until the previous product is finished. Adding 5 workers does not help if all 5 still wait for the same product and work one after another. A pipeline changes the process. The first worker completes stage 1 and passes the product to the second worker. The first worker immediately begins stage 1 on the next product. Soon, all 5 workers are active simultaneously, each handling a different stage of a different product. After the pipeline fills, completed products emerge continuously. The Chinese system applied this idea to neural network inference. The 5-layer image denoising network was divided across 5 FPGAs. The first FPGA performed the first convolutional encoder stage. Intermediate feature maps moved directly from one FPGA to the next through the optical network. Each processor used local on-chip memory to buffer incoming data and digital signal processing units to execute its assigned convolution. Because each layer remained permanently deployed on its own FPGA, the system did not need to repeatedly load new kernels, store every intermediate result in external memory, and then retrieve that result for the next layer. Once the pipeline was filled, all 5 processors worked concurrently. This is where the enormous latency advantage came from. The optical link provided enough throughput to keep the pipeline moving, while the specialized hardware mapping prevented the processors from becoming idle. The demonstration. The researchers tested the architecture using a 5-layer convolutional neural network trained to remove noise from images in the Fashion MNIST dataset. Fashion MNIST contains simple grayscale images of clothing items. For the experiment, each image had a resolution of 32 by 32 pixels. Every pixel was represented using 32-bit floating point precision, giving 32,768 bits per image. Each network layer used a 5x5 convolutional kernel, followed by a rectified linear unit activation. The feature maps were reduced to 28 by 28 pixels during convolution and then padded back to 32 by 32. The model was trained offline before being deployed onto the FPGAs. That distinction is important. The optical system demonstrated inference, meaning it used an already trained model to process new inputs. It did not perform the much more demanding process of training the model from the beginning. The researchers sent 1,000 images through the completed pipeline in batches of 10. The total measured latency was 105.16 microseconds. The 5 FPGAs used a combined total of 5,040 digital signal processing units running at 390.625 MHz. Their estimated peak FP32 computing rate was about 1.969 teraflops. For the 1,000 image workload, the network required about 196 million floating point operations. Under perfect utilization, the calculation should have taken approximately 99.6 microseconds. The measured result of 105.16 microseconds means the computing hardware achieved 94.7% utilization. That number may be more significant than the headline speedup. The system did not win because it contained more arithmetic power. It won because almost all of its smaller arithmetic capacity remained busy. The GPU comparison. For comparison, the researchers ran the same workload using 32-bit floating point precision on a commercial GPU. The paper describes that GPU as containing 3072 CUDA cores operating at 2.76 GHz, with a theoretical FP32 performance of approximately 16.96 teraflops. On paper, the GPU provided more than 8 times the raw computing capacity of the 5 FPGA system, yet it required 15.643 milliseconds to process the images. That made the optical pipeline nearly 149 times faster while using only 11.6% of the GPU's theoretical computing resources. This sounds impossible until we separate peak performance from workload efficiency. The GPU handled the 5 network layers sequentially. After completing one layer, it stored the intermediate feature map in external memory. It then prepared the weights for the next layer, fetched the stored feature map, and resumed calculation. The GPU's thousands of cores were extremely powerful, but this particular workload was too small and too sequential to keep them fully occupied. Launching operations, moving data, changing layers, and accessing memory consumed far more time than the arithmetic itself. The FPGA system was purpose-built for the network. Every layer had dedicated hardware. Data streamed continuously between those layers. The optical pipeline removed much of the waiting. This is a valid comparison for the demonstrated task, but it is not proof that 5 FPGAs will beat every GPU by 149 times on every AI model. A larger GPU batch, a better optimized implementation, a different network, or a heavier workload could produce a very different result. Modern GPUs are designed to handle enormous parallel workloads, and they become more efficient when enough computation is available to fill their cores. The experiment instead reveals how badly a powerful general processor can perform when communication and scheduling dominate a relatively small latency-sensitive task. Why light changes the equation? Light offers several advantages for chip-to-chip communication. Different wavelengths can travel through the same waveguide or fiber simultaneously. This allows wavelength division multiplexing, where several independent data channels share one physical path. Optical signals can also travel across longer distances with lower loss than extremely high-speed electrical signals. They do not create the same electromagnetic interference, and a passive optical switch does not need to inspect, buffer, schedule, and retransmit every packet like a conventional electronic switch. In the Peking University system, the switch acted as a physical routing fabric. The researchers removed much of the overhead associated with a full Ethernet networking stack. They retained essential encoding and error correction functions, but the optical switch itself performed no packet queuing or buffering. That helped keep latency extremely low. However, the system was not completely optical. The FPGAs still calculated electronically. The transceivers still converted between electricity and light. Memory remained electronic. Control logic remained electronic. The correct description is hybrid optoelectronic computing. Light handled high-speed communication, while electronic processors handled the neural network mathematics. This hybrid approach may be more practical than trying to replace every transistor with a photonic device. Why this matters for AI data centers? The AI industry is currently building larger clusters because individual chips cannot contain the largest models or serve every user alone. Thousands of accelerators must communicate during training and inference. The faster processors become, the more damaging communication delays become. A GPU that finishes its work quickly may simply spend more time waiting for another GPU, memory bank, or network switch. This creates a paradox. Companies purchase more computing power, but a growing portion of that power can be lost to coordination. Optical interconnects could help at several levels. The Peking University demonstration focuses on a tightly coordinated group of processing chips executing a pipeline. It shows that co-designing the algorithm and the interconnect can produce far more useful performance from modest hardware. That idea is especially relevant for inference. Many inference applications care about latency more than total throughput. An autonomous vehicle, industrial robot, medical instrument, communication system, or edge device may need an answer immediately. Waiting several milliseconds can matter. A specialized optical pipeline could process a fixed model with very low delay while using less expensive computing hardware. Large cloud systems could also divide frequently used models into permanent pipeline stages, although real commercial workloads are far more complicated than the demonstrated denoising network. What the headline does not mean, the phrase 100 times faster without more GPUs, is accurate only within the context of this experiment. China has not created a universal processor that makes NVIDIA obsolete. The system did not outperform a current flagship accelerator across large language models, generative video, scientific simulation, and model training. It processed a small 5-layer convolutional network on 1032 by 32 images. The comparison used one commercial GPU with 3072 CUDA cores, not an entire modern AI cluster. The model was already trained. The researchers did not publish a complete commercial power comparison showing that the entire optical system used 1/9 of the energy. They reported 1/9 of the theoretical computing resources. The transceivers, optical switch, FPGA boards, control systems, and supporting equipment still consume power. The system also used 5 separate processing boards to defeat one GPU on a workload specifically mapped to those boards. That does not invalidate the result. It defines what the result actually proves. The experiment proves that communication architecture and algorithm mapping can matter more than peak teraflops for some workloads. It proves that an optical network can transmit 400 gigabit data streams without errors while connecting multiple computing nodes. It proves that a carefully designed pipeline can keep modest processors operating near their theoretical limit. And it proves that buying a larger processor is not always the most efficient answer. The scaling challenge. The researchers acknowledge that the demonstration remains small compared with modern AI workloads. 5x5 convolution kernels and a 5-layer network are not comparable to a large transformer containing billions or trillions of parameters. Scaling the architecture would require more processors, more memory, more optical channels, more sophisticated scheduling, and support for many different computational operations. The current system's remaining bottleneck was not the optical transceiver. It was the input and output capability of the FPGAs. The paper notes that the photonic technology can already support 200 gigabits per second on each wavelength and aggregated transceiver capacities up to 1.6 terabits per second. Future processing chips would need more high-speed channels to exploit that bandwidth. The optical switch can theoretically connect 16 processors, but larger AI systems may require hundreds or thousands of nodes. Engineers would need multi-stage optical networks, fault tolerance, calibration, monitoring, and software capable of placing models across changing hardware. Programmability is another challenge. The demonstrated network benefited from a simple model with clear layers. Real AI services run different models, variable input sizes, dynamic workloads, attention mechanisms, sparse operations, and unpredictable user demand. A fixed pipeline may become inefficient when the workload changes. The system must retain enough flexibility to justify its infrastructure. China's strategic advantage. This research fits China's broader effort to improve computing performance despite restrictions on access to the most advanced foreign AI chips and manufacturing equipment. If the best individual processors are difficult to obtain, connecting available processors more efficiently becomes strategically valuable. An architecture that extracts more real work from modest chips can reduce dependence on brute force scaling. China also has growing capabilities in silicon photonics, optical communications, FPGA development, packaging, and data center infrastructure. Combining those fields could create systems that compete at the architectural level, even when individual chips remain behind the leading edge. But this should not be framed as China defeating NVIDIA overnight. NVIDIA's advantage includes hardware, memory systems, networking, software libraries, developer tools, and a massive installed ecosystem. The company is also investing heavily in optical networking and faster interconnects. The global industry already understands that communication is becoming the next major bottleneck. The race is not between China using light and the West ignoring it. The race is about who can turn photonic interconnects into reliable, programmable, manufacturable systems first. My take is that the 149 times result is real, impressive, and easy to misunderstand. The researchers did not build a processor with 149 times more computing power. They built a system that wasted far less of the computing power it already had. That may be the more important achievement. For decades, performance improvements came primarily from faster transistors, more cores, and larger chips. AI is reaching a stage where moving information can cost more time and energy than calculating with it. When that happens, architecture becomes as important as the processor. The Peking University system demonstrates a different philosophy. Divide the model across specialized chips. Keep each stage permanently ready. Stream data directly from one stage to the next. Use light to prevent communication from slowing the pipeline. And design the algorithm, processors, and network as one machine. The experiment is still far from replacing GPU clusters. Its model is small, its hardware is specialized, its commercial energy advantage remains unproven. Its scaling challenges are serious, but the result exposes a weakness in the current AI race. A system with 16.96 teraflops lost badly to a system with 1.969 teraflops because the stronger machine could not use its strength efficiently. That is the warning. The next breakthrough may not come from a GPU with twice as many cores. It may come from a network that keeps every existing core busy. China has shown that optical pipeline parallelism can deliver that advantage on one carefully chosen task. Now researchers must prove that the same principle can scale to larger models, more processors, dynamic workloads, and real products. If they succeed, AI data centers may stop being collections of isolated superchips connected by increasingly desperate wiring. They may become optical computing fabrics where many modest processors operate like one coordinated machine. So what do you think? Is optical interconnection the missing technology that will unlock the next generation of artificial intelligence? Or is this result too specialized to threaten the GPU-centered data center? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because China did not make one chip 100 times stronger, it showed that connecting chips with light can make a smaller system behave as if it were. Imagine buying a new stick of Corsair Vengeance memory. The black heat spreader looks familiar. The specifications look ordinary. DDR5, 6,000 megatransfers per second. Support for both Intel and AMD platforms. Nothing on the packaging suggests that this particular module represents a major change inside the global semiconductor industry. But then someone opens the software that identifies the components hidden beneath that heat spreader. The manufacturer listed is not Samsung, it is not Micron, and it is not SK Hynix. Instead, the DRAM chips appear to come from Changxin Memory Technologies, better known as CXMT, a Chinese company that, only a few years ago, was barely visible outside the domestic market. That detail may sound small. After all, companies change component suppliers all the time. But memory is not a normal industry. For decades, nearly every modern computer has depended on a remarkably concentrated group of manufacturers. Whether you bought a gaming PC, a workstation, a laptop, or a server, the memory inside was overwhelmingly likely to originate from the same three companies: Samsung, SK Hynix, Micron. Now, Chinese-made DDR5 has apparently appeared inside a product carrying one of the most recognizable names in enthusiast computing. This does not mean China has suddenly defeated the established memory giants. It does not prove that CXMT has better technology, lower prices, or superior reliability. But it does suggest something more subtle, and potentially more disruptive. The door may finally be opening, and once a new supplier enters a market built around only 3 dominant producers, the first thing that changes is not necessarily technology. It is leverage. People love talking about processors. They compare the number of CPU cores, they debate graphics cards, they analyze clock speeds, cooling systems, and benchmark charts containing more colored bars than most human beings should ever be forced to examine. Memory receives far less attention. RAM usually becomes important only when there is not enough of it. Open too many browser tabs, launch a demanding game, edit a large video, or run an artificial intelligence model locally, and suddenly the computer begins hesitating. Data that should remain immediately available has to be moved elsewhere. Applications stutter. Response times stretch. The CPU may be the worker performing calculations, but RAM is the workbench. A faster worker does not help much if the workbench is too small, too slow, or constantly being cleared. Modern DRAM stores information inside billions of microscopic cells. Each cell represents a bit of data by holding a tiny electrical charge. That charge does not remain indefinitely, so the system must refresh it thousands of times every second. Dynamic random access memory. That is what the D in DRAM means. The process sounds straightforward until you remember the scale. A single memory chip must contain billions of these cells, manufacture them with extremely low defect rates, refresh them reliably, and move enormous quantities of information without corrupting the data. One weak cell can become a problem. One unstable timing margin can produce crashes that appear only under certain temperatures. One manufacturing variation can turn a fast chip into a slower one, or into scrap. Making DRAM is not simply printing a large number of identical switches. It is closer to constructing an apartment tower where every room must repeatedly switch its light on and off in perfect coordination, billions of times, while the entire building is moving. And customers expect it to work for years. That difficulty helps explain why the industry became so concentrated. Today, Samsung, SK Hynix, and Micron dominate conventional DRAM production. They did not reach that position because nobody else ever attempted to compete. The history of memory manufacturing is filled with companies that entered confidently, spent enormous sums, suffered through a downturn, and disappeared. DRAM is brutally cyclical. When demand is high, memory prices rise. Manufacturers earn strong profits and expand production. New capacity arrives. Supply increases. Prices fall. Margins collapse. Companies reduce investment or exit the business. Then demand returns. The survivors become stronger. Every cycle acts like an industrial filter, removing manufacturers that lack scale, manufacturing efficiency, or enough cash to survive the bad years. Eventually, only a handful remain. This concentration creates a strange situation. RAM modules are sold under many familiar brands: Corsair, Kingston, G-Skill, Crucial, and others, but the actual silicon beneath the heat spreaders often comes from the same small group of DRAM manufacturers. The module company selects the chips, tests them, places them on a circuit board, programs the operating profiles, adds cooling, and sells the finished product. But the microscopic memory dies themselves are the difficult part. Think of the difference between a bakery and a wheat farm. Many bakeries can package and sell bread under different names, but if almost all of them depend on only 3 farms for wheat, the apparent diversity at the store hides a concentrated foundation. CXMT is attempting to become another farm, and that is why one ordinary-looking Corsair module matters. The module in question appears to be a 16GB Corsair Vengeance DDR5 stick purchased in China. Its reported part number ends with the letters CN, indicating a model intended for the Chinese market. It operates at DDR5 6000 with CL36 timings and a voltage of 1.35 volts. Those numbers are not revolutionary. DDR5 6000 has become a widely used performance point for modern desktop computers. CL36 is respectable, although enthusiasts can purchase lower latency kits. The module is reportedly compatible with both Intel XMP and AMD eExpo memory profiles, allowing systems to apply its rated settings automatically. In other words, this is not an experimental chip sitting beneath laboratory lights. It appears to be ordinary consumer RAM. That may be the most interesting part. Industry changes are not always announced by a dramatic machine, a record-setting benchmark, or an executive standing beneath a giant screen. Sometimes the change is buried beneath a black metal heat spreader, working quietly inside a gaming computer. However, an important qualification is necessary. Corsair has not publicly confirmed the reported CXMT configuration. The evidence comes from photographs and diagnostic information shared online. It appears convincing, and several hardware publications have analyzed it, but it should not be treated as a formal company announcement. That distinction matters. Yet even with that caution, the possibility is significant. A respected international memory brand appears willing to put its name, warranty, and compatibility expectations behind a module using Chinese DRAM. For CXMT, that is more meaningful than another presentation slide. A specification tells people what a company claims it can manufacture. A retail product suggests someone may be willing to depend on it. Changxin Memory Technologies was founded in 2016. That makes it remarkably young compared with the established memory producers. Samsung's semiconductor history stretches back decades. Micron was founded in the late 1970s. SK hynix traces its origins through a long series of companies, factories, and acquisitions. CXMT entered an industry where its future competitors already possessed enormous factories, experienced engineering teams, established customer relationships, and libraries of manufacturing knowledge built through multiple generations of DRAM. It was not entering at the starting line. It was entering while the race was already moving. CXMT initially focused heavily on domestic customers and more mature forms of memory. That was sensible. A new DRAM manufacturer does not immediately begin by challenging the fastest chips available. It must first learn how to manufacture reliably at scale. Yield is everything. Suppose a factory processes a wafer containing hundreds of memory dies. If most of those dies work, the cost of the wafer can be spread across many sellable products. If a large percentage fails, every surviving chip becomes far more expensive. The drawing may be correct. The transistor may function. The first prototype may impress engineers. But until yields rise, the economics remain broken. This is the invisible mountain every new chip producer must climb. CXMT has apparently climbed far enough to offer a broad DDR5 portfolio. The company officially lists memory dies with capacities of 16 gigabits and 24 gigabits, reaching advertised speeds of up to 8,000 megabits per second. It has also displayed multiple kinds of memory modules for desktops, laptops, workstations, and servers. That does not automatically place CXMT beside the leaders. Published specifications are not the same as independent validation, and maximum speed tells only part of the story. But it shows that the company is no longer confined to yesterday's market. The 24 gigabit figure sounds technical, but it creates a practical advantage. 8 bits make 1 byte. Therefore, a 24 gigabit memory die stores 3 gigabytes of data. Place 8 of those dies on a module, and the result is a 24 gigabyte stick of RAM. That enables unusual but increasingly useful configurations. 2 modules can create a 48 gigabyte kit. 4 modules can create 96 gigabytes. For years, desktop memory capacities usually doubled in a predictable pattern: 8, 16, 32, 64, and then 128 gigabytes. 24 gigabit dies fill the large gaps between those levels. A gamer might not need 64 gigabytes, but could benefit from more than 32. A video editor may find 48 gigabytes ideal. A creator running local AI models might want 96 without paying for 128. This is not a cinematic breakthrough. No glowing reactor activates. No computer becomes 1,000 times faster. But semiconductor industries are often transformed by awkward little improvements that make products fit customers more precisely. A 24 gigabyte module is one of those improvements. Chinese brands such as Gloway and Kingbank have already presented DDR5 products using high-density domestic memory. If CXMT can provide these dies consistently, it gains a way to compete that is not based only on being cheaper. It can compete through configuration. That matters because entering an established market with an identical product is difficult. Entering with a slightly different answer to a real customer problem is easier. Why would a company like Corsair consider another supplier now? The answer may begin far away from gaming computers. Inside AI data centers, advanced accelerators depend on high bandwidth memory, or HBM. Unlike conventional desktop RAM, HBM stacks multiple memory dies vertically and places them extremely close to the processor. This architecture can move huge amounts of data while using less space and energy than a collection of ordinary modules. For artificial intelligence, that bandwidth is critical. An AI accelerator without enough memory bandwidth is like a fire engine connected to a garden hose. The processing units may be extraordinarily powerful, but they cannot remain productive if data arrives too slowly. HBM solves part of that problem. It is also extremely valuable. Memory companies can earn far more from advanced data center products than from ordinary consumer DRAM. Naturally, Samsung, SK hynix, and Micron are investing aggressively in HBM and other premium server products. But factories do not possess unlimited capacity. HBM consumes more wafer resources than conventional DDR5. Micron has explained that producing a given amount of HBM can require roughly 3 times the wafer capacity needed for the same quantity of DDR5 bits, with future generations potentially demanding even more. So the AI boom creates a paradox. The world is producing increasingly sophisticated memory, yet ordinary memory can become tighter and more expensive because manufacturing resources are moving toward the premium end of the market. The penthouse is expanding. The ground floor apartments become harder to find. For a new supplier focused on conventional DDR5, that creates an opening. CXMT does not need to outperform the best memory Samsung has ever built. It does not need to lead HBM technology tomorrow. It does not need to win every benchmark. It needs to become good enough, stable enough, and available enough that module manufacturers consider it a practical alternative. That is a very different target. In established technology markets, customers often remain with the same supplier because changing creates risk. New parts require testing. Firmware may need adjustment. Warranty behavior must be understood. Engineers must confirm that the component performs consistently across different systems and temperatures. Even a cheaper alternative may not be attractive if it introduces unpredictable failures. But shortages change the calculation. When the familiar supplier cannot provide enough chips, or when prices rise sharply, the inconvenience of testing a new source begins to look smaller. Scarcity does not merely increase prices, it lowers the walls surrounding the market. This may be the true opportunity for CXMT. The company is arriving at a moment when conventional DRAM customers are actively looking for more supply, while the established manufacturers are chasing the extraordinary economics of artificial intelligence. It is similar to a busy restaurant focusing almost entirely on expensive private events. The regular customers still need dinner. Eventually, another restaurant opens across the street. At first, people may enter only because the usual place is full. Then some discover that the alternative is acceptable. A few may even prefer it. This is where the story requires restraint. A label showing DDR5 6000 does not reveal long-term reliability. It does not tell us how consistently different modules perform. It does not reveal how much overclocking headroom exists, how the chips behave at elevated temperatures, or how efficiently CXMT can manufacture millions of identical dies. Those questions require independent testing. Memory stability can be deceptive. A system may boot normally, run everyday software and appear perfect, then produce an error after several hours under a heavy workload. That is why serious qualification takes time. Manufacturers test voltage margins, temperature ranges, signal integrity, compatibility, retention, and repeated stress cycles. Server customers can be even more demanding, because a small failure rate multiplied across thousands of machines becomes a large operational problem. Corsair's involvement, assuming the module is genuine and production-ready, provides some reassurance. A company selling performance memory has a reputation to protect, but the logo on the heat spreader cannot replace comprehensive testing. At present, the most accurate conclusion is not that CXMT has matched Samsung, Micron, or SK Hynix. It is that CXMT appears to have reached a level where its DDR5 can be considered for a mainstream branded product. That sentence is less dramatic. It is also more important. The immediate threat is not that millions of customers will suddenly reject Korean and American memory. The immediate threat is bargaining power. When only 3 suppliers can provide a critical component, customers have limited options. If one company reduces output, another encounters production problems, and the third prioritizes higher-margin products, buyers must accept the available price. A credible fourth supplier changes those conversations. Corsair does not need to replace every Samsung or Micron chip with CXMT memory. The mere possibility of shifting part of its volume can influence negotiations. This is why new competition can affect a market long before it wins a large share. Imagine 3 taxi companies serving an airport. Prices remain relatively predictable because every traveler must choose one of them. Then a 4th operator arrives with enough cars to handle only 10% of passengers. It has not conquered the airport, but suddenly every existing operator knows customers have another choice. Prices, service, and availability begin to matter more. CXMT could play that role in conventional DRAM, even if its products remain concentrated in China and selected international markets. The additional capacity may reduce pressure on global supply. It may encourage module brands to diversify. It could also force established producers to think carefully before moving too much manufacturing attention away from ordinary consumer memory. Competition does not require a new company to become number one. Sometimes it only requires the company to become impossible to ignore. There is another reason the Corsair appearance matters. Trust moves through layers. Most consumers have never heard of the company that manufactured the individual DRAM dies inside their memory kit. They trust the brand printed on the outside. Corsair performs the testing, creates the product profile, provides support and handles the warranty. If the module works, customers rarely investigate further. That allows a relatively unknown semiconductor supplier to enter the market behind a familiar name. This is how industrial acceptance often spreads. First, a component appears in a limited regional product. Then it enters more models. Another brand qualifies it. A laptop manufacturer tests it. Volumes grow. Engineers collect reliability data. Manufacturing improves. Customers become less nervous. Nothing appears to happen, and then the supplier is suddenly part of the normal ecosystem. The hardest step is often not producing the chip. It is persuading the first major customer to take the risk. That is why one Corsair module can mean more than its sales volume suggests. It creates a reference point. Future customers no longer have to ask, "Has anyone used this?" They can ask, "How did it perform?" That is a much easier conversation. Samsung, Micron, and SK Hynix are not standing still. They operate some of the most advanced semiconductor facilities on Earth. They have deep relationships with server companies, computer manufacturers, and smartphone brands. Their technologies have passed years of qualification across enormous product volumes. They also lead in areas where the greatest value is currently being created. HBM is central to AI acceleration. Low-power memory is critical for mobile devices. Advanced server DRAM must combine capacity, efficiency, reliability, and bandwidth at a scale that leaves little room for error. CXMT's presence in DDR5 6000 does not erase those advantages. There is also a difference between demonstrating an 8,000 megabit per second product and shipping it profitably in massive quantities. Yield, cost, consistency, and delivery schedules decide whether a manufacturer becomes a permanent competitor. The established companies have survived multiple market crashes. They understand how to reduce cost from one generation to the next. They can combine technology leadership with enormous purchasing power and global support networks. CXMT therefore faces two races simultaneously. The first is technical, improving density, speed, efficiency, and reliability. The second is economic, producing enough working chips at a low enough cost to earn money throughout the memory cycle. Winning one race does not guarantee victory in the other. Still, the incumbents should not dismiss CXMT because its current products are behind the frontier. Semiconductor progress is cumulative. Every wafer teaches the manufacturer something. Every defective die reveals where the process failed. Every customer qualification exposes another compatibility issue. Every production increase gives engineers more data. A company can purchase equipment, hire experts, and study designs, but manufacturing intuition emerges only through repetition. The first million chips are not merely products, they are lessons. If CXMT begins supplying more module brands, it gains real-world feedback that cannot be replicated inside a laboratory. More shipments reveal failure patterns. More revenue funds better factories. Better yields reduce cost. Lower cost attracts more customers. The loop begins turning. This does not guarantee that CXMT will catch the leaders. Semiconductor history is full of expensive attempts that never closed the gap. But a supplier inside recognized commercial products has crossed a threshold. It is no longer learning only from prototypes. It is learning from the market. Samsung and Micron do not need to fear the exact chip inside today's Corsair module. They need to monitor what the company manufacturing that chip may learn over the next 5 years. Potentially, but not automatically. More supply usually creates downward pressure on prices, particularly for products that can be substituted easily. If module manufacturers can choose between 4 major DRAM sources instead of 3, competition should improve. However, several conditions must be met. CXMT must produce enough volume to influence the market. Its yields must be competitive. Customers must trust the chips. The company must continue manufacturing during downturns rather than disappearing when prices fall. And the savings must reach consumers. A module company can purchase cheaper chips without reducing the retail price. The difference may simply become additional margin. There is also the possibility that new supply is absorbed immediately by growing demand. AI computers, larger software, high-resolution content, and local machine learning workloads are increasing the amount of memory used across many devices. Yesterday, 16 gigabytes felt generous. Today, 32 gigabytes is becoming ordinary for performance systems. Tomorrow, 48 or 64 may feel normal. So CXMT might not make RAM dramatically cheap. It may instead prevent prices from rising even faster. Consumers rarely notice the disaster that did not occur. But economically, avoiding a shortage can be as valuable as creating a discount. For years, the memory industry has resembled a table with 3 chairs. Samsung occupied one. SK Hynix occupied another. Micron occupied the third. Many companies sold memory modules, but nearly all eventually returned to that same table to obtain the underlying chips. CXMT is now pulling another chair toward the room. It has not been invited to the head of the table. It may not yet be trusted with the most demanding dishes. And nobody knows whether the chair will survive the next severe market downturn. But it is visible. That alone changes the atmosphere. The Corsair module is not proof that the old order has ended. It is evidence that another supplier may have reached the beginning of commercial acceptance. And beginnings are easy to underestimate because they look unimpressive. A single module. A regional model. 6,000 megatransfers per second. No world record. No dramatic reveal. Just a computer component performing the ordinary job it was designed to perform. Yet entire industries are often disrupted not when a new technology performs an impossible trick, but when it becomes boring enough to use. My view is that Samsung, Micron, and SK Hynix do not need to panic, but they absolutely need to pay attention. CXMT is not yet an equal competitor across the entire DRAM market. The established manufacturers remain far ahead in advanced memory, especially the HBM products powering the AI boom. They possess enormous technical, financial, and manufacturing advantages. But the Corsair discovery suggests that CXMT may be crossing from technical capability into commercial credibility. That is the transition that matters. A company can remain irrelevant for years while producing impressive prototypes. The moment trusted brands begin placing its components inside normal products, the equation changes. The biggest threat to the established companies may not be that CXMT builds faster memory next year. It may be that CXMT provides adequate memory at the exact moment traditional suppliers are concentrating on more profitable AI products. The leaders are moving upward. CXMT is filling the space they leave behind. And once a new manufacturer establishes volume, customers, and manufacturing experience in the mainstream market, it can begin climbing toward the premium segments later. That journey will be difficult. It could take years. It may encounter technical setbacks, weak yields, or another brutal memory downturn. But for the first time, the possibility no longer looks theoretical. A Chinese DRAM supplier appears to be hiding beneath a Corsair heat spreader. That is small enough to overlook, and perhaps too important to ignore. So what do you think? Would you buy a Corsair memory kit containing CXMT chips if it offered the same warranty and performance at a noticeably lower price? Or would you stay with memory manufactured by Samsung, Micron, or SK Hynix until Chinese DRAM has built a longer record for reliability? Let me know where you stand in the comments. And if you want to see how China's semiconductor industry is moving from laboratory announcements into real products, supply chains, and computers, subscribe to Eastern Engine. Because the next major shift in technology may not arrive inside a futuristic supercomputer. It may already be sitting inside an ordinary stick of RAM. In 1972, an American astronaut climbed back into his lunar module, took one last look at the gray horizon, and left the moon behind. That was the last time any human stood on the surface of another world, 50-some years ago. And ever since, going back has been something the world's biggest space powers have talked about far more than they've actually done. But here's the thing, almost nobody outside the space world is paying attention to. While America's return to the moon keeps slipping, one delay, then another, China has quietly set a date, 2030, and it is hitting its checkpoints one by one, almost exactly on schedule. So the question is no longer whether humans will walk on the moon again. It's who gets there next, and whose flag is planted when they do. Today, let's look at exactly how close China really is, why NASA is genuinely nervous, and whether the country that's never sent a single person to the moon could actually beat the country that's already done it 6 times. Let's start with what China is actually saying, because it would be easy to wave this off as the kind of grand announcement countries love to make and then never follow through on. China's Manned Space Agency has stated, plainly and repeatedly, that it intends to land astronauts on the moon before the year 2030. And recently, officials doubled down, saying the program is on track and that the hardware is, in their words, progressing smoothly. Now, talk is cheap. Plenty of moon promises have come and gone. What makes this one different is that China has spent the last 2 decades building a track record that's almost boringly reliable. They say they'll do a thing, set a date, and then, more often than not, they do it. Consider what they've already pulled off. They've landed robotic missions on the far side of the moon, the side that always faces away from Earth, which no other country had ever soft landed on. They've scooped up lunar soil and flown it back to Earth. They've built and fully staffed their own space station, orbiting right now with crews rotating in and out. This is not a country fumbling towards space. This is a country that has been methodically climbing a ladder, rung by rung, and the top of that ladder is a human footprint on the moon. So what does it actually take to put people on the moon? 3 big pieces of hardware, and China is building all 3 at once. First, the rocket. It's called the Long March 10, a giant 3-stage heavy-lift rocket designed specifically to throw enough mass toward the moon to make a crewed landing possible. Building a rocket this powerful is one of the hardest things any space program can attempt, and only a handful of nations have ever managed it. To put it in perspective, getting a crew to the moon and back isn't like launching a satellite into orbit a few hundred miles up. You have to push a heavy spacecraft nearly 250,000 miles, slow it down, and then have enough power left to bring everyone home. That demands raw muscle that very few rockets in history have ever had, and China is building theirs from the ground up. What's interesting is the approach they've taken. Rather than inventing something wildly experimental, they've scaled up and refined technology they already trust, clustering proven engines together to generate enormous thrust. It's a conservative, methodical design philosophy. And in spaceflight, conservative and methodical is often exactly what gets you to the finish line in one piece. Flashy doesn't matter on the launch pad. Reliable does. Second, the crew spacecraft. It's named Mengzhou. Think of it as China's version of the capsule that carries astronauts out to the moon and safely back home. It's built in 2 parts, one section that brings the crew back to Earth, and another that provides power, propulsion, and life support along the way. It's designed to carry a crew of around 6, which is notable on its own, because more seats means more capability, more scientists, more equipment, more ambition per mission. And critically, parts of it are being designed to be reusable, which is a sign China is thinking past a single heroic landing and toward a sustained program of going back again and again. This capsule has to do something genuinely difficult too. Coming home from the moon, a spacecraft slams into Earth's atmosphere far faster than anything returning from low orbit. We're talking a fiery, high-speed re-entry that demands a heat shield and a guidance system that simply cannot fail. The fact that China is already flight testing this hardware, rather than just sketching it on paper, tells you how far along they really are. And third, the lander itself, named Lanyue, which translates beautifully to embracing the moon. This is the vehicle that would actually carry astronauts down to the surface and back up to lunar orbit. It's reportedly capable of bringing along a small rover, so the crew wouldn't just plant a flag and leave. They'd actually drive across the surface and explore. Think about what that signals. A flag and footprints mission is a photo op. A mission that brings a rover is the beginning of real exploration, covering ground, studying the terrain, scouting for resources. China isn't designing a quick visit, they're designing a foothold. Here's the part that should make you sit up. China says testing on the lander began back in 2024. The crew capsule is already going through prototype flights, and they've laid out a clear sequence: robotic test flights first, then uncrewed system tests, then a joint test mission near the end of the decade, with the crewed landing a year after that. Every piece has a slot on the calendar. They've even talked publicly about testing the emergency escape systems, the hardware that would yank a crew to safety if a launch went wrong, which is the kind of unglamorous safety-first detail that serious programs obsess over and pretenders skip. It's a staircase, and so far, they're walking up it on time. Now, let's talk about the other side of this race, because you can't understand why people are nervous without it. America's plan to return to the moon is called Artemis. And to be clear, Artemis is real, it's serious, and it has made genuine progress. NASA has flown crews around the moon for the first time in 50 years. The ambition is enormous, not just to visit, but to build a lasting presence. A stepping stone towards sending humans all the way to Mars. But Artemis has one persistent problem: delays. The timeline has slipped again and again. A mission that was once aimed at 1 year got pushed to the next, and then the next. At one point, NASA restructured the program entirely, adding an extra test flight before the actual landing, which pushed the boots on the moon moment even further out. The program has run years behind its original schedule and tens of billions of dollars over budget. And it's worth being fair about why these delays happen, because it's not simple incompetence. Part of it is that NASA holds itself to an extraordinarily high safety bar. These are human lives, and the agency carries the memory of past tragedies. Part of it is that the program depends on a web of contractors and commercial partners, each with their own timelines and technical hurdles. And part of it is politics. Budgets shift, administrations change, priorities get rewritten every few years. America's space program has to survive a gauntlet that China's, run by a single centralized state, simply doesn't face in the same way. But the reasons for the delays don't change the result of the delays. And this is where the math gets uncomfortable. On paper, America is still aiming to land first. NASA's leadership has said publicly they intend to be on the surface before China is. But on paper is doing a lot of work in that sentence. Because every time Artemis slips, the gap between America's target and China's 2030 deadline gets thinner. A program that's ahead but keeps sliding backward is, at some point, just a program that's running out of cushion. It's like watching two runners. One has a head start and far more experience, but that runner keeps stopping to retie their shoes, while the other is running at a steady, relentless pace and never breaks stride. The runner in front is still in front, for now, but anyone watching can feel which way the momentum is flowing. So why does this rattle people in Washington? Why not just shrug and say, we've been to the moon, we'll get there again? Because in this race, second place has consequences that go way beyond bragging rights. Members of the US Congress have openly warned that the country cannot afford to let China reach the moon first. NASA's own leadership has framed this as a great competition with a rival that has both the will and the means to challenge America in space. Those are not casual words. That's the language of a country that has realized it might actually lose something it assumed it owned. And here's the strategic twist that makes this more than a symbolic contest. Both China and America are aiming for the same destination, the moon's south pole. Why there? Because scientists believe those permanently shadowed craters hold water ice. And water on the moon is everything. You can drink it, you can split it into oxygen to breathe, and into hydrogen for rocket fuel. In other words, whoever establishes a foothold at the lunar South Pole first gets first pick of the most valuable real estate off of planet Earth. This isn't about a flag and a photo. It's about who sets the rules for the next era of space, who builds the first base, who controls the best landing sites, who writes the playbook everyone else has to follow. And there's a deeper layer here that's easy to miss. The first moon race, back in the 1960s, was about proving a point. A contest of ideologies between two superpowers settled the moment a boot hit the dust. This new race is different. It's not about a single symbolic moment, it's about staying. Both sides are talking about permanent bases, long-term presence, and using the moon as a launch pad for going even deeper into space, eventually to Mars. The moon, in this version of the story, isn't the finish line. It's the gas station, the outpost, the high ground. There's also a question of leadership that goes beyond the moon itself. Space achievement has always been a kind of global advertisement, a way of telling the rest of the world, look what our system can do. When a country lands humans on another world, it doesn't just win a scientific prize. It wins prestige, influence, and the ability to pull other nations into its orbit, sometimes literally, by inviting partners onto its missions and into its station. China has been openly courting international partners for its lunar ambitions. Every country that signs on with China is a country not signing on with America, and vice versa. The moon, in that sense, has become a stage where a much larger competition plays out. That's why a country that already won the moon race once is suddenly very, very focused on not coming in second the second time around. Now I want to show you the moment that, to me, really captures how serious China is, and most people scrolled right past it. Recently, China launched a fresh crew to its space station. Routine on the surface, but buried in the details was something remarkable. One of those crew members is expected to stay in orbit for roughly a year, the longest single human spaceflight in China's history. Why does that matter for the moon? Because going to the moon and building a presence there means keeping humans healthy in space for long, grueling stretches. Long-duration missions are how you prove your life support systems, your food, your radiation protection, your crew's bodies can take the punishment. Every long stay in orbit is a rehearsal for something bigger. And it's not just the crewed flights. Look at how often China is launching anything into orbit. They went from around 68 orbital launches in 1 year to more than 90 the next, and they're on track for more than 140 in a single year. That's the tempo of a country that has turned spaceflight into something closer to an assembly line, and a fast-moving one. When a space program is launching that often, testing that aggressively, and keeping people in orbit for a year at a time, it tells you something. They're not hoping to reach the moon. They're training for it. Let me zoom out for a second, because I think the single most important thing to understand about China's space program isn't any one rocket or capsule, it's the pattern. For decades, China's approach to space has followed the same quiet rhythm. Announce a clear goal, set a realistic date, build the pieces step by step, and let the results do the talking. No dramatic press conferences promising the impossible. No moonshots in the reckless sense of the word, just a long, patient climb. Look at how the space station came together. They didn't try to build it all at once. They launched a test lab, learned from it, then launched the real modules one at a time, until they had a fully functioning station with crews living aboard. Each step de-risked the next. By the time the hard part arrived, they'd already practiced most of it. The Moon program is following that exact same template. Robotic landings came first, including on the far side, which nobody had ever done. Then sample returns, bringing actual lunar material back to Earth, proving they could get to the Moon, operate on it, and come home. Now they're building the crude hardware, testing it piece by piece, with a joint rehearsal planned before the real thing. It's the same staircase, just taller. And this is what makes the 2030 target so credible. It's not a number someone picked out of the air to grab headlines. It sits at the top of a sequence that's already mostly built, with each lower step already proven. When a country tells you it'll do something in 5 years, the right question is, have they been doing the work for the last 15? In China's case, the answer is yes. That doesn't make success guaranteed, but it does mean this deadline deserves to be taken seriously, far more seriously than the West has tended to take it. All right, the big question, can China really beat America back to the Moon? Let me be honest with you, because that's the whole point of this channel. Nobody knows for certain, and anyone who tells you they're 100% sure is selling something. China still has enormous work ahead. They've never flown a human anywhere near the Moon. Every piece of their lunar hardware, the giant rocket, the deep space capsule, the lander, still has to be tested, flown and proven, all within a few short years. That is a brutal timeline, and spaceflight has a long history of humbling anyone who gets cocky. One serious failure could push everything back. But, and this is the part that's hard to argue with, America's biggest enemy in this race might not be China at all. It might be America's own delays. If NASA holds its current schedule, it likely still lands first. If. And that little word has been the weak point in the Artemis program from the beginning. So here's the real shape of it. America is ahead, but stumbling. China is behind, but sprinting at a steady, disciplined pace. And when you've got one side losing momentum and the other gaining it, the gap doesn't just shrink, it can close all at once. Here's my honest opinion. For whatever it's worth, I don't think this comes down to who has the better engineers, because both sides are extraordinary at what they do. I think it comes down to consistency. China's superpower in this race isn't a magic piece of technology. It's that they pick a date, build the staircase, and climb it without drama. America has more raw capability and more experience, but it keeps tripping over its own budgets, politics, and shifting priorities. And if I'm being straight with you, I think the safe bet is not that China definitely lands first, but that this race is going to be far, far closer than most people in the West assume. The comfortable belief that America obviously wins because it won before, that assumption is exactly what makes a country slow down, and slowing down in a race this tight is the most dangerous thing you can do. Whoever gets there first, one thing is certain, a new era on the Moon is coming this decade. And for the first time since Apollo, it genuinely won't be a one-horse race. So now I want to hear from you. Do you think China actually pulls it off and lands on the Moon by 2030? Or does America's experience win out in the end? And honestly, does it even matter to you who gets there first, as long as humanity goes back? Drop your answer in the comments. I read them. And the best takes sometimes become whole videos of their own. And if you want to keep up with this race, and everything else happening in China's technology, economy, and space programs as it unfolds, hit that subscribe button and ring the bell. This is Eastern Engine, where we break down the forces shaping the future, clearly and without the hype. New videos regularly, so you'll never miss what's coming next. Thanks for watching. I'll see you in the next one. For most of recent history, the Moon was treated like a chapter humanity had already finished writing. During the 1960s and early 1970s, the Apollo program landed 12 astronauts on the lunar surface. They gathered rocks, planted flags, and proved beyond any doubt that human beings could walk on another world. And then, almost abruptly, it stopped. For nearly half a century, the Moon became a place humanity had visited and moved on from, a closed file in the history books. That has changed completely. One country keeps returning. Orbiters, rovers, sample return missions, and now concrete plans to send astronauts. On the surface, it might look like the opening moves of a new space race, but the actual motivation runs far deeper than national competition. China is not simply exploring the Moon, it is preparing to use it. Understanding why requires looking at how the whole effort was designed, because none of this happened by accident or in a hurry. China's return to the Moon was built around a carefully structured long-term plan known as the Chinese Lunar Exploration Program. Rather than rushing to put astronauts on the surface, planners laid out a deliberate, sequential roadmap where each phase would build directly on the success of the one before it. The sequence was clear. First, orbit the moon and study it from above. Second, land robotic explorers on the surface. Third, retrieve samples and return them to Earth. And finally, develop the technologies needed for a lasting human presence. No phase could begin until the previous one had succeeded completely. The first mission launched in 2007, Chang'e-1, named for the moon goddess of Chinese mythology. It became China's first lunar orbiter, spending more than a year mapping the surface and producing detailed three-dimensional images of the terrain. 3 years later, in 2010, Chang'e-2 dramatically improved on that work, capturing high-resolution images that allowed scientists to identify promising landing sites across the lunar surface. These early missions never captured public attention the way crewed landings do, but they accomplished something essential. They produced the most detailed geological maps of the moon that China had ever created, helping researchers pinpoint regions that might contain valuable resources. That groundwork would shape everything that followed. The first true breakthrough arrived in 2013, when China achieved its first successful lunar landing with Chang'e-3. For the first time in nearly 4 decades since the Apollo era ended, an active spacecraft was operating on the lunar surface again. Chang'e-3 carried a small robotic rover named U2, meaning Jade Rabbit. Almost immediately, it began transmitting data that caught scientists off guard. As U2 rolled across the surface, its instruments analyzed the composition of nearby rocks and soil. The results were unexpected. Some of the rocks in the region were basalt, volcanic rock formed from ancient lava flows. But these samples did not match the chemical composition of the rocks scientists had studied from the Apollo missions. They were genuinely different. The mineral arrangements and chemical signatures suggested that parts of the moon had formed through volcanic processes unlike anything previously documented. The implication was significant. The moon's geology was far more varied than researchers had assumed. For decades, almost all human understanding of lunar rock came from a small handful of Apollo landing sites, every one of them located on the near side. Chang'e-3 revealed that those samples represented only a fraction of the full picture. Vast stretches of the moon had never been examined directly, and entire regions could still be hiding completely new types of lunar material. But as surprising as that discovery was, it was only a prelude. A few years later, China set out to attempt something no nation had ever managed. In 2019, China launched a mission that many scientists had long considered nearly impossible. Chang'e-4 became the first spacecraft in history to land on the far side of the moon, the hemisphere that permanently faces away from Earth. Because the moon is tidally locked, we only ever see one side of it from our planet. The far side stays perpetually hidden, and that creates a serious technical obstacle. The moment a spacecraft lands there, it loses direct line-of-sight communication with Earth entirely. China's solution was elegant. Before the landing, they positioned a relay satellite called Kuiqiao into an orbit beyond the moon, where it could maintain contact with both the far side and Earth simultaneously. Signals could then bounce between the lander and ground control through this orbiting intermediary. With that communication link established, Chang'e-4 touched down inside the South Pole Aitken Basin, an enormous impact crater stretching more than 2,500 kilometers across, ranking among the largest known impact structures anywhere in the solar system. Scientists believe this basin may have exposed material from deep within the moon's interior, potentially offering a window into what lies beneath the crust. Then came an even more ambitious milestone. China launched Chang'e-6, designed to do something that had never been accomplished: collect and return samples from the far side of the moon. The mission successfully gathered roughly 2 kilograms of lunar soil and rock and brought it back to Earth. Early analysis indicated some of the volcanic rock had formed around 2.8 billion years ago. That finding mattered because it challenged long-held assumptions about when lunar volcanic activity ceased. It suggested the moon may have remained geologically active far longer than scientists previously believed, meaning its history is more complex and more interesting than the textbooks ever recorded. And yet, despite all of these remarkable achievements, the far side is not the ultimate goal of China's lunar program. The real target lies somewhere else entirely. At first glance, the lunar South Pole appears to be one of the most hostile environments imaginable. Towering peaks surround enormous craters that never receive direct sunlight. Because the moon's axis tilts only slightly, some of these craters have remained in permanent shadow for billions of years. Inside them, temperatures can drop below -200 degrees Celsius. colder than almost anywhere else in the solar system. But those brutal conditions may have produced something extraordinarily valuable. Scientists believe these permanently shadowed craters could hold substantial deposits of frozen water ice. And water on the moon is far more significant than it might initially sound. Water can be broken down into its two fundamental components: oxygen, which astronauts can breathe, and hydrogen, which happens to be one of the most powerful rocket fuels ever developed. If those resources exist in meaningful quantities, the moon transforms from a simple destination into something revolutionary, a refueling station in space. Instead of launching every drop of fuel from Earth's surface, future spacecraft could top up on the moon before continuing deeper into the solar system. That capability would dramatically lower the cost of missions to destinations like Mars. This is precisely why China's upcoming lunar missions are concentrated on the South Pole. But before anyone can use those resources, they first have to confirm the resources are actually there. China's next major step in this search is Chang'e 7, currently planned for launch around 2026. Unlike earlier missions, focused mainly on broad exploration, Chang'e 7 is purpose-built to investigate the moon's most valuable potential resource, water. To do this, the mission will deploy an entire team of robotic explorers working in coordination. An orbiter will circle the moon from above, mapping the region and relaying communications. A lander will set down near the South Pole. A rover will then traverse the rugged terrain, studying the surface and analyzing the chemical composition of the soil. But Chang'e 7 also carries something never before used in lunar exploration: a small robotic hopping probe. Rather than driving across the surface like a conventional rover, this probe can leap directly into deep craters that are permanently cut off from sunlight, the exact places where standard solar-powered machines simply cannot operate. Inside those shadowed regions, the probe will hunt for water molecules, hydrogen signatures, and frozen deposits embedded in the soil. If it succeeds, Chang'e 7 could deliver the first direct, on-site confirmation of water ice in these ancient craters. That single discovery would fundamentally reshape how humanity thinks about the moon, because finding the resources is only the first half of the challenge. The harder part is learning how to actually use them. Launching construction materials from Earth is extraordinarily expensive. Every kilogram delivered to the moon costs a substantial amount in rocket fuel and engineering. So if humans are ever going to live on the lunar surface for extended periods, they will need to construct habitats from materials that already exist on the moon itself. That is the central purpose of Chang'e 8, planned for around 2028. This mission focuses on a set of technologies known as in situ resource utilization, often abbreviated as ISRU, the practice of using local resources rather than importing everything from home. One experiment will attempt to convert lunar soil into building material. Robotic systems may heat and compress the moon's dusty surface layer, known as regolith, into solid blocks that could be used for roads, landing pads, or protective barriers. Other experiments will explore whether oxygen or water can be extracted directly from lunar minerals. Some proposed designs even involve 3D printing structures from lunar soil, allowing robotic systems to build shelters layer by layer. The vision is that autonomous robots could eventually assemble walls, foundations, and protective domes long before any human crew ever arrives. If these technologies prove themselves in the actual lunar environment, they would demonstrate something genuinely transformative: that humanity does not merely have to visit the moon, but could actually build a lasting presence on it. Once those capabilities are proven, the next phase becomes possible. China's robotic missions are laying the foundation. The phase that follows is human. China is now developing the systems required to send astronauts to the moon, with the stated goal of achieving a crewed lunar landing before the end of the decade. At the heart of this effort is a new launch vehicle called the Long March 10, designed to deliver roughly 27,000 kilograms of payload into lunar orbit, enough to support a crewed landing. The mission architecture is carefully structured and requires two separate launches from Earth. The first rocket carries the crewed spacecraft into lunar orbit. The second launch sends up the lunar lander. Once both vehicles reach the moon, they dock together in orbit. Two astronauts then transfer into the lander and descend to the surface. There, the crew would carry out scientific experiments, collect geological samples, and test new technologies designed for long-term operations. These early missions may last only hours or a few days, similar to the brief surface stays of the Apollo era. But these initial landings are not intended to be the endpoint. China is not setting out to recreate Apollo. It is preparing for something considerably larger. Every piece of this effort, the orbiters, the rovers, the sample returns, the resource experiments, and eventually the astronaut landings, points toward a single ambitious goal: a permanent human presence on the moon. China's long-term project is called the International Lunar Research Station, or ILRS. Formally announced in 2021, it represents one of the most ambitious space infrastructure proposals ever put forward. Its planned location is the lunar South Pole, the same region where scientists believe large frozen water deposits may exist. The station will not materialize all at once. The first phase begins with robotic construction missions. Across the early 2030s, China plans a series of landings designed to gradually assemble the infrastructure needed for a base. Somewhere between roughly 2031 and 2035, multiple missions are expected to deliver the components that will form the station's foundation. These early systems could include communication networks, power generation units, and scientific laboratories. Autonomous robots may handle much of the initial construction, operating on the surface long before any human arrives. Additional systems will focus on resource extraction, experimenting with methods to produce oxygen, water, or fuel from the moon's soil and ice. Initially, the station would function as a robotic research outpost, but over time it is designed to support human crews living and working there for extended stretches. China has also invited international partners to take part, positioning the ILRS as a shared global research platform rather than a purely national venture. If the station becomes operational, it could mark something humanity has never achieved before: a genuine, lasting foothold on another world. This is where the modern era of space exploration enters a new phase. If these plans succeed, the moon could become far more than a target for occasional scientific missions. It could become a foundational piece of a future space economy. The moon offers several advantages that make it uniquely valuable. Its gravity is only about 1/6 that of Earth's, which means spacecraft can launch from its surface using far less fuel. If water ice can be extracted and converted into hydrogen and oxygen, the moon could serve as a refueling depot for deep space missions. Rather than launching enormous, fully fueled rockets directly from Earth, future spacecraft might stop at the moon to refuel before continuing toward Mars or the outer solar system. In effect, the moon could function as a launch platform that dramatically reduces the cost of reaching the rest of the solar system. Beyond transportation, the lunar surface offers something rare for science. Observatories placed on the far side would be shielded from Earth's constant radio noise, creating one of the quietest environments in the solar system for studying the universe. Taken together, these possibilities suggest that whoever establishes the first sustainable infrastructure on the moon may gain a meaningful long-term advantage in space exploration. That helps explain why China is investing so heavily in returning, again and again. When you strip everything down, China's repeated return to the moon comes down to three fundamental motivations. The first is scientific discovery. Even after decades of study, the moon still preserves clues about the earliest history of our solar system. Records that may reveal how planets formed billions of years ago, information largely erased on a geologically active Earth. The second is strategic resources. If water ice exists in large quantities near the lunar poles, it could supply the oxygen and rocket fuel needed to power the next era of space exploration, turning the moon into a stepping stone rather than a final stop. And the third is the largest of all: permanent presence. The moon may become humanity's first long-term settlement beyond Earth, a place where science, industry, and exploration converge on another world. If China succeeds in building that foothold, the next great chapter of human civilization might not begin on Earth at all. It might begin 250,000 miles away, on the surface of the moon. Huawei may be building something no other Chinese technology company has ever controlled at this scale. The processor, the memory, the storage, the software, and perhaps even the factories that produce the most important chips inside its devices. And that matters because Apple, despite designing some of the world's most advanced consumer processors, still depends on outside companies for the memory and flash storage inside every iPhone, iPad, and Mac. Huawei appears determined to reduce that kind of dependence as far as possible. The latest reports focus on DRAM, the fast-working memory used by smartphones, computers, servers, vehicles, and nearly every modern electronic system. Huawei has not confirmed that it owns or operates a DRAM manufacturing network. In fact, it has denied claims that it controls a hidden group of semiconductor factories. But analysts, industry publications, corporate connections, and earlier satellite investigations have continued pointing toward a much deeper relationship between Huawei and several Chinese chip companies than official ownership records suggest. One name now receiving major attention is Shueisha, a Shenzhen memory company that has been linked to a planned 12-inch DRAM facility. Reports describe a production target of roughly 140,000 wafers every month, although that figure remains unconfirmed. If the facility reaches anything close to that scale, it would not be a laboratory experiment. It would be industrial capacity designed to supply large volumes of memory for Chinese phones, computers, servers, networking equipment, and other products. That is where this story becomes much bigger than another new semiconductor factory. Huawei already develops its own Kirin processors through HiSilicon. It sells enterprise solid-state drives and storage systems, and it has spent years developing proprietary SSD controllers, storage software, and flash management technology. Huawei also builds phones, computers, networking equipment, cloud infrastructure, vehicle systems, and data center hardware. Adding a reliable domestic source of DRAM could connect those separate pieces into one unusually integrated technology platform. Apple is often described as the master of vertical integration. It designs the iPhone, the operating system, the processor architecture, many supporting chips, and the services surrounding the device. That control creates excellent performance because Apple can optimize hardware and software together. But Apple does not manufacture its own leading-edge processors. TSMC produces them. Apple does not fabricate its own DRAM. Suppliers such as Samsung, SK Hynix, and Micron provide memory. Apple also relies on outside companies for NAND flash and many other essential components. Huawei's ambition appears different. It is not merely trying to design the best phone processor or create a polished operating system. It is trying to build a supply chain that can continue functioning even when foreign governments restrict access to crucial technologies. In that environment, owning more of the stack is not only about performance or profit, it becomes a form of strategic protection. The United States placed Huawei on the Entity List in 2019, sharply limiting its access to American technology. Later export rules also restricted foreign-made chips produced with certain American software or equipment. Those measures disrupted Huawei's smartphone business, weakened its access to advanced processors, and forced the company to search for alternatives across nearly every level of semiconductor development. For several years, many observers believed the restrictions had permanently stopped Huawei's momentum. Its global phone shipments collapsed, Google services disappeared from new international devices, and advanced chip supplies became difficult to secure. Then Huawei returned with new premium smartphones powered by domestically produced Kirin chips. Those processors did not immediately match the most advanced Apple or Qualcomm products, but their existence demonstrated that China's semiconductor network had progressed further than many outside analysts expected. Now the next stage may be memory. This timing is important because memory has become a geopolitical product, not merely a commodity. Washington is debating how Chinese DRAM should be treated, while Beijing is encouraging domestic substitution across strategic supply chains. A Huawei-linked memory project would therefore serve two goals at once: supplying commercial products and insulating critical Chinese hardware from future restrictions imposed unilaterally abroad. A processor receives most of the attention because it performs the calculations and carries the recognizable brand name, but a processor without memory cannot do useful work. DRAM temporarily holds the information that the processor needs immediately. Faster memory can improve responsiveness, multitasking, gaming, professional software, and the efficiency of large computing systems. When memory is scarce, expensive, or restricted, even a powerful processor can become difficult to deploy at scale. Huawei currently has to obtain memory through suppliers and partners, just like most technology companies. China's strongest established DRAM producer is CXMT, which has expanded rapidly and is now at the center of political pressure in Washington. American lawmakers have discussed tighter restrictions on Chinese memory chips, especially as reports suggest major global companies have evaluated Chinese components. That pressure gives Huawei another reason to support an alternative source. If Shueisha can produce usable DRAM in large quantities, Huawei could gain a second domestic pathway. It could potentially shape memory specifications around its own processors, storage systems, phones, servers, and networking products. It could coordinate product development earlier, test components more closely, and reduce the risk that a foreign supplier suddenly becomes unavailable because of sanctions or licensing decisions. However, building DRAM is extremely difficult. Memory chips may look repetitive compared with complex processors, but manufacturing them economically requires enormous precision, strong yields, advanced materials, reliable equipment, and years of process knowledge. A factory can technically produce working chips and still lose money if too many wafers contain defects. Samsung, SK Hynix, and Micron have spent decades improving production and spreading their research costs across huge global businesses. The reported Suisure facility is associated with 28-nanometer DRAM technology. That sounds old when compared with the small node numbers used to market processors, but memory processes cannot be compared directly with logic processes. Mature equipment can still produce valuable memory for industrial devices, networking systems, automobiles, consumer electronics, and many other products. The first objective may not be defeating the latest Samsung memory chip. It may be creating dependable capacity using tools China can obtain, maintain, and eventually replace domestically. This strategy would follow a familiar pattern. Start with products that are possible today. Use domestic demand to keep factories busy. Improve yields through repeated production. Train engineers. Localize more equipment and materials. Then move toward higher density, lower power consumption, and more advanced memory generations. Huawei has the scale to support that process. According to its official 2025 annual report, the company generated 880.9 billion yuan in revenue and invested 192.3 billion yuan in research and development. That means more than 1/5 of annual revenue went back into research. Huawei also reported that approximately 114,000 employees worked in research and development by the end of 2025. Few companies anywhere can sustain that level of engineering investment. The money does not guarantee success, but it changes the odds. A smaller company might abandon a difficult semiconductor project after several years of losses. Huawei can spread the cost across telecommunications, consumer devices, enterprise storage, computing, automotive technology, energy products, and services. It can also become the customer for its own components, giving new factories demand before they are competitive in the open market. That internal demand is one of the biggest advantages of vertical integration. Imagine Huawei developing a new processor for a future phone. If it also influences the DRAM, storage controller, SSD firmware, operating system, and device design, engineers can optimize the entire system instead of waiting for standardized components from unrelated suppliers. They might reduce power consumption, improve data transfer, change packaging, or prioritize features designed specifically for Huawei products. Samsung is the clearest example of this model. Samsung designs processors, manufactures chips, produces DRAM and NAND flash, builds displays, assembles phones, sells appliances, and operates enormous factories. It does not control every component in every product, but its manufacturing depth gives it options that most competitors lack. Huawei appears to be moving toward a Chinese version of that broad industrial structure, although it remains far behind Samsung in advanced memory production and global manufacturing experience. The comparison with Apple is more complicated. Apple's business model does not require owning chip factories. It uses its purchasing power to secure leading production from specialized suppliers, while concentrating its resources on design, software, product integration, and services. That model has been extraordinarily successful. Apple can access TSMC's newest manufacturing without carrying the cost and risk of operating fabrication plants itself. But Apple's model depends on an international supply chain remaining available. Apple can negotiate with suppliers, diversify orders, and reserve enormous amounts of production, but it cannot directly command a memory factory it does not own. Huawei has experienced what happens when political decisions suddenly break those relationships. Therefore, Huawei may accept higher costs and less advanced technology today in exchange for greater control tomorrow. This does not mean Huawei is already independent. It still depends on outside companies, imported equipment, specialized materials, manufacturing partners, and technologies that China has not fully replaced. Even its domestically produced advanced processors have been associated with SMIC rather than factories openly owned by Huawei. Semiconductor manufacturing equipment remains a major weakness because the most advanced lithography, inspection, deposition, and testing systems are concentrated among a small number of foreign suppliers. There are also serious questions about the reported network of 11 fabs. Industry reports have described factories connected to Huawei through employees, financing, customers, technology transfers, or local government support. Yet indirect relationships are not the same as legal ownership or operational control. Huawei denies operating a secret fab network, and public evidence does not allow outsiders to verify every claim. Any responsible interpretation must separate confirmed Huawei products from alleged manufacturing connections. What is confirmed is Huawei's direction. The company openly develops processors, computing systems, enterprise SSDs, storage controllers, networking chips, operating systems, and full hardware platforms. In May 2026, Huawei presented a new semiconductor design strategy built around advanced packaging, architecture, software, and system-level coordination, rather than relying only on smaller transistors. Huawei also said future Kirin chips would use its logic folding architecture to improve performance through greater integration. That approach reveals how Huawei intends to compete while access to the most advanced manufacturing remains limited. Instead of waiting until Chinese factories can copy every part of the global supply chain, Huawei is redesigning products around the capabilities it has. Multiple chiplets can be connected through advanced packaging. Software can schedule workloads more efficiently. Larger systems can combine many processors. Memory, storage, networking, and computation can be coordinated as one platform. DRAM fits naturally into that strategy. Memory bandwidth and latency can become bottlenecks when processors are combined into larger systems. A company that controls the processor architecture but depends entirely on external memory roadmaps has less freedom. A company that can influence both sides can experiment with packaging, interfaces, capacity, and power targets designed around its own products. The same logic applies to storage. Huawei already sells Ocean Disk Enterprise SSDs and Ocean Store all-flash systems. Its public materials describe proprietary SSD controller technology and end-to-end storage development. Yet selling an SSD does not necessarily mean fabricating every NAND memory cell inside it. The strategic goal is not instantly owning every atom of the device. It is steadily gaining control over the most important designs, controllers, software layers, suppliers, and production routes. For China, Huawei's expansion could also support a wider domestic ecosystem. A DRAM facility needs wafer equipment, photoresists, gases, chemicals, masks, testing tools, packaging services, and trained engineers. Even if early chips trail foreign competitors, each production run creates experience for local suppliers. That industrial learning can spill into other companies and make future restrictions less effective. For foreign competitors, the immediate threat may not be Huawei taking global market share with the world's fastest DRAM. The bigger threat is Huawei becoming harder to pressure. Sanctions work most effectively when a target depends on something only outsiders can provide. Every domestic processor, memory chip, controller, production tool, and software platform removes one potential point of leverage. This could reshape competition inside China first. Huawei could favor its own components, direct large orders toward affiliated suppliers, and bundle processors, memory, storage, networking, and software into complete systems. Chinese customers seeking stable domestic supply may accept lower efficiency or higher prices, especially in government, telecommunications, infrastructure, and strategically important industries. Over time, scale could reduce those disadvantages. More orders can finance better equipment. Higher production volumes can improve yields. Larger engineering teams can solve defects faster. Suppliers can justify developing specialized materials. What begins as an expensive sanctions workaround can eventually become a competitive industrial base. Still, the path is not guaranteed. Memory markets are brutally cyclical. Prices can collapse when too much capacity enters the market. Established producers can lower prices, accelerate investment, and use their technological lead to squeeze new competitors. Huawei and Shueisha would need to prove not only that they can manufacture DRAM, but that they can do so reliably, efficiently, and repeatedly across multiple generations. There is another risk: stronger American restrictions. If Washington concludes that Huawei is using related companies to obtain restricted tools or technology, more firms could be added to export blacklists. Shueisha has already faced American scrutiny. Expanded controls could make equipment maintenance, software updates, spare parts, and future factory expansion more difficult. But restrictions can produce two opposite effects. In the short term, they can slow production and raise costs. In the long term, they can convince a large country that dependence itself is unacceptable. Huawei's current semiconductor strategy is a direct result of being cut away from suppliers it once treated as normal business partners. The more pressure increases, the more resources China may direct toward replacing every vulnerable component. That is why the real story is not whether one rumored factory immediately beats Samsung or Micron. The real story is whether Huawei can connect enough domestic capabilities to create a self-reinforcing technology system. Huawei processors generating demand for Chinese fabs, Chinese memory supporting Huawei devices, Huawei storage products creating demand for controllers and NAND, and domestic equipment companies learning from every new production line. Apple's ecosystem is powerful because millions of customers, developers, devices, services, and custom chips reinforce one another. Huawei is attempting to build a different kind of ecosystem, based not only on software and consumer loyalty, but on industrial survival. It wants the device, the operating system, the processor, the networking, the storage, the memory, the packaging, and eventually more of the machinery beneath them. In my opinion, Huawei is still years away from true semiconductor independence, and some claims about its hidden factories may be exaggerated. But dismissing the strategy because its first products are behind would repeat the mistake many observers made before Huawei's smartphone comeback. The company does not need to lead immediately. It needs to keep producing, learning, improving, and removing one dependency at a time. If Huawei eventually controls reliable supplies of CPUs, DRAM, SSD technology, and advanced packaging, America will face a much harder target than the company it sanctioned in 2019. Apple may continue building faster and more profitable devices, but Huawei could possess something increasingly valuable in a divided world: the ability to keep building when outside suppliers are ordered to stop. So what do you think? Is Huawei creating the next Samsung-style semiconductor empire, or will manufacturing limits prevent it from closing the gap with Apple and the world's leading chip makers? Tell us your opinion in the comments. And for more stories about China's processors, memory, storage, manufacturing, and the global technology race, subscribe to the Eastern Engine channel. Here's something that should bother you. Right now, somewhere in the Gobi Desert, a machine is releasing air that was frozen solid last Tuesday, and that release is powering a city through the night. In Shanghai, a factory is pulling carbon dioxide out of the sky, combining it with hydrogen split from seawater, and producing jet fuel molecule for molecule identical to what comes out of an oil well. In Shanxi province, an ammonia plant is running on nothing but nitrogen from the air and sunlight. No natural gas, no extreme heat, no fossil fuels, and it hasn't stopped for 50 days straight. 6 breakthroughs, all running right now. Not in labs, in the real world, on factory floors, with real investors writing real checks. And almost none of it is in the news. That's not an accident. The story underneath all of it is so large and so structurally threatening to how the world currently works that it's easier to report each piece individually as a curiosity than to report them all together as what they actually are: a coordinated dismantling of the energy architecture the entire modern world was built on. This is that story. And by the end, you'll understand why a Chinese oil refinery voluntarily spending 800 million yuan to stop being an oil refinery is actually the most important data point in all of it. The choke point everyone ignores. To understand why these breakthroughs matter, you need to understand what they're solving for. China manufactures more physical goods than any economy on Earth. Pick up a random product in any store in any country. There's a high probability that something inside it, a component, a material, a subassembly, started as energy consumed inside a Chinese factory. That scale of production is staggering, and it has a single, brutal vulnerability almost nobody outside military planning circles talks about. More than 70% of China's oil comes from abroad. That alone is manageable. What isn't manageable is the geography of how it arrives. Almost every drop travels by ship through the Strait of Malacca, a stretch of water between Malaysia and Indonesia that, at its narrowest point, is under 3 kilometers wide. 1 in 4 barrels of oil traded on the entire planet squeezes through that gap. Military strategists have a name for the anxiety this creates: the Malacca dilemma. At its core, it's simple. If that passage gets blocked, by conflict, by political decision, by anything, Chinese factories don't slow down, they stop. Not in weeks, days. China has spent decades trying to route around it. Pipelines through Central Asia, deepwater ports in Pakistan, underground emergency reserves. None of it solves the root problem because the oil still has to cross the ocean first. The pipeline from Pakistan helps until the oil reaching Pakistan is cut off upstream. The only solution that actually works is making the energy locally, from materials that are everywhere, that nobody can blockade. That's what these 6 breakthroughs are. Not energy innovation for its own sake. A systematic, deliberate disassembly of the Malacca dilemma, one technology at a time. Fuel made from nothing. The first piece is almost offensive in its simplicity once you understand it. A facility in Shanghai, opened January 2026, built by a company called Carbonology, is producing jet fuel from carbon dioxide and water. Not biofuel, not almost jet fuel, actual aviation fuel, chemically identical to what refineries pump out of crude oil. A plane engine cannot tell the difference. A pilot cannot tell the difference. The only way you'd know is if someone told you. The process. Machines pull CO2 from the atmosphere. Solar-powered electrolyzers split water into oxygen and hydrogen. The CO2 and hydrogen combine under controlled heat and pressure. The result is a liquid hydrocarbon, the same molecule, built from scratch, from ingredients that exist literally everywhere on Earth. Current output is 100 tons per year, a proof of concept scale. But the roadmap goes 1,000 tons, then 5,000, then a commercial facility targeting 100,000 tons annually by 2027. Sequoia China has already written a check. And here's the detail that tells you this isn't vaporware. European aviation law already mandates a minimum percentage of sustainable fuel in aircraft, growing to a much larger share by 2050. The buyers were legally required to exist before the factories finished building. That almost never happens. It means the market was created by regulation before supply could catch up, the most favorable commercial position possible. This solves the "where does the fuel come from" problem. But fuel requires power to produce, and power has its own problem. The night problem, solved with frozen air. Solar and wind have a flaw so obvious it almost goes unexamined. They stop when conditions change. The sun goes down. The wind dies. Even the largest battery installations in the world typically bridge gaps of 4 to 5 hours. That's enough to cover a residential suburb. It is not enough to run a continuous industrial operation through a cloudy week. In the Gobi Desert, engineers tried something so straightforward it sounds like it shouldn't work. They froze air. Take normal atmospheric air, the mixture you're breathing right now, and cool it to -194 degrees Celsius. At that temperature, it becomes a liquid you can pump into tanks and store like diesel. When you need the energy back, you let the liquid air warm up and expand. It expands 700 times. That expansion spins turbines. The turbines generate electricity. The facility next to a 250 megawatt solar farm uses daytime surplus power, energy that would otherwise be wasted, to freeze air instead. At night, that stored air powers a city for 10 hours, double the duration of the best battery systems available, using no lithium, no cobalt, no rare earth minerals requiring international supply chains, just air and industrial equipment that can be manufactured anywhere. The plant has been running since late 2025, not a prototype. A working facility producing roughly 180 gigawatt hours of energy per year. The night problem is solved. But there's a separate category of machine, ships, heavy industrial equipment, long-haul freight, that can't run on stored electricity. Those need actual fuel, and the answer to that comes from a molecule most people associate with cleaning products. The boring chemical that could end oil shipping. Ammonia, industrial solvent, fertilizer precursor, the smell from a horse stable. Also, the most promising carrier for clean hydrogen that humanity currently has. Here's the problem ammonia solves. Hydrogen is a spectacular clean fuel. Burn it, and the only byproduct is water. But hydrogen is also the lightest element in existence, which means storing and shipping it requires either extreme compression or extreme cooling. Expensive, technically demanding, and logistically difficult at ocean freight scale. You can't casually ship hydrogen across the Pacific the way you ship crude oil. Ammonia solves this by acting as a container. Pack hydrogen into ammonia molecules, ship the ammonia as a liquid at normal industrial temperatures, unpack the hydrogen at the destination. It's a lunchbox for energy that happens to use chemistry instead of plastic. The traditional ammonia production process, Haber-Bosch, invented in 1909, requires massive heat, enormous pressure, and enormous quantities of natural gas. It also feeds roughly half the world's population through fertilizer. Stopping it isn't an option. In Shanxi province, a facility is now making ammonia at room temperature. No natural gas, no extreme pressure, nitrogen pulled from air, hydrogen made from water via solar power, combined without the energy-intensive conditions the century-old process requires. It has operated continuously for over 50 days at more than 90% efficiency. Japan and South Korea are already running ammonia-powered cargo ships on live ocean routes with real freight. If bulk shipping, which moves 90% of everything traded globally, migrates to ammonia, oil's role in maritime fuel doesn't get smaller. It becomes optional. That word, optional, is the one that should give you pause. An optional commodity is a different kind of commodity than a necessary one. The thread connecting all of it. Every technology described so far needs hydrogen. The synthetic jet fuel factory needs hydrogen to build the fuel molecule. The ammonia plant needs hydrogen as its core ingredient. The electrolyzers powering the frozen air facility run on clean electricity. Electricity that's increasingly used to produce hydrogen as an intermediate step. This isn't coincidence. Hydrogen is the connective tissue of the entire system, so the relevant question becomes, how much can one country produce? In 2019, China's clean hydrogen output was roughly 23,000 tons annually. By 2024, it was 125,000 tons, nearly a six-fold increase in 5 years, still accelerating. One province, Guangdong, is building an offshore wind installation specifically to power water-splitting electrolyzers, targeting 80,000 tons of hydrogen per year from a single project. The more significant number, China currently manufactures approximately 65% of the world's electrolyzers, the machines that split water into hydrogen. This is the detail most coverage of this space completely ignores. It doesn't matter how much hydrogen a country wants to produce if it needs to import the machine that makes it. Whoever builds the electrolyzer controls the pace of the entire transition, not just domestically, but for every nation purchasing those machines globally. South American hydrogen programs, African green ammonia plants, European synthetic fuel facilities, they all need electrolyzers. Most of those machines will ship from one country. The end game. Every technology discussed so far still has one constraint. It needs energy input. Solar needs sun, wind needs wind. Even liquid air storage is just shifting energy in time, not creating it. There is one technology that, if it works, removes that constraint permanently. China's East Reactor, experimental advanced superconducting tokamak, set a new world record this year for sustained plasma stability, surpassing what physicists call the Greenwald limit, a threshold in plasma density that defines the boundary of what a controlled fusion reaction can sustain. It held that condition longer than any machine on Earth has managed before. Fusion is not ready to power cities. Anyone claiming otherwise isn't doing analysis. They're selling something. The engineering distance between a record-breaking plasma duration and a grid-connected power plant is still measured in decades of work. But here's the honest framing that most coverage misses. Fusion doesn't need to arrive soon to matter now. The investment patterns around it are themselves a signal. When a country commits serious capital and serious scientific infrastructure to fusion research, it's communicating a planning horizon that most Western governments don't operate on. China is building for 2050 and 2070, the way it built high-speed rail for 2030 in 2005. Fusion is the long bet underneath the short bets. The honest catch: none of this is frictionless. Synthetic fuel at 100 tons per year is not synthetic fuel at 100 million tons per year. Scaling industrial chemistry is not just multiplication. Every increase in volume introduces new engineering problems. Carbonology's 2027 target of 100,000 tons is ambitious. Whether the unit economics stay favorable at that scale is unproven. Green ammonia at room temperature has run for 50 days. 50 days is not 50 years. Long-duration industrial reliability is a different test than initial proof of concept, and the transition from works in a pilot to works in a global supply chain has killed more promising technologies than most people realize. And fusion is still, realistically, not a near-term grid technology. Pouring investment into it now is rational long-term strategy, but it cannot solve an energy security problem in this decade. The honest version of this story is, the foundation is being laid with real materials, real facilities, and real operating data. It is not finished. The gap between this works and this replaced oil is still significant, and the timeline for closing it is uncertain. What isn't uncertain is the direction. My take: here's what I actually think, having looked at all of it together. The pieces aren't individually revolutionary. Synthetic fuel has been a research concept for decades. Liquid air storage has existed in various forms since the 1970s. Ammonia as an energy carrier is well understood chemistry. What's different is that all of these are now simultaneously crossing from laboratory to factory floor, at a moment when one country controls 65% of the critical manufacturing hardware, has declared hydrogen a national infrastructure priority on par with oil and gas, and has a documented track record of taking impossible manufacturing problems and systematically solving them through scale. The more revealing data point isn't any single technology, it's the refinery. One of China's largest oil refining companies posted a profit decline of more than a third in 2025. Not because people used less energy, but because alternatives started competing with it. And its response was to commit 800 million yuan to converting its oil facilities to synthetic fuel production. A company whose entire identity, infrastructure, and business model was built on oil is voluntarily rebuilding itself around something else. Companies don't do that because a trend is interesting. They do it because they've run the numbers and concluded the future is moving, whether they move with it or not. The world that ran on oil didn't announce its own ending. It just slowly started losing ground to something that was cheaper and harder to interrupt. That transition is further along than most people outside this space understand. And the country building the machines that power it, the electrolyzers, the fuel factories, the storage systems, is doing to energy what it already did to solar panels, becoming the supplier the rest of the world depends on, before the rest of the world fully understood what it was depending on. The map used to be power. Whoever sat above the oil field held the leverage. Whoever controlled the strait controlled the flow. If you can make fuel from air and water, the map stops mattering. And one country just got significantly better at making fuel from air and water. My question for you, if energy can genuinely be produced anywhere from ingredients that exist everywhere, who do you think loses the most? Which economy is most exposed when the geography of energy stops being relevant? Drop your honest take in the comments. I read every one. If you want to keep following this, the quiet moves, the overlooked technologies, the shifts that matter before the headlines catch up, subscribe to Eastern Engine and hit the notification bell. This is where the actual story is. Thanks for watching. See you in the next one. Apple launched the MacBook Neo with one promise that instantly changed the conversation around affordable laptops. A real MacBook starting at $599. For students, families, first-time Mac buyers, and people who simply wanted Apple's software without paying MacBook Air prices. That number was the entire story. It made the Neo feel less like another premium Apple product and more like a direct attack on inexpensive Windows laptops and Chromebooks. But only months later, the $599 price has already disappeared. The current model starts higher, and new reports suggest the next version may become more powerful while moving even farther away from the bargain that made it famous. That creates a strange situation. Apple may be preparing a second-generation MacBook Neo with an A19 Pro processor and 12 GB of unified memory, replacing the current A18 Pro chip and 8 GB. On paper, that sounds like exactly the upgrade buyers wanted. 12 GB would give the laptop more breathing room for multitasking, modern applications, web browsers with many tabs, creative software, and future versions of macOS. Yet the same reports warn that Apple could eliminate the cheapest 256 GB storage configuration. If that happens, the Neo may become a better computer while becoming a worse deal for the people it was originally created to reach. To understand why this matters, remember how unusual the first MacBook Neo was. Apple had spent years moving its laptop lineup upward. The MacBook Air became faster, more premium, and more expensive, while the MacBook Pro moved deeper into professional territory. Refurbished and older models filled some of the affordable space, but Apple did not offer a truly new Mac at the price of an ordinary mid-range Windows notebook. The Neo changed that. It arrived with an aluminum body, a sharp 13-inch display, long battery life, macOS, and an Apple-designed processor at a launch price that looked almost un-Apple-like. The compromises were obvious, but they were carefully chosen. The current Neo uses the A18 Pro, a chip originally designed for an iPhone rather than an M-series Mac processor. It has 8 GB of unified memory, a 256 GB base drive, 2 USB-C ports with different speeds, no Thunderbolt, no MagSafe, and a simpler keyboard configuration on the cheapest model. It is not a MacBook Air disguised as something cheaper. It is a separate machine designed around the idea that many buyers do not need professional ports, massive storage, or workstation performance. They need a reliable laptop for school, documents, browsing, streaming, calls, and light creative work. That strategy worked because the price excused the limitations. At $599, 8 GB of memory felt restrictive but understandable. A 256 GB drive felt small but manageable for people who use cloud storage. The absence of premium features could be accepted because Apple was offering a modern Mac experience near the price of plastic Windows machines. Even customers who disliked the compromises had to admit that Apple had created something genuinely different. The Neo was not competing with the best laptops. It was competing for buyers who previously believed a new Mac was automatically outside their budget. Then the economics changed. Apple's United States store now lists the MacBook Neo from $699, a full $100 above its launch price. The 512 GB version sits higher again. That does not automatically make the Neo a bad value, but it changes the psychological appeal. $600 feels like an aggressive budget price. $700 begins to overlap with discounted MacBook Air models, stronger Windows Ultrabooks, and laptops offering more memory or storage. Once the Neo enters that territory, every compromise becomes easier to criticize and every upgrade becomes more important. This is why the reported move to 12 GB matters. Memory is not just a number placed on a specification page. It determines how comfortably a computer can keep applications open, how often data must be moved to slower storage, and how well the machine may age as software grows more demanding. 8 gigabytes can still handle basic tasks, especially on an efficient operating system, but the margin is narrow. A browser, messaging software, a video call, music, cloud syncing, and several background services can consume that space quickly. The computer may remain usable, but it has less room for tomorrow. 12 gigabytes would not transform the Neo into a professional workstation, but it would make the machine easier to recommend. It could reduce memory pressure during everyday multitasking and give buyers more confidence that the laptop will remain comfortable for several years. For students who keep research tabs, documents, presentations, and video calls open together, that difference could be meaningful. For families buying one machine to last through school, the extra memory may matter more than a small processor speed increase. It would address the most common criticism surrounding the current Neo without pushing the product directly into MacBook Air territory. The A19 Pro could also improve the balance. Apple's A-series processors are designed for efficiency, and using an iPhone-class chip allows the company to create a thin, quiet, low-cost laptop without developing a separate entry-level Mac processor. The current A18 Pro already handles everyday computing surprisingly well. A newer A19 Pro should bring performance and efficiency improvements, although the exact Mac configuration remains unconfirmed. The more important point is that the chip and memory are closely connected. If the reported processor arrives with 12 gigabytes, Apple gains an elegant way to upgrade the Neo without redesigning the entire concept. But better hardware costs money, and the industry is dealing with pressure across memory and storage supply. RAM and NAND flash are used in phones, laptops, servers, game consoles, vehicles, and data centers. When demand rises faster than production, manufacturers face higher component costs and tighter availability. Apple has enormous purchasing power, long supplier relationships, and the ability to negotiate at a scale almost no other consumer company can match. Even so, Apple cannot completely escape a market in which important components are becoming more expensive. Apple has already shown that it will adjust prices and configurations when costs move against it. The Neo's launch price has disappeared. Other products have also moved upward or lost cheaper configurations. That gives credibility to the possibility that Apple could remove the 256GB Neo and make 512GB the new starting point. From Apple's perspective, this could simplify production, improve the product's usefulness, and protect margins. From a buyer's perspective, it could erase the last connection to the original promise of a truly inexpensive MacBook. There is an important difference between value and affordability. A 12GB MacBook Neo with 512GB of storage might be a better value than today's base model, especially if the processor is faster and the keyboard gains Touch ID. Buyers would receive more memory, more storage, and potentially better longevity. But if the entry price rises to $799 or beyond, the machine becomes less affordable even if every dollar buys more hardware. Someone with a strict $600 budget cannot benefit from a better value that costs $200 more than they can spend. That is the danger for Apple. The Neo created excitement because it opened the Mac ecosystem to people who had been priced out. If Apple keeps upgrading the product while steadily raising the entry point, it risks turning the Neo into another mid-range laptop, rather than a true gateway Mac. The company already has the MacBook Air for customers who want a stronger display, faster ports, an M-series processor, MagSafe, and a more premium overall package. The Neo only makes sense if enough distance remains between those products. At $599, that distance was obvious. At $699, it is narrower. If the next Neo begins at $799, shoppers will compare it directly with discounted or previous generation MacBook Air models. Retailers frequently reduce older Apple laptops, and those sales can create awkward situations where the more capable Air costs nearly the same as the newer budget machine. Apple may control official pricing, but it cannot fully control the discounts appearing across major retailers. The higher the Neo climbs, the harder it becomes to explain why buyers should not simply wait for an Air deal. Windows competition also becomes more serious at higher prices. Around $600, many laptops use plastic construction, lower quality displays, weaker battery life, or inconsistent trackpads. The Neo's aluminum body, efficient processor, and polished software experience stand out clearly. Around $800, however, buyers can find Windows laptops with 16 gigabytes of memory, 512 gigabytes or more of storage, OLED screens, touch support, faster ports, and wider compatibility with games and specialized software, Apple's ecosystem remains attractive, but the hardware comparison becomes less forgiving. The education market is especially important. Apple has long built loyalty by reaching students early. A low-cost MacBook can introduce a young buyer to macOS, iCloud, Apple services, and the connection between a Mac and an iPhone. That customer may later purchase a more expensive laptop, phone, watch, or subscription. The Neo is therefore more than a low-margin device. It can be an entry point into a much larger relationship. Raising the price may protect profit on each laptop while reducing the number of new customers entering the ecosystem. Schools and parents also think differently from enthusiasts. They often buy based on fixed budgets, durability, battery life, and the expectation that a machine will survive several years. 12 gigabytes of memory and 512 gigabytes of storage would improve longevity, but only if the device remains within budget. A school buying hundreds of units feels every $100 increase. A parent purchasing 2 laptops for children feels it twice. Apple must decide whether the Neo's purpose is to maximize specifications or maximize access. There may be another reason to remove the 256GB version. Storage expectations are changing. Applications, photos, videos, offline media, and system files continue to grow. A 256GB drive can fill quickly, especially when part of its capacity is reserved for the operating system in temporary files. Apple may believe that 512 gigabytes creates a better customer experience and reduces complaints. It also allows the company to present the new model as a meaningful upgrade rather than a simple processor refresh. Still, Apple has used storage tiers strategically for years. Low starting prices attract attention, while many buyers upgrade after seeing the limitations of the base configuration. The cheapest model acts as the headline, even when the next tier is more practical. Removing that entry tier means surrendering a powerful marketing number. The phrase MacBook from $599 reached people who normally ignored Apple laptop announcements. MacBook from $799 sounds far more ordinary, even if the machine behind the number is significantly better. Apple could choose a middle path. It might keep a lower capacity configuration for education, preserve the current model at a reduced price, or offer the new 12GB version above an older 8GB entry model. The company has used previous generation devices to cover lower price points before. That strategy would protect the affordable gateway while allowing the next Neo to become more capable. However, maintaining multiple generations can complicate the lineup and weaken the clean simplicity Apple usually prefers. Another possibility is that Apple absorbs some cost to defend the category. The company earns money not only from hardware but also from services and ecosystem loyalty. A cheaper MacBook can generate future App Store spending, iCloud subscriptions, Apple Music memberships, accessory purchases, and upgrades. Apple may decide that keeping the Neo accessible is strategically more valuable than maximizing immediate margin, but the recent price increase suggests there are limits to how much pressure the company is willing to absorb. Buyers should also remember that the second-generation Neo is still reported, not announced. Apple has not confirmed the A19 Pro, 12 gigabytes of memory, new colors, the removal of 256 gigabytes, or a final price. Product plans can change before launch. Different prototypes may be tested, supply conditions may improve, and Apple may choose a configuration that has not appeared in current reports. The most responsible conclusion is not that a specific price increase is guaranteed. It is that the original $599 idea is already under pressure. That pressure reveals something larger about affordable technology. Companies can launch aggressive products when component prices, supply contracts, and strategic goals align. But maintaining those prices is harder than creating them once. Memory and storage markets move in cycles, currency values change, shipping, manufacturing, and tariffs affect costs. A laptop designed as a breakthrough bargain can quickly become difficult to sustain. Apple's challenge is to preserve the feeling of accessibility, even when the economics that enabled it become less favorable. The Neo also tests how much buyers value the Apple experience itself. Some customers will accept less memory, fewer ports, and smaller storage because they want macOS, battery efficiency, build quality, and integration with an iPhone. Others will compare specifications line by line and choose a Windows machine offering more hardware. At $599, Apple could win both emotional and practical arguments. At a higher price, the emotional appeal may remain, but the practical argument becomes more complicated. For existing Neo owners, the rumored upgrade should not make the current machine suddenly obsolete. The A18 Pro model still performs the tasks it was designed to handle. Someone who bought it at the original price may have secured one of Apple's most aggressive laptop deals in years. The next model could be faster and more future-proof, but it may also cost enough to make the first generation look even better in hindsight. Sometimes the best value is not the newest product. It is the product purchased before the market changes. For potential buyers, timing becomes difficult. Buying the current Neo now means paying more than its launch price for 8GB and 256GB. Waiting could bring 12GB and a better processor, but possibly at a higher starting price. Shopping for a discounted MacBook Air may offer stronger overall hardware, but not always at the same cost. There is no universal answer. The right choice depends on budget, urgency, storage needs, and how long the buyer expects to keep the laptop. The final decision will reveal what Apple believes the Neo should be. If it is a volume product, Apple must protect a low entry price. If it is a way to introduce cheaper Apple silicon without weakening the Air, upgrades and price increases may be acceptable. Buyers will learn whether affordability was the permanent foundation of the Neo or simply the headline that launched its first generation. In my opinion, Apple should treat affordability as the Neo's defining feature, not merely its launch strategy. 12GB of memory is the correct upgrade, and 512GB would make the machine more comfortable, but Apple should not allow those improvements to push the entry price too close to the MacBook Air. The smartest move would be to keep a genuinely affordable model available, even if that means continuing the current generation alongside the new one. The Neo succeeds when it gives more people access to a good Mac, not when it becomes another expensive laptop with better specifications. So what do you think? Would you rather buy a cheaper MacBook Neo with 8GB of memory and 256GB of storage, or pay more for 12GB and 512GB? At what price would the Neo stop feeling affordable to you? $699, $799, or something higher? Share your opinion in the comments. And for more clear coverage of Apple, chips, memory, laptops, and the technology changing what consumers pay, subscribe to the Eastern Engine channel. China's memory crisis is spreading into a part of the semiconductor industry most people barely notice. A Chinese supplier called Giantech Semiconductor has reportedly told distributors that prices across its entire NOR flash product portfolio will rise by 25% beginning July 6th. The increase applies not only to newly signed orders, but also to outstanding orders that have not yet been delivered. That is a major move for a component that usually receives far less attention than RAM, high-bandwidth memory, or solid-state drives. NOR flash is the small, reliable memory that stores firmware, boot code, configuration data, and essential instructions inside cars, routers, industrial machines, communications equipment, and countless connected devices. Without it, many electronic systems cannot even start. Contract prices for mature memory products have already surged sharply during the first half of 2026. Artificial intelligence infrastructure is absorbing investment, factory space, and customer attention. Automotive and edge AI systems are demanding larger amounts of dependable embedded memory. And now one Chinese supplier is adding another 25% to its price list. The question is whether this is a temporary adjustment from one company, or whether the global memory shortage is moving into the overlooked chips that keep the world's electronics running. What NOR flash actually does? NOR flash is not the same as the DDR5 memory inside a gaming computer. It is also different from the NAND flash used inside an SSD or smartphone storage drive. The easiest way to understand NOR flash is to think of it as instruction memory. When a device powers on, it needs a trusted place to find the first code it will execute. That code may initialize the processor, check connected hardware, load safety settings, verify security keys, and prepare the operating system. NOR flash is well suited to that job because it keeps data when power is removed and allows fast, direct access to stored instructions. A vehicle may use NOR flash inside electronic control units, infotainment systems, driver assistance computers, cameras, radar modules, telematic systems, and digital instrument clusters. A network switch may use it to store boot firmware and configuration code. An industrial robot may depend on it for control software that must survive vibration, heat, and years of continuous operation. A product containing powerful processors and expensive sensors can still become unusable if its boot memory is missing, unreliable, or delayed. Why prices are rising now? Mature memory products such as NOR flash and SLC NAND are often manufactured on older process technologies. Those production lines remain useful, but they do not generate the same excitement or margins as advanced AI memory. Large semiconductor manufacturers are investing heavily in high-bandwidth memory, enterprise SSDs, advanced DRAM, and newer NAND products. Those categories are being purchased in enormous quantities by cloud companies building AI infrastructure. Factory equipment, engineering teams, capital budgets, and wafer capacity are therefore moving toward the products with the highest demand and profit. But suppliers have little incentive to build large amounts of new mature node capacity when investors and customers are focused on AI. Modern cars contain more electronic systems than ever. Digital cockpits, advanced driver assistance, connectivity, over-the-air updates, cameras, radar, battery management, and intelligent lighting all require firmware. Edge AI devices also need more local code because they process information near the user instead of sending everything to a distant cloud. As software grows more complex, manufacturers move toward higher-density NOR flash products. That creates pressure on a market where supply is already becoming less flexible. The 25% increase. According to current industry reporting, Giantech's new prices take effect on July 6th. The increase covers the company's full NOR flash portfolio and applies to both new orders and undelivered existing orders. Normally, customers may assume that an accepted order protects them from a later price adjustment. Applying the new price to outstanding shipments suggests that the supplier sees the market tightening quickly enough to reset terms immediately. It does not mean every NOR flash manufacturer has raised prices by exactly 25%. It does not mean every chip buyer will pay the same amount. Large customers may have long-term contracts, negotiated allocations, or different product mixes, and a 25% increase in one component does not mean the final price of a car, server, or router will rise by 25%. The decision signals demand strong enough and availability limited enough to raise prices across an entire category without waiting for the next pricing quarter. A broader memory shock. TrendForce says contract prices for NOR flash and SLC NAND rose by more than 100% during the first half of 2026. It expects additional increases during the second half because major new capacity is not arriving quickly. When demand suddenly rises, manufacturers can sometimes solve the problem by running existing factories harder or releasing inventory. That becomes difficult when the underlying production base is shrinking. Mature memory is not the highest growth destination for semiconductor investment. High bandwidth memory can sell for far more than a small embedded flash chip. Enterprise SSDs are being purchased through large multi-year agreements. Advanced server memory is receiving priority because cloud companies are willing to pay to secure supply. The result is that mature products can become scarce, even when total global memory investment is rising. The industry is building more memory, but not necessarily the specific kinds every customer needs. Why cars are exposed. Automotive companies are especially vulnerable because they cannot replace a qualified memory chip overnight. A consumer gadget manufacturer may redesign a board or switch suppliers relatively quickly. A vehicle component must pass demanding validation for temperature, vibration, reliability, and long operating life. Changing one part can require new testing, software verification, documentation, and approval. Automakers also need predictable supplies for many years because vehicles remain in production and require replacement parts after sales end. This dependence gives approved suppliers more pricing power when capacity tightens. Driver assistance systems need firmware for sensors and processing units. Connected vehicles need secure boot functions and update mechanisms. Higher levels of automation can increase the number and complexity of electronic modules. A shortage of relatively inexpensive NOR flash can therefore interrupt production of a much more expensive vehicle. Factories were forced to slow or stop because one missing controller or memory device prevented an entire car from being completed. AI servers are next, but with context. The title says cars and AI servers are next. That does not mean NOR flash will replace HBM or become the largest memory cost inside an AI server. Servers, network switches, accelerators, storage controllers, power systems, and management boards all require firmware. As AI data centers expand, they install enormous numbers of devices that must boot, authenticate, communicate, and recover reliably. Every additional server rack contains many embedded systems. The amount of NOR flash per device may be modest, but the number of devices is growing rapidly. AI clusters depend on high-speed switches, optical modules, smart network cards, and management controllers. These systems use dependable code storage for startup, configuration, diagnostics, and updates. Edge AI hardware creates another source of demand. Cameras, robots, industrial computers, vehicles, and smart appliances increasingly run models locally. That requires more sophisticated firmware and often larger embedded memory capacities. So AI contributes to the shortage in two ways. It pulls investment toward premium memory such as HBM and enterprise NAND. At the same time, it increases demand for the smaller firmware chips used throughout the infrastructure. China's position. Giantech is not the largest memory company in the world. Samsung, SK Hynix, Micron, Kioxia, and other major suppliers control far larger portions of global memory production. But China has been expanding its presence in mature and embedded semiconductor categories. That matters because domestic customers want secure supplies for vehicles, communication systems, industrial equipment, and consumer electronics. Chinese technology companies are also trying to reduce dependence on foreign components where possible. A stronger domestic NOR flash industry can support that goal. Yet higher Chinese prices show that localization does not automatically mean cheap supply. Domestic manufacturers still respond to capacity, demand, equipment costs, yields, and market conditions. If Chinese automakers and electronics companies compete for the same limited output, prices can rise inside China even while production expands. The shortage could benefit suppliers through higher margins. It could also encourage investment in additional capacity. But new semiconductor output takes time. Equipment must be ordered, installed, qualified, and operated at acceptable yields. Customers must test the finished chips. The market may remain tight long before any new line reaches meaningful volume. Duchu pays the final bill. The immediate buyers are distributors, module makers, electronics manufacturers, and system suppliers. They must decide whether to absorb the higher cost or pass it onward. For an expensive vehicle or server, one NOR flash chip may represent only a small fraction of the final price. Manufacturers may instead accept lower margins. They may negotiate with suppliers, reduce inventory, delay projects, or redesign future products around alternative parts. Smaller companies have fewer options. They purchase lower volumes, possess less negotiating power, and may not have second sources already approved. They could face longer delivery times or steeper price increases. The most serious risk is not the added cost of one chip, it is interruption. A missing component can delay an entire board, controller, machine, or vehicle. Companies may therefore pay a premium simply to guarantee allocation. This behavior can make the shortage worse because customers order earlier and hold more inventory than usual. What could end the shortage? Several developments could weaken the price surge. Demand for AI hardware could slow. Automotive production could weaken. Customers could reduce memory capacity or redesign products to use alternative devices. Manufacturers could reopen older lines, improve yields, or shift capacity back toward mature products. Chinese suppliers could expand faster than expected. But each solution has limits. Redesigns take time. Automotive qualification is slow. Building capacity is expensive. And suppliers may prefer to keep production disciplined rather than create another oversupply cycle. Memory companies remember what happens when too many factories chase temporary demand. Prices collapse, inventories rise, and expensive equipment sits underused. That history encourages caution. The market may eventually balance, but buyers should not assume prices will return quickly to previous lows. What this does not prove. One supplier's notice is not proof that every electronics category faces an immediate crisis. Giantech's increase must be separated from broader claims. We do not know the exact price paid by every customer. We do not know how much inventory distributors currently hold. We do not know whether competitors will match the full increase. And we do not know how long the new pricing will remain in place. The report is best understood as evidence that pressure has reached another memory category. NOR flash was once treated as a stable, mature component. Now it is being affected by the same forces reshaping DRAM, NAND, HBM, and enterprise storage. AI demand is changing investment priorities across the entire memory supply chain. My take is that the 25% increase matters less as an isolated number than as a warning. The memory supercycle is spreading outward. It began with the obvious products: HBM for accelerators, server DRAM, and enterprise SSDs. Now pressure is reaching the smaller chips that store the code required to start cars, routers, robots, and industrial systems. These devices are not glamorous. They do not appear in benchmark charts. Most consumers will never know which company made them. But modern hardware depends on them. Giantech's decision shows that mature memory can become strategically important precisely because the industry spent years treating it as ordinary. Supply is limited, qualification is slow, demand is becoming more sophisticated, and manufacturers are focusing investment elsewhere. That combination creates pricing power. The final impact may not be a dramatic 25% increase in the price of a car or server. It may appear as delayed production, smaller margins, redesigned products, and manufacturers paying more to secure guaranteed supply. China's domestic memory industry could eventually add enough capacity to ease the pressure. But today, one of its own suppliers is signaling that the shortage remains strong. So what do you think? Is the NOR flash increase another temporary spike? Or is it proof that the AI memory crisis is reaching every layer of modern electronics? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the next hardware bottleneck may not be the processor everyone watches. It may be the tiny memory chip that tells that processor how to start. For 60 years, the entire technology industry has obeyed a single rule. It was never a law of government. Never a law of physics, really. It was a prediction, made by a man named Gordon Moore in 1965, that quietly became the heartbeat of the modern world. Every smartphone, every laptop, every data center, every AI model you've ever touched exists because of it. The rule was simple. Every 2 years, you make the transistors on a chip smaller, you pack twice as many of them onto the same sliver of silicon, and everything gets faster, smaller, smaller. For 6 decades, that one word drove a trillion-dollar industry forward. And on May 25, 2026, on a stage in Shanghai, a woman the Chinese tech world calls the chip queen stood up and told a room full of the world's leading engineers that the rule is finished, done, that the future of computing would not be won by making things smaller, and that her company had spent the last 6 years quietly proving it, building 381 chips in total secrecy to back up the claim. Her name is He-Ting Bo. The company is Huawei, and what she proposed isn't a new chip, it's a new rule to replace the one that's governed all of technology since before the moon landing. Now, is this a genuine breakthrough, or a desperate company spinning a limitation into a headline? That's the real question. And by the end of this video, you'll be able to answer it yourself. Let's get into it. To understand why this matters, you have to understand why Moore's law was running out of road in the first place. Because this part isn't propaganda, it's physics, and the whole industry agrees on it. Picture a transistor as a tiny switch. Moore's law was the promise that engineers would keep shrinking that switch, year after year, fitting more and more of them into the same space. In 1971, a leading chip had a few thousand transistors. Today's most advanced processors have tens of billions. That staggering journey is Moore's law in action. But here's the problem. Transistors are now so small, they're measured in nanometers. And a few nanometers is a span of just a handful of atoms. You cannot shrink something forever. Eventually, you hit a wall where the switch is so tiny that electrons start leaking through it even when it's supposed to be off, where heat becomes unmanageable, and where the machines needed to etch these features cost hundreds of millions of dollars each. The closer you get to the size of individual atoms, the more every further step costs, and the less you get back. The returns don't just shrink, they collapse. The entire industry has known this reckoning was coming for years. Even Moore's own law was, in a sense, always going to expire. You can't keep having your way down to nothing. The question was never whether the smaller is better era would end. The question was what comes after it, and who would define the rule that replaced it. That's the door Huawei just walked through, and the reason Huawei walked through it first has a lot to do with something that was supposed to cripple them. Here's the twist that makes this story genuinely fascinating. Huawei didn't develop this new approach purely out of scientific curiosity. They developed it because they had no choice. For years, Huawei has been cut off from the most advanced chip-making machines on Earth. Specifically, the extreme ultraviolet lithography systems built by a single Dutch company, the only tools capable of etching the very smallest transistors. Those machines are the engine of Moore's law. No access to the machine, no way to keep shrinking. So while the rest of the industry kept racing down the shrinking path, the path that requires those banned machines, Huawei was locked out of the race entirely. Most observers assumed that meant Huawei would simply fall further and further behind, permanently. Instead, being locked out forced a different question. If you can't win by making transistors smaller, can you win some other way? Can you get more performance out of chips you're already able to build, without needing the forbidden machine at all? That question is the seed of everything. Huawei's chairman has even pointedly thanked the export restrictions for supercharging China's semiconductor industry. And as strange as that sounds, this is exactly what he meant. The wall didn't stop them. It redirected them down a road nobody else was seriously exploring, because nobody else was desperate enough to need it. And what they found at the end of that road is a genuinely different way of thinking about what a chip even is. So what actually is this new rule? Let me explain it in a way that sticks, because the core idea is beautiful in its simplicity. Huawei calls it the Tau scaling law. Tau, written as the Greek letter tau, is a symbol engineers use to represent time, specifically, the time it takes for a signal to travel from one part of a chip to another, and that single shift, from measuring size to measuring time, is the whole revolution. Think of a chip as a city. Moore's law was obsessed with one thing: making the buildings smaller so you could cram more of them into the city. Huawei's Tau scaling law asks a completely different question. Forget the size of the buildings. How fast can a message get from one side of the city to the other? Because here's the secret the industry doesn't advertise. In a modern chip, a huge amount of time and energy isn't spent on the transistors switching. It's spent on signals traveling, crawling down long wires from one part of the chip to another. Shrinking transistors does nothing to fix that. You can have the smallest, fastest switches in the world, but if the messages between them have to travel a long way, the whole system waits. Huawei's insight: stop fixating on the switches, start attacking the distance. Make the signals travel less, arrive faster, and the entire chip speeds up, without shrinking a single transistor, and without ever touching the band machine. That's the rule. Not smaller, faster. And to make it real, they built something that sounds like science fiction, but is already rolling off production lines. The technology that turns this idea into reality is called logic folding, and the name is the perfect description of what it does. Imagine a city again, but this one is flat. Everything spread out across the ground, connected by long roads. Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Now imagine you could fold that city upward, stacking neighborhoods directly on top of each other, so the journey between them shrinks from miles to inches. That's logic folding. Instead of laying circuits out flat across a single layer of silicon, Huawei folds them into vertically stacked active layers, building up instead of out. The payoff is enormous. By stacking circuits vertically, the wires connecting them get dramatically shorter. Signals travel less distance, so they arrive faster. That's the time, the tau, being compressed. And as a bonus, folding the circuits upward also lets you pack more of them into the same footprint. Huawei claims this approach can deliver up to 55% higher transistor density and significantly better power efficiency, all at the same manufacturing process, with no need for the smaller, forbidden node. Read that again, because it's the heart of why this matters. More density, more performance, without shrinking the transistors, and without the machine they're banned from buying. If it works the way Huawei claims, it's a way to keep advancing chips that completely sidesteps the chokehold the restrictions were designed to create. And here's the detail that makes this more than a slideshow promise. Huawei says this isn't theoretical. Over the past 6 years, the company quietly designed and mass-produced 381 chips built on these principles, across smartphones, AI processors, and more. The first chips to fully adopt the logic folding architecture will be Huawei's new flagship Kirin processors, launching in the autumn of 2026. This isn't a lab demo. It's a production reality that the rest of the industry only just learned existed. Now here's the claim that made headlines around the world, and the part where I need to be straight with you. Huawei says that by 2031, chips designed with this approach could reach a transistor density equivalent to a 1.4 nanometer process. To understand why that's a bombshell, the most advanced chips being mass-produced today, by the world's leading foundry, sit at the 2 nanometer level. A 1.4 nanometer class density would put Huawei's designs ahead of where the global frontier is right now, achieved without the machines everyone assumed were absolutely required to get there. If that lands, it doesn't just close China's chip gap, it potentially erases it. But, and this is the honest catch you won't get from a hype video, there are real reasons for skepticism, and you should hold both things in your head at once. First, 1.4 nanometer equivalent is a claim about density equivalence, not the same thing as actually manufacturing a true 1.4 nanometer chip. It's a clever reframing, and critics argue it blurs an important line. Second, Huawei did not release independent performance data to back the headline numbers. We largely have the company's word. And third, stacking circuits vertically creates its own brutal problems, especially heat. When you fold a city upward, you also concentrate all its heat into a smaller space, and managing that is genuinely hard. So is this a real breakthrough, or a desperate company dressing up a limitation? The most honest answer is probably both. It's clearly born of necessity. Huawei built this because it was cornered. But born of necessity and genuine breakthrough are not opposites. Some of the most important leaps in history came from exactly that pressure. The 6 years of work and 381 real, shipped chips suggest there's substance here, not just a press release. The grand 2031 target is the part to watch with healthy skepticism. Step back, and here's what makes this a genuine turning point, rather than just another product announcement. For 60 years, the rule that governed chips was written by the West, followed by the West, and led by the West. Moore worked at the company that became Intel. The entire framework of progress, smaller, 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 was an American idea that the whole world adopted. Whoever defines the rules of a technology tends to lead that technology. What Huawei just attempted is not merely to catch up within the old rules, it's to rewrite the rules themselves, to propose a new definition of progress that happens to play directly to China's strengths and around its weaknesses. He Tingbo framed it not as a Huawei product but as a new guiding principle for the entire industry, openly inviting engineers worldwide to build on it. That's not the language of a company selling a chip. That's the language of a company trying to set the agenda for everyone else. And whether or not the 2031 target is hit precisely, the deeper shift is already real. The era where progress meant one thing, shrinking, is genuinely ending, for everyone, by the laws of physics. Something has to come next. And for the first time in the history of computing, one of the most serious proposals for what comes next was written in Shanghai, not Silicon Valley. There's one more detail worth sitting with. He Tingbo ended her keynote with a quiet promise. Before winter 2026, we will bring the surprise, a big leap ahead. Whatever that surprise is, the industry is now watching China to find out. And that, more than any single number, is the real story. The watching has reversed direction. Here's my honest opinion. I think the smartest way to see this is to refuse both of the easy takes. The people screaming, Huawei just destroyed Moore's Law and humiliated the West, are getting ahead of the evidence. The headline numbers are unverified, the 2031 target is far off, and the heat problems are real. But the people waving it away as just propaganda from a cornered company are missing something just as important. 6 years of secret work and 381 mass-produced chips is not a press release. It's a track record. What genuinely fascinates me is the pattern. Glass substrates, diamond cooling, and now a wholesale attempt to redefine the rule of chip progress. Over and over, the same story repeats. A restriction designed to stop China instead forces China down a road no one else was exploring, and sometimes that road leads somewhere new. The wall meant to contain them keeps functioning as a map. I don't think that's a coincidence anymore. I think it's becoming the defining dynamic of this entire era of technology. Moore's Law was always going to end. The only real question was who would write the sentence that comes after it. The fact that Huawei is even in the running to write that sentence, that's the thing nobody saw coming 5 years ago. Here's my question for you, and I want your honest answer, because this one genuinely splits people. When you cut a competitor off from your best technology, are you protecting your lead, or are you forcing them to invent something better that you'll eventually have to compete with? Huawei's own chairman thanked the restrictions for making his company stronger. Was cutting China off a brilliant move, or the biggest strategic mistake of the decade? Drop your real take in the comments. I read them all. If you want to keep following this, the breakthroughs, the rule changes, the moves nobody saw coming until it was too late, subscribe to Eastern Engine and turn on notifications. Chips, materials, energy, the whole foundation of modern technology is being rewritten right now, and we break it down before the rest of the world catches up. Thanks for watching. I'll see you in the next one. For decades, 3 companies have controlled almost the entire global market for computer memory: Samsung, SK Hynix, and Micron. Their chips sit inside smartphones, laptops, gaming computers, servers, and artificial intelligence data centers. Now, a Chinese manufacturer founded only 10 years ago is preparing an expansion that could change that balance. Changxin Memory Technologies, better known as CXMT, is expected to add roughly 85,000 wafer starts per month of new DRAM manufacturing capacity during 2026. Samsung is expected to add around 15,000. That means CXMT could install more than 5 times as much new wafer capacity as Samsung this year, not 5 times as much total production. Samsung remains far larger, but in terms of new capacity being added during 2026, China's leading DRAM producer is moving faster, and CXMT is preparing to raise another 29.5 billion yuan, approximately $4.3 billion, through one of the largest technology IPOs ever attempted on Shanghai's star market. The money is expected to support production expansion, research, and the development of more advanced DRAM, including memory designed for artificial intelligence. This is arriving at an extraordinary moment. AI data centers are consuming memory faster than manufacturers can comfortably supply it. Memory prices have risen. Samsung, SK Hynix, and Micron are earning enormous profits, and CXMT's revenue reportedly increased more than sevenfold in the first quarter of 2026. But rapid expansion does not automatically make CXMT a technological equal to Samsung. The Chinese company is still behind in advanced high-bandwidth memory. Its manufacturing efficiency, product mix, and total output remain smaller. And increasing wafer capacity during a memory shortage can be highly profitable, or extremely dangerous if demand weakens before the new factories are ready. So is CXMT becoming a genuine fourth global memory giant, or is it expanding at the most expensive point in a historically unstable industry? Why memory has become the new AI bottleneck? When people discuss artificial intelligence, most attention goes to processors. NVIDIA GPUs, custom accelerators, massive clusters filled with computing power. But a processor is useful only when it can receive data quickly enough. Every AI accelerator needs memory to hold model weights, temporary calculations, instructions, and the information moving between layers of a neural network. If memory cannot deliver that data fast enough, the expensive processor waits. That waiting time is one reason memory bandwidth has become so important. Traditional DRAM serves as the working memory inside computers. It stores information that processors need immediately. Unlike an SSD, DRAM is extremely fast, but it loses its contents when power is removed. A modern server may contain hundreds of gigabytes or several terabytes of DRAM. An AI cluster can contain thousands of servers. Multiply that memory across an entire data center, and demand becomes enormous. AI is also increasing demand for a specialized form of DRAM called high bandwidth memory, or HBM. HBM stacks multiple memory dies vertically and places them close to an AI processor. Thousands of tiny connections move data between the layers and the processor at extremely high speed. But HBM is difficult to manufacture. It requires advanced DRAM dies, precise stacking, specialized packaging, and strong control over heat and yield. Producing more HBM can also consume manufacturing capacity that could otherwise make conventional server, smartphone, or computer memory. This creates pressure across the entire market. As the established manufacturers redirect advanced production toward profitable AI products, supplies of standard DRAM can tighten. That is the opening CXMT is trying to exploit. The Chinese company that appeared almost from nowhere. CXMT was established in 2016. That makes it extremely young compared with its major competitors. Samsung has manufactured semiconductors for decades. SK Hynix traces its history through several older Korean memory companies. Micron was founded in the 1970s. DRAM is one of the hardest semiconductor markets to enter. Each memory cell must store a reliable electrical charge while occupying as little silicon as possible. Factories must produce enormous volumes because memory is usually sold as a standardized product. A small difference in manufacturing yield can determine whether a company makes money or loses billions. CXMT initially focused on providing China with a domestic source of conventional DRAM. Its early products trailed the leading manufacturers in density, power efficiency, and process technology. But the company continued expanding. It introduced newer generations of DDR memory for computers and servers. It moved into low-power LPDD, our products used in mobile devices. And it gradually increased production inside large 300mm wafer fabrication plants. By the fourth quarter of 2025, estimates placed CXMT at nearly 8% of global DRAM revenue. In the first quarter of 2026, Counterpoint estimated its share at approximately 8%. Samsung remained the leader with around 38%. SK Hynix held close to 29%, while Micron remained another major supplier. CXMT was still far behind the top three, but it had clearly separated itself from the industry's smaller manufacturers and established itself as the world's fourth largest DRAM supplier. The gap remains large. The direction is what matters. What 85,000 wafers per month really means. Semiconductor manufacturing capacity is often measured in wafer starts per month. A wafer start occurs when a blank silicon wafer begins its journey through the fabrication process. Each wafer passes through hundreds or sometimes thousands of manufacturing steps. Thin films are deposited, patterns are printed, materials are etched away, ions are implanted, connections are formed, the wafer is cleaned, measured, and inspected repeatedly. Depending on the chip and process, completing one wafer can take several months. After fabrication, the wafer contains many individual dies. Those dies are tested, cut apart, and packaged into usable memory chips. When analysts say CXMT may add approximately 85,000 wafer starts per month during 2026, they do not mean the company will manufacture only 85,000 wafers during the year. They mean its factories may gain the ability to begin processing roughly 85,000 additional wafers every month once that capacity is operational. That could represent hundreds of millions of additional memory dies over time, depending on die size, process technology, and manufacturing yield. Samsung's estimated addition of around 15,000 wafer starts per month is much smaller, but the comparison needs context. Samsung already operates an enormous installed manufacturing base. It does not need to add as much conventional DRAM capacity to remain larger than CXMT. Samsung is also spending heavily on process upgrades, HBM, advanced packaging, and new facilities whose full capacity may arrive in later years. A company can increase memory output without adding an equal number of wafers. Moving to a more advanced process can place more memory bits on each wafer. Improving yield allows more usable chips to leave the same production line. Changing the product mix can also dramatically alter revenue. So CXMT's 85,000 versus 15,000 comparison is powerful, but it is not a complete measurement of who will produce the most memory. It shows aggression, it does not yet show leadership. Why CXMT is expanding right now? Memory manufacturers have lived through repeated cycles of shortage and oversupply. When demand rises, prices increase. Manufacturers earn large profits and build new capacity. But semiconductor factories take years to construct and equip. By the time production begins, demand may have weakened. Several manufacturers can then bring new supply online at the same time. Prices collapse, profits disappear, investment slows. Then demand eventually recovers and the cycle begins again. AI is making the current cycle unusual. Memory suppliers believe demand from data centers may remain strong for longer than previous consumer electronics booms. Large cloud companies are building enormous AI clusters. Each new generation of accelerator uses more memory. Models are becoming larger. Inference workloads are spreading into more services. Micron has said it expects tight memory supplies to continue through at least 2027. Major manufacturers are signing longer-term agreements with customers that include deposits, minimum purchases, and pricing protections. CXMT is entering this market while prices are high and supply is limited. Its first quarter 2026 revenue reached approximately 50.8 billion yuan, representing a year-over-year increase of more than 700%. The company moved from losses into substantial profitability. Part of that improvement came from increased shipments, part came from better products, but a major factor was the sharp rise in global memory prices. That financial improvement makes an IPO much easier to sell. Investors are no longer being asked to fund only a long-term semiconductor ambition. They are being shown a company generating large revenue during one of the strongest memory markets in history. What the $4.3 billion IPO could fund CXMT plans to raise 29.5 billion yuan through its Shanghai listing. That equals roughly $4.3 billion. The offering would be the largest mainland Chinese IPO of 2026 and the second largest listing in the history of Shanghai's technology-focused star market. For a semiconductor company, $4.3 billion is significant, but it is not unlimited. A modern memory fabrication plant can cost tens of billions of dollars when buildings, cleanrooms, lithography systems, deposition tools, etching equipment, testing systems, and supporting infrastructure are included. CXMT is therefore not building its entire expansion with IPO money alone. The company already has factories, investors, financing, and other sources of capital. The IPO adds another pool of funding. According to its listing plans, the proceeds are intended for manufacturing upgrades, research and development, process improvement, and product expansion. That last category may be the most important. Standard DDR and LPDDR products helped CXMT establish volume. HBM could determine whether it becomes strategically important to the AI market. The HBM gap CXMT's biggest weakness is not basic DRAM capacity. It is advanced memory. Samsung, SK Hynix, and Micron are already producing high-bandwidth memory for leading AI accelerators. SK Hynix became especially successful by investing early in HBM and building a strong relationship with NVIDIA. HBM carries higher margins than ordinary memory, but it also demands better technology. The DRAM dies must be manufactured efficiently. The dies must be thinned. Tiny vertical connections called through-silicon vias must pass signals through the stack. Multiple dies must be aligned and bonded. The final package must remain reliable while transferring enormous amounts of data and operating beside a hot AI processor. One defective die can damage the value of an entire stack. CXMT is investing in an HBM packaging facility in Shanghai and has targeted production by the end of 2026. But starting production is not the same as reaching high-volume manufacturing. It must demonstrate acceptable yields. It must qualify its products with accelerator designers. It must prove long-term reliability. And it must catch competitors that are already moving toward newer HBM generations. This means CXMT's immediate expansion will probably have a larger impact on standard DRAM than on the most advanced AI memory. It may pressure prices in consumer, mobile, and server memory before it seriously threatens SK Hynix in premium HBM. Could CXMT actually hurt Samsung? Samsung is not facing an immediate collapse. It remains the largest DRAM supplier by revenue. It has far more manufacturing experience. It operates advanced process technology, major research facilities, and a global customer network. It also produces NAND flash, processors, image sensors, displays, and complete electronic products. CXMT is much more concentrated, but that concentration can become an advantage. CXMT can focus capital and engineering effort on DRAM. It can compete aggressively in the Chinese market, and it can supply domestic computer, smartphone, server, and accelerator manufacturers that want alternatives to foreign memory. CXMT does not need to defeat Samsung worldwide to create pressure. It only needs to capture enough volume to affect industry supply. Memory products are highly sensitive to small differences between demand and production. If the world needs 100 units of DRAM and manufacturers produce 98, prices can rise quickly. If they produce 105, prices can collapse. An extra few percentage points of supply can change profitability for every company in the market. SemiAnalysis expects the DRAM market to remain undersupplied even after accounting for CXMT's expansion. But the expected shortage does not last forever. Capacity being installed now may influence prices in 2027 and 2028. If AI demand continues rising, the new supply could be absorbed. If AI investment slows, CXMT's expansion could arrive just as the market becomes oversupplied. What this could mean for consumers. For buyers of computers, servers, and smartphones, more competition is generally positive. Additional supply can reduce shortages. It can provide device manufacturers with more negotiating power. It may eventually lower the price of DDR5 modules, laptop memory, and server DRAM. CXMT manufactured chips have already appeared in memory products sold under recognizable international brands. That does not necessarily mean those brands have committed to CXMT for every model or every market. Memory module manufacturers frequently source chips from different suppliers depending on price, availability, and qualification. But it shows that CXMT is no longer restricted to experimental or purely domestic products. Its chips can enter commercial supply chains when they meet the required specifications. The question is whether the company can maintain performance and reliability while rapidly increasing output. Expanding too quickly can create yield problems. New production lines require trained workers. Equipment must be calibrated. Processes must remain consistent across multiple factories. A chip that works in one small production run must continue working when millions are produced every week. Scale exposes weaknesses that laboratory demonstrations can hide. The biggest risks. CXMT faces three major risks. The first is technology. Adding wafer capacity is valuable only if the products are competitive. A less advanced process may produce fewer memory bits per wafer and consume more power. That can make apparently large manufacturing capacity less productive than a smaller but more advanced factory. The second risk is the market cycle. CXMT is investing during a period of exceptional memory prices. Those prices helped create its recent profits. If supply catches demand and pricing falls, the financial picture could change rapidly. The third risk is execution. Semiconductor expansion is not simply a construction project. Factories need complex tools, materials, software, replacement parts, and skilled engineers. Any bottleneck can delay production, and advanced DRAM requires constant process improvement. Samsung, SK Hynix, and Micron will not remain still while CXMT expands. They are investing in denser DRAM, more efficient manufacturing, and newer generations of HBM. CXMT is chasing moving targets. My take is that the 5x number is not proof that CXMT has overtaken Samsung, but it may be evidence of something more important. China is no longer treating domestic DRAM as a small backup industry. It is building for global scale. CXMT already holds a meaningful share of the market. Its revenue has accelerated. Its factories are expanding. Its IPO could provide another $4.3 billion for manufacturing and research, and it is beginning the difficult move from conventional memory toward HBM. Samsung remains larger. SK hynix remains stronger in high-end AI memory. Micron remains deeply connected to major American technology companies, but the memory industry may no longer be a permanent three-company market. CXMT is becoming a fourth participant capable of influencing supply, prices, and investment decisions. The most important test will not be how much money the IPO raises. It will be what comes out of the factories afterward. Can CXMT convert 85,000 additional monthly wafer starts into reliable competitive memory? Can it improve yields while increasing volume? Can it manufacture HBM at scale? And can it remain profitable when today's memory shortage eventually ends? If the answers are yes, Samsung, SK hynix, and Micron will face a competitor with domestic scale, strong financial backing, and one of the fastest capacity expansions in the industry. If the answers are no, CXMT could discover the same lesson that has punished memory manufacturers for decades. Building capacity is easy compared with filling it profitably. So what do you think? Is CXMT on its way to becoming the world's fourth true memory giant? Or is it expanding too aggressively during a temporary AI-driven shortage? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering breakthroughs changing the technology industry. Because China is not adding 5 times Samsung's total memory production, but it may be adding more than 5 times as much new wafer capacity this year. And in an industry where a small shift in supply can move the entire market, that difference could matter far more than it first appears. Artificial intelligence has a networking problem. The world is building larger GPU clusters, larger data centers, and increasingly powerful computing systems. But all of those processors must constantly exchange enormous amounts of data. If the network connecting them is too slow, expensive, or power-hungry, even the most advanced AI chips can spend valuable time waiting. Now, China says it has completed a major test of a technology designed to attack that bottleneck. Yangtze Optical Fiber and Cable, better known as YOFC, worked with China Telecom and optical equipment company Decoli to transmit 51.3 terabits of data per second across 206.5 kilometers, or roughly 128 miles. The system reached as much as 1.2 terabits per second on a single wavelength, and it completed the entire distance without electronically regenerating the signal or using remotely pumped amplifiers along the route. But the most unusual part was the cable. Instead of sending light through a conventional solid glass core, the system used hollow core fiber. Most of the light traveled through an air-filled channel surrounded by a carefully designed glass structure. That allows optical signals to move faster and experience far less interaction with the glass itself. YOFC says its technology can reduce latency by approximately 31%, increase optical propagation speed by around 47%, and sharply reduce nonlinear distortion. The question is whether this is simply another impressive telecommunications demonstration, or whether air-filled fiber could become a critical part of the infrastructure connecting the world's largest AI systems. Why normal fiber uses glass? Modern communications depend on fiber optic cables. Internet traffic, cloud services, financial transactions, video streaming, mobile networks, and data center connections all rely on pulses of light traveling through extremely thin strands of glass. Traditional optical fiber contains a solid core made primarily from silica. That core is surrounded by another layer of glass with different optical properties. The structure keeps light confined inside the cable as it travels across long distances. This technology transformed global communications because fiber can carry vastly more information than copper while losing relatively little signal strength. But conventional fiber still has physical limitations. Light does not travel through glass at the same speed that it travels through a vacuum or through air. The refractive properties of silica slow the signal down. In ordinary fiber, optical propagation is typically around 2/3 of the speed of light in a vacuum. That delay may sound insignificant, but over hundreds or thousands of kilometers, microseconds accumulate. For ordinary video streaming, the difference may not matter. For distributed artificial intelligence clusters, financial trading, cloud infrastructure, or scientific computing, small delays can affect performance. Glass also interacts with intense optical signals. As more power and more data channels are pushed through the same fiber, nonlinear effects can distort the signal and limit how much information can be transmitted reliably. Hollow core fiber attempts to avoid those problems by moving most of the light away from solid glass. How hollow core fiber works. The name can be misleading. Hollow core fiber is not simply an empty plastic tube. It is still an advanced glass structure, manufactured with extremely precise geometry. Around the air-filled center are thin glass membranes or tubes arranged to keep light trapped inside the hollow region. The structure reflects and guides the optical signal through the air-filled core, while allowing only a small portion of the light to interact with the surrounding material. Because the light travels primarily through air, it can move significantly faster than it does through solid silica. The lower interaction with glass also reduces several types of distortion. This can allow engineers to send stronger optical signals, use more advanced modulation, and potentially increase the distance between major network equipment. The concept is not completely new. Researchers have studied hollow core fiber for decades. The problem was loss. Early designs allowed too much light to leak out of the core. A signal weakened so quickly that the lower latency was not enough to justify the technology. Conventional fiber remained cheaper, easier to manufacture, easier to connect, and more reliable over long distances. The important change is that hollow core attenuation has been falling. YOFC says its latest fiber has achieved loss as low as 0.04 decibels per kilometer under reported test conditions. That is a critical milestone because low latency only matters commercially if the signal can also survive a useful distance. What China's trial achieved. The new Chinese trial combined high capacity, long distance, and a real cable deployment. The system transmitted an aggregate 51.3 terabits per second across a 206.5 kilometer hollow core fiber span. Aggregate capacity means the total data rate across multiple wavelengths. It does not mean one optical channel carried all 51.3 terabits. The maximum reported rate for an individual wavelength was 1.2 terabits per second. Different colors, or wavelengths of light, can travel through the same fiber simultaneously. This technique is called wavelength division multiplexing. Each wavelength carries its own stream of information. When many channels are combined, the fiber can transport an enormous total volume of data. The companies used a self-developed optimization system to adjust the data rate and optical power of individual wavelengths. That matters because not every channel experiences exactly the same conditions. Rather than forcing every wavelength to operate at one fixed setting, the system could allocate resources more efficiently. The result was a very high total capacity across a long hollow core span. What without repeaters really means, some headlines have suggested that the trial required no signal boosting. That is not completely accurate. The system used conventional erbium-doped fiber amplifiers, commonly called EDFAs. These devices amplify optical signals without first converting the information into an electronic form. What the system avoided was signal regeneration along the 206.5 kilometer span. A regenerator receives a weakened optical signal, converts it into electrical data, cleans and retimes that data, and then creates a new optical signal for the next section of the journey. Regeneration can extend network reach, but it adds equipment, power consumption, cost, latency, and potential failure points. The trial also avoided remotely pumped amplifiers placed at difficult locations along the cable route. So the achievement is not that the light traveled completely unassisted. The achievement is that the companies maintained a 51.3 terabit per second connection across the full span, using optical amplification without needing intermediate electronic regeneration. That makes the result far more relevant to real long-distance networks. Why this matters for AI? An AI cluster is not just a room full of processors. It is a networked system. During model training, thousands of accelerators repeatedly exchange gradients, parameters, activations, and other information. The processors must remain synchronized. If communication takes too long, expensive hardware can sit idle while waiting for data from another machine. Inside one server, this problem is addressed through extremely fast chip-to-chip connections. Inside one rack, specialized networking connects multiple systems. But the AI industry is increasingly moving beyond individual racks and even beyond individual buildings. Power availability may force companies to divide computing infrastructure across several data centers. One location may not have enough electricity, cooling capacity, or physical space to contain an entire cluster. Distributed AI infrastructure therefore needs high-capacity connections between separate buildings or regions. This is where hollow core fiber may become valuable. Lower propagation latency could help distant data centers behave more like one coordinated computing system. Lower optical nonlinearity could allow stronger signals and more data channels. Longer spans without electronic regeneration could reduce network complexity and energy use. Hollow core fiber will not make a slow network switch faster or improve poorly designed software, but it could improve the physical layer carrying information between major computing facilities. The energy question. AI data centers are already placing enormous pressure on electrical grids. The processors consume power. Cooling systems consume power. Memory and storage consume power. And the networking equipment connecting everything also consumes power. Long-distance optical systems require amplifiers, transponders, switches, and sometimes regenerators. If hollow core fiber allows longer distances between regeneration points, operators may be able to remove some equipment from a network route. That could reduce power consumption, maintenance requirements, and physical infrastructure. However, the total savings will depend on the complete network. A faster fiber does not automatically make every attached device more efficient. Transceivers still consume energy. Switches still process traffic. Cooling is still required. Installation costs may also remain high. The strongest case for hollow core fiber may initially appear in networks where latency and capacity are more valuable than the lowest possible cable price. The global race. China is not developing hollow core fiber alone. Microsoft acquired British hollow core specialist Luminicity and has been deploying the technology in parts of its Azure infrastructure. Microsoft has also worked with manufacturing partners to expand production. Researchers associated with Luminicity and the University of Southampton have demonstrated hollow core designs with losses below some long-standing solid core fiber benchmarks. Amazon and other major cloud companies have also examined advanced fiber technologies as data center networks expand. This means the Chinese trial should not be interpreted as proof that China invented the entire field or has permanently defeated Western competitors. It shows that China is building its own manufacturing, deployment, and optical equipment ecosystem around the technology. YOFC says it has established an integrated production chain covering preform manufacturing, fiber drawing, coating, cabling, and testing. The company has also produced a continuous hollow core fiber length exceeding 90 kilometers and participated in multiple pilot or commercial projects. That manufacturing capability may become as important as laboratory performance. A fiber technology cannot transform global networks if it can only be produced in short, fragile pieces. The manufacturing challenge. Conventional fiber has decades of industrial experience behind it. Manufacturers can produce enormous quantities at low cost. Telecommunications companies understand how to install it, splice it, test it, and repair it. The supporting standards and equipment are mature. Hollow core fiber must compete with that entire ecosystem. Its internal geometry is far more complex. Small manufacturing defects can increase optical loss. Joining two hollow core sections can be difficult because the air-filled structures must remain precisely aligned. Connections with conventional fiber can also introduce additional loss. Bending, cabling, environmental stress, and long-term reliability must be carefully tested. A record achieved on one route does not prove the same performance can be reproduced cheaply across millions of kilometers. Operators also need compatible amplifiers, transceivers, connectors, monitoring equipment, and installation procedures. This is why hollow core fiber is unlikely to replace all conventional fiber in the near future. Traditional silica fiber is already extremely effective for most communications. It is inexpensive, reliable, and widely available. Hollow core technology will probably enter the market first where its unique advantages justify the added cost. Where it could be used first. The most obvious early applications are financial networks, major cloud regions, AI data center links, scientific facilities, and telecommunications backbones. High-frequency trading companies pay large amounts of money to reduce network latency by tiny fractions of a second. Cloud providers may value faster communication between separate data centers. AI companies may need to connect clusters located near different power sources. Scientific institutions may use the fiber to transfer enormous datasets or synchronize precision instruments. Military and government networks could also value lower latency and reduced signal distortion. Consumer broadband will probably not be the first major market. Replacing the fiber entering individual homes would be expensive, and most household internet connections are limited by service plans, routers, Wi-Fi, and network congestion rather than the propagation speed of the glass itself. The technology makes more sense in the backbone of the network, where enormous quantities of data travel across long distances. My take is that this trial is important, but not because conventional fiber is suddenly obsolete. Solid core silica fiber will remain the foundation of global communications for many years. It is proven, inexpensive, and good enough for an enormous range of applications. The breakthrough is that hollow core fiber is moving out of small laboratory experiments and into longer commercial-scale lengths. China's 51.3 terabit per second trial demonstrates that an air-filled core can support high-capacity transmission across more than 200 kilometers without electronic regeneration along the span. That is a meaningful engineering result. The technology still faces manufacturing costs, splicing challenges, standardization questions, and competition from improving conventional fiber. But AI is changing the value of network performance. When companies spend billions of dollars on processors, memory, and data centers, the cost of a better cable becomes easier to justify if that cable keeps the entire computing system operating more efficiently. The next AI bottleneck may not be the chip. It may be the connection between the chips. And China has just demonstrated a fiber designed to move that data through air instead of solid glass. So what do you think? Could hollow core fiber become the next major upgrade to global AI infrastructure? Or will manufacturing complexity keep it limited to specialized networks? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the future of computing will not depend only on how fast processors can calculate. It will also depend on how quickly information can move between them. A camera looks at a handwritten number. A radar signal bounces off an object. A laboratory instrument measures the optical fingerprint of a pharmaceutical sample. To a normal computer, these are three different worlds. The image is made from pixels. The radar arrives as a changing radio frequency waveform. The chemical sample appears as a spectrum, different wavelengths rising and falling according to the material being measured. Each normally requires its own sensor electronics, conversion hardware, and processing pipeline. But researchers in China have built one photonic intelligence chip designed to handle all three. Instead of forcing every signal through a conventional digital processor first, the system converts images, spectra, and radio frequency signals into a common optical language, light. Those optical patterns enter the chip through a single fiber. They are separated, weighted, and processed by microscopic waveguides. The result passes through an optical neural network and reaches a classification output with a measured response time of just 1.33 nanoseconds. 1.33 billionths of a second. The chip successfully classified handwritten images, recognized pharmaceutical spectra, and distinguished radar targets, and it performed part of that computation using only 29 femtojoules per operation. A femtojoule is 1/quadrillionth of a joule. This does not mean the chip can understand every image, identify every chemical, or operate a complete autonomous vehicle by itself. It is still a research prototype. The laboratory setup includes external light sources, amplifiers, and test equipment that would need to be reduced or integrated before practical deployment. But the achievement points toward a new kind of edge intelligence. A sensor may no longer need to capture information, digitize everything, send it to a processor, and wait for a response. It may process the signal almost immediately, using the physics of light before the data ever becomes a conventional stream of digital numbers. The delay hiding between a sensor and AI. Modern sensors generate enormous quantities of analog information. A camera receives changing light intensity. A radar antenna detects reflected electromagnetic waves. A spectrometer measures how materials absorb or reflect different wavelengths. Nature produces analog signals continuously. Computers prefer digital numbers. So before a conventional AI model can process the information, the sensor output must usually pass through several steps. First, the analog signal is sampled. Then, an analog to digital converter turns it into numbers. Those numbers move into memory. The processor retrieves them. Software reorganizes the data into a format the AI model can accept. Only then does inference begin. Each step adds delay. Each conversion consumes energy. And each movement of data creates another bottleneck. This may not matter when a cloud server has several seconds to analyze a photograph. It matters enormously when a robot must avoid an obstacle, a radar system must identify an approaching object, or a medical sensor must react immediately to a changing signal. At the edge, milliseconds matter. Sometimes microseconds matter. Researchers therefore want to move intelligence closer to the sensor, not inside a distant data center, not after a long digital pipeline, directly where the signal first arrives. The Chinese team's photonic edge intelligence chip, called PEIC, was designed around that goal. One chip, three different languages. The central problem was not only speed, it was compatibility. An image is spatial. Its information is arranged across two dimensions. A chemical spectrum is spectral. Its information is distributed across wavelength. A radar signal is temporal. Its information changes through time. These data types do not naturally fit into the same computing architecture. Trying to process all three with one ordinary analog circuit would be like asking one translator to interpret a photograph, a melody, and a weather map using the same alphabet. The researchers solved this by converting every input into a broad optical spectrum. They call the process modal fusion. For image data, the system uses a scattering structure. The image passes through an optical setup that converts spatial patterns into a unique spectrum. A different image creates a different spectral fingerprint. For chemical data, the input is already spectral. A pharmaceutical sample can absorb or reflect light differently depending on its composition. For radar, the radio frequency waveform is used to modulate an optical carrier. This converts time-domain radar information into sidebands distributed around an optical frequency. 3 original formats. 1 optical representation. Once every signal becomes a spectrum, all 3 can travel into the same chip through one fiber. That is the first major innovation. The chip does not need a separate entrance for every type of sensor. It asks the sensors to speak light. Why light changes the computation? Electronic processors perform operations by moving and switching electrical charge. They are extraordinarily capable, programmable, and mature. But moving charge creates resistance and heat. Digital systems also process many tasks through sequences of clocked instructions. Light behaves differently. Multiple wavelengths can travel through one waveguide at the same time without being processed one after another. This is called wavelength parallelism. Imagine one road carrying cars of many colors. An electronic system may inspect each car separately. A photonic system can route all the colors simultaneously according to their wavelength. That makes optical computing attractive for mathematical operations that repeat across large datasets. Neural networks depend heavily on those operations. They multiply inputs by weights, combine the results, and pass them through nonlinear functions. A conventional chip performs those multiplications electronically. A photonic chip can encode values into light intensity or phase, then let interference, routing, and detection perform part of the mathematics physically. The answer emerges from how the light propagates. In the PEIC, the first major processing stage is built around an arrayed waveguide grating. It is one of the most important components in the system. The prism built inside a chip. An arrayed waveguide grating, or AWG, behaves somewhat like an advanced microscopic prism. A normal prism separates white light into colors because different wavelengths bend differently. An AWG performs a related function, using many waveguides with carefully controlled lengths. Light enters the device and splits across an array of paths. Each path is slightly longer than the previous one, but light waves accumulate different phase delays. When those paths recombine, different wavelengths interfere constructively at different output ports. One wavelength travels toward one output. Another wavelength travels somewhere else. The researchers' AWG contained 185 arrayed waveguides and occupied roughly 1.5 by 1.5 millimeters. It separated the optical spectrum into channels spaced 100 gigahertz apart. But the component did more than detect wavelengths. The team also used it as a convolution engine. Convolution is one of the fundamental operations in machine vision and signal analysis. A small pattern, called a kernel, moves across the input and measures particular features. One kernel may respond strongly to edges, another may detect curves, another may identify a repeating frequency pattern. Instead of performing those calculations sequentially in digital logic, the PEIC weights different parts of the optical spectrum and routes them through the AWG. The optical energy arriving at each output represents the convolution result. The chip is sensing and computing in the same structure. That combination avoids moving raw sensor data into a separate processor before useful features can be extracted. Why 29 femtojoules matters. The researchers estimated that the sensing and convolution stage consumed around 29 femtojoules per operation. The number is almost too small to visualize. 1 femtojoule is 0.000000000000000000000001 joules. A common household light bulb uses tens of joules every second. The energy used in one optical operation is a microscopic fraction of that. This does not mean the complete laboratory system runs on 29 femtojoules. External lasers, amplifiers, control electronics, and supporting equipment consume far more power. The number applies to the optical computation itself. That distinction matters. A chip can have an extremely efficient core while the complete system remains bulky or power-hungry. Still, core efficiency is important because edge devices live under strict limits. A drone cannot carry a data center power supply. A wearable sensor cannot become hot against the skin. A small robot cannot devote most of its battery to converting and moving sensor data. If optical pre-processing can reduce the amount of digital work required later, the entire device may become more efficient. The light does not need to solve every problem. It only needs to remove enough work from the electronic processor to justify its presence. The part that makes it a neural network. Convolution alone is not enough. Neural networks also need nonlinearity. Without a nonlinear activation function, multiple processing layers collapse mathematically into one large linear transformation. The network cannot learn complex decision boundaries. Electronic AI chips implement nonlinear functions with transistor circuits and software instructions. Optical systems find this more difficult because light propagating through ordinary waveguides is naturally linear. Double the input and the output usually doubles. The PEIC uses a nonlinear activation layer built from photodetectors and microring modulators. The photodetector converts optical power into an electrical response. That electrical signal controls a ring-shaped optical device, producing a nonlinear change in the outgoing light. After this activation stage, a fully connected optical layer combines the extracted features and produces the final classification result. The output is physical. The researchers determine the result by identifying which output port receives the highest optical power. No additional digital post-processing is required for the final decision. That makes the system an end-to-end optical neural network, rather than just an optical filter connected to a conventional classifier. What 1.33 nanoseconds really means. The measured response time of the nonlinear activation unit was 1.33 nanoseconds. That number represents the critical response inside the optical neural network pipeline. It is not the same as saying the entire laboratory can classify 751 million completely independent images every second. The present proof-of-concept system operates in approximately the 100 MHz range. That means its practical repetition rate is closer to 100 million cycles per second. Still fast, but different from the simplest interpretation of 1.33 nanoseconds wide the gap. A complete system includes modulation, signal preparation, optical propagation, control, and repeated operation. The nonlinear ring modulator relies on carrier injection, which limits how quickly the full architecture can reset and process the next sample. The optical input itself can carry enormous bandwidth, potentially in the terahertz range, but the current nonlinear stage limits the full system's operational rate. Think of a warehouse with an extremely wide entrance but a smaller sorting station inside. Huge amounts of material can arrive. The sorting machine determines how quickly completed packages leave. Future nonlinear optical devices could increase that rate. For now, the measured nanosecond response demonstrates extremely low latency, while the system-level rate remains around 100 MHz. Both numbers are valuable. They simply describe different parts of the machine. Test 1. Recognizing images. For image classification, the researchers used handwritten digits. These are the familiar black and white numbers often used to test machine learning systems. The image was displayed through an optical setup and projected onto a random scattering chip. The scattering structure transformed the two-dimensional image into a spectral fingerprint. A handwritten 3 produced one pattern. A handwritten 8 produced another. Those spectra traveled through the fiber and into the PEIC. The chip extracted features using the AWG-based convolution stage, passed the signal through nonlinear activation, and produced a classification output. This approach is unusual because planar photonic chips struggle with two-dimensional images. A chip waveguide naturally guides light along one direction. Routing every pixel of a large image into separate paths would create a complicated maze of connections and crosstalk. The scattering approach compresses spatial information into the spectral domain. Instead of giving every pixel its own road, it transforms the entire image into a unique combination of wavelengths. The chip then analyzes that combination. It is less like looking at the image directly, and more like identifying the echo the image leaves in light. Test 2. Reading pharmaceutical spectra. The second task involved drug spectrum recognition. Different pharmaceutical samples produce different spectral signatures. A material may absorb strongly at one wavelength and weakly at another, creating a pattern that functions like an optical fingerprint. Traditional analysis may digitize the entire spectrum and send the values into a computer. The PEIC receives the spectral data in its native optical form. No image conversion is required. No radio frequency modulation is required. The spectrum travels directly into the chip. The AWG separates the wavelengths and performs the weighted feature extraction at the same time. This is one of the clearest examples of the architecture's advantage. The sensor output and the computing medium are already compatible. Light measures the sample. Light carries the information. Light performs much of the classification. Potential future uses could include compact pharmaceutical inspection, environmental monitoring, and wearable biochemical sensing. But the experiment did not prove that the chip can identify every unknown chemical. It classified samples within a defined research dataset. General chemical analysis would require larger training sets, careful calibration, and robust handling of noise and temperature changes. Test 3. Classifying radar targets. Radar presents a completely different challenge. A radar system transmits electromagnetic waves and measures how they return after hitting an object. The returned signal contains clues about shape, distance, motion, and orientation. Traditional radar processors digitize the waveform and perform signal processing operations electronically. That can consume significant power and add latency. The researchers modeled radar returns from different target geometries. These time-varying electrical signals drove an electro-optic phase modulator. The modulator placed the radar information onto light by creating frequency sidebands around an optical carrier. A more complicated radar waveform produced a different optical spectrum. The PEIC then classified the target by analyzing those spectral features. This approach could eventually support robotics, autonomous navigation, and compact sensing platforms. A machine could receive radar data and begin extracting target information almost immediately, without first sending every sample through a large digital processing chain. Again, the current experiment was controlled. The radar signals were modeled and generated using laboratory equipment. A real outdoor environment introduces rain, interference, multiple reflections, and unexpected objects. Practical deployment would require testing under those conditions. The chip can also learn. The researchers demonstrated both supervised and unsupervised learning. Supervised learning uses labeled examples. The network sees an input and is told the correct answer. It adjusts its internal weights to reduce future errors. Unsupervised learning works without explicit labels. The system searches for structure or clusters inside the data. Supporting both approaches matters because many edge environments do not provide perfectly labeled information. A sensor may encounter patterns that were never categorized in advance. The optical chip's weights are controlled through programmable phase-shifting elements. An FPGA-based electronic framework supplies control voltages, allowing the researchers to adjust the network during inference and training. This reveals an important truth about photonic AI. The system is not purely optical. Electronics still configure the chip, calibrate components, and control its weights. The advantage comes from assigning the right task to each domain. Electronics provide flexibility and memory. Photonics provides parallelism, bandwidth, and low-latency signal processing. The future may not belong to light instead of electricity. It may belong to systems that use both where each works best. What is still outside the chip? The laboratory demonstration relied on several external components. A broadband optical source generated the light, a programmable wave shaper created controlled spectra, an optical amplifier increased signal strength, a spatial light modulator helped generate image inputs, a waveform generator and phase modulator produced radar signals. These machines are useful for research because they can simulate many sensors and inputs. They are not intended to sit beside the chip in a finished robot. In a practical system, a camera, spectrometer, or radar front end would feed signals into a smaller integrated optical interface. The researchers also note that weak real-world signals may require amplification. Their current experiment used an external erbium-doped fiber amplifier. Future versions could integrate optical gain into a silicon nitride photonic circuit, reducing the need for bulky external hardware. That path is technically plausible. It is not yet completed. The chip at the center is compact. The entire laboratory around it is not. This is common in early semiconductor research. The first transistor needed a room of test equipment. Commercial value arrives when the surrounding system shrinks. Why this could matter most at the edge? Cloud AI can tolerate complexity. A data center has powerful cooling, large power supplies, and racks of supporting electronics. Edge devices do not. An autonomous drone has limited battery capacity. A medical wearable must remain small. A factory sensor may need to react without depending on an internet connection. A vehicle cannot send every radar reflection to a distant server before deciding whether to brake. These devices need local intelligence, but local intelligence creates a trade-off. More processing increases power consumption. Lower power often means slower response. Photonic edge computing aims to weaken that compromise. Raw analog information can be converted into an optical spectrum, processed in parallel and classified with extremely low latency. Only the final result may need to reach the electronic controller. Instead of sending a complete radar waveform to the CPU, the optical front end could report a target category. Instead of digitizing every point in a chemical spectrum, it could report whether a sample matches a known pattern. The processor receives less data. The device responds faster. The battery lasts longer. That is the vision. The honest catch. The PIC does not replace a general CPU, GPU, or AI accelerator. It is specialized hardware. Its strength comes from performing a limited set of operations extremely efficiently. Changing the task requires new training and reprogrammed weights. Some applications may require different optical interfaces. The chip's demonstrated network is also far smaller than the giant models used in modern generative AI. It is designed for classification at the edge, not for writing essays or generating video. Accuracy must remain stable outside the laboratory. Photonic components can drift with temperature. Manufacturing differences can change phase and transmission. Calibration circuits can correct some variation, but they add complexity. The 1.33 nanosecond figure should also be interpreted carefully. It describes a measured component response within the network, not the entire end-to-end world-to-decision time of a finished product. And while 29 femtojoules per operation is excellent for the optical core, the complete system's energy consumption includes light generation, amplification, and control electronics. The research proves a powerful architecture. Commercial engineering must prove the product. My take. My view is that the most important part of this breakthrough is not the 1.33 nanosecond number by itself. It is the decision to unify very different sensors before computation begins. Images, spectra, and radar signals normally travel through separate pipelines. The researchers converted all three into one optical language and fed them through one photonic neural network. That could be more important than building the fastest possible chip for only one sensor. Real machines use multiple senses. A robot may need a camera in daylight, radar in fog, and chemical sensing in a hazardous environment. Today, each sensor often brings separate converters, processors, and software. A common optical intelligence layer could simplify that architecture, but the phrase "could" matters. This technology still needs integration, environmental testing, larger networks, and lower-cost packaging. The current system is not ready to appear inside a smartphone or vehicle tomorrow. Even so, the direction is convincing. Sensors naturally produce analog signals. Light naturally carries enormous parallel bandwidth. Neural networks naturally depend on repeated matrix and convolution operations. The PEIC brings those properties together. It does not wait for the world to become digital before intelligence begins. It starts computing while the information is still light. A camera image becomes a spectrum. A radar echo becomes a spectrum. A pharmaceutical sample becomes a spectrum. One fiber carries them. One chip separates them. One optical network decides what they represent. And one part of that decision responds in 1.33 nanoseconds. So what do you think? Will photonic chips become the standard front end for cameras, radar, and scientific sensors? Or will the difficulty of lasers, calibration, and packaging keep conventional electronics in control? Let me know your view in the comments. And if you want more grounded stories about the chips, materials, and hidden engineering breakthroughs reshaping computing, subscribe to Eastern Engine, because the next generation of AI may not begin by converting the world into numbers. It may begin by letting light understand the world first. China's largest electric vehicle company has spent years proving that it can build batteries, motors, power electronics, and complete cars at enormous scale. Now BYD is moving deeper into the part of the vehicle that may matter most next decade, the computer that controls intelligent driving. The company has unveiled its Xuanji A3 processor. BYD describes it as China's first domestically designed 4-nanometer chip built specifically for advanced driving systems. One chip delivers around 700 trillion operations per second. A 3-chip configuration exceeds 2,100 TOPS, and BYD says the processor has already entered chip-level mass production. A Chinese automaker is no longer satisfied with buying batteries, sensors, software, and processors from separate suppliers. BYD wants to control the complete stack. But the headline needs an important qualification. The Xuanji A3 has not yet been independently proven to beat NVIDIA's best automotive platform. Mass production of the chip does not mean millions of BYD vehicles are already using it. and a 4-nanometer design does not prove that the processor is fabricated entirely with Chinese manufacturing equipment. Still, BYD is clearly trying to turn the vehicle into a vertically integrated platform, with the processor, software, sensors, battery, motors, and architecture developed around one system. The question is whether BYD can use its scale to make those chips an industry standard. Why BYD built its own car brain? Modern vehicles are becoming computers on wheels. Cameras, radar, LiDAR, ultrasonic sensors, navigation systems, battery controls, entertainment displays, and driver assistance software all generate enormous amounts of data. That information must be processed quickly enough for the vehicle to recognize lanes, detect pedestrians, predict nearby traffic, and decide when to brake or change direction. Traditional vehicles divided these tasks among many separate control units. Advanced driving requires tighter coordination, larger neural networks, millisecond decisions, and safe operation even when one component fails. This is why automotive computing is moving towards centralized platforms. Instead of dozens of isolated control units, more functions are combined inside a smaller number of powerful computers. The Xuanji A3 is designed for that transition. It is the centerpiece of a compact central computing platform, intended to connect intelligent driving, the digital cockpit, and core vehicle control functions. That gives BYD more control over how information moves through the car. It also allows the company to optimize the processor around its own vehicles, instead of adapting every design to a general-purpose chip from another supplier. What 700 TOPS really means. The number attached to the Xuanji A3 is 700 TOPS. TOPS means trillions of operations per second. It is commonly used to describe the peak performance of artificial intelligence accelerators. A higher number can support more camera feeds, larger neural networks, or several models at once. But TOPS should not be treated like horsepower. Two chips with the same advertised number may deliver very different real-world performance. The result depends on numerical precision, memory bandwidth, software efficiency, thermal limits, and how much of the processor can actually be used by the workload. BYD says the Xuanji A3 includes a 16-core CPU and around 273 gigabytes per second of memory bandwidth. One chip provides roughly 700 TOPS, while three working together exceed 2,100 TOPS. That is an enormous figure for a passenger vehicle. However, three chips do not automatically behave like one perfectly unified processor. The system must distribute work efficiently, move data between chips, avoid duplication, and manage power and heat. The important question is not only how much peak performance exists, it is how much useful performance the software can extract in real traffic. BYD says combining the chip with its own algorithms improves computing utilization. That is one reason vertical integration matters. The company can design models around the exact structure of the processor, then adjust the hardware around the software's needs. Why three chips? Most vehicles will not require 2,100 TOPS. A basic assisted driving system can operate with far less. Premium vehicles, however, may run cameras, LiDAR, radar, perception models, parking, driver monitoring, and cockpit intelligence simultaneously. Three chips give BYD room to divide workloads and create redundancy, with separate processors potentially handling perception, planning, cockpit functions, or backup capacity. Level 3 and Level 4 systems require more than speed. Level 3 automation can allow the vehicle to control itself under limited conditions, but the human driver may still need to take over. Level 4 systems are designed to operate without human control inside defined areas or situations. Supporting those levels requires fail operational design. If one component stops working, the system must remain safe. Extra processors, independent power paths, redundant sensors, and multiple communication networks can all contribute. BYD says the Xuanji A3 is designed to support future Level 3 and Level 4 systems. That does not mean every vehicle carrying the chip will immediately become autonomous. Regulation, software validation, sensors, mapping, and road conditions still determine what the car is legally and technically allowed to do. The NVIDIA comparison. NVIDIA has spent years building one of the strongest automotive computing ecosystems in the world. Its drive platform combines processors, networking, development tools, simulation software, and artificial intelligence models. Automakers do not simply purchase a chip. They purchase access to an established software platform with global engineering support. That is hard to replace. BYD's advantage is different. It does not need to sell the Xuanji A3 to every automaker in the world to make the project successful. BYD can deploy the chip across its own enormous vehicle portfolio. That creates a guaranteed internal customer. Each vehicle can generate data, receive software improvements, and reuse parts of the same architecture. NVIDIA must support many brands, while BYD can optimize around its own sensors, batteries, motors, networks, and factories. This does not prove BYD has beaten NVIDIA. NVIDIA still has deeper experience in AI software, simulation, developer tools, and advanced computing. But BYD may not need to win a direct benchmark battle. It may only need a processor that is powerful, efficient, reliable, and cheap enough for its own cars. The mass production claim. BYD says the Xuanji A3 has entered mass production. That claim must be interpreted carefully. Chip-level mass production means the processor has moved beyond a small laboratory sample. It suggests that the design has completed major validation steps and is being manufactured in meaningful quantities. But it does not necessarily mean the chip is already installed across BYD's current vehicle range. Automotive deployment moves slowly because chips must survive vibration, humidity, voltage changes, extreme temperatures, and long service periods. The full system also needs software validation, sensor integration, cybersecurity testing, and safety approval. Reports indicate that the first major vehicle deployments may arrive later, potentially beginning with premium BYD brands before spreading into higher volume models. So the breakthrough is real, but the rollout should not be exaggerated. The Xuanji A3 is entering the production phase. Its true impact will become visible when BYD reveals which vehicles use it, how many chips are installed, and what driving functions are activated. Who actually manufacturs it? Another major question is fabrication. BYD designed the Xuanji A3, but designing a chip and manufacturing it are different businesses. A 4-nanometer processor requires advanced lithography, materials, process control, packaging, and testing. BYD has extensive semiconductor operations, especially in automotive power electronics and mature node components. But there is no clear evidence that BYD manufactures this particular processor entirely inside its own factories. Chinese automakers and chip designers still depend heavily on outside foundries for leading-edge production, including manufacturers in Taiwan and South Korea. That means the Xuanji A3 is a major step toward design independence, but not necessarily complete supply chain independence. A company can control the architecture, software, and roadmap while still relying on foreign fabrication. That is strategically valuable, but trade restrictions or supply disruptions could still affect production. BYD's long-term challenge is larger than designing one successful chip. It must secure fabrication capacity, advanced packaging, memory, and automotive-grade testing at the scale required for millions of vehicles. BYD's vertical integration advantage. BYD began as a battery company. It later expanded into vehicles, electric motors, power electronics, semiconductors, energy storage, and manufacturing equipment. This vertical integration has helped BYD lower costs and react when supply chains become unstable. The Xuanji A3 extends that strategy into advanced computing, connecting its batteries, electric drive systems, vehicle platforms, and assisted driving software. The driving system could share information more directly with braking, steering, suspension, battery management, navigation, and the cockpit. That could reduce latency and simplify software updates. It may also lower cost. A processor designed for BYD's exact requirements may avoid features the company does not need. Once production reaches sufficient scale, BYD can spread development costs across a very large number of vehicles. This is where BYD may have an advantage over smaller automakers. Designing an advanced chip costs an enormous amount of money. The investment only makes sense if the company can deploy enough units to recover the expense. BYD has the scale to use the same architecture across several brands, vehicle classes, and price categories. The Chinese chip race. BD is not alone. Chinese automakers are rapidly developing their own intelligent driving processors or working with domestic semiconductor companies. NIO has introduced its own driving chip. XPeng has developed the Turing processor. Li Auto is working on its Mach series hardware. Geely, Huawei, Horizon Robotics, and other companies are also building automotive computing platforms. This competition shows how important the car chip has become. Automakers once differentiated themselves through engines, transmissions, and chassis tuning. In the electric vehicle era, batteries and manufacturing became central. The next competitive layer may be computing. A company that controls the processor can decide how quickly features are added, how data is handled, and how dependent the vehicle remains on suppliers. But fragmentation creates risk. Separate tools and operating systems increase costs and make every platform harder to support. Some automakers may eventually discover that designing chips is too expensive. BYD is better positioned than most because of its scale and its ability to connect the chip directly to its own vehicles. The real economic impact. The biggest opportunity may not be the most expensive autonomous vehicle. It may be bringing advanced computing into affordable cars. BYD has already pushed driver assistance features deeper into mass market segments. If the company controls the processor, it can reduce the amount paid to foreign suppliers and decide how aggressively to spread intelligent driving hardware across its lineup. That could pressure competitors. A feature that begins in a premium vehicle can move into mid-range models once production scales, just as Chinese automakers did with batteries, fast charging, displays, and electric drivetrains. If BYD installs its own chip across hundreds of thousands of vehicles, it gains an enormous data and software advantage. More vehicles create more data, better models, more useful hardware, and a stronger platform. That feedback loop matters far beyond the TOPS number. What remains unproven? Several important questions remain unanswered. We do not yet have independent benchmarks showing how the Xuanji A3 performs against NVIDIA Drive Thor, Huawei's automotive platforms, or rival Chinese chips under identical conditions. We do not know the final production cost, real-world power use, manufacturing yield, or volume of secure foundry capacity available to BYD. And we do not know how quickly the chip will move from premium vehicles into mass-market models. The real test will happen on the road. Can the system recognize unusual objects? Can it handle rain, glare, construction zones, and unpredictable drivers? Can it fail safely? Can BYD maintain the software for years? A large TOPS number cannot answer those questions. My take is that the Xuanji A3 is not important because BYD has already defeated NVIDIA. It is important because BYD is removing another external dependency from the vehicle. The company already controls batteries, motors, power electronics, and much of its manufacturing. Now it is attempting to control the computing architecture that will define intelligent cars. A single chip delivering around 700 TOPS is significant. A 3-chip system exceeding 2,100 TOPS is visually impressive, but the real advantage is integration. BYD can design the processor, algorithms, sensors, vehicle controls, and production process as one system. That is difficult for a traditional automaker coordinating outside suppliers. Limits remain. The chip may rely on foreign fabrication. Mass production does not equal mass deployment. Level 3 and Level 4 support does not mean fully autonomous. BYD cars are already operating everywhere, and NVIDIA remains a much stronger global computing platform. But BYD does not need to replace NVIDIA worldwide. It needs to make outside processors less necessary inside its own vehicles. If it succeeds, the company will not simply be an electric car manufacturer. It will become a large-scale automotive computing company with millions of vehicles serving as the deployment platform. That could reshape global competition. So what do you think? Can BYD turn the Xuanji A3 into a genuine alternative to NVIDIA's automotive processors? Or will manufacturing limits and software complexity prevent the chip from reaching its full potential? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because BYD built its rise on batteries, but its next advantage may come from the computer controlling the car. Picture the most valuable company in the history of the world being told it's no longer welcome in the largest technology market on Earth. Not fined, not warned. Shown the door. That's what just happened to NVIDIA in China, the company whose chips power virtually every artificial intelligence system on the planet. The company that became worth more than the entire economies of most countries has just been pushed out of China by the Chinese government itself. Beijing has effectively told its biggest technology giants, the Alibabas and ByteDances and Tencents of the world, to stop buying NVIDIA. Cancel the orders, sell off whatever inventory is left, and from now on, you buy Chinese. And here's the part that makes this almost poetic. For 3 years, the story was the exact reverse. It was the United States slamming doors on China, banning the sale of the best NVIDIA chips, trying to choke off China's access to the silicon that powers modern AI. The whole world watched America wield NVIDIA like a weapon. And now, in a twist almost nobody saw coming, China has taken that same weapon, turned it around, and pointed it the other way. We don't want them anymore, Beijing is essentially saying. We'll build our own. It is one of the most dramatic reversals in the entire technology war. And this is exactly the kind of story where the headline and the reality pull in different directions. The truth underneath is far stranger and more interesting than China bans NVIDIA at the end. There's a secret dependency Beijing isn't advertising. There's a question of whether this is confidence or a calculated bluff. And there's a real chance this backfires spectacularly. I'm going to walk you through all of it. By the end, you'll understand what actually happened, why China would reject the best chips on Earth, who's stepping in to replace them, and whether this is a masterstroke or a massive gamble. Let's get into it. To feel how strange this moment is, you have to rewind and remember how we got here. Because the whole thing reads like a story with a twist ending. Act 1 belonged entirely to America. Worried that advanced AI could hand China a military and economic edge, the United States rolled out wave after wave of export controls. The crown jewels of NVIDIA's lineup, the chips that train the world's most powerful AI, were forbidden from sale to Chinese buyers. Washington even leaned on NVIDIA to create deliberately weakened, China-only versions of its chips, throttled down to stay just inside the legal lines. The message was unmistakable. You may buy our scraps, not our best. For a while, China took it. Chinese companies bought the watered-down chips because something was better than nothing. They grumbled, they stockpiled, they waited for the politics to shift. Everyone assumed that the moment America loosened the rules, Chinese firms would come sprinting back to NVIDIA with open wallets. Then came the twist. In a surprise move, the US actually approved the export of a more capable NVIDIA chip, the H200, to China. The door cracked back open. And this is the moment everyone expected China to pour through it. Instead, Beijing slammed it shut from its own side. China's government turned around and told its companies, don't buy them. Don't buy the H200. Don't buy the consumer cards either. We're not interested. According to reporting from the Financial Times, Chinese firms that had even placed orders were told they couldn't follow through. American officials confirmed the bizarre situation out loud. The US Commerce Secretary publicly acknowledged that NVIDIA still hadn't sold the chips because China itself was blocking the imports. Let that sink in. America spent years trying to stop China from buying these chips. Now America is willing to sell, and China is refusing to buy. The jailer unlocked the cell and the prisoner said, "No thanks, I built my own door." That is the reversal. And it raises the obvious, almost dizzying question. Why on earth would China reject the very technology it spent years fighting to get? It sounds insane at first. Turning down the most advanced AI chips on the market is like a thirsty traveler refusing a glass of water. But once you understand Beijing's reasoning, it stops looking crazy and starts looking like cold, deliberate strategy. There are three forces driving it, and they stack on top of each other. The first is the hard lesson of dependence. China learned something painful over the last few years. Relying on a foreign supplier for a critical technology is a leash, and the other end of that leash is held by your rival. One day, the chips flow. The next day, a politician in Washington signs a paper and they stop. You can't build the future of your entire economy on a supply line someone else can cut whenever they please. From Beijing's view, every NVIDIA chip bought is a vote of dependence, and every Chinese chip bought instead is a step toward never being strangled again. Even if the domestic chip is worse today, it's yours. Nobody can take it away. The second force is more cold-blooded: leverage. By refusing to buy even the chips America is now willing to sell, China sends a loud, deliberate signal. We don't need you. Whether or not that's fully true, saying it loudly changes the balance of power at the negotiating table. It tells Washington that the export control weapon is losing its bite, that the threat of being cut off doesn't terrify Beijing the way it once did. Some analysts believe this entire move is partly theater for exactly that reason. A power play designed to win better terms in the broader trade war by projecting total independence. And the third force is the most practical of all: protecting the home team. By clearing NVIDIA off the field, Beijing hands its own chipmakers something priceless: a giant, guaranteed captive market, with the most fearsome competitor suddenly removed. Imagine being a young company trying to sell soda in a country where Coca-Cola has just been ordered to leave. Overnight, every thirsty customer is yours. That's what China just did for its domestic chip industry. It didn't just block a rival, it gifted its own companies the single largest AI market on the planet, with no NVIDIA in the room. Three motives: security, leverage, and protectionism, pointing in the same direction. But a strategy is only as good as the alternative behind it. Kicking out NVIDIA only makes sense if someone at home can actually fill the hole. So who's stepping up? This is where the story gets genuinely interesting, because China isn't betting on one savior. It's unleashing an entire roster of domestic challengers, each circling the space NVIDIA left behind. At the front of the pack, unmistakably, is Huawei. If you've watched this channel, you know Huawei has become the central character in China's chip saga. the company America sanctioned hardest, which somehow keeps clawing its way forward. Its Ascend line of AI chips is now positioned as the literal backbone of China's state-backed AI ambitions. And Huawei has a clever answer to a real weakness. Individually, its chips still can't match NVIDIA's best one-on-one. So instead of fighting that battle, Huawei changed the rules. It built what it calls supernodes, systems that lash thousands of its own chips together into a single massive cluster. The logic is blunt but effective. If one of your chips is weaker, use far more of them, wired together so tightly they act as one brain. Huawei's deputy chairman openly admitted a single Ascend can't beat a single NVIDIA chip, then claimed its supernode clusters are the most powerful in the world anyway. Brute force, engineered cleverly to turn a weakness into a non-issue. But Huawei is far from alone, and that's the part most coverage misses. There's a whole ecosystem rising behind it. Cambricon, a Chinese AI chip specialist, posted a revenue surge of over 4,000% in a recent period. Not a typo, 4,000, as orders flooded in from companies scrambling for NVIDIA alternatives. Baidu has its own Kunlun chips, already powering a training system built from tens of thousands of processors. Alibaba's chip division, T-Head, is designing its own silicon. So is Tencent. The giants that used to be NVIDIA's biggest Chinese customers are now, one by one, becoming NVIDIA's replacements, building in-house the very thing they used to import. And there's a deeper layer still, one that hints at how far China's ambitions really reach. Some of these companies, like Alibaba's T-Head, are building their chips on something called RISC-V, an open, free chip architecture that anyone can use, completely outside the control of any single Western company. It's a quiet but profound move. It's not just about replacing NVIDIA's chips. It's about escaping the foundations those chips are built on entirely, owning not just the engine, but the very blueprint of the engine. China isn't trying to swap one dependency for another. It's trying to own the whole stack, top to bottom. So the replacements are real, numerous, and backed by the full weight of the state, which makes it sound like a done deal. It is not. And this is where I have to be completely honest with you. Here's the part the triumphant headlines leave out. And it's the most important section in this whole video, so stay with me. Despite the ban, despite the bravado, despite the "we don't need you" messaging, China's AI industry is still, right now, deeply and quietly dependent on NVIDIA. Not a little, enormously. Look past the announcements at the actual numbers. By credible estimates, somewhere around 75% of the chips training AI models inside Chinese data centers still run on NVIDIA's technology. 3 out of every 4. The company has shipped more than 1 million of its export-compliant chips into China since late 2024, reportedly outpacing its closest domestic rival's shipments by something like 5-1. So even as Beijing publicly shoves NVIDIA out the front door, an enormous amount of NVIDIA silicon is already humming away inside the country, doing the heaviest lifting in Chinese AI. And there's a crucial technical reason for this, one we've touched on before. There are 2 halves to building an AI: training, the brutally demanding process of creating the model's intelligence, and inference, the lighter job of running it for users. China's homegrown chips have become genuinely competitive at inference, but for the hardest, most punishing work, frontier training, they still lag. As one analyst put it bluntly, Chinese companies can keep the lights on with domestic chips, but they can only sustain truly frontier-level progress with continued access to NVIDIA hardware. The domestic chips can run the house, they can't yet build the mansion. So the honest picture is full of tension. China is banning the very chips it secretly still leans on. It's projecting total independence, while 3/4 of its most important AI work quietly depends on the rival it's pushing out. That's not a contradiction born of confusion. It's a high-stakes bet. Beijing is essentially saying, we will force ourselves to need you less by cutting you off now, and trust that the pressure makes our own industry strong enough, fast enough, to survive the gap. It's ripping off the band-aid before the wound has fully healed, gambling that the shock accelerates the cure. That's a bold, genuinely risky move, and it might just work, because, strangely enough, it's worked before. Here's the thing that should make anyone betting against China pause. We have seen this exact movie several times already, and it keeps ending the same way. Think back over the stories that keep surfacing in this space. Cut off from the world's best chip-making machines, China was told it could never make advanced chips, then it found a way to manufacture them anyway, using older equipment and sheer engineering stubbornness. Told it couldn't build a frontier AI model without American software, a Chinese lab went and built one that runs without it. Told its supercomputers would stall without forbidden processors, China built a world-class one on entirely different chips. Over and over, the same shape, A wall goes up to contain China, and instead of stopping, China is forced to build the very thing the wall was meant to deny it, and sometimes ends up with an independent capability it would never have bothered to create if the wall had never existed. This is the deep irony at the center of the entire technology war, and it's worth saying plainly. Restrictions meant to keep China dependent have, again and again, become the exact pressure that forced China toward independence. The leash, pulled too hard, taught the animal to live without one. Necessity didn't just inspire invention here. It practically mandated it, funded it, and gave it a guaranteed market. The Nvidia ban is simply the boldest version of this pattern yet. Instead of waiting for America to cut the cord, China is cutting it itself, on its own timeline, deliberately, to force its domestic industry to grow up faster. It's a country betting that self-inflicted pressure now is better than foreign-controlled vulnerability later. And given the track record, given how many times the impossible wall has turned into a merely expensive speed bump, betting confidently against China's ability to adapt has been a losing position for a while now. But, and I promised you honesty, confidence based on a pattern is not the same as certainty. This bet is bigger than the others, and the ways it could go wrong are real. Let me give you the other side, because no honest analysis skips it. The most obvious danger is the training gap. If Chinese chips genuinely can't handle frontier-level AI training yet, and the evidence says they largely can't, then cutting off Nvidia too aggressively could leave Chinese AI labs starved of the horsepower they need to keep pace with the absolute cutting edge in America. While a US lab trains its next giant model on a mountain of Nvidia's best, a Chinese lab might be stuck doing the same job slower, more expensively, on chips that aren't quite there. In a race measured in months, a self-imposed handicap is a serious risk. China could win independence and lose the speed race at the same time. The second danger is that this is partly a bluff that could get called. If a big slice of the motivation here is negotiating leverage, projecting we don't need you to win a better trade deal, then it only works as long as the bluff holds. If China's domestic chips stumble, if the supernodes can't scale, if the training gap widens instead of closing, then the we don't need Nvidia posture collapses, and Beijing is left having rejected chips it actually needed purely for a power play that didn't pay off. And there's a quieter problem. Even China's homegrown champions still aren't fully homegrown. Some of the most advanced domestic chips still rely, somewhere in the supply chain, on manufacturing tools and processes that trace back to foreign technology China doesn't yet fully control. True, total independence, every layer, every machine, every line of code domestic, is still a goal, not a finished reality. Declaring independence and achieving independence are different things, and the gap between them is where this bet could unravel. So this is genuinely a gamble. A bold, calculated, pattern-backed gamble, but a gamble all the same. It could accelerate China's chip industry by years, or it could leave it exposed at the worst possible moment. Probably, the truth will land somewhere in between, and we'll spend the next 2 years watching which way it tips. Here's my honest opinion. I think both of the easy reactions to this miss the point, and the interesting truth lives in the friction between them. The triumphant take, China just crushed Nvidia and declared total independence, is getting way ahead of reality, because 3/4 of China's serious AI work still quietly runs on Nvidia, and the hardest training problems remain unsolved at home. Anyone telling you Nvidia is finished in China is ignoring the silicon already humming inside Chinese data centers right now. But the dismissive take, it's just posturing, China still needs Nvidia, ignore it, is the bigger mistake, and it's the one that's been wrong over and over, because it focuses on the gap that exists today and ignores the direction everything is moving. The single most revealing fact in this entire story isn't a chip spec or a market share number. It's this. When America finally offered to sell, China chose to refuse. That choice tells you Beijing has decided, at the highest level, that the future is worth a painful present, that it would rather struggle now on its own chips than stay comfortable on someone else's. Countries don't make that choice from weakness. They make it from a cold, long-term confidence that the gap is closable. And that's what makes this the most fascinating move in the whole technology war so far. It's not a country reacting to a wall someone built around it. It's a country building its own wall, on purpose, to force itself to become the thing it wants to be. That's either visionary or reckless, and honestly, it might be both at once. The pattern says don't bet against it. Common sense says the risk is real. The only thing I'm certain of is that we're watching one of the boldest industrial gambles of our lifetime play out in real time. So here's my question for you, and I really want your honest answer. Was banning Nvidia a brilliant power move, forcing China's industry to grow up fast and breaking its dependence for good, or a reckless gamble that could leave Chinese AI stuck in the slow lane right when the race is at its most intense? Did China just free itself, or just shoot itself in the foot? Drop your real take in the comments. I read every single one, and I have a feeling this one is going to spark a serious debate down there. If you want to keep following this, the bans, the breakthroughs, the bold gambles the rest of the world keeps underestimating until it's too late, subscribe to Eastern Engine and hit the notification bell. Chips, AI, the entire foundation of the modern world is being rewritten right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. Have you ever wondered why NVIDIA keeps building faster and faster AI chips, yet the biggest AI companies still complain their systems are waiting around instead of actually computing? It turns out the biggest problem isn't always the GPU anymore. Sometimes, it's what connects them. And now China says it has built an AI network that moves information so quickly it could remove one of the largest bottlenecks in modern artificial intelligence. If that's true, it changes far more than benchmark scores. It changes how future AI supercomputers are designed, how much they cost to build, and who can compete in the global AI race. Today, we're breaking down why this network matters, why NVIDIA has spent years trying to solve the same problem, and why China's latest breakthrough has the entire semiconductor industry paying attention. When most people hear about AI hardware, they immediately think about GPUs. NVIDIA has become almost synonymous with artificial intelligence because its graphics processors train and run many of the world's largest language models. Every headline talks about faster chips, more memory, more tensor cores, and larger AI clusters. But here's something many people don't realize. The bigger an AI system becomes, the less important the individual chip is compared to the speed at which thousands of chips communicate with each other. Imagine you own the fastest sports car in the world. It can reach incredible speeds in seconds, but then you place that car in the middle of a traffic jam where every road is clogged. Suddenly, it doesn't matter how powerful the engine is because it spends most of its time waiting. That's exactly what happens inside massive AI data centers. Thousands of incredibly powerful processors constantly need to exchange enormous amounts of information. If those connections become congested, the expensive GPUs sit idle waiting for data instead of performing calculations. That waiting time is incredibly expensive. Some of today's largest AI clusters cost hundreds of millions, sometimes even billions of dollars to build. Every second a GPU isn't fully utilized represents wasted money, wasted electricity, and slower AI development. This has become one of the biggest engineering challenges in modern computing. For years, NVIDIA has been attacking this problem with technologies like NVLink and InfiniBand. These aren't GPUs themselves, they're the highways connecting those GPUs together. The faster the highway, the more efficiently every processor can work. Building these high-speed connections has become almost as important as designing the chips themselves. Now China appears determined to solve this challenge from another direction. Rather than simply building faster processors, Chinese researchers and technology companies have been investing heavily in networking technologies specifically designed for artificial intelligence workloads. Their goal isn't just faster downloads or faster internet. Their goal is dramatically reducing the time it takes for thousands of AI accelerators to exchange data while training enormous neural networks. That sounds simple until you realize just how much information modern AI systems move every second. Training a cutting-edge language model isn't like downloading a movie. Imagine thousands of processors all solving different pieces of the same giant puzzle simultaneously. After each step, every processor needs to share what it learned with thousands of others before moving to the next calculation. This exchange happens millions of times during training. If even one part of that communication slows down, the entire system becomes less efficient. That's why networking has quietly become one of the most valuable technologies in artificial intelligence. The interesting part is that networking has traditionally received far less public attention than GPUs themselves. Headlines celebrate trillion-parameter models and record-breaking chips, but the infrastructure connecting everything together usually stays behind the scenes. Yet many engineers argue these connections are becoming just as important as compute power itself. China clearly recognizes this trend. Over the last several years, enormous investments have gone into domestic networking equipment, optical communication systems, advanced switching technologies, silicon photonics research, and ultra-fast data center architectures. Instead of relying entirely on imported networking ecosystems, Chinese companies have increasingly focused on building their own complete AI infrastructure stack. That strategy mirrors what we've already seen happen across semiconductors. First came investments in domestic chip manufacturing, then memory, then advanced packaging, then AI accelerators. More recently, optical communication and photonic technologies began receiving massive attention because engineers realized future AI systems would eventually hit limits not inside processors, but between them. This is exactly where the latest reports become so interesting. Instead of asking how to make a single GPU faster, researchers are asking something much bigger. What if every GPU could spend dramatically less time waiting? Even a relatively modest improvement in communication efficiency can produce surprisingly large improvements across enormous AI clusters. Think about a warehouse filled with thousands of workers. If every employee loses only 10 seconds waiting for supplies every hour, the total lost productivity becomes enormous. Now imagine eliminating most of that waiting time across an operation employing thousands of people. The overall improvement becomes much larger than those 10 seconds initially suggested. Large AI clusters behave similarly. Tiny communication improvements, repeated millions of times, can save extraordinary amounts of computation. This is why companies around the world are investing billions into networking technology. It's also why China's latest efforts have attracted international attention. Many analysts believe future AI competition won't simply revolve around who builds the fastest processor. Instead, it may depend on who builds the fastest complete system. That's a major difference. A complete AI system includes processors, memory, networking, storage, cooling, software, power management, manufacturing capability, and increasingly, optical communication. Whoever optimizes every layer gains advantages that individual component improvements alone can't match. China appears increasingly focused on this systems approach. Rather than chasing one spectacular headline after another, many recent projects fit together like pieces of a much larger strategy. You've probably noticed this pattern if you've watched several videos on this channel. First, there were domestic AI accelerators, then high-speed memory developments, then glass-based technologies, then advanced packaging, then ultra-fast optical fibers, then AI servers, then CPU breakthroughs, now networking. Individually, each story seems impressive. Together, they begin forming an ecosystem. That's important because AI isn't powered by isolated inventions anymore. It's powered by entire infrastructures. This also explains why many governments have started viewing artificial intelligence less like traditional software and more like national infrastructure. Countries aren't simply competing to build chatbots. They're competing to build entire computing ecosystems capable of supporting future industries. Healthcare, autonomous transportation, scientific research, drug discovery, manufacturing, defense applications, climate modeling, financial systems. Every one of these increasingly depends on artificial intelligence processing massive data sets at extraordinary speeds. And every one of those workloads depends on communication. The challenge becomes even greater as AI models continue growing. A decade ago, training systems containing millions of parameters seemed impressive. Today, billions have become common. Trillions are already appearing. Future systems may become even larger. As models expand, communication requirements grow dramatically. Moving that information efficiently becomes one of the defining engineering challenges of modern computing. That's why networking engineers have suddenly become some of the most valuable specialists in artificial intelligence. They're building invisible technologies that determine whether tomorrow's AI systems spend their time calculating or waiting. This is where optical communication enters the conversation. Traditional electrical connections eventually face physical limitations involving heat generation, signal degradation, and energy consumption. Optical communication offers an alternative by transmitting enormous amounts of information using light rather than conventional electrical signaling. China has invested heavily in this area. Recent announcements involving air-filled optical fibers, photonic devices, advanced optical switching, and integrated communication technologies all point toward one long-term objective: move vastly more information while consuming less energy. If successful, that combination becomes extremely attractive for AI infrastructure. Energy consumption has quietly become one of artificial intelligence's biggest challenges. Every new generation of larger AI clusters requires enormous amounts of electricity. Data centers already consume significant power. Future AI facilities may require even more. Improving communication efficiency doesn't only accelerate computation, it can also reduce wasted energy by allowing expensive processors to spend less time idle. That creates a double benefit: higher performance, lower operational cost. Those economics matter enormously. The largest technology companies now spend billions constructing AI infrastructure. Even relatively small percentage improvements can translate into hundreds of millions of dollars over time. This explains why networking technologies have become strategic assets rather than supporting components. The companies that master them may gain advantages extending far beyond raw processor performance. And according to recent developments, China clearly wants to compete at every layer of that stack. So what exactly makes this reported AI network different from the traditional approach? Instead of treating networking as an accessory to AI hardware, the latest Chinese developments suggest networking is becoming the foundation around which future AI systems are designed. The objective isn't simply increasing raw bandwidth. Engineers are trying to reduce latency, improve synchronization between thousands of processors, eliminate communication bottlenecks, and make every computing node behave almost like part of one enormous machine. That distinction is incredibly important. Imagine trying to coordinate 10,000 people on a project. Communication is fairly easy. Now imagine coordinating 10,000 people who all need updated information every few milliseconds. Suddenly, communication itself becomes the biggest challenge. Modern AI clusters face exactly that problem. Every training cycle requires processors to exchange parameters, gradients, weights, and intermediate calculations. As clusters grow larger, the amount of communication grows even faster than the amount of computation. That's why networking has become one of the hottest areas in semiconductor research. Several Chinese companies have already demonstrated advanced AI servers, domestic switching equipment, optical interconnect technologies, and high-speed communication platforms. While each announcement might seem unrelated, together they point toward an effort to reduce dependence on foreign AI infrastructure. This also explains why Alibaba's recent 128-chip AI server attracted so much attention. Many people focused on the processors themselves, but the more interesting question was this: how efficiently do all 128 processors communicate? The same applies to China's no GPU supercomputer projects, its photonic chip developments, and its advanced optical fiber demonstrations. These aren't isolated breakthroughs. They're pieces of a larger puzzle. If China successfully combines domestic processors, domestic memory, domestic networking, domestic packaging, and domestic manufacturing into one complete ecosystem, it becomes far less vulnerable to outside supply restrictions. That's a strategic advantage that extends well beyond artificial intelligence. It means researchers can continue building larger AI systems using technologies developed and manufactured within their own industrial ecosystem. For NVIDIA, however, this creates an interesting challenge. The company remains the global leader in AI hardware, and its networking technologies are among the most advanced in the world. NVIDIA doesn't simply sell GPUs anymore. It sells complete AI infrastructure, including networking, software, switches, communication libraries, and integrated systems. That's one reason NVIDIA has been so successful. Customers aren't buying individual chips, they're buying an entire AI platform. China appears to be pursuing a similar strategy, but using domestic technology wherever possible. Whether that ecosystem ultimately matches NVIDIA's performance remains an open question, but even approaching comparable performance would represent a significant achievement, especially considering how quickly China's AI hardware ecosystem has evolved over the past several years. Another reason this matters involves cost. Building one of today's frontier AI data centers requires staggering amounts of capital. GPUs represent only part of that expense. Networking equipment, optical transceivers, switches, storage systems, cooling infrastructure, electrical distribution, and physical construction account for enormous portions of the overall investment. If communication technologies become more efficient, companies may need fewer networking devices to achieve the same workload. If processors spend less time waiting, fewer processors may accomplish the same training task. If energy consumption drops, operational costs decrease year after year. Those savings compound across facilities containing tens of thousands of accelerators. Suddenly, communication improvements become financial improvements. That's exactly why investors closely watch networking announcements even when they don't generate the same headlines as new processors. Now consider another trend happening simultaneously: AI inference. Training enormous models receives most of the attention, but inference, actually running AI after it's trained, is becoming an even larger market. Billions of users interacting with AI assistants, image generators, autonomous vehicles, industrial robots, medical systems, and enterprise software require enormous infrastructure. Inference also benefits from faster communication, especially when requests must travel between multiple processors and memory systems almost instantly. Future AI won't exist inside one processor. It will exist across entire distributed computing environments. That's why networking matters for both training and deployment. There's also another technology quietly entering this discussion: silicon photonics. Instead of moving information using traditional electrical signals through copper connections, silicon photonics uses light traveling through optical pathways. Light experiences lower resistance, generates less heat, and can carry tremendous amounts of information simultaneously. Several countries are investing aggressively in this technology because many engineers believe future AI data centers will increasingly rely on optical communication rather than purely electrical connections. China has been especially active here. You've already seen stories on this channel involving glass chips, photonic manufacturing, air-filled fiber, optical communication, and integrated photonic devices. Viewed separately, each seemed like a fascinating breakthrough. Viewed together, they reveal a long-term direction. Replace communication bottlenecks with light. That doesn't happen overnight. Entire industries must adapt. Manufacturing changes, software changes, data center architecture changes. But once that transition begins, the performance gains can become substantial. It's similar to the transition from hard drives to solid-state storage. At first, only premium systems adopted SSDs. Eventually, they became standard because the performance difference was simply too significant to ignore. Networking may follow a similar path. The fastest future AI systems could increasingly rely on optical communication internally. Another fascinating aspect of China's strategy is diversification. Rather than betting everything on one technology, Chinese companies appear to be exploring multiple complementary directions simultaneously. Photonics, advanced packaging, novel memory, glass substrates, three-dimensional integration, domestic AI accelerators, optical networking, ultra-fast fiber. Each technology strengthens the others. That's important because AI performance rarely depends on one breakthrough anymore. Progress happens when dozens of improvements arrive together. Think about Formula One racing. Winning doesn't come from having only the strongest engine. Teams optimize aerodynamics, suspension, tires, brakes, fuel efficiency, weight distribution, driver strategy. Tiny gains across every category produce enormous advantages on race day. Artificial intelligence infrastructure works the same way. Every percentage improvement compounds. Better networking improves GPU utilization, better memory reduces weighting, better packaging shortens communication distances, better cooling allows higher sustained performance, better software coordinates everything more efficiently. Eventually, the combined improvement becomes much larger than any single breakthrough. That's exactly why complete AI ecosystems matter. Looking ahead, analysts expect competition to become even more intense. The next generation of AI models will almost certainly require even larger computing clusters. That means networking requirements will continue growing. Data movement will become even more critical. Energy efficiency will matter even more. Infrastructure spending will likely continue breaking records. Every company wants faster AI. Every government wants technological independence. Every cloud provider wants lower operating costs. Networking sits directly in the middle of all three goals. For viewers, the biggest takeaway isn't whether one country wins tomorrow. The real takeaway is understanding where the industry is heading. For years, headlines focused almost exclusively on processors. Now the conversation is expanding. Memory matters, packaging matters, cooling matters, optics matter, networking matters. And increasingly, the companies mastering every layer of the AI stack will likely shape the future of artificial intelligence. Whether China's latest AI networking technologies ultimately outperform competing solutions remains something the industry will continue evaluating as more systems are deployed and independently tested. Performance claims always require real-world validation across diverse workloads. But regardless of exact benchmark numbers, one conclusion is becoming increasingly difficult to ignore. The global AI race is no longer only about building faster chips. It's about building faster systems, complete systems, integrated systems, entire ecosystems capable of training, deploying, and scaling artificial intelligence more efficiently than ever before. That's why announcements involving networking may soon become just as important as announcements involving GPUs themselves. The future winners won't necessarily be those with the fastest individual processor. They may be the ones whose processors spend the least amount of time waiting. And if that's the direction artificial intelligence is heading, then today's networking breakthroughs may end up being remembered as some of the most important developments of this entire AI era. Because in the next generation of AI, speed won't just be measured inside the chip, it will be measured between them. If you enjoyed today's breakdown, Don't forget to like the video, subscribe to the channel, and turn on notifications because every day we cover the biggest breakthroughs shaping China's technology race, from AI chips and memory to photonics, robotics, semiconductors, quantum computing, and everything in between. Thanks for watching, and we'll see you in the next one.
Okay, so let me ask you, you said something recently that was quite provocative. You said that China was winning the AI race, the AI competition. I know that you've got a powerful, competitor in Huawei, and Huawei has a lot of advantages you don't have. Why don't you describe this?
In March 2026, an engineer walked onto a stage in Shenzhen and held up a single card, small enough to fit in one hand. Then he said the number out loud: 1.56 petaflops. If that means nothing to you, here's the translation. That is roughly 1.5 quadrillion AI calculations every second, about the muscle of 150 high-end laptops, compressed into a slab of hardware the size of a paperback book. And according to Huawei, that single card is close to 3 times more powerful than the best AI chip the company was previously able to get its hands on for the Chinese market. But the performance number, as wild as it sounds, is not actually the story.
Competition. Are we really losing?
It was a very good headline.
It was a great headline, yeah.
And it apparently caught a lot of attention. As you know, with headlines, the disclaimer part, the foundation part, was left out of the headline.
The story is what's hiding underneath that chip, and why it just exposed a weakness in the most dominant company in artificial intelligence that almost nobody was talking about out loud. Because for years, one company has effectively owned AI. Not most of it, almost all of it. And the assumption everyone made was that its position was untouchable, that there was simply no way around it. This chip is the first real crack in that assumption. By the end of this video, you'll understand exactly what it does, how it was built when every rule said it couldn't be, and why the part that should make NVIDIA nervous isn't the speed at all. Let's get into it. To understand why this matters, you first have to understand the chip this thing was designed to kill. When export restrictions tightened on advanced semiconductors heading into China, NVIDIA, the company that supplies the overwhelming majority of the world's AI chips, was put in an awkward position. It couldn't sell its best hardware into one of its biggest markets, so it built a special, deliberately weakened version specifically for China, a chip known as the H20. The whole point of the H20 was to be a ceiling, powerful enough for everyday tasks, but intentionally held back so it couldn't be used to train the largest, most ambitious AI models. It was a compromise, enough to keep selling into China, but not enough to let Chinese companies reach the frontier. And the expectation was that this ceiling would hold for years. Huawei's new chip didn't just bump against that ceiling. According to the specs Huawei presented, it blew straight through it. The company claims its single card delivers nearly 3 times the throughput of that limited H20, carries a massive pool of high-speed memory, and, here's the part that made executives sit up, sits at roughly the same price point Chinese companies were already budgeting for the American chip it's now meant to replace. Same price, far more power, no restrictions. You can already guess what happened next. Within weeks, China's biggest technology companies, the Alibabas, Tencents, and ByteDances of the world, reportedly started placing bulk orders. Huawei's AI chip business, which was already growing fast, is now projected to balloon further in 2026. That alone would be a big story, a new challenger, undercutting the dominant player in its own backyard. But it's not the story, because the truly remarkable thing isn't how fast this chip is. It's that by every conventional rule of how advanced chips get made, it should not exist at all. Here's something most people never think about when they hear the word chip. A modern AI accelerator isn't made by one company in one place. It's the end product of a global supply chain so specialized that only a tiny handful of companies on Earth can even participate in it. Picture an assembly line that stretches across multiple continents. The most advanced processors are manufactured in Taiwan, using almost unimaginably complex machines built by a single company in the Netherlands. Machines that cost hundreds of millions of dollars each and that nobody else on the planet knows how to build. The ultra-fast memory that feeds those chips comes from 2 companies in South Korea. Pull out any single link in that chain, and the conventional wisdom has always been simple. You cannot build a competitive AI chip without it. China was cut off from essentially all of those links at once. no access to the most advanced manufacturing machines. So Huawei's manufacturing partner had to use older equipment, a generation behind, with lower yields and bigger chips for the same performance. By every spreadsheet in every Western tech company, the conclusion was identical and confident. You cannot get there from here. And then Huawei did something that genuinely wasn't supposed to be on the table. They didn't just work around the manufacturing problem, they tackled the memory problem too, by building their own from scratch. This is the detail that deserves a second of your attention. That fast memory I mentioned, the kind that comes from those two South Korean companies, Huawei says it developed its own version, in-house from the ground up. Not licensed, not borrowed, not a copy of someone else's design. A proprietary memory standard, engineered inside China, tuned specifically for the messy, irregular data patterns that large AI models throw at hardware. Think about what that means. Practically every AI chip, in practically every data center, in practically every country, relies on memory from those same two suppliers. According to Huawei, this one doesn't. The processor, the memory, the connective fabric that ties it all together. For the first time, the whole thing is sourced domestically. The closest comparison I can think of is this. Imagine someone confiscates every machine shop, every specialized supplier, and every blueprint you'd need to build a jet engine. And then you build the jet engine anyway, out of parts you had to invent yourself, and it actually flies. That's roughly the scale of what's being claimed here. But even the hardware isn't the most important part of this story. The thing that should genuinely worry NVIDIA is something you can't hold in your hand at all. Here's what most people get completely wrong about NVIDIA's dominance. They think it's about the chips. It isn't, or at least not only. NVIDIA's deepest, strongest, most defensible advantage is something called CUDA. Let me explain why that's the real story. Because this is the actual weakness in the title, and it cuts both ways. CUDA is NVIDIA's software layer. It's the bridge that sits between the physical chip and the AI models that run on top of it. And over more than a decade, virtually every major AI model in existence, the famous chatbots and assistants you've heard of, was written to run on CUDA. The entire ecosystem of AI development grew up speaking CUDA's language. That's NVIDIA's true moat. It was never just that the chips were fast. It was that switching away from them was almost unthinkable. Moving your AI work off CUDA isn't like swapping out a part. It's like deciding to rewire an entire building while people are still working inside it. The cost, the risk, the time. For years, that was enough to keep everyone locked in. Most analysts assumed that lock would hold China back on the software side for years, even if the hardware caught up. This is the weakness the title is talking about. NVIDIA's greatest strength, that everything depends on its software, is also its single biggest vulnerability. Because a dependency that's strong is exactly the kind of thing a determined competitor will spend everything to break. And in 2026, someone tried. A Chinese AI company released a new frontier-class model and made a striking claim about it, that it was built with no NVIDIA dependency anywhere in its stack, not trained on NVIDIA chips, not optimized for CUDA. Instead, its engineers reportedly spent months rewriting the deepest, most technical layers of their software to run natively on Huawei's hardware, using Huawei's own alternative to CUDA. If that holds up the way it's described, it's genuinely significant, because it means the unthinkable rewiring job, the one everyone assumed was too painful to ever attempt, somebody just attempted it. And the building still had the lights on at the end. Now step back and look at the whole picture, because this is where it stops being about a single product. Stack it up. The chip is domestically made. The memory is domestically developed. The software framework that runs it is domestically built. And now a frontier AI model has reportedly been trained and deployed on top of all of it. For the first time, you have a complete AI system, from the raw silicon all the way up to the finished model, built without relying on the usual handful of irreplaceable suppliers. That's the thing that's actually new here. Not a chip, a whole parallel ecosystem. And the numbers around NVIDIA's position in China tell the other half of the story. The company's chief executive himself has acknowledged that its sales into China effectively collapsed, going from dominating the market to almost nothing in a remarkably short window. That's not a rumor or a projection. That's the company's own leadership, describing a market worth tens of billions of dollars largely slipping away, and being candid that it may not come back. Here's the irony at the center of all this, and it's worth sitting with. The restrictions were designed to do one specific thing: slow China's AI progress by cutting off the tools, the memory, and the chips. The logic seemed airtight: no advanced hardware, no advanced AI. What appears to have happened is closer to the opposite. In a span of roughly 18 months, the world's largest AI chip market went from near total reliance on NVIDIA to building a homegrown alternative across the entire stack. Not because any restriction was lifted, but precisely because it wasn't. Every barrier that was meant to be a wall ended up functioning more like a blueprint. It told Chinese companies exactly which capabilities they had to develop themselves, and gave them an enormous guaranteed domestic market to sell into once they did. That's a pattern worth recognizing, because it shows up again and again in the history of technology. When you cut a determined, well-funded player off from something, you don't always stop them. Sometimes you just force them to build their own version, and once they do, they never need yours again. Now, I want to be straight with you here, because I'd rather give you the real picture than pure hype. And there's a temptation with a story like this to overstate it. This does not mean NVIDIA has been beaten. It hasn't. Globally, NVIDIA is still the dominant force in AI by an enormous margin, and its newest chips are still, by most measures, ahead of what Huawei can currently produce. Huawei's approach involves real trade-offs. Older manufacturing means bigger, hotter, less efficient chips and lower production yields, which makes scaling up genuinely hard. Many of the most eye-popping specifications here come from Huawei's own announcements, not from independent testing. So a healthy amount of "let's see it proven at scale" is warranted. So the accurate framing isn't "China crushed NVIDIA." It's something more interesting and, honestly, more important. China demonstrated that NVIDIA's position is not unbreakable. The moat everyone assumed was permanent turned out to have a crossing point. That's the weakness that got exposed. Not that NVIDIA is weak today, but that its single greatest advantage, total dependency, can be escaped if someone wants it badly enough and is willing to spend years and billions to do it. And that's a different world than the one we were in 2 years ago. 2 years ago, there was one AI hardware ecosystem, and everyone lived in it. Now there appear to be two, one centered on NVIDIA, one centered on Huawei, developing in parallel on opposite sides of the Pacific. And the gap between them, which was supposed to be widening, looks like it might actually be narrowing. Zoom all the way out, and here's why this matters beyond the corporate scoreboard. AI is rapidly becoming the foundation that everything else runs on. The models behind search, software, medicine, science, defense, and the tools millions of people now use every day. And the hardware those models run on is the foundation beneath that foundation. Whoever controls the chips and the software ecosystem effectively sets the terms for the entire industry built on top. For the last decade, that control was concentrated in one place, with one company. A single ecosystem, a single set of rules, a single point of dependency for the whole world. What this chip represents, whatever you think of the politics around it, is the emergence of a genuine second option. And in technology, a second option changes everything. It drives competition. It pushes prices down. It forces the incumbent to move faster. And it means no single company gets to dictate the future entirely on its own terms. That's the real headline. Not that one chip is fast, but that the most locked in, most dependent corner of the entire tech world just proved it has an exit, and somebody walked through it. Here's my honest opinion, for what it's worth. What I find most fascinating about this isn't the hardware specs, which we'll all be debating for months as real-world tests roll in. It's the strategic lesson buried inside it. The whole effort to contain China's AI ambitions rested on one assumption: that certain pieces of technology were simply too hard to replicate, that the supply chain was too specialized to ever be rebuilt from scratch. This chip is a direct challenge to that assumption, and whether or not every claim about it holds up perfectly, the bigger trend is undeniable. A second, fully independent AI ecosystem is taking shape, and that genuinely reshapes the next decade of computing. I think the people who dismiss this as just propaganda and the people who treat it as NVIDIA is finished are both wrong. The truth is in the uncomfortable middle. NVIDIA is still ahead, but its position is no longer guaranteed, and that single fact changes the entire game. Here's the question I genuinely want your take on, and be honest, because people get heated about this one. Is it a good thing that the AI world is splitting into two competing ecosystems, because competition makes everyone build better and cheaper? Or is it dangerous to have the most powerful technology on Earth fragmenting into two separate camps that don't depend on each other at all? There are real arguments on both sides. Where do you land? Drop it in the comments. If you enjoy these deep dives that get underneath the headlines and explain what's really happening before the rest of the world catches on, subscribe to Eastern Engine and turn on notifications. We break down the chips, the breakthroughs, and the strategic moves that decide who leads the next decade of technology. And there's a lot more coming. Thanks for watching. I'll see you in the next one. His name is Dong Hui. He is 39 years old. 6 years ago, a car accident left him paralyzed from the neck down. He couldn't move his fingers. He couldn't write. Something as ordinary as holding a pen had become completely impossible, and every specialist he'd seen told him the same thing in different words. "This is permanent." Then surgeons placed a coin-sized chip between his skull and his brain. 11 months later, sitting in the courtyard of his home in China's Henan province, Donghui picked up a pen. Slowly, carefully, deliberately, he wrote his name. Then he wrote, "Thank you." Then he wrote the date. He later told journalists he was so overwhelmed that he missed a stroke in his own name. "I couldn't believe I was able to write again. I was so excited." That chip, the one that gave Donghui back his hands, just became the first invasive brain-computer interface in history to receive full commercial approval anywhere on Earth. Not a trial permit, not a research exemption, a product license. Available to real patients, covered by China's national health insurance. In production right now, scaling to meet demand. And here's the part that changes the entire story. While that was happening, Elon Musk's Neuralink, the most famous, most funded, most publicized brain chip project in the world, still has 21 people in an experimental trial. No commercial approval, no product license, no insurance coverage, anywhere. The race that everyone assumed Elon Musk would win, someone just crossed the finish line. And it wasn't him. To understand what just happened, you need to understand how this competition looked from the outside for the past several years. Neuralink was the story. Full stop. Elon Musk announced it, hyped it, described a future where paralyzed people would walk again, where blind people would see again, where the entire interface between human consciousness and computing would be reinvented. He is the most followed person on the planet. Every announcement got global coverage. Every trial update was front-page news. The assumption baked into almost every article written about brain-computer interfaces was simple. Neuralink leads, everyone else follows. Meanwhile, in Shanghai, a startup called Neurical Technology was quietly doing something different. No celebrity CEO, no viral announcements, no promises about controlling computers with your thoughts or uploading your memories. Just a research team, a partnership with Tsinghua University, one of China's most prestigious technical institutions, and a singular focus on getting one specific device approved for one specific group of patients. The device was called Neo. It's roughly the size of a coin. It takes about 90 minutes to implant. It sits between the skull and the outer protective membrane of the brain, called the dura mater, with 8 sensors pressing gently against that membrane, without ever penetrating the brain tissue itself. Wireless signals travel from the implant to an external processor, which translates the brain's electrical activity into commands for a robotic glove, allowing patients with severe hand paralysis to perform basic grasping movements they hadn't been able to do in years. In March 2026, China's National Medical Products Administration gave it full commercial clearance. 36 clinical trials, 32 of them completed in a compressed window in 2025 alone. And then, approved. Not for trials, for hospitals, for patients, for production. The first invasive brain implant ever cleared for sale anywhere in the world. Here's the counterintuitive part of this story. Neo is not the most powerful brain chip ever built. It almost certainly isn't. Neuralink's N1 chip penetrates the brain's outer cortex directly, accessing neural signals closer to their source and potentially enabling finer, more precise control. Neuralink's long-term ambitions, restoring sight, enabling full-body movement, eventually merging human consciousness with computing, are technically more audacious than anything Neo currently does. So how did the less aggressive device win the regulatory race? Because less aggressive and commercially viable are not opposites. They're often the same thing. Neo's design is epidural. It sits on top of the brain's protective membrane, rather than inside the brain tissue itself. A researcher at the University of Technology, Sydney, speaking to MIT Technology Review, explained why that distinction matters enormously in a regulatory context. An epidural approach carries significantly lower risk of bleeding and lower risk of signal loss over time than electrodes that penetrate the cortex. When a regulator is evaluating a device for broad commercial use, not just in a handful of carefully selected trial participants, but in real hospitals with real patients who have varying health conditions, risk profile is everything. Neo didn't win because it outperformed Neuralink. It won because it was designed to be approvable, not just impressive. And Neurical had something else that Neuralink doesn't: state-level strategic backing with matching urgency. China has listed brain-computer interface technology as one of 6 national strategic priorities, alongside quantum computing and humanoid robotics. That designation isn't symbolic. It comes with coordinated funding, expedited regulatory pathways, and the kind of institutional alignment between researchers, companies, and government that compresses the timeline from lab to clinic in ways that are genuinely difficult to replicate in a system where commercial interests, regulatory bodies, and research institutions operate independently. Neuracle ran 32 of its 36 trials in a matter of months in 2025. That pace of clinical validation reflects a system operating in a different gear from what Neuralink has been navigating. The facts and the regulatory milestones are important, but there's a human being at the center of this story, and he deserves more than a footnote. Everything you do online is being watched: your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Dong Hui was paralyzed in 2018, 6 years of his life spent unable to use his hands. Then he saw something on television, a news report about another paralyzed man in China who had regained some movement through a brain-computer interface trial. He signed up for Neuracle's program in October 2023, 1 month after watching that report. The implant went in. The rehabilitation process began. Slowly, painstakingly, his brain learned to communicate with the device, and the device learned to interpret his brain. 11 months later, he wrote his name in his own courtyard. He also told journalists he hadn't expected it to work. He'd spent 6 years being told his condition was permanent. The moment he picked up that pen was the moment 6 years of that certainty collapsed. This is what Neo actually is, underneath all the regulatory language and competitive framing. It is a device that gave a man back the ability to write his own name, and it is now approved for use in a country of 1.4 billion people, covered by the National Health Insurance System, with more patients entering the program as production scales. The numbers behind that aren't just impressive, they're staggering. Hundreds of thousands of people in China live with the kind of spinal cord injury Neo is designed to treat. Here's the pattern that keeps appearing in technology, and it's directly relevant to everything covered on this channel. A technology is invented, usually in a Western lab, usually by researchers with enormous resources and high ambitions. For years, everyone watches that original team. They assume the leader stays the leader. They write articles about when the technology will mature, when it will become commercial, when it will change the world. All the attention stays focused on the most famous version of the thing, and then something else happens somewhere else. Quietly, methodically, without the celebrity or the headlines. A different team, with different priorities, in a different system, makes different design choices. And while everyone is watching the famous version, the less famous version crosses a threshold that matters. It happened with glass chips. The semiconductor industry was fixated on transistors and lithography while the substrate layer changed underneath everyone. It happened with diamond cooling. NVIDIA's CEO was flying to China while most of the world was still debating whether diamond was even practical. And now it's happening with brain chips. Neuralink has more press coverage than every other BCI company combined. And a startup most people have never heard of, built in Shanghai with funding from Tsinghua University and backing from China's National Technology Strategy, just became the first to put a commercially approved brain implant into a patient outside a clinical trial. The pattern isn't that the famous version is wrong or that the quiet version is always better. The pattern is that fame and leadership aren't the same thing. And in technology, the milestone that actually counts isn't who announced it first, it's who shipped it first. Neo is the first. It will not be the only. China has at least 2 more BCI devices behind Neo in the pipeline. Neuroxess and StairMed are both developing competing implants domestically. The Beijing Brain Institute's BEINA01 system is expected to reach market by 2028. Within the span of roughly 2 years, China could have multiple commercially approved brain implants operating in its healthcare system, each generation learning from the one before it, while the rest of the world is still working through regulatory trials. The advantage this creates isn't just about one device, it's about data. Every patient who receives Neo generates real-world performance data in a commercial healthcare setting. That data, how the implant performs over months and years, which patient profiles respond best, which failure modes appear, and how often, is exactly the kind of evidence that makes second-generation devices better. And it is the kind of evidence that regulators in other countries will eventually require before approving anything. China now has a head start not just in commercial approval, but in the accumulation of long-term, real-world safety and performance data. That compounding lead is far harder to close than a regulatory gap. It's the same dynamic as the glass substrate story, the same dynamic as the diamond chip story. Being first doesn't just mean you got there early, it means every subsequent year of operation makes you harder to catch. For Neuralink specifically, the competitive picture has shifted in a way that doesn't get fully acknowledged. Neuralink's technical ambitions remain larger. Its long-term vision, the idea of a general-purpose brain-computer interface that goes far beyond motor rehabilitation, hasn't changed, but it is now competing in a landscape where a rival has commercial approvals, insurance coverage, real patients, and accumulating real-world data, while Neuralink is still adding participants to a clinical trial. That's a different kind of pressure than it was 12 months ago. Here's what strikes me most about this story, and it's something I keep coming back to. Neuralink had everything: the money, the attention, the most famous founder in technology, a decade of runway, and Neo, a startup from Shanghai with a fraction of the profile, shipped first. Not because Neuralink is more talented than Neuralink's engineers, both teams are world-class, but because Neuralink made a device that was designed to clear regulatory hurdles rather than one designed to impress a keynote audience. They optimized for approval, not for ambition. And in the market for medical devices, approval is everything. The most powerful chip in the world is useless inside a lab. I think the Neuralink story is far from over. A device that actually penetrates the cortex and accesses finer neural signals will likely enable capabilities that Neo simply can't. But Neuralink now has to develop and prove those capabilities while a competitor is already in hospitals, already covered by insurance, already generating data, and already treating patients. That's a completely different race than the one Neuralink thought it was running. Here's my question for you, and I want your honest answer. Does this change how you think about Neuralink? Because here's the tension. Neo got to market first, but Neuralink's ambitions are larger. Is first to market in medicine the thing that matters most, or does the device with the higher ceiling eventually win regardless? Drop your actual opinion in the comments. This one I'm genuinely curious about. If you want to keep following these stories, the ones that rewrite which country leads in a technology that seems settled, subscribe to Eastern Engine and turn on notifications. Brain chips, diamond chips, glass chips, the substrate layer, the thermal layer, all of it connects. And all of it is moving faster than most people realize. Thanks for watching. See you in the next one. NVIDIA once controlled almost the entire market for advanced artificial intelligence chips in China. Today, that position is unraveling. A new forecast from Bernstein estimates that NVIDIA's share of China's AI accelerator market could fall to just 8% in 2026, down from roughly 40% in 2025. Huawei, meanwhile, could rise to around 50%. That would represent one of the fastest reversals in the history of the semiconductor industry. But the headline needs an important qualification. NVIDIA has not already been measured at 8% across the full year. 8% is a forecast based on current sales restrictions, delayed approvals, government policy, and the rapid growth of Chinese alternatives. Still, the direction is unmistakable. NVIDIA once held about 95% of China's advanced AI chip market. Now Huawei and other domestic suppliers are taking the customers, software support, and infrastructure projects that NVIDIA once expected to dominate. The central question is no longer whether China can build an alternative AI hardware industry. It is whether NVIDIA can prevent that alternative from becoming permanent. How NVIDIA lost its near monopoly. NVIDIA's dominance was built on more than fast chips. Its graphics processors became the standard hardware for training artificial intelligence because developers already knew how to use them. The company's CUDA software platform gave researchers tools, libraries, and optimized code that made complex AI workloads easier to run. Chinese universities, startups, cloud providers, and internet giants built their systems around that ecosystem. When a company wanted to train a large model, NVIDIA was usually the safest choice. That created a powerful feedback loop. More customers attracted more developers. More developers created more software. More software made the hardware even more valuable. At one point, NVIDIA controlled approximately 95% of China's advanced AI accelerator market. Then Washington changed the rules. The United States introduced export controls designed to limit China's access to the most advanced computing hardware. The concern was that powerful AI chips could support military systems, cyber operations, surveillance, and other strategic capabilities. But those rules continued evolving. Chips that were permitted under one standard could later become restricted, and Chinese companies began asking whether dependence on an American supplier had become too risky. The H200 problem 1974 was NVIDIA's H200. But approval from the United States did not guarantee immediate access to the Chinese market. Chinese authorities also had reasons to slow or discourage purchases. Beijing wants domestic companies to use Chinese technology whenever possible. Allowing unlimited imports of NVIDIA hardware would weaken that strategy. So even when export permission existed, orders remained surrounded by uncertainty. This placed NVIDIA between two governments with opposing objectives. Washington wanted to control China's access to advanced chips. Beijing wanted to reduce reliance on American chips. Nvidia wanted to sell. Chinese customers wanted computing power, but every transaction became a political decision. That uncertainty is one reason market share can collapse faster than product performance. A customer building a multi-year data center